Hi, it's time for another math easy solution. Today I'm going to go over a video for a change. It's been about 4 months since I last made a video, and yeah, the world's changed a lot, or has it really? Anyway, so I'm going to go over hashtag MES Science number 2, and this is going to look at Vortex Math, and I was going to do a full all at once, but then I realized it's taking a bit too long, so I'm going to do part 1. It's going to go on number theory and modular arithmetic. And yeah, like always, before every video I will state that if you don't have time to watch this whole video, you can always skip to the end for summary conclusions. You can play this video at a faster speed, and top secret life hack, your brain gets used to faster speed, and so on. Here's my recommendations. You can also download, read the notes. Notes will be in the link in the description, as well as reading the notes on the Hive blockchain. So yeah, Hive is a hard fork of Steam. I'll explain that in another video, but yes, lots has changed. And also you could watch the video in parts. Alright, so let's keep going further. So MES Research Note, it has been several months since my last video upload, since I've been researching extensively on, quote, Vortex Math. When covering topics that I've not done before, especially ones where there are no adequate explanations from either mainstream or alternative sources, I first do an extensive review of everything currently in existence on the topic. Yes, I do. And during this review, I often realize I have to restructure and reorganize my previous research and work schedule to be able to learn topics that are beyond the scope of what I have been previously accustomed to. How can we learn how to learn? That's a very good question. Anyways, making this video has allowed me to streamline the general learning process, so future videos will not have a big delay. Hashtag hopefully. And also note on part 1, I had originally planned on making one Vortex Math video, but it was extending too long and required more research, so I've decided to do it in parts. The first part will be in regards to the basics of Vortex Math, and in later parts I'll extend to the 3D vortex torus geometry and the, quote, more advanced vortex patterns, so stay tuned for those. And here are the topics to cover. So yes, we're going to cover a lot of topics, or a lot of concepts within this Vortex Math. So number 1, or part 1, I'm going to go Introduction to Vortex Math, and then look at Marko Rodin's claims and discovery, and then also go over the Fallacy of Reification. There's a lot of fallacies going on. And also grand coil claims, more claims, and so on. Overview, I'm going to go over overview of base number systems, the numbers 0 and 10 in general number systems, and then go over example 1, base 4 number system, example 2, base 2 number system, and then also converting number systems, and then go over example 3, which is base 16 or hexadecimal or hex number system. Very interesting number system there. And then also go over summing of integers and the remainder after division. MES convention, vortex sum versus the digit sum. And then I'm going to discuss the modulo operation, determining remainders, yeah, just the way of determining remainders. And then also go over a proof. The vortex digit sum is equal to the mod of the base minus 1 for whichever base number system you're using. Using base 10, and then I'm going to go over using base 10 to determine vortex sum of different bases. And also note, can calculate base 4 vortex sum using base 10 mod function without conversion. MES note, all numbers used are by default in base 10 unless stated otherwise. And I'm going to go over multiplying a number and its vortex sum result in the same vortex sum. This is the causation of most vortex patterns. So yes, get that ingrained into your head once you get to that section. And also go over the modulo multiplication identity, and then discuss modular arithmetic, and also go over the vortex doubling patterns, the 1, 2, 4, 8, 7, 5 pattern, the 3, 6, 3, 6, 3, 6, continuously going on pattern, and then the 9, 9, 9, 9 pattern. And then also discuss how the symmetry of number systems causes the specific doubling patterns, and also factors that govern vortex patterns, even in odd base number systems, size of base number system, and then also synchronization of doubling pattern and size of base. Odd base number systems can't synchronize with doubling, which is, yes, very interesting. Starting point of pattern is also a big factor, and the multiplying factor, either doubling or times 3, 4, 5, etc. And then also vortex halving patterns, the 1, 5, 7, 8, 4, 2 pattern, which is the reverse of this doubling pattern right there. Then go over how halving, halving The L is silent apparently. Depends on the base number system, and then converting halving into multiplication. Halving is the reverse of doubling. Vortex halving doesn't work for odd base number systems, question mark. So yeah, if you know a way, let me know once you get to that section. So powers of 10 pattern, and then go over the general division to multiplication. And here actually I added just, so general division to multiplication, vortex conversion. Yes, just to be more specific. And also go over dealing with, quote, irregular division. Example 4, halving in base 5. Example 5, converting division by 4 to multiplication by 7 in base 10. And example 6, division by 7 in base 10 pattern. Or here just reworded that a bit. So example 6, division by 7 in base 10, and then we get this 1, 4, 2, 8, 7, 5 pattern. And also I just added example 7, forgot to include in this topics to cover. So example 7, summary of base 10 division to multiplication conversions. It's just very interesting stuff. So then go over polar number pairs in addition, different base number systems, odd base number systems, and the modulo addition identity. Then go over summary, conclusions, and discussion on the future parts. Alright, so now let's jump right into Introduction to Vortex Math. So I had been made aware of, quote, Vortex Math, VM, or otherwise known as, quote, Vortex Based Mathematics, VBM, several years ago, but I had suspected people were too overly focused on patterns of numbers rather than any actual explanation. Furthermore, the claims made by some regarding VM, I'll use this notation throughout this video, just because the VBM is used by others, but it's a bit longer. I'll just stick to VM so that it's MES convention. So I'll use this notation throughout this video. Yeah, so the claims are quote a bit far-fetched to say the least. In this video, I will focus mainly on the patterns claimed to be, quote, divine, and will seek to explain each one by generalizing them to arbitrary number systems, essentially Vortex Math, and this video in particular will be my first deep dive into, quote, number theory. So here's from the mainstream explanation of number theory from Wikipedia. So number theory, or arithmetic, or high arithmetic in older usage, is a branch of pure mathematics devoted primarily to the study of integers and integer-valued functions. German mathematician Carl Friedrich Gauss from 1777 to 1855 said, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." Very, very interesting. Number theorists study prime numbers as well as the properties of objects made out of integers, for example, rational numbers, or defined as generalizations of the integers, for example, algebraic integers. And going further, the older term for number theory is arithmetic. By the early 20th century, it had been superseded by, quote, number theory. Note that, quote, integers are whole numbers such as 3, 4, 0, negative 11, etc. So it includes negative numbers. And quote, arithmetic, in general refers to, here I spelled that wrong, so refers to the basic operations of addition, subtraction, division, and multiplication. And basically, so number theory is going to be dealing with integers of integer arithmetic, with these whole numbers and basic addition, subtraction, division, multiplication, and so on. So let's go further. So Marko Rodin's claims and discoveries, or claims and claim of discovery, and so on. So Marko Rodin claims to have discovered the, quote, mathematical fingerprint of God by converting the name of God in the Baha'i religion, which is Abha, into numbers. Yes, and here's an explanation from Marko Rodin's one of many defunct or no longer existing websites, and there's a whole lot of them. I don't know. I don't know why he keeps removing them. Anyways, so this is from archived page. It's from October 2nd, 2009. Some rodin.freelancepartnership.com, and go to this introduction of Rodin, Coil, and Vortex Based Mathematics. So Marko studied all the world's great religions. He decided to take the most great name of Baha'u'llah. Actually, I think it's pronounced Baha'u'llah. Yes, I think that's correct. So prophet of the Baha'i faith, which is Abha, or Abha. Or actually, I think it's pronounced Abba. So yes, I just saw it from here. Interesting. In many of my videos, I've been asked to figure out how to pronounce words before I make the videos. So let's try and do that right now. So yeah, so Abba, okay, and then he converted it into numbers. He did this in an effort to discover the true, precise, mystical intonation of the most great name of God, and intonation is the it's the pitch or the rise and fall of the voice in speaking, and so on. Or basically, the precise sound of the most great name of God. Since the Baha'i sacred scripture was originally written in Persian and Arabic, Marko used the abjad numerical notation system for this letter-to-number translation. This was a sacred system of allocating a unique numerical value to each letter of the 27 letters of the alphabet, so that the secret quantum mechanic physics could be encoded into words. What Marko discovered was that A equals 1, B equals 2, H equals 5, and A equals 1. These add up to 9, so these all equal 9. The fact that the most great name of God equaled 9 seemed very important to him, as everything he had read in both the Baha'i scriptures and other religious texts spoke of 9 being the omnipotent number. So next he drew out a circle with 9 on top and 1 through 8 going around the circle clockwise. He then discovered a very intriguing number system within this pattern, within the circle. Marko knew he had stumbled upon something very profound. This circle with its hidden number sequence was the, quote, symbol of enlightenment. This is the mathematical fingerprint of God. So Marko uses the, quote, abjad numerical number system rather than the conventional English alphabet numerology, as well as a bunch of divine words and so on. Yeah, so if we go to Wikipedia just for the mainstream of the abjad numerals, so we have here, this is value 1 is going to be the letter A or the Aleph, and then number 2 is the B, which is Abba, and then if you go to the 5th letter, we have H, so there is, so we have the Abba, so A, B, H, A, so we get A. This is A, and then we get B, H, and then go back there. So this, then back to there. Yes, and this A could also be this other little symbol there. And so basically from these numerical count of the abjad numerical slash letter system, we get so we get the Abha into numbers, which is 1, 2, 5, 1, and then equals 9. So yes, continue further. Right, so going further, so the Abha 1-2-5-1 pattern represents the start and end of a typical cycle of doubling and adding the digits of the sum until a single digit is achieved. So 1 doubles to 2, and that's a single digit, so we stop there. 2 doubles to 4, so we stop there. 4 doubles to 8. Now here we have 8 doubles to 16, which sums to 7. So we have 1 plus 6 is 7. So yeah, just go 1 plus 6 equals 7. So we have that, and then we have 16 doubles to 32, and then which sums to 5, so 3 plus 2 is 5. Note that we could also go from here. We could also double this one, 7. So instead of doing this one, we could just double this one. 7 doubles to 14, which sums to 5, same thing. And also we have, so then this number here, so we always take and double and then sum it up. So 32 doubles to 64, which sums to 10. So 6 plus 4 is 10, which sums to 1. So we have 1 digit. But we could also have done this one. We could also have done 5 times 2 is 10, and that sums to this. So yeah, so we could do either or, and that's going to be very, very important as we get further into this video. So note 5 doubles to 10, which sums to 1. So the cycle and the resulting pattern, we get this 1, 2, 4, 8, 7, 5, and goes back to 1. So the resulting pattern 1, 2, 4, 8, 7, 5 repeats indefinitely. So it just continues forever. And so the numbers 3 and 6 oscillates when doubling. Again, this is all from his website there. And you can have a read when you want to build for the full website. But anyways, going further, so we have here, so the numbers 3 and 6 oscillate when doubling. So 3 doubles to 6, 6 doubles to 1, 2, or to 12, which sums to 3, and then 12 doubles to 24, which sums to 6, and then 24 doubles to 48, which sums to sums to 12. So 4 plus, let's go 4 plus 8. This equals to 12. Yeah, and then this equals to. Let's put an arrow. Actually, no, this does equal. It's not the vortex sum. So 4 plus 8 equals to 12. And then this breaks down to 1 plus 2 equals to 3. So yeah, which sums to 3 over there. So the cycle and resulting pattern of 3, 6, 3, 6, and on repeats indefinitely. And then also now going over to the number 9, the omnipotent, super powerful number 9, doubles to itself always. 9 doubles to 18, which sums to 9. 18 doubles to 36, which sums to 9. 36 doubles to 72, so 7 plus 2 is 9, and so on. So the cycle and resulting pattern of 999 repeats indefinitely. So these doubling sequences are essentially the bulk of the Vortex, Vortex Math, or just put of Vortex Math, and they, along with other patterns, are shown in Rodin's website. So we have here, so a link to images from here. So we have doubling patterns. So we have 1, 2. If you draw it on the circle, we're 9 on top. 1, 2, 3, 4. This would be 5. This would be 6. This is 7, and that's 8. Like that. So we have 1 doubles to 2. Actually, I'll draw it in red. So we have the 9 there. So we have 1 doubles to 2, 2 doubles to 4, and then 4 doubles to 8 all the way up top, like that. And then 8 doubles to 7, because 8 times 2 is 16. So that's the, let's go over here. So 8 doubles 16, which sums to 7. And then goes over here. 7 is just, the 16 or 7. And then the 16 doubles to 32, which is 5. So it goes like that. And 32 goes all the way up here. So then just repeats non-stop. And here I'll just erase these just because it's already pretty clear like that. So yeah, this is just going to be 5. This is 7. So yes, it just goes on and on. Put some arrows like that. Arrows, arrows, arrows indicating direction. Goes up and down. Yeah, so that's the doubling sequence. And then you could, it keeps going on for more and more numbers. So 32 doubles to 64, and that goes to 1. Big doubles here, goes here, and it goes up like that, and so on. Just keeps going on in a loop like that. In a quote lazy infinity, which is often referred to. And also you have this triangle there, the 3, 6, 3, 6, 9 there. And this goes back and forth like that, and so on. Anyways, going further, so halving maintains a pattern as well, but in the reverse direction. So if we have 1 over, yes, we have 1 like this. So 1 divided by 2 is 0.5, and then this sums up to 5. If we ignore the 0 and decimal. So we just ignore those, so it's going to be 5, and then this 5 right here, let's put the, this goes backwards. Notice this 1 divided by 2 goes here. And then 0.5 divided by 2 is 0.25, goes up like that. And this is going to be 7. 2 plus 5 is 7. And then this goes, so this is just a doubling pattern, but in reverse. So 0.25 halves into 0.125, which is 1 plus 2 plus 5 is 8. And this goes, divide that, goes all the way down here. Sum these up, it's going to be 6 to 5. Yes, 6 plus 2 is 8. 6 plus 2 is 8 plus 5, so we have 8 plus 5. It goes 8 plus 5. This is going to be equals to 13. I'll just put an arrow, so they don't actually equal. Yeah, I just reworded that a bit better. So 6 plus 2, which is 8 plus 5, is going to be 13, and then 13 sums to 1 plus 3 is 4. Like that, and this goes all the way up across there. So 3, you could also just double check. This should sum up to 2, so it's going to be a 3 plus 1. Plus 2 plus 5. This is going to be 4 plus 2 is going to be, 4 plus 2 is 6. 6 plus 5, so this equals to 11. And that sums up to to 2. So this goes to 2, like that. Yeah, so it basically goes backwards, goes here, and then this all the way goes over to this side. Sum these up, it's going to be 1. And then it keeps on going and going. So it's going to be backwards like this, the other way around, and so on. And now if we take the powers of 10 here, so the powers of 10, they are basically the parts that we ignored here. So this is 0.5, that's just going to be 5 divided by 10. So there's a 10 there. This one is 125. To get the full number, you have to divide this one out by 1,000. That's this 1,000 right there. This one is the 100th decimal place, or the, just go back here, 1020, so that's the 100th of that. And basically you multiply this to get this to a whole number. And then we get this 10 goes up to here, goes up to there, goes down, and so on. And then we also have this 1, this is going to be 1 million, this is going to be 1,000, then this is going to be 100, this is going to be 100,000, this is going to be 10, this is going to be 10, and this is going to be 10, this is going to be 100,000, and this one here is going to be 10, what's that, billion, I think. So 10 billion is 10 million. So all the 10s line up. So 100, 1, 1, so 1 billion, 1 million, and so on. So we have this pattern of it's always lining up like that. So yes, very good circling by me. Anyways, so note that the quote powers of 10 are the amount needed to multiply the halving results to get a whole number. So 1 times 1 is just 1. That's this part right here. 0.5 times 10 is 5. 0.25 times 100 is 25. 0.125 times 1,000 is 125. Then we have 0.0625 times 10,000 is 625. And then 0.03125 times 100,000 is going to be, well, 3,125. And again, the number of zeros is going to be 5 zeros. It's going to be 1 decimal place, 2, 3, 4, 5. So 5 ways across there. So let's keep that there. So yes. And that just indicates the decimal place, how many zeros you shift to the right. So, and now here's the doubling sequence. Yeah, extended to very large number. The numbers on the left, horizontal addition result on the right. Note how the 1, 2, 4, 8, 7, 5 number pattern repeats indefinitely. So we have here, doesn't matter the size of the number, it's always going to get this 1, 2, 4, 8, 7, 5 when you sum up the digits. This all the way across here, 7, 5, and then this is going to be repeating always. So you're going to have this right here, 1, 2, 4, 8, 7, 5. So it just repeats, and then you have another, I'll just get to the 5, like that. And now we have this 1, 2, 4, 8, 7, 5 all the way up across here. And as you can see, it doesn't matter what the numbers is, you could try it yourself and sum those up. It will always get to this exact pattern. So yes, you could always go there. This is going to be another like that. 1, 2, 4, 8, 7, 1, 2, 4, 8, 7, 5. And then 1, 2, 4, 8, 7, 5. And so on. It keeps going on and on. Yes, keeps going on. Yeah, so furthermore, Rodin reframes the classical yin-yang symbol or yin-yang duality symbol. Duality. Or actually, I'll just keep that like that because I already wrote it here. So Rodin reframes the classical yin-yang symbol as a trinity of 3, 6, 9 instead of the usual duality. So we have this, it's usually viewed as a duality, but if you consider the 9 as in between. Alright, so now going further, the doubling 1, 2, 4, 8, 7, 5 pattern, when made going one way and another going in reverse direction, interspaced with another 3, 9, 6, 6, 9, 3 pattern, creates a blueprint for the torus. And so what do we have here? So 1, 2 doubles this way, doubles. And then if you have the doubling or halving the other way, so this now we have this 1, 2 going this way. This is going to be doubling like that, or halving the other reverse. Remember, halving, doubling are the reverse. And now we have this 3, 9, 6, 6, 9, 3 pattern, like that. And then interspace that in between every single one. So, yeah, so I'll just highlight that right here. So there's that 3, 9, 6, 6, 9, 3. And then let's click this arrow. So now we have, yeah, so that's the 3, 9, 6, 6, 9, 3. Now the doubling interspaces as well. So here, so 1, 2, 4, 8. Doubling this way, and then reverse back all the way there, like that. So this is going to be doubling. Or actually, I'll just put the all arrows here. So this is going to be doubling, like that. Just put it like that. Doubling right here. So 1, 2, 4, 8. Yeah, so right here, 1, 2, 4, 8, 7, 5. This is going to be doubling. And so on. I'll just write this down. Just for completeness. So doubling, then this is going to be the reverse doubling. So 1, 2, 4, 8, 7, 5. This is going to be doubling. Again, this is from Marko Rodin's website. When I cover this in part 2, it's going to be much more clear. It's going to be doubling like that. And let's just interspace, put this yellow there. This is going to be this interspaced like that. Interspaced like that, the 3, 9, 6, 6, 9, 3, and also in reverse, relative reverse direction, but it's hard to see that here. And yeah, this is supposed to be in a diamond grid because it's hard to see. The other pattern that arises here is that you'll notice that if you go across here, let's look at this, 1, 2, so we have this this count right here. If you go all the way, let's just pick a number here, so from here, 1, 2, actually I'll just highlight that. So we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way across like that. And here it's made this green a bit smaller. So yeah, we have this 1, 2, 3. So it counts all the way to 1 and resets again, which is very, very interesting. And then if you go further, it starts doing that as well here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, like that, and so on. And at the same time, you also have it in the reverse direction. So we have this 1, 2, I'll put this in blue. Yeah, it's reverse direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way. And it just keeps going and then repeats on this other side there. And where it's interspaced with... Actually, no, the interspacing is only on this vertical side here. Because again, it's supposed to be in diamonds. But nonetheless, pretty interesting. So now this is going to be... This alternates back and forth. So the blue is going to be on this one. This is counting 1, 2, 3, like that. All the way across here, and then in between that is going to be the green, and so the green is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'll just put this in red. Like this is going to be, I'll just put it in green. Actually, this is going to be 1 to 9, and then this is going to be on the other side. Yeah, so 1 to 9, all the greens, and the blue is going to be this right here is going to be 9 to 1. Etc. So again, yeah, this is a bit rough right here. Yeah, it's a bit rough, but this is just what I'm working with because I'm using it from his website, just copy and paste it and deal with that. But again, in my later video, I'll make it much more simpler. And here I also made this highlight a bit thinner, the thickness, so that it's a bit better lines up. So yes, basically those are the main patterns that arise. There's about a bunch of, as well as a bunch of other diamond shapes in there, but it needs to be in a diamond. So anyways, let's go further. So yeah, so these patterns always go adds 1 to 9 and then alternates a 9 to 1 and so on. And this is the doubling from this side. Doubling goes back and forth, and then there's always this interspaced 396, 693, etc. So 396, 693, and so on. And also note that the above grid is supposed to be in a diamond grid, but but I guess yes, most spreadsheets are default in a square or rectangular, etc. So you'll need to adjust those manually. So anyways, going further, so Rodin claims that the resulting torus demonstrates the winding of a coil. So we have a coil like this, and then if you just wrap this around into a torus, I'll explain this in a later video. Then you're going to get a windings that looks like this, where you can see this is a doubling pattern all the way across here. Yeah, so we have this doubling pattern, 1, 2, 4, 8, 7, 5. This is 1, 2, 4, 8, 7, 5. And we also have it in the reverse direction, 1, 2, 4, 8, 7, 5. And notice how the increments, let's see where they're supposed to add up incrementally. Yeah, so these are going to be 1, 2, 3. So this would be 1, 2, 3, 4, 5, 6, 7, etc. And then the opposite is going to be, where's the opposite here? 6, 7, 8. No, it's actually over here. It's actually here. So 1, 2, 3, 4, 5, 6, 7. So it goes in and out, 1 to 9, and then 9 to 1, etc., going outwards. And yeah, so I'll just put it like this: 1, 2. This is going to be extending 1 to 9, and then alternates with 9 to 1. I'll just leave that for a future video. But yeah, so the windings based on the doubling patterns in and out, or reverse and forward direction, and then you also have the increments 1 to 9 in and out from the center part right here. And yeah, so those are the windings that you can make of a coil. And you could design it according to these numerology. So the number 9, according to Marko Rodin, continues further. And the 9 demonstrates the omnidimension, which is the higher dimensional flux emanation called spirit that always occurs within the center of the magnetic field line. Okay. Anyways, apologies for the laughter. I'm just trying to... Yeah, I'm just trying to follow along, but again, he jumps into different topics without explaining or defining each term and why he's doing so. So anyways, so it always occurs within the center of the magnetic field lines, so discussing the coil and the windings. So the last number, the last number left to be explained from the mathematical fingerprint of God is the number 9. The number 9 is energy being manifested in a single moment event of occurrence in our physical world of creation. So yes. It is unique because it is the focal center by being the only number identifying with a vertical upright axis. It is a singularity or the primal point of unity. The number 9 never changes and is linear. For example, all multiples of 9 equals 9. 9 times 1 equals 9. 9 times 2 is 18, but 1 plus 8 is 9. 9 times 3 is 27, but 2 plus 7 is 9. This is because it is emanating in a straight line from the center of mass out of the nucleus of every atom and from out of the singularity of a black hole. It is complete, revealing perfection, and has no parity because it is always equal. It always equals itself. The number 9 is the missing particle in the universe, known as dark matter. Anyways, apologies again. So Rodin states that the number 9 emanates from the center point of the hexagonal infinity symbol, which is off-center from the global circle, linearly in all directions, and emanates the universe, or animates the universe. So the number 9 lines up with the center of the infinity symbol, and it is from the center that the linear emanations we call spirit emanate from the center of mass outwards. So there's that the number 0 or the the off-center, the off-center. All right, here I just erased it. Yeah, so this is the off-center point where the 9 emanates from. From this center that the linear emanations we call spirit emanate from the center of mass outwards. There's the infinity symbol, the hexagonal lazy infinity symbol, and the number line lines up with the center. So you have this number 9 like that, and it lines up with the center there. And it is from this center that the linear emanations we call spirit emanate from the center of mass outwards. Spirit is the only thing in the universe that moves in a straight line. Spirit is the inertia ether or aether that Einstein postulated. Spirit is what makes everything else warp and curve around it. The perfect number patterns are actually created by the spirit energy. Without spirit, the universe would become destitute and void. Spirit flow is the source of all movement, as well as the source of the non-decaying spin of the electron. All right. So yes, it's a pretty cool imagery right here. But yes, it's a mouthful right here, tying in all these different physics concepts and so on. So yeah, and going further, so another pattern shown is that incrementing the 1, 2, 4 numbers by themselves and summing the digits mirror the 8, 7, 5 numbers, doing that to themselves as well. The corresponding pairs 1 and 8, 2 and 7, and 4 and 5 are called polar number pairs. So if you have here, so 1 plus 2 is, 1 plus 1 is 2, so just plus 1. So 1 plus 1 is 2, and then this is going to be another plus 1 is going to be 3, 4, 5, 6, 7, 8, 9. So this is going to be just plus 1. And then it goes back to starting to number 1. That's the pattern. This one here, 8 plus 8 is going to be 16. So 8 plus 8 is 16. And then this is going to go into 1 plus 6 is 7. Yeah, this is going to be 7. So it goes to 7, and it keeps going on. And then, in fact, this is going to be, it looks like, yeah, this is going to be a minus 1. So here's going to be plus 2. Same thing, 2, 4, 6, 8, it goes plus 2. This one right here, 7 plus 7 is 14, which is 1 plus 4 is 5. So this is going to be a minus 2. In fact, you can include the 9 here. So if this is 8 plus 9, and this goes to 9, you didn't mention this one. But yeah, so 8 plus 1 goes to 9, then plus 1. So it basically is a continuous loop. So 7 plus 2 is going to be 9, and then 9 plus 2 is going to be, well, 1 plus 1, 2. This is going to be 2. So this would be a continuous loop like this, or reverse. It's going to be positive this way, or negative 2 this way. And same with that above there. And likewise over here on the 4, we have 4 plus 4 is 8. It's going to be plus 4, then plus 8 plus 4. Yeah, it's 12, and then 12 is just going to be 3. So 1 plus 2 is 3 is going to be plus 4, and then going backwards this way it's going to be minus 4. So 5 plus 5 is 1, or 5 minus 1 is 4. It's going to be minus 4. And you can also include the 9 here. So 5 plus 4 is 9. Or 4 minus 4, as the remember there's going to be, 4 minus 4 is going to be, there's no 0. It just goes straight to the 9 in Vortex Math. So yes, this is going to be as well. Plus 4, let's do it for completeness, like this. Plus 4 or minus 4. I just gave away the reasoning behind this. And this one here is going to be plus 1. Or minus 1 this side. And again, yeah, you could just do the 5s, the 7s. The 7 is the same as minus 2, and the 2 is just plus 2, like that. Or you could also do minus 7 if you look at negative numbers, and then it also gets to the 9. I mean, it wraps around. So if you have 2 minus 7, this equals to, well, Yeah, which equals to negative 5. If you consider as a difference between 9, it's going to be 9. It's going to be 9 minus 5 is going to be 4. 5 equals 4, and so on. You do that, and I'll explain this later in the video. And you get to this 4 right here. And you see that right here. So 8 minus 7, this equals to this equals to 1. And it's the same thing as 8 plus 2 is going to be equal to 10, which goes to 1. So yeah, same thing. So minus 7 plus 2, this one here, plus 7 minus 2, and so on. So yes, let's keep going further. I'll explain this all in detail. Lastly, Rodin views the nature. You've used nature. You've used nature arbitrarily as contracting and expanding. So you have vortex in and vortex out. There's black hole, white hole. It goes out and so on. It cycles back in. So yes, this is all included in the vortex introduction. So nature is expressing herself with numbers. The symmetry of our decimal system is a principle of nature. The 9-axis causes the doubling circuit, and it is the point towards which matter converges and away from which it diverges or expands. Thus, the polar number pairs will be mirror images of each other, both flowing in opposite directions from the central axis. There is perfect symmetry wrapped around a single point, coiling outwards the way that petals are wrapped in a rose or a nautilus shell. Yeah, actually, I think it's pronounced a nautilus shell, just those spiral shells. Shell spirals outwards, and yeah, I just double checked with this pronouncing. So while interesting philosophical rhetoric, many questions arise regarding both the leaps Rodin makes in his conclusions and likely his agenda. In all honesty, this is a bit too much. Yeah, a bit too much, and just out of place commentary on numbers and with nature. And so on. So let's go over further. So let's look at the fallacy of reification. So Marko Rodin, in every article and video he has ever produced, I've seen most of them, or pretty much all of them, turns the abstraction of numbers into concrete physical reality. In other words, reifies numbers. The mainstream Wikipedia definition of reification is shown below. Reification, also known as concretism, hypostatization, or the fallacy of misplaced concreteness, is a fallacy of ambiguity when an abstraction or abstract belief or hypothetical construct is treated as if it were a real event or physical entity. In other words, it is the error of treating something that is not concrete, such as an idea, as a concrete thing. A common case of reification is a confusion of a model with reality. The map is not the territory. So Rodin perfectly exemplifies this fallacy in his following sentence: physics is the base 10 number system. That is, again, ambiguous, and it's it's abstract just abstract thinking that's making it concrete. How can someone say physics is the base 10 number system? This is just a abstract idea, and then this is physics. Even physics is abstract when formulating it towards nature. But anyways. Alright, going further, I just added this pretty interesting, it's a very interesting, good philosophical example of reification, is in mistaking one's name, occupation, personality, hobbies, etc. with who they actually are. Who are you? Not what's your name or what you do. That's a grand question to ask. It is going further. So grand coil claims. Beyond just reifying math and claiming that the number 9 is divine, the main claim is in regards to boosting electromagnetic coils' efficiency and capabilities by simply changing the geometry. So here's from another link on that website. So computer processors and operating systems. Yeah, so the Rodin solution enables Marko Rodin to design circuitry for computer microprocessors that have no waste heat and thus require no refrigeration or heat sink, eliminating all friction, resistance, and parasitics. This is possible because Rodin knows the natural pathways that electricity wants to take without forcing it, scientifically known as the longest mean free pathway of least resistance. Rodin has discovered the source of the non-decaying spin of the electron. Rodin uses electricity's own magnetic field to bathe conductors in a magnetic wind to maintain constant temperature without any risk of short-circuiting or incinerating conductors. So here's a winding in the supposed vortex coil design. So it's basically saying that setting it up in that vortex coil design gets some superconducting coil somehow. So going further, so more claims. Marko even makes claims of space travel and cancer treatment, and with the help of an also defunct website / company NASA-Inc. hashtag. Interesting name. So interesting. Let's just read this here. So it also archives a PDF of it on his website. That's no longer existing. So NASA-Inc. North American Sales and Advertising Inc. So Marko Rodin devices, also markorodin.com. I think that just redirects to his YouTube channel now. Again, this is all from 2000. This is date archive 2013, but this is from 2000. I think the link's on there, 2009 or so, or somewhat. So going further, so these are the claims. Yeah, so space travel, vertical lift craft. Space travel will be revolutionized by reactionless drives, flush thruster atom pulsar that are unaffected by the weight they pull, making the present day combustion rocket engine obsolete. Benefit can transport satellites and there's an extra space there. Anyways. The grammar is a bit off. Anyways, can transport satellites and astronauts into space inexpensively without creating any pollution and make mankind intergalactic. So he has design and proof of concept, require engineering and prototype, cancer treatment, new improved devices. Life-saving medical devices based on the Rodin coil torus are currently being manufactured. Where? Are currently being manufactured and used in the treatment of cancer patients. Have design, requires engineering. And so that's it for this introduction on this. Interesting, I could have gone many hours with this many defunct websites, and also other proponents of Vortex Math that are also push in my opinion, just absolutely ridiculous claims, because and it's not even because the claims are far-fetched, it's because there's no backing to it. The actual Vortex Math, interesting, but then there's a big jump to stuff that there's no connection. There's no connection stated or explained. So anyways, we'll maybe discuss those in a future video. And especially because if you've been watching my channel for long enough, you'll realize that my view is that space travel, cancer treatment, or cures, etc., those are all real. But these claims as to the Vortex Math and it's a bit out there. Alright, so now that I've covered over the introduction, which involved very little mathematics, and basically just jumps to the claims, and I've seen a lot of Vortex Math videos, but very few have actually even bothered to try to dissect the causation of the patterns, as opposed to just get some patterns in and then all of a sudden some pretty far-fetched claims. Anyways, let's just jump right in. So, overview of base number systems. To help understand patterns in mathematical number systems, it is important to first get a grasp of number systems in general, which I will go over in this section. So, the number 10 in general number systems. The mainstream Wikipedia definition of quote base or quote radix is shown below. Alright, so here's radix. In a positional numeral system, the radix or base is the number of unique digits, including the digit 0, used to represent numbers. For example, for the decimal or denary system, the most common system in use today, the radix or base number is 10, because it uses the 10 digits from 0 through 9. Radix is a Latin word for, quote, root. Root can be considered a synonym for base in the arithmetical sense. So let's consider the base 10 number system, which is comprised of the numbers 0 to 9. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now incrementing past the largest single digit 1 is by convention equal to 10. So 9 plus 1, we restart, we add a 0, and now we have 10. Okay, so the number 10 signals a quote transition beyond the single digit base numbers 0 to 9, and it basically cycles back and to the 0. So we have basically goes to 9, and all of a sudden we put a 1. So yeah, basically cycles all the way back here and goes here, and we just increment by 0 there. And then the next one will be 11, 12, 13, and so on. So so this transition also restarts the same 1 to 9 counting scheme, but with an extra 1 digit indicating the digit to the right is added to 10. So in other words, we'll have 10, 11, or 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, or we could write it as 10, then 10 plus 1, 10 plus 2, 10 plus 3, 4, 5, 6, 7, 8, all the way to 9. So we have this extra 10 there indicating we've gone past, so that's going to be 10 digits, or 9 plus 1 digits. And likewise, the transition beyond 19 gets restarted at 20, and so on for for 30, 40, etc. So we have 1, 2, 3, 4, all the way to 9, then we jump to 10, 11, 12, so we have 1, 2, 1, 3, 1, 4, all the way until 19, and now the next digit, there's no other unique base digit, so we have to jump to the 2. So now we have 2, 0, all the way, 20, 2, 0, or 20, 21, or 2, 1, 2, 2, 2, 3, so and so on. Now incrementing past 99, because we do this all the way for 30, 40, all the way to 90, and then incrementing past 99, because now you have both these digits are the maxed out of the base digits, the biggest number, which is 9. So this restarts to 100, so we just add 2 zeros now. So 99 plus 1 is 100. Likewise, incrementing past 999 restarts the count from, restarts the count to 1,000, or restarts at 1,000. So we have 999 plus 1 is going to be 1,000. And then transitioning further just means adding more zeros. We have 10, 100, 1,000, 10,000, 100,000, 1 million, etc. So we just add more zeros, or we write this as 10 to the power of 1 for the 10. 10 to the power of 0 is going to be just 1. So 10 to the power of 0 equals 1. That's just the by convention. I'll include that later. Alright, so likewise, going backwards requires crossing the quote 0 transition and follows the same pattern but with negative numbers. So if we go backwards, this is 1, 2, 3, 4, all the way, this is positive 1. So go backwards, we just add a negative sign. So we have negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way there. And then we just add, now it's going to be negative 10 as the transition. Then we go negative 11, negative 12, or 1, 2, 1, 3, etc. So we just add a negative sign there. Yeah, so we've covered base 10, but let's look at an example that involves different bases, just to show that this number 10 can be viewed as a transition beyond the base number system. So if we look at the base 4 number system, so to illustrate the use of the number 10, let's consider the base 4 number system, which has the following single-digit integers. Note that integers, again, are just whole numbers. So we have 0, 1, 2, 3. So these are four single digits of the base 4 system, so you include 0 there. And now incrementing past the biggest number, biggest integer 3, or biggest number 3, the usual convention is again to set it to the number 10. So 1, 0, we just restart. So 0, 1, 2, 3, and then 10. And 3 plus 1 is defined as 10 in the base 10 or base 4 number system. And incrementing further, we get the usual as expected. So we have 0, 1, 2, 3, and then 10. Then 1, 1, 1, 2, 1, 3, and then we get to the 20, and we keep going, 21, 22, 23, then 30, because remember, it's we're going in 4s, so this is every 4, but now, yes, the next one's 31, 32, 33, but there is no number 4 in either case, so it's maxed out, so we jump to 100. So this is the 100th number there, it's number 100 in base 4. And then we go the same exact as the base 10, but we cut off at the 3, so 101, 102, 103, and then 110, or 110. Yeah, so we just jump there. Similarly, the transitions are in the same notation as in base 10, so we have 10, 100, 1,000, 10,000, 100,000, 1 million, but again, it's in base 4, so they don't actually equal the usual 1 million that we think of in base 10. And then you could write this as well in powers form, so 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, etc. And yes, a reminder that the actual value of the quote 10 is dependent on the number system, even though the notation is the same for different number systems. So 10 in base 4 is not equal to 10 in base 10. So now let's look at another example just to illustrate it further. So base 10 number system. Lastly, let's consider the base 10 or binary system, which is widely used in most computers. So the integer for base 2 are 0 and 1, so just 2 of them. Incrementing past the biggest integer 1 gets a similar sequence. So we get 0, 1, then 1 plus 1 is going to go to 10. Then the next one's 1, 1, and then next is add 2 zeros, then 1, 0, 1. And so then we have 1, 0, 1, 1, 10, 1, 11, and then we have 1,000, and again, we just do the exact same thing. So we have this 1, 0, 1, 1, 0, 1, 0, and then, so 1, 1, add another 0, 1, 0, 1, add another, just increment past that. Actually, I think I made a mistake there. So this should be 110. Remember, this is 1101. So then the next one, this needs to increment, and that goes to 0. And then this is going to be 1111. And then there's a 10,000. So yes, that should be right. Let me know if I made a mistake anywhere. But yeah, it should be correct. So anyways, so once again, the transitions are in the same notation as in base 10 or base 4 number systems. And that's, again, 10, 1,000, 100, 1,000, 10,000, 100,000, etc., 1 million, etc. 1 million, where, again, in base 2, or binary does not mean 1 million in base 10 or base 4. Or you can write it as 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4, 10 to the power 5, etc. Alright, so now let's take a look at converting a number system. So the conversion between number systems depends on the relative value of the transition number, quote, 10. The number 111, not its actual value, can be written in the same way for base 10, 4, 2, or any base number system in general, just because the number or the digit 1 is included in all of these base number systems. So 10 is included from 0 to 9, and this one's included from 0 to 3 for the 4, and for binary 1 is the only digit, just 1, 0 to 1, or if you include 0, so 0 to 1, and so on. So we could write these all, and it's all going to look in the same format. So 111 equals to 100 plus 10 plus 1. Which equals to 10 to the power of 2 plus 10 to the power of 1 plus 10 to the power of 0, where note 10 to the power of 0 is equal to 1, which is equal to just any number to the power of 0 by definition, and but 0 to the power of 0 gets a little tricky, but we won't be dealing with that in this video. Anyways, let's go further. So the conversion from most bases to base 10 is relatively straightforward because most calculators, including the built-in one-node calculator, which I'm using for these video notes, is in base 10 by default. So that means if we have this 1 plus 1, this one's built in. If I just press space, it automatically calculates to 2. So it's automatically calculated. But if I was trying to calculate in base 2 right here, so 1 plus 1 equals 2, we'll have to type this manually because it's base 2. There's no number 2. There's no digit 2. It's only 0 and 1. But I have to manually calculate that, or manually type that in. So that's 1 plus 1 is 10 in base 2. But notice the conversion right here. 10 base 2 is equal to 2 base 10, because these are just 1 plus 1. 1 plus 1, these are the same value. So the exact value is of base 2, the number 10 or 10 is equal to 2 in base 10. So thus, to convert the number 111 from base 2 to base 10, we can simply replace the transition number, quote, 10 with a relative value of 2, and then simply add up the terms using the base 10 calculator. So if you have 111 in base 2, this equals to, well, 10 to the power of 2 plus 10 to the power of 1 plus 10 to the power of 0, as I went over earlier. And now we just replace the 10 by 2, so we have 10 to the power of 2 plus 10 to the power of 1 plus 10 to the power of 0. This is all base 10 equivalent, and we just calculate these up. So 2 to the power of 2 is just 4. And then 2 to the power of 1 is 2, and then 2 to the power of 0 is 1. So what we have is 4 plus 2 plus 1 is just 7. And here's automatic calculator, 7. Alright? This means that 111 in base 2 is equal to 7 in base 10. We can see that this is true by counting in base 10 the numbers in base 2 up to and including 111. So we have 1 and then 10, 1, then 10, that's 2 numbers. Then the next one after that is 11, and then we get so we maxed out these 2 digits. We needed another 0, so another 2 zeros. So 100, then 101, 110, and all of a sudden we get this 111 number. And these are 5 numbers. So there's 2 numbers on top. There's 5 numbers. So 2 plus 5 is 7 numbers, which is base 10 count. So 111 is equal to 7 numbers in base 10. So that's the conversion. So likewise for base 4, the transition number now has the transition number, quote, 10 has a value of 4 relative to base 10. So thus, to convert this to base 10, we'll do 111 base 4 is equal to 4 to the power of 2 plus 4 to the power of 1 plus 4 to the power of 0. Now this is going to be written, now this is base 10. So this equals to 16 plus 4 plus 1. 4 to the power of 2 is 16. This is 4 times 4, and 4 to the power of 1 is 4, plus 1, and you add these all up, you get 21. Here's the automatic calculator, 21. So that means 111 base 4 is equal to 21 base 10, and we can count these up as well. So 1, 2, 3, and then 10, that's 4 numbers. And then we go 1, 1, 1, 2, 1, 3, and then we go to the 20, or 2, 0, we have to jump there. So 2, 1, 2, 3, 2, 2, yes, 2, 1, 2, 2, 2, 3, the next one's going to be 3, 0. and we go 3, 1, 3, 2, 3, 3, and then we add another 0, go to the 100, so 1, 0, 0. These are 12 numbers. You can see this is going to be, let's see, this is going to be 4 plus 4 plus 4. Yeah, so 12 numbers. The first one's 4 numbers, and then 12 numbers, and then the next one after this is 1, 0, 1, and then 1, 0, 2, 1, 0, 3, and then 1, 0, 1, 1, 0, and then after that is 1, 1, 1, that's 5 numbers. So we'll have 4 plus 12 plus 5, 4 plus 12 plus 5 is equal to 21 numbers, or base 10 count. So that's how you can, double check. That's exactly the same thing. So now converting from larger base numbers to smaller base number systems is similar. Yeah, but for those cases, it requires accounting for the extra digits not present in the lower bases. So yeah, so for example, base 10 to base 4, you're gonna have the deal with the number 9, the number 5, number 6, etc., even the number 4. So so to do that, we'll do right here. So 10 and base 10 is equal to, well, 4 plus 4 plus 2. Yeah, so I had to actually write that out there, and notice this 4 and base, we could just add these up. So this is gonna be 2 times 4 is just 4 plus 4. Plus 2, and now this 4 and base 4, because we're converting it, in this case, to base 4, this is going to be 2 times 4 to the power of 1 plus 2 to the power 2 times 4 to the power of 0. Just include that 1 there, that's invisible, because 1 times 2 is just still 2. So now we'll change this into 10 now. So this is written in this form, but this 4 doesn't exist in, this 4 is equivalent to 10 in base 4, so we go 2 times 10 to the power of 1, plus 2 times 10 to the power of 0, and base 4. In other words, we get now 2 times 10, because 10 to the power of 1 is just 10. So 2 times 10 is 20, plus 2 times this is just 1. So 2 plus, 20 plus 2, base 4. So we have 22. And we can see that this is the right way as well by, again, counting up. So if we go look at base 4, so we go 1, 2, 3, and then 10. That's going to be 4 numbers, and then 1, 1, 1, 2, 1, 3, then go to 20, and then 21, 22. These are 6 numbers. So in other words, we have 4 plus 6, 10 numbers. So 4 plus 6 is 10 numbers, base 10 count, so they're equivalent. Similarly, converting from base 10 to base 2 is visualized as follows. Again, just for completeness, we have 10, base 10. Yeah, from base 10 to base 2, this is visualized as follows. So 10 base 10 is equal to, I'll put this as 8 plus 2. And the reason for that is because 8 is just 2 to the power of 3. So we just wrote it as a power. And then this 2 is just 2 to the power of 1, and there's no 2 to the power of 0. So we just have this now. So then convert this into base 10, so write that as a 10. So 10 to the power of 3 plus 10 to the power of 1, because this relative value 2 goes to 10. And now we have this, and this just equals to, well, 10 to the power of 3 is equal to 1,000. So yes, 10 to the power of 3. 10 to the power of 2 is 100, 10 to the power of 1 is 10. So we have 1,000 plus 10 to the power of 1 is just 10. So we have 1,000 plus 10 is just 1, 0, 1, 0, base 10, and base 2. And we can confirm this by, well, writing this out or expanding it or counting it. So we have 1, 1, 10, 1, 1, then 1, 0, 0, 1, 0, 1, and then we have 1, 1, jumps there, 1, 1, 1, and then 1,000 right there. That's 6 numbers. So we have this 2 numbers, 6 numbers, and then we got to keep going to this number. So we go 1, 0, 1, 1, 0, 1, 0, 1, 0. So that's 2 numbers. So we have 2 plus 6 plus 2. That's 6 plus 4, that's 10 numbers, base 10. That's pretty amazing stuff. And lastly, we can convert from base 4 to base 2 as follows. So we could write this 10 base 4. This equals to, well, 2 plus 2. Because again, this is base 4, so that's the equivalent value of 4 in base 10, or 2 plus 2 in base 2. That's just 2, this is 2 to the power of 2. This just equals to 4. Or 2 to the power of 2, or 2 times 2, same thing. And this equals to, replace that with a 10. So 10 to the power of 2, base 2. So in other words, 10 to the power of 2 is 100. So 100. And we can see that. So we go 1, 1, 0, 1, 1, and then we go 100. 4 numbers, base 10 count. Just to show that they're equivalent. So we have 4 numbers, the same value as this 2 plus 2. And this is the number 10 in base 10. And base 4. And which is as expected. Again, 4 numbers, base 10 count, just because used to that counting method. So now, since most calculators are in base 10 by default, and my brain and most people's brains, it can be tedious to convert from and to non-base 10 systems. Now, nonetheless, I have developed a simple base 10 to base X conversion calculator on Microsoft Excel, which calculates as per the following example. Just illustrate how it does it here. So if we have base 10 to base 8, or octal, this is also called octal, and there is a built-in function in Excel to convert to octal or binary and so on. So we have base 10 to, so if we have a base 10 number 11, we want to convert it to base 8. What we'll do is, the procedure is divide 11 by 8. So if 11 divided by 8 equals to 1.375, then separate this out into a whole number plus the remainder, so 1 plus 0.375. Now if we have 0.375 times 8, that equals to 3, so it's it goes evenly into 8. So that means if we just move this 8 over here, so 3 over 8 is equal to 0.375. So what we could do is we can write this as 11 over 8 equals 2, and we're going to write this number 1 as 1 divided by 8 times 8. So we're not changing anything here. We just have divided by 8 times 8, that's 1, it goes over there. And then there's going to be plus 3 over 8. So we'll show you why we're doing that in a bit. So next step is 1 divided by 8. Divide this out. We're going to have 1 divided by 8 equals to 0.125. And then write this as a remainder plus, the whole number plus remainder. And the whole number is 0 in this case, plus 0.125. And 0.125 times 8 gets an even number, or a whole number 1. So that means just divide this 8 over here. 1 over 8 equals to 0.125. So that means 1 over 8 equals to 0 plus 1 over 8. And the 0 is redundant, but I'm just going to keep it there so that we know when to stop. So 0 over 8 equals 0. Just stop here. And now, let's bold this one. So the next step is we can write this all together. So we'll have 11 over 8, which equals to this over here. 11 over 8 equals to 1 divided by 8 times 8 plus 3 over 8. And then we're going to add this inside this 1 over 8. We're going to put this inside here, and then we're going to get this entire formula there. And then multiply this 8 out, expand this whole thing out. So we're going to have a 0 times 8 plus this is going to be 1 over 8. So those cancels. We're just going to have a 0 times 8 plus 1 plus 3 over 8. So that is what we have thus far. But this is 11 over 8. So now we'll multiply everything by 8 to get rid of this 11. So 11 equals to 8 times 11 over 8. So then when we multiply this all out, what ends up happening is, well, this 0, we're going to have 0 times 8 is going to be, 8 squared. So 8 times 8. And then this 1, we're going to have times it by 8, which is 8 to the power of 1. And then we're going to have this 3 there. 3 over 8 times 8, that just cancels into 1, or 8 to the power of 0. That's just equal to 1. And then we can convert this into base 8. So 11 base 10 is equal to 0. Write this as 10, because remember it's 8. This is base 8, so that's in base 8 will be just 1, 0. So 0 times 1, 0 times 10 squared plus 1 times 10 to the power of 1 plus 3 times 10 to the power of 0. In other words, those are the transition numbers, and this is base 8. So we can just add up these terms. This is going to be 11 base 10 is equal to 0, 1, 1, 3 base 8, and the 0 is just redundant. It just tells us when to stop our algorithm. So we're going to have is equal to 113. Or just 13 is the number. And we can see that here. Here's the Excel sheet. There's a link to it. And here it's in the worksheet base 10 conversion. So yes, keep hold of this one. I'm going to use this Excel sheet in this video throughout, and likely the future videos. So we have base 10 number. Here's the exact procedure. So we have a number 11 like here, and there's the base. We want to convert this into base 8, and this is base 10 there. And it's number 11 base 10. And also there's an octal base 8 conversion within Excel. It shows automatically goes to 13. And there's a check. It just subtracts this 13 from this to see if it's correct, and 0 is checked. There's also a binary one here. Just ignore this check because it depends on the binary. Binary is base 2, octal is base 8. Like an octopus, I believe that's 8. Yeah, octopus, I believe there's 8 tentacles and so on. So anyways, so if we divide this out, so we start out by this number base 10. 11. So if we have 11 divided by 8, we get this 1.375. It's the starting one. It's the only part that's not part of this formula where I divide this into here. So anyways, so we'll have round down divided by base, but except this orange one, which is this. So this divided by here, by 8, we get to this point right there. And then this equals to, we'll round down, it's going to be 1 plus 0.375. But then if you multiply that, that's just 3. That's our 3 over 8. Yes, that's our 3 over 8. This part right here, this is times by 8. And then the next step is going to be 1 divided by 8, which is divided by 8 right there, 0.125. It equals to 0 plus 0.125. So we've finished there, and that just equals to 1 times by 8 equals to 1, like that. And then you just add up the digits. It's going to be 0, 1, 3, but in this case, yeah, 0 is ignored. So 1, 3. And decimal or base 10 sum, that's going to be 4, 1 plus 3 is 4. Anyways, note that decimal refers to base 10. Alright, so now let's keep going further. Now let's look at another example just to illustrate further this conversion, and hopefully it gets ingrained into your head. And it will be very useful once we go further into the Vortex Math patterns. So example 3, base 16 or hexadecimal or hex number system. The base 16 number system, known mainly as hexadecimal or hex, uses 16 single-digit numbers slash symbols or letters, and which are commonly chosen as follows. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10 total, including the 0. And then we start at A, B, C, D, E, F. So we have 0 to 9 is 10 digits, and we have A to F is 6 digits, so A, B, C, D, E, F. Yeah, so once again, the number 10 indicates a transition beyond the single digit 0 to F. So 0 all the way to F here. So if you increment beyond that, so 10 is equal to, well, the biggest digit is F, so F plus 1. And then we could write this out as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Then 10, 1, 0, and then we go restart again. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. All the way, we have this 1, 9. Then we have 1A, 1B, 1C, 1D, 1E, 1F, and then 20, or 2, 0, 2, 1, 2, 3, 2, 2, 2, 3, etc. The hexadecimal system is used widely in computing to represent binary numbers in a human-friendly way. The following example illustrates the conversion from base 2 to base 10, then to base 16, and then again going to base 10 in between, because the calculator is built in base 10, as most are, so it's convenient to just convert to this, and then we can convert to that straightforward. So if we just make a note as well here, so 1 byte in computing is equal to 8 bits, which equals to a string of 8 binary or base 2 1s or 0s, and that means you can have equals to a value, any value between 0, 0, 0, 0, 0, 0, or 8 zeros to 8 1s. In other words, from 0 all the way to this value right here, and once we get to solve this example, it's going to be 255 in base 10. But both numbers, the 0 and 255, are both stored in 8 bits in common computing practice. So 8 bits or 1 byte to store these numbers from 0 to 255. Alright, so now let's look at this 8 bits right here, and let's try to convert it into base 16. But first, let's convert it to base 10. So this is 8 1s, that's base 2, and we could write this as our typical fashion, break these all down into their components and sum them up. But here I'm going to write them from right to left. So we have 1 plus 10 plus 100 plus 1,000 plus 10,000. Again, it's in binary all the way to 10 million. This is just 7 zeros plus this digit right here. That's 1, so it's 8 digits total. And then if we write this in our power notation, this equals 10 to the power of 0, which equals to just 1. And then 10 to the power of 1, which is 10. Then we have 10 to the power of 2, all the way to add 10 to the power of 7. And now we can convert this to base 10 just by changing the relative value of 10. So 10 in base 2 is equal to 2 in base 10. So what we could do is now, just write 2 to the power of 0 plus 2 to the power of 1 all the way to 2 to the power of 7. And then with the built-in calculators, press equals, goes to 255. So it automatically calculates 255 like that. And now what we'll do is do a shortcut to convert this. Note that now if we look at base 16, so so the number 10 in base 16, this adds a relative value of 16 in base 10. Again, note that even the base number, so 16, is also written in base 10. So yes. Yeah, so everything is by default base 10. So this relative value is 10 equals to 16. And now if we look at 100, this is base 16. Yeah, the 100, this is going to be 16 squared in base 10. If you write equals, this equals to 256, like that. And interestingly, the reason we're squaring it is because if we look at over here, if we look at, if you write 2 to the power of 4, and this is using this number 2 for the binary, this equals to 16. So in other words, this 256 is equal to 2 to the power of 4 squared, which is going to be 2 to the power of 8, equals 2 to the power of 8, like that. Yeah, and as a side note, 2 to the power of 8, yeah, just notice that. So 2 to the power of 8, that's just one above it, and if you write that in base 10, base 2, we could write 2 to the power of 8 base 10 is equal to 10 to the power of 8, just working backwards, base 2. So this just means we'll have 1, and then we'll have 8 zeros. So we'll have 1, 2, 3. Let's go 1, 2. Actually, not 3. Let's put like that. So 100, and then 1, 2, 3, 1, 2, 3. So we have 3 plus 3 is 6, plus 2 is 8. So we have 8 zeros as opposed to the biggest term, and this one is 10, like that. So that then if we subtract 1, we're just going to get this 1, 1, 1, 1, 1, 1. Anyways, that's an interesting side note. So now let's keep going further. So if we look at this number, this is 100 base 16 is equal to 256 base 10, which is which is if we subtract by 1, we get over here. Whoops. Yeah, whoops. So let's do that again. I don't know why it's not doing this. Yeah, so we get it like that. Yeah, he just made an arrow better. So if we subtract by 1, we get this term right there. So in other words, 100 minus 1 in base 16 is equal to 256 minus 1 in base 10, which equals to, well, 255. And now this is base 16. This is, again, 100 is going to be, or 100 minus 1 is going to be it's going to be 2 digits of the largest base 16 single digits, which is FF. Yes, which is F. So that's going to be FF equals to 255. And yeah, so this FF equals 255, and we could see that. Let's just go back over here and let's just expand this. Yeah, so if we expand this further all the way until we get the biggest digit, which is F. So we go 1, yes, we have, once you pass the letter F or the number F, goes 1, 0, then 1, 1, 1, 2, all the way to 1F, then we jump to 2, 0, and then eventually we're going to jump to F. So we're going to have F0, F1, F2, and here I just added the rest, so F4, F5, F6, F7, F8, F9, all the way until then we get to FA, BC, FB, FC, FD, FE, FF, and then once we're maxed out our single digits, we go to 1, 0, 0. So in other words, 100 minus 1 is going to be FF. So, and that's why it's human friendly or it's considered human friendly in computing, because we could write 1 byte, which is again a string of 8 digits, which is the numbers from 0 to 255 in base 10. This equals to 8 bits, which equals to 8 ones or zeros. Or for completeness right here, so 8, yeah, so it equals to 8 zeros, 2 8 ones, and base 2. Again, that's hard to read. Hard to read manually. But it's good for computers. And then this equals to 0 to 255 base 10, or 0 to FF. So yes, if you have FF, that just equals to 1 byte of all ones. So yes, much easier, and that's base 16. So yes, hopefully follow along there. Alright, so now that we've covered converting different number systems, now let's look at summing of integers and the remainder after division. This is the key aspect of Vortex Math, or one of the main ones. Actually, it is the main one. So the key aspect of Vortex Math is the continual summing of digits to get a singular digit. For each digit sum, or quote vortex sum, I will use the terminology quote v equals vortex sum, just to indicate when I sum the digits of the number. Let's consider the number 11 and in base 10. Again, so so for each digit sum, I'm just going to write v equals. So let's consider the number 11 in base 10. So 11, I'm going to put v equals, I'm going to sum the digits. So v equals 1 plus 1 equals 2. Since we are using base 10, we can write the number 11 instead as follows. Yeah, notice what happens here instead if we write it like this. So instead of just summing up like that, what we could do is we're using base 10, we could write the number 11 as follows. We could write 11 equals to 10 plus 1, just for the normal terminology. And then this 10, that just equals to 9 plus 1. So 9 plus 1 plus 1. Yeah, then yes, we'll have 9 plus 1 plus 1 equals to 9. And then move this 1 outside. Yeah, just move it outside of the 9, just move it like that, outside. And then what we're going to get is... yeah, we're going to get 9 plus 1 plus 1. Put that in brackets just to make it separate. So we're going to have 9 plus 2. I did that extensively, yeah, but that's obviously going to be 9 plus 2 is 11. But the reason I'm doing that is, notice we have 11 equals to 9 plus 2. And now if we divide 11 by 9 and simplify the fraction, we get, well, 11 over 9, 11 divided by 9, just put in the calculator, equals 1.2222, and it keeps going on and on. In fraction form, what we could write is, well, let's just write this, expand this out. So 11 over 9 is in fraction form. This equals to 10 plus 1 over 9. Again, this 10 is equal to 9 plus 1 in base 10. Plus 1 over 9, like that, and then move this over, so we're going to have this equals to a 9 plus 2 over 9. And so right here, what this equals to, we could just move it all the way over here. So this 9 plus 2, 9 divides by 9 evenly, that's just going to be, or just for completeness, just write it like this, 9 plus 9 over 2 plus 9. Yeah, just write this out like that. 2 to the, so 9, this 11 over 9 equals to 9 divided by 9 plus 2 over 9. And this divides out evenly. This is going to be 1 plus, except this 1 doesn't. So the 9 over 9 is just becomes 1. And then this one's going to be 2 over 9. So in other words, we have 1 plus a remainder. This is considered the remainder. Or I'll put the arrow opposite this way. This is the remainder of a division. And notice that the this vortex sum, this goes to, or this digit sum, vortex sum is 2, and then we can write this as 9 plus 2, and then we divide this out, we get a remainder 2. Yeah, so thus 11 over 9 is equal to a whole number 1 and a remainder 2 that doesn't divide cleanly, so there's a 9 over there still. Let's try this for a bigger number, just to illustrate it further. Let's try this for a big number 6, 7, 8. So if we look at number 6, 7, 8, we get, if you look at the vortex sum, or the digit sum, v equals, so 6, 7, 8 is just 6 plus 7 plus 8, and this equals to, equals to 21. And then this sums up to 2 plus 1 is 3. So yes, 2 plus 1 is 3. But now if we divide by 9, again, this is all base 10. So we divide by 9, 6, 7, 8, divide by 9, this equals to 75, 75.333. Yeah, notice the other interesting thing. So we have this 3 there, there's a 3 there as a remainder, this is the sum, and I'll show you it's always going to be that. This one's a 2, there's the 2, and there's the 2 remainder. So now if we write this out in fraction form, so we get 6, 7, 8 over 9, this equals 2. And now we're going to do some next level MES derivations. So this is going to equal to 600 plus 70 plus 8, like that, over 9. Yeah, so we're just expanding those, and this is going to equal to, well, the 600 is just equal to 6 times 100. Write this in as simple terms as we can, plus 7 times 10 plus 8, like that. I'll divide this by 9. And now what we'll do is get rid of this generic 100 or 10, and we're going to write that in base 10 terms. So we're going to do 6, this is going to be times, 100 just equal to 99 plus 1. Or, let's write it like this, so 1 plus 99 is equal to 100. And this is going to be, next one is going to be plus 7 times 1 plus 9, like that. And then the next one just 8. Just leave it there. Because it's because we have the 10 to the power of 0, that's just 1, so no point in over complicating everything. So I don't know why that keeps happening. Alright, so now that we divide this all by 9, and now what we'll have is, is this here, but now if we expand further, what we'll have is a 6. 6 times 1 is just 6, plus 6 times 99. Just leave it like that. And then next one's going to be plus 7. Yeah, plus 7, and then plus, 7 times 1 is a 7, plus 7 times 9. Just leave it like that. And then plus 8 over here. I'll divide this by, again, I don't know why my OneNote is doing that. So now divide this by 9 like that. Alright, so what I'm going to do is I'm going to move this over to this side, as well as this 6, and leave those others on their own, and then divide this all out by 9 on both sides. So we're going to have, this equals to 6 times 99 plus 7 times 9, like that, all over 9. And this is going to be now the next one plus, over here, 6 plus 7 plus 8 over 9, like that. And we already know what 6 plus 7 plus 8 was. That's just over here. This is 21. Or since we're doing everything manual, let's just solve this manually right here. So 6 plus 8, that's just equal to 10 plus 4, so that's 14. And then, plus 7 is 21. So in other words, 6 plus 8 equals to 14. 14 plus 7 equals to 21. Yeah, so what do we have here? This part right here, this can divide easily because this is just a factor of 9. There's 9s everywhere. Factor of 9. So we can divide this easily through. And this 21 is the remainder. That's just the remainder of this first division. But we can continually go on. And notice it's 21, exactly as we have here 21. Then we do the next step. We should expect a 3. So that's a factor of 9. Let's just divide everything out there. This equals 2. 99 divided by 9, or 6 times 99 divided by 9, we just divide this out. 99 divided by 9 is equal to 11. So that just equals to 6 times 11. And this 7 times 9 divided by 9, that just equals to 7 times 1. So this equals to plus 7 times 1. Now this next part is going to be 21, or not plus, equals plus 21 over, 21 over 9. There's the remainder, 21, like that. And now what we'll do here is, well, this part right here, repeat division. So let's just do this part again. Because this 21 is greater than 9. And I'll just write since 21 is greater than 9. In other words, it could still be divided further out. So what we'll have is, let's keep these all in there. 6 times 11 is going to be 66 plus 7. Times 1 is just 7. And now this next one, this equals 2 in the usual notation. Just break this up again. It's going to be 2 times 10, or 2 times 1 plus 9. And then plus 1. That's just plus 1 like that. I'm just doing exactly as we did before. Then divide this by 9. And now this part right here, 66 plus 7, that equals to the 70 plus 3, so 73. Like that. Plus right here, we can multiply this 2 inside. So we're going to have a 2, and then there's a 1 there to separate the 9s and 2s. So what we're going to have is it's going to be a 9 plus a 2 plus 1. Like that. We have that, and then just divide this out by 9. So now, divide this out by 9. Actually, forgot to times by the 9s, by the 2. So this can be a 2 times, it's 2 times 9. So when we multiply 2 inside, 2 times 1 plus 2 times 9, so 2 times 9 like that, plus over there. Alright, so finally what we end up having is this equals to 73 plus 2 times 9, 2 times 9, divide this by 9, then plus 3 over 9 like that. That's just our 2 plus 1 divided by, this 2 plus 1 over there. Also, write 2 plus 1 for completeness right now. And then divide that by 9. And now right here, this just cancels, it gives us a factor of it. So what we get is a 73 plus 2, which equals to 75, plus, and then 2 plus 1 is 3 over 9. In other words, 678 divided by 9 is equal to 75 plus 3 over 9. This is the remainder. And which equals to our vortex sum. So that equals to the vortex sum as well. And again, we got the 75 over here, 75.333. So we have 75 and 3 over 9 remainder. It's fascinating stuff. So it doesn't divide cleanly in. So once again, the remainder is the same as the vortex sum, which is 3. So there is the vortex sum here, 3. There's the 3, the remainder there, the 75.33. And when you divide it, it's the same thing there. And when we went over this, pretty much this fraction form division, we get that 3 as well. Even the 21 is included in the first remainder, or the first digit sum or vortex sum. So yes, that's fascinating stuff. So now this is in fact always the case, which I will discuss further after covering the modulo function, because basically we're dealing with modular modulo mathematics and so on. So let's go further. Also notice here division by the largest, just make a quick section on division by largest unique digit and repeating digits after decimal place. Let's write that after decimal place. Note that the earlier vortex sum corresponded to the remainder and repeating number after the decimal place. If you had 11, this vortex sum is 1 plus 1 is 2, and 11 divided by 9 is going to be 1.22222, and here 2 divided by 9 is also equal to 0.22222. And similar over here is the 6, 7, 8, the vortex sum is 3, and then 6, 7, 8 divided by 9, 9 is again the highest digit in the base 10 system, equals 75.333, the remainder is 3 over 9, which is 0.33333, so the threes, these all line up. The repeating digit is a result of dividing by the highest unique digit of a number system. In this case, in this case it's 9 for. It is 9 for base 10. So, for example, let's look at this one. So, base 10 has the 10 digits. So, 0, 1, 2, 3, 4, all the way to 9. The 9 is the biggest one. And now, if we look at, just look at an example here, we'll go 3 divided by 9. We could write this out, again, using the fraction method, fraction long division, and so on. But we could write this as, if you multiply top and bottom by 10, so we could write this as, let's write this as 3 over 9. Times it by 10 over 10, so then this equals 2, and just rearrange it, move the 10 on the front side. So 1 over 10 times, and this is going to be 3, 3 times 10 is 30, or just leave it as 3 times 10 like that. Or actually, furthermore, we'll just move this 3 out of there, actually. Leave the 3 there, move the 10 on this side, move the 9 on this other side, just switch these places. So we're going to have a 3 over 10 times it by a 10 over 9. So we have this scenario. And now we could write this as our 9 plus 1, so the highest digit 9 plus 1 for base 10. So we're going to write this as 3 over 10 times it by 9 plus 1. 9 plus 1 over 9, like that. And now what this equals to, this equals to 3 over 10 times it by, now this splits up. So 9 divided by 9 is just going to be 1. And then plus the remainder there is 1 over 9. Like that. So now what do we have here? So what we have here is this 1 over 9. If we multiply this 3 over 10 inside, this is going to equal to 3 over 10, just expand it, 3 over 10 times 1. And plus 3 over 10 times 1 over 9, which equals to 3 over 90, or I'll just put it as 3 over 10 times it by 1 over 9, like that. Or even better yet, just move this 3 and 1, replace them, so move this like that, and that's 3 over there. Where we already know what 3 over 9 is, that's just this scenario. This 3 over 9 is 3 over 9. That's just the starting one, so we just plug this back in. So we get a loop. So we have a continuous loop like that. So then this is going to equal to, well, 3 over 10 is just 0.3. The 10 just divides moves it over 1 decimal place. This is going to be 3 over 10 plus, 3 over 10 plus, and that's going to be 1 over 9. And then replace 3 over 9 with this 3 over 10, put this in a bracket like this, times it by 1 plus 9 over, 1 over 9. So we can just keep repeating the same procedure. This is the same thing as this whole thing. We just moved it over there. And now if we expand this out, this is going to equal to 0.3 plus, this is going to be 1 over 10, multiply that inside. We're going to have a 3 over 100, multiply this 1 inside, it's going to be by itself. And then plus a scenario where now we're going to have move this inside. So move this all the way inside here. We're going to have, so 1 over 10 times 3 over 10 is going to be 3 over 100. And then over here, 3 over 100 times 1 over 9. So we're going to have a 3 over 100 times 1 over 9. Or just move this 3 inside. Just switch the 3's. Switch them over like that. So and now this is the same thing. We keep throwing this inside. We're just going to have this more and more. And where this 3 right there, or this 3 over 100, that just equals to 0.3 plus 0.03 plus, now we have another 100 times it by 3 over 9. And it just keeps repeating on. And again, I just cycle this back in there. See, these are all the exact same things, and just cycle it back in, and we're going to eventually have it as add these up. 0.3 and 0.03 is going to be 0.33 plus 1 over 100 times 3 over 9. And you can keep repeating on and on. This equals to plus 3, 3, 3. Yeah, 3, 3, 3. Keeps going on. And if you put a line up here, it just means the 3 is going over continuously. And also notice here that this one here, just for completeness, this would be equal to, is 3 over 9 is going to be, again, 3 over 10. So you always increment by, this 100 becomes 1,000 and so on. And then this is going to be plus, 3 over 10. Put this like that, 1 plus 1 over 9. And so on. And it keeps going on and on. You can keep going on forever. And yeah, so there's nothing unique about this 3. We could just replace 3 with 1, 2, or whatever, up to 8. And what we'll see is this, up to 8, which is the just before 9, where you get an even division, or a whole number. So we can replace 3 with any integer 0 to 8 to obtain the following repeating digits pattern. So right here we have 0 over 9, this is just 0, or you can consider it as 0.0000. That's a special case. Or if you have 1 divided by 9, so just replace 3 with 1. Replace 3 with 1, all you're going to get is just the 1 there. So this is going to be 1, 1, 1, 1. 2 divided by 9 is 0.0222, etc. And you could even see this. You just press equal, and it automatically calculates as that. And it cuts off there. But yeah, so you keep going on and on. So 8 divided by 9 is 0.88888, and then 9 divided by 9 is just 1. So that you start there. And a similar pattern is expected for base 5, or any base number. So base 5... the digits are 0, 1, 2, 3, 4, and the biggest digit is 4. So if you have, let's say, 1 over 4 now, we can write this as, just for completeness, we multiply the top and bottom by 10 over 10. So this equals to 1 over 10 times it by 10 over 4. So it doesn't change anything. I just write it like that. So times the top by 10 divided by 10. So it doesn't change anything. So now we have this, write this in our usual notation for the highest integer plus 1. This again is base 5. So this is going to be written as 1 over 10 times it by 4 plus 1. 4 plus 1 is equal to 10 or 5, but we're in base 5, so 4 plus 1 is 10, or 1, 0. And then divided by 4. This equals to 1 over 10, and then divide this all out. 1 plus 1 over 4. So there's the cycle. That's much simpler. Yeah, much simpler than that 3, but it doesn't change anything. Just a 1 there, there's 1, 1. And yeah, multiply this out. This is going to be equal to 1 over 10 plus 1 over 10 times 1 over 4. And now we just repeat the same exact cycle. Throw this inside. Throw this whole thing inside. This is equal to 1 over 4. So then we could just throw this inside. Whoops. So you could just throw this inside this 1 over 4. And then we get the exact same pattern. 1 over 10 is just 0.1. And then plus another 1 over 10. And this is going to be square bracket 1 over 10 times it by 1 plus 1 over 4. And then this becomes, expand this out, 0.1 plus 1 over 100. Multiply that inside, plus 1 over 100 times 1 over 4. So in other words, yeah, this is going to be a 0.1 plus a 0.01, then plus this part right there, and you can keep going on and on. 1 over 4, like that. Let's write this a bit neater. Yeah, so we could write this out, and then this is just going to be 0.1111. Again, you could keep replacing this entire thing, put that back in here, and keep going on and on. The next one's going to be 1 over 1,000 times 1 over 4, and so on. This can be non-stop. Alright, so now summarizing for base 5, we have 1 over 4 equals 0.111, 2 over 4 is 0.222, 3 over 4 is 0.333, and then 4 over 4 is just going to be, well, 1, because that's just a whole number. So in general, if we have base n, and then we have 0, which is the number 0, 1, 3, 4, 1, 2, 3, 4, 5, 6, etc., all the way to p, where p is n minus 1. Then 1 divided by p is equal to 0.111. 2 divided by p is 0.222. 3 divided by p is 0.333, etc. Or p minus 1, so the second largest digit, divided by p is again equal to 0 point, and then p minus 1, p minus 1, p minus 1, and then yeah, it keeps going on forever. And then p divided by p is just 1. And yeah, there's some pretty interesting stuff indeed. So let's continue further. So MES convention, vortex sum versus digit sum. Note that whenever I refer to, quote, vortex sum, I'm referring to the continual digit sum until a single digit is achieved. So we have 9, 8, 7, 6, 5. Then what we have is V equals is a digit sum. Yeah, that's a digit sum. So we sum the digits 9 plus 8 plus 6 plus 5. Then we write V equals, yeah, so then this equals to, well, actually we need to sum this first. This equals 28. You could just write equals to 28. This is the digit sum. And then we could go V equals again, so 2 plus 8 equals 10. Actually, yeah, this is not the vortex sum. This is going to be, again, V equals 1 plus 0. Yeah, 1 plus 0. This equals to, yeah, this equals to 1. Which is the vortex sum and digit sum. Whereas this one is, this is just, again, another digit sum. So yes, digit sum just refers to anytime you sum the digits, and vortex sum refers exclusively to the final single digit of the base number system. So now let's go further. So let's look at the modulo operation, which involves determining remainders. Alright, so the process or operation of calculating the remainder is known as the, quote, modulo operation. Here's a mainstream wiki definition of it. So in computing, the modulo operation finds the remainder or signed remainder after division of one number, so sign includes a positive or negative, of one number by another called the modulus. So if you divide a number by another one, the divisor is the modulus of the operation. Given two positive numbers, a and n, a modulo n, abbreviated as a mod n, is the remainder of the Euclidean division of a by n, where a is the dividend and n is the divisor. And yeah, Euclidean division, just the what we were dealing with earlier. Yeah, so thus the remainders of the previous calculations can be written as 11v equals 1 plus 1 is equal to 2. 11 divided by 9 is 1.222. Again, there's a 2 over 9 is 0.2222. Or you could write 11 mod 9 equals to 2. This is the remainder. And it just so happens it's the exact same thing. And here's the automated built-in calculator. Just type equals 11 mod 9 equals that. That's the same thing as writing 11 divided by 9 and finding the remainder. And similarly here we have 6, 7, 8, v equals, this is 6 plus 7 plus 8 is 21, v equals 2 plus 1 is 3, and then 6, 7, 8 divided by 9 is 75.333, 3 over 9 is 0.333, or you could just write 6, 7, 8 mod 9 finds the remainder. And it's always 3. Yes, it's always the same thing. The remainder, and hence mod 9 and base 10, appears to be always equal to the vortex sum. Note 1. The only issue is that when a number has a digit sum of 9, or vortex sum of 9, the mod function will give a remainder of 0. For example, if you have 1 plus 8, if you have 18, v equals 1 plus 8 equals 9. The problem here is 18 mod 9 is equal to 0, because the remainder is going to be 0. So this is the only case that's different. But yeah, so in Vortex Math, I'll just put this as Vortex so we're all understanding what we're doing here. So if it's 0, we just have to set it to 9. Note 2, typical convention for modulo operations is as follows. 12 mod 3 equals, 12 mod 9 equals 3 can be written as, actually here I forgot to show this calculation. So you write equal and it goes to 0. 12 mod 9 equals 3 can be written as 12 equals 3 mod 9. Yeah, in other words, yeah, some people write it like this. They would write, instead of writing 12 mod 9 equals 3, some notation or some convention is written as 12 equals to 3 and then in bracket mod 9 to show that it's a remainder after dividing by 9. But I prefer this one right here. But for the purposes of this Vortex Math video, I will use mainly the v equals notation as well in this case. So thus 12 mod 9 equals 3 can be written as 12v equals 1 plus 2 equals 3. And here actually to provide more info, I just rewrote this. And for the purposes of this Vortex Math video, I'll use the same quote v equals notation used for the vortex sum, since they are since they're equivalent or equal, except when the modulo equals 0. That's the only issue. We'll have it 9 for the vortex sum, as in the proof in the and as in the proof, or better yet, which I prove in the next section below in this section right here. So we could write this as 12 mod 9 equals 3 can be written as 12v equals 1 plus 2 equals 3, or yes, 12v equals 3. A vortex sum is 3, so they're equivalent. So proof. the vortex digit sum is equal to the mod of base minus 1. The modulo function allows for quickly determining the remainder of very large divisions. So yeah, the modulo function allows for quickly determining the remainder of very large divisions. So let's compare the vortex digit sum with mod 9 of very large numbers. And again, we're looking at mod 9 because base 10 is, so base is 10, 10 minus 1 is 9. So if we look at 1, 2, 3, 4, v equals to 1 plus 2 plus 3 plus 4, which equals to 10, and you could just press equals 10 and then v equals 1. So 1 plus 0 is 1. And then, or you could just type in 1, 2, 3, 4 mod 9, and it gets you the right answer. Equals 1. Or if you have 7, 7, 7, v equals 2, and you add these all up, it gets 21. So you have 7 times 3 is 21, it goes to 3. Or you could just write 7, 7, 7 mod 9 equals 3. And likewise, you can go 11, 1, 1, 1, v equals 1 plus 1 plus 1 equals 3. Or you can go 1, 1, 1 mod 9 equals 3. And again, type it in, equals 3. You can also go 9, 9, 9, v equals 9 plus 9 is 27. So again, this should equal to 0. This equals to 2, the vortex sum. But if you have mod 999 mod 9, remainder is 0, so it's 0 as expected. So only this scenario, they're not equal. But we can just set it as equal to 9. So notice that the vortex digit sum is always equal to the mod 9 in base 10, except when it's equal to 0. Let's put that here. Except when the modulo is equal to 0. In fact, it is always equal to the mod n minus 1, and again, just outside of the, except when it's equal to 0. Always equal to the mod n minus 1, where n is the base number system. Note, I will look to do a formal proof in a later video, but the general proof below suffices for this video, because I usually make it super general. But this one is just a general number ABC, but you can expand it to A, B, C, D, F, G, H, just infinite. But yeah, I may do a more mathematical formal one, but this is pretty good still. So for a general number in base 10, let A, B, and C be any integer between 0 and 9. Thus, the number ABC is equal to... whoops, I already have these. These are my notes. Let me just delete that and start again. Yeah, so that's my notes. I usually do a write-up before I start filming. And then now I do it live. So let's go A, B, C. So this number. So if you have the number A, B, and C, so it's A, B, C. This equals to, well, you can expand this out as A times 100. Again, that's the 100th term, or the 2 zeros and then the A there. So again, these are the exact same thing. Imagine it was number 2, it would just be 2 times 100 or 200 or A100. And then this is going to be B10 or B0, or just write this as B times 10. Then plus C. C times 1 is just C. And now we do the same thing as before. So we have A times by, this one's going to be 99 plus 1. Yeah, this is 99 plus 1 times A. Then the next one is going to be the same thing. It's going to be 9 plus 1. Again, we're dealing with base 10. Like that, and a plus C. So you could always do this, and you always have that 1. So that means you're always going to be summing up the digits in the remainder. So A times 99. Like that, and then plus A. I'm just going to move the A over to this side, so we're going to have A plus A right here. And then this next one's going to be plus B times 9, and then plus B. Let's move it all over here. So this is going to be equal to plus A plus B plus C. So what we get is, well, we get this part right here. This is a factor of 9, because there's a 99 and then a 9 there. Factor of 9. That means you could just divide by 9 evenly in a whole number. And then this is going to be the first digit sum. This is the remainder. Or I'll just put the first digit sum. Digit sum. Then we could repeat the process. Yeah, then we could repeat this process right here. So we could go first digit sum. I'll just put it like this. Repeat process, and just put it like that. Repeat, this equals to dot dot dot. Just change up the arrow. So repeat process. Repeat process if this digit sum, so this is, I'll just write this as DS. if ds is greater than 9. So in other words, we're going to write this as a factor of 9 plus another remainder, and eventually we're going to get a dot 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 equals to a factor of 9. Doesn't matter what it is, it's going to be a factor of 9 when we separate the remainder, and then plus a remainder here, like that. That is less than 9. Yeah, so what this means is this remainder, this final remainder, is just going to be the same digit sum. So we're going to be continuously adding the digits non-stop, and this is just going to be digit sum. And then yeah, this is digit sum when this is going to be less than 9. In other words, this equals the vortex sum. Because we just continuously repeat the same digit sum as a plus b plus c, and so on, until we have a digit sum that's less than 9, which equals to the vortex sum. Yeah, so thus the remainder, again, when it is not equal to 0, is always equal to the vortex digit sum, and we can obtain it by dividing the number abc by 9, or the n minus 1. The base n minus 1, or using the mod function to calculate it, which is the number 9. So remainder equals digit sum until it is a single digit less than 9, which equals to the vortex sum. And then if we have ABC, this is equal to a factor of 9 plus remainder. ABC divided by 9, if we divide it, we're going to get a factor of 9 divided by 9, which is a whole number. Then it's going to be plus remainder divided by 9. In other words, calculating this remainder, we could just use the mod function, which automatically calculates it using its own algorithm. So ABC mod 9 equals the remainder. Note again, when the remainder is 0, the vortex sum is 9. We said that. That's the only difference. For any other base system, yeah, we could do the exact same thing, but we're just going to let p equals n minus 1. So for any other base system, let n equals base, p equals 1, and then we'll go abc, or any integer between 0 to p. Thus, number abc for a general base n number system is, and we could just do exactly the same thing as we have here, but replace the p with, the 9 with a p, or just mirror this 9 into a p. So let's do this quickly. Yeah, just to ingrain it into our brain. So we have A, B, C. This equals to A times 100. This is going to be B times 10 plus C. Because remember, the 10s are always, it depends on the number system. So those are just placeholders. This just equals to A is just going to be A times 1 plus P. And then plus here we're going to have B times 1 plus P. Plus C, this equals to, as always, A times P plus B times P plus, and then these A, when you we have an A times 1 and a B times 1, as always, it's going to be A plus B plus C. And then this right here is going to be a factor of P. And then this right here is the digit sum. Sorry, digit sum. And then we repeat the same process. This equals to dot dot dot, and this is going to be a repeat. Yeah, repeat process. Repeat process until digit sum ds is less than 9. This is d dot s. And then what we end up having is just a factor of p, and then plus a remainder. And we can solve this remainder by dividing. Alright, so once again, the remainder, when it's not equal to 0, is always the vortex digit sum. That is ABC mod P equals remainder, which equals digit sum of A plus B plus C until a single digit remains, which equals to vortex sum. Because again, this factor of P, when we divide ABC divided by P, if this is a factor of P, that's just going to be a whole number. So then the remainder is this remainder right there. Now let's put that for completeness. So we have ABC divided by, let's move this over here. So ABC divided by P is equal to, well, factor of P divided by P, and then plus remainder. divided by p. Yeah, so there's the remainder, and then the ABC mod p gets that value. The remainder, which is a digit sum a plus b plus c until the single digit remains, which equals to the vortex sum right there. Alright, so now let's continue further into this pretty extensive video. So using base 10 to determine vortex sum of different bases. So since base 10 is the most widely used base number system and the default that most calculators are programmed with, it is preferred to find the vortex sum of any base number system, but still in terms of the base 10 system. This is especially important since the built-in modulo function in both Microsoft Excel and OneNote are in base 10, or pretty much anywhere you go, it's the default base 10. So for example, if you have 22, which is base 8, the V equals 2, this is a vortex sum, 2 plus 2, it equals to 4. But if we have 22 mod 8 minus 1, again that's n, 8 is n, we'll have, which equals to 22 mod 7, but this equals to 1, which is wrong. So this is not the right answer, because again, this is in base 10. Since OneNote calculates the mod function base 10, we can just convert the number 22 base 8 to base 10. So 22 base 8 equals 2. We could write it again as a 20 plus 2, which equals to, now you convert it, this is going to be 2 times 10, or 10, which is going to be just the equivalent is number 8 in base 10. So 2 times 8 power of 1, or just 8, because 8 power of 1 is just 8, 10 to the power of 1 is just 1. So let's put that for completeness. This equals to 2 times 10 power of 1. Oops, the equals auto calculates. And then this is going to be a, I guess this is going to be plus 2. You could also plus 2 times 10 to the power of 0, which is just, yeah, this just equals to 2 times 10 plus 2. So those are the equivalent. So now we just replace this 8 with this 10 with 8. So we'll have 2 times 8 to the power of 1 plus 2. This equals 2 in base 10. Again, just built in, just calculate is becomes 18. So 22 base 8 is equal to 18 base 10. So now we do 18 mod 7. It should get the right answer. It goes 4, which is right. So there's the right answer. This one's wrong using the base 10 one. You need to convert to base 10. So let's double check with a more difficult number. Let's look at 1, 2, 3, 4, 5, 6. Base 7. This V equals to 1 plus 2 plus 3 all the way until 6. Again, we're adding, remember, we're adding in base 7. So we're not adding in base 10. So you can't just go and do this equals to 21, which is wrong. So we have to do it as this. So this is equal to 7 plus 7 plus 7. Well, let's look how we did that. This is base 7. So 1 plus 2 plus 3 is equal to 6. Or actually, better yet, we'll just do this. 3 plus 4 is 7. I want to write it in 7 because it's base 7. Let's do this again. So this is 7. And then this right here, 5 plus 2 is 7. And then 6 plus 1 is 7. So 7 plus 7 plus 7, which is again, change that into 10. Because these are, this would be in base 10 notation. So it's going to be 10 plus 10 plus 10, which equals 30, which equals to V equals 3, 0, like that. Let's put it right here. V equals 30. Actually, no, just equals to 30. Then V equals to 3. Yeah, and I just removed this right here. All right. Actually, I need the I need the space, so let's leave it back here. So anyways, so now if we do 1, 2, 3, 4, 5, 6 mod 6, which is 7 minus 1, this equals to 0, which is wrong. Because again, it's using base 10, the number. So if we do this, this equals to 0, which is wrong. So because it needs to be 3, this is the vortex sum. So we need to convert this into base 10 first. So 1, 2, 3, 4, 5, 6 equals 2. Well, 1,000 plus 2,000 plus 3,000 plus 4,000, 400 plus 50 plus 6 in again base 7, not base 10. And then you can write these out. This is how many zeros is 5 zeros. So we can write this as equals to 7 to the power of 5 or 10 to the power of 10 to the power of 5, but just to convert it into base 10, so it's going to be 7 to the power of 5 plus 2 times 7 to the power of 4, and then plus 3 times 7 to the power of 3, then plus 4 times 7 to the power of 2, plus 5 This is the second last one. 5 times 7 power of 1 plus 6 times 7 power of 0, which is the 1. And then if you write this out, automatically calculates, you get 22,875 base 10. And now, if we go at 22875 mod 6, which is 7 minus 1, it's right. Absolutely amazing. Now that is, look at that. Look at the size of these numbers and getting the remainder, which is the vortex sum instantly, which is absolutely fascinating. Right, so since the base 7 number system is smaller than base 10, then the remainder, I'll just put so since that is the case, the remainder and hence vortex sum is identical when converted to base 10, since the unique digits 0 to 7 are included in both bases, are identical in notation. Because the value is still going to be the same, but just notation as well. So, for example, if we have base 7 possible remainders, it's going to be from 0, 1, 2, 3, 4, 5, 6, and base 7 possible vortex sums is going to be 1, 2, 3, 4, 5, 6, 7. Because remember, when the remainder is 0, we assign it into 7. So just bold that like that. And then the base 10 unique digits is just going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but the 0 to 7 are included. So if we have if we convert this number into base 10, we're going to get a vortex sum such that the value is going to be between 0 to 6 for the remainder, because what it essentially is doing is converting the remainder into base 10. But since the base 7 is going to be like this, it's going to be maximum somewhere in here, so it's going to be the same notation. However, for base number systems larger than 10, the remainder in base 10 can be in double digits, and larger than 10, thus the notation will not be the same, but the value will be nonetheless. So for example, if we have 19 base 16, this is going to be equals to 1 plus 9, and remember, this is hexadecimal, and 1 plus 9 is equal to A. And then it keeps going on. 11 is going to be it's going to be 1 to 9. All of a sudden, it's going to be A, B, C, D, E, F. F is the largest single digit. So that's the number right here. But 19 mod 15 equals to 4, which is wrong. In other words, so 19 mod 4. This is base 10 because it automatically calculates base 10, which is wrong. It should be 15 is 16 minus 1. It should be A in hexadecimal, which equals to 10 in base 10. But if we convert this, so if we have a 19 base 16, then write this in our usual 10 plus 9, so 10 then plus the 9. This equals to F plus 1 plus 9. And then the equivalent of F plus 1 or 10, this just equals to 16 in base 10, then plus the 9. 9 is included in both. So 16 plus 9, so this number adds up to 25. So then if we go 25 mod 15 equals 10, which is right. So even though this is 10, it's not the same notation. This A, that's the exact one, but the conversion value is correct. They're both 10. So 1 plus 9 is 10 in base 10, but it's A in base 16. So note that since we're referring to the base 16 number system, the base 10 remainder of 10 remains as is and represents the hexadecimal number A. So we're going to leave it that when we're dealing with different base number systems, and I'm just going to leave it as the conversion to base 10. So since we're referring to the base 16, the base 10 remainder of 10, so this remainder of 10 remains as is and represents a hexadecimal number A, and we don't digit sum 10 to 1. Just bold this, so we don't, it's the digit sum, the vortex sum is not 1. It's going to be just as is. It's going to be 10 because we're dealing with base 16. So for convenience and practicality, I'll be writing all base number systems in their equivalent base 10 as shown below. So if we have base 16, if we have base 16 right here, 0, 1, 2, 3, 4, all 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then equivalent base 10, then afterwards is going to be 10, 11, 12, all the way until 1A, 1B, 1C, 1D, 1E, 1F, and so on. But I'm going to just write these strictly as base 10 for the most part. So in other words, this top part is going to be just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 15. And yes, you can see the 10 right here is the A. So bold this. And then bold this. And then now we have the next one's going to be, 16 right here is the number 10 for base 16. And then so 17, 18, 19, 20, just the usual count which we're all used to. So 24, 25, 26, 27, 28, 29, 30. 30 is 1F, which is And actually, yeah, it's not 30 because this is the number. This is 16 on top here. Then this is going to be another 16, but this 10 is included in the count. So this is 16 plus 16 is 32, but there's a 0, so we don't count that. So this should be a 31. So yes, that should be right. So this should be yeah, 16 digits in both. Yeah, so 16 included is 16. Yeah, so that should be correct. So 15 plus 1, 16. And then this is going to be 15 plus 1, 16. So yes, 31 right there. Yes, going further. So the vortex sum of the number 10 base 16 and 16 base 10 equivalent should be the same. So 10 base base 16. So if we look at this one right here, so that's number 10, and then you have vortex sum of number 10 in base 16, not number 10 in base 10, but number 16. This is just equals to v equals to 1. And now if we go 16 mod, this is base 10 equivalent, 16 mod 15, and this is because, let's write this down, 10 base 16 equals to, this equals to 16. Yeah, this equals 16 base 10. That's equivalent. So 16 mod 15 equals to 1, base 10 equivalent. Let's put equals and 1. Hashtag amazing. It's pretty amazing. So there's our 16 right there, bold it. And then this is our 10, bold this again. So yes, these are the equivalent of it. And again, just to reiterate, so this 10 base 16, it's a number, there's no 10 single digit in base 16. It goes to it goes to 9, then it goes to A, B, C, D, E, F, and the next one's 10. But then V equals to, the vortex sum is 1. And we can still calculate 16 mod 15 equals 1 by converting 10 to 16. Alright, so let's continue further in this in this journey. So note, can calculate base 4 vortex sum using base 10 mod function without conversion. Here's a note I just figured out when I was making this the summary of this video. So consider the vortex sum of the number 1, 1 in base 8. Yeah, this is just equal to, well, 1, 1 base 8 just equals to v equals to 1 plus 1 is 2. But then if we go 11 mod 7, which is 8 minus 1, equals to 4, which is wrong. Converting to base 10 gets the right answer, so we get 11 base 8 just equals to 1 times 8 plus 1. This is base 10. That's 1 times 8, which is our 10. And then this is going to be 8 plus 1 is 9. Then 9 mod 7, which is equal to 2, which is right. Which equals to this one, correct, right there. We can see why we have to convert to base 10 by counting up until the number 11 in both base 8 and base 10. So if we count up, so if we have base 8, we go 1, 2, 3, 4, 5, 6, 7, then we go 10, 1, 1. What we end up having is 11 equals to a factor of 7, which is just 7, plus a remainder 2. So remainder 2. So 7 plus 2, v equals to 2. Yeah, v equals to, because it's just a remainder. All we care about is a remainder. This is the factor of 7. That's the n minus 1. So this equals to a remainder. But if we go base 10, we get 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11. What the mod function does is basically finds a factor of 7 plus remainder, but now we have 1, 2, 3, 4, 5, 6, 7. Then we have 4 digits right here, 8, 9, 10, 11. So 11 equals factor of 7 plus remainder equals to 7 plus 4. This is base 10. V equals to 4, it just gets the remainder, which is wrong. And 11 mod 7 is 4, which is also wrong. So now consider the same number 11, but in base 4. So that's why it's wrong, because it's looking at a base 7, and it's not a factor of, if it was a factor of 9, we just get 1, 2, the remainder, which is correct. Now consider the same number 11, but in base 4. So base 4, we have 1, 2, 3, and then 1, 0, 1, 1. Factor of 3 plus remainder, we just have factor of 3 plus remainder. Over here is 2, so it's equal to 3 plus 2, v equals to 2, I don't know why I have so many 2's there. Yeah, v equals to 2, because that just equals the remainder. The vortex sum is just this 2. And now if we do the base 10 equivalent, count, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 is a factor of 3, is what the calculator calculates. Factor of 3 plus a remainder. And then the remainder is going to be, well, 3 plus, over here we have 8. But this is a partial remainder. It keeps calculating, keeps repeating the same process. So we have a 3 there plus an 8. V equals to 8 is the partial remainder. Now if we repeat the cycle, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have a factor of 3 plus remainder. So we have 3 plus the 5 And then, yeah, so we have 3 plus 5, v equals to 5, is again a partial remainder because it's greater than 3. Repeat cycle, we have 1, 2, 3, and then 4, 5. So we have 5 equals factor of 3 plus remainder, which equals to 3 plus 2, v equals to 2, which is the correct answer. And this is all using just a base 10 counting system right there. So we can simplify this further by realizing that the modulus 3, or the divisor when you're trying to get the remainder, and this is in base 4, is a factor of the modulus 9 in base 10, so the same factor. So in other words, if we have base 10, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 equals factor of 3 plus remainder, which still equals 9, because the 3 is a factor of 9. I guess 3 times 3 is 9, it's evenly in. So we have 9 plus 2, which equals 3 times 3, plus 2, v equals to 2, which is the correct answer right there. Yeah, which is the correct answer. I don't know why it keeps calculating automatically. So 11 mod 3 equals to 2. So we don't need to convert it, because 9 is a factor of, or 3 is a factor of 9. Yeah, so in other words, in base 3, in base 4, 1, 1, base 4 equals the factor of 3 plus 2, which equals factor of modulus 3 plus 2. Just write that out so we have the exact same thing. So that's going to calculate the v equals to, it's going to be 2. V equals 2 is the remainder. And then 11 in base 10, so without needing to convert, we just calculate it as base 10, equals the factor of 3 times 3, which is 9, plus 2, which equals the factor of 9, plus 2. These are the exact same things. So 2 is going to be v equals to 2. Thus, for the base 4 system, we can calculate the vortex sum or remainder just by using the built-in base 10 mod function without conversion. So without conversion, we have 11 base 4, v equals 1 plus 1 equals to 2. And we can just write 11 mod 3 equals 2. But if we want to convert it, we'll get 11 base 4 equals to 4 plus 1. And then, yeah, this is in base 10. So this equals to 4 plus 10, or equals, let's make it for completeness, 10 plus 1 equals to, 10 plus 1, and then base 10 is going to equal to 4 plus 1. The relative value of 10 in base 4 is 4 in base 10. So this is going to equal to be 5, and 5 mod 3 is just going to be equals like that. And again, you can just show this here, 11 mod 3. So we can convert to 5, or we can leave it as 5, and it's going to be the exact same thing, even though we're using a base 10 mod function with this one-node calculator. We can double check with large numbers to see this is always the case. So if we have 1, 2, 2 base 4, this equals to 1 plus 2 plus 2, which equals to, this is going to be 11. The question is, why is it 11? Well, this is 1 plus 2, plus 2. We're dealing, this is the v equals to. This is the v equals, we're adding the digits. This is going to be equal to 1 plus 4, which is 10. Yeah, so 1 plus 4 equals 10. And then add those up, the digits 11. Again, this is dealing with base 4. So that's why converting the base 10 is pretty good. But this one, just to show that you could just use it. Anyway, so it equals 11, v equals 1 plus 1 equals 2. So 1, 2, 2, mod 3 equals 2. And now we can go, even bigger numbers. So 1 with 6 ones. This is v equals to 1 plus 1 plus 1 plus 1. This equals 2. Well, every 4, we add 10. So that's going to be a 10. So this is going to be let's put a 10 right here. This is 10, and then plus 2. So 10 plus 2 is 12 in base 4. And then this is going to be v equals to 1 plus 1 is 3. And then we could also go 1, 1, 1 mod 3. This equals to 0, which is v equal vortex sum is 3. Just set it to that. And now let's go even bigger numbers. 1, 2, 2, 3, 3, 2, 2, 1, 1. This equals to 1 plus 2, 2, plus, just add up the v equals 1 plus 2 plus 2 plus 3 plus 3 plus 2 plus 2 plus 1. This equals 2. So every 4, let's just do, this is going to be 10. So let's, I don't know why I added this complex example. So 10, this is going to be 10. So just see how many 10s we have. This is going to be a 10, 1 plus 3 is 4, or 10 in base 4. And then we have another 10. We have another 10. Then we have another 10 right here. So in other words, we just have 4 10s. So 10 plus 10 plus 10 plus 10 equals to, 30 plus 10, because we can't get a 4. Yeah, so if it's 40, yeah, the 40 just goes to 100. So 30 plus 10 equals to 100, v equals 1. And then you can just go mod, 1, 2, 2, 3, 3, 2, 2, 1, mod 3, and you should get a 1. Absolutely amazing. Some amazing stuff here, guys. This is actually, this is pretty amazing. And that's why I do mathematics. It's pretty cool stuff. Alright, so anyways, MES note, all numbers used are by default in base 10 unless stated otherwise, and this is for convenience and uniformity, especially when we deal with random different number systems. So whenever I reference any number and I've not stated otherwise, then it will be in base 10. So now let's go further. So multiplying a number and its vortex sum result in the same vortex sum, and this is it's a mouthful, but this is pretty much the crux or the main reason or main causation of most vortex math patterns. So let's go further. So note that a quote factor of 9, which I've been stating a lot, a factor, but I didn't explicitly write it down earlier, but I'll just write it down now. So note that a factor of 9 simply means a whole number that can be divided cleanly by 9. For example, 27 is a factor of 9 because 27 divided by 9 equals to 3. 9 is a factor of 9 because 9 divided by 9 equals to 1. Also, you could do this for any other number. So 9 is a factor of 3 because 9 divided by 3 equals to 3, just a whole number. Alright, let's go further. So now recall that when we write numbers as factors of 9, then the remainder that isn't part of the factor is equal to the vortex sum in base 10, which I showed earlier. So which I proved earlier or derived earlier. So if we have 11, v equals, to get the vortex sum, just digit sum, 1 plus 1 equals to 2 equals vortex sum. Now let's go further. So if we have 11, you could also write this as the factor of 9. 11 equals 9 plus 2, which is a factor of 9 plus remainder. And 11 mod 9 is just a remainder formula or calculation algorithm that you can use to quickly calculate the remainder, and equals to 2, which is remainder, and vortex sum equals to the remainder, which is quite fascinating in and of itself. So now if we multiply 11 by 6, we get 11 times 6, just a random number. Here, 11 times 6 equals 66. Now v equals, to get the vortex sum, just to see what happens when we multiply, equals to 12 right here. So 11, and yeah, so v equals 6 plus 6 equals to 12. V equals, reduce it again because this is greater than 9. It's not a single number. So this is going to be 1 plus 2 equals to 3 right there. Or we could write this as a factor of 9. So 11 times 6 equals to our 11, which is in our 9. 9 plus 2 is just right here, which is equal to a factor of 9 there. So what we're going to have is equals to 9 times 6 plus 2 times 6, because when we multiply this inside, and but this is still going to be a factor of 9, because 9 times 6 divided by 9 is just going to be 6. Or a factor of 9 times by a factor, times by any number, it's still going to be a factor of 9. Because you're just gonna, you're still gonna have a whole number. Now we're just gonna be multiplying this whole number. For example, if you have 27 over 9 equals 3, if you multiply 27 by 3, 4, 5, 6, all you're doing is gonna be multiplying this 3 by 3, 4, 5, 6. So you're always gonna have a whole number. So in other words, it's always gonna be a factor of 9. So when we multiply this inside, 9 times 6 plus 2 times 6, we're gonna have here, this is just a factor of 9. Because number 9 times 6 divided by 9 is just 6. And then we have a remainder, or partial remainder, because it's going to be greater than 9, 2 times 6. So note that both 11 and 11 times 6 are both written as a factor of 9. In other words, we have 11 equals to a factor of 9 plus 2. And 11 times 6 is a factor of 9, which is, or 9 times 6. Doesn't matter what it is, it's still a factor of 9. So it does not count for the remainder. So then we have 11 times 6 equals a factor of 9 plus 2 times 6. Since the remainder governs the vortex sum, then we just have to compare the remainder. For example, 11 v equals 1 plus 1 equals 2 equals the vortex sum. The remainder is 2, which is also equal to the vortex sum. And notice here, 11 times 6 equals to 66. V equals 6 plus 6, which equals to 12. V equals to 1 plus 2 equals 3 equals vortex sum. And then if we just take the remainder equals 2 times 6 equals 12, v equals 1 plus 2 equals to 3. In other words, here I just took the vortex sum of this remainder, which is 2 times 6, and that's going to be equal to the exact same thing. Note that multiplying 11 or its vortex sum 2 by 6 results in the same vortex sum. These are the exact same ones. This is absolutely fascinating stuff. So now, for example, if we have 11 let's write this down like this. V equals to, this is the vortex sum, equals to 2. Now if we multiply 11 times 6, we get 66, and then this V equals the vortex sum is going to be equal to 3. And we could have done the same thing here, so times by 6 over here, and then we're going to have a 12, V equals to 3. So these are the exact same. So these are the same thing. Yeah, and here I just quickly added, rewrote this, so right, yeah, same. So these are the exact same stuff. And we can in fact prove this is the case for any integer and in any general based number. And so if we have n equals to just any base, yeah, for any base number system, and then p equals to n minus 1, or the base minus 1, then what we have is, and also let's say we're given a, b, c as before is any integer between 0 to p, then also I'm going to define capital A equals to integer, and this is just equal to these this a, b, c and these corresponding digits right there. So if we have a equals to abc, or capital A equals to lowercase abc, then you can just break this up into its parts for any number base number system. Here we'll have a times 100 plus b times 10 plus c, and then we have a, then break this number 100 up based on its number system. In this case, p is the largest digit, so we can have a equals, or this equals to a times pp plus 1, and then b times, this is a 10, p plus 1, and then c is just c times 1, just ignore the 1, just leave it. So it's plus c. This equals to now a times, and just multiply this inside, a times pp plus a times 1, which move those to the right, the a times 1 and the b times 1. So then we're going to have a times pp plus b times p plus a, plus in this bracket, a plus b plus c, where again, this one right here is our factor of p. And then this part right here is our remainder, or remainder until when we take when we repeat the process, remainder. Yeah, when we repeat the process until we have the remainder is equal to just less than p, so that it's equal to the vortex sum, and hence the remainder, or the a mod p value right here. So that's the remainder, and again when we get to one single digit, so that it's the vortex sum. But yeah, when the remainder is 0, then that's just a mod p is equal to 0, and then we just set that equals to p for vortex math purposes. So anyway, so this is a factor of p plus remainder, so that means our capital A is equal to a factor of p plus, I'll call this R1, which is, because we're going to deal with R2 later. So R1 is just a remainder, and you could calculate that as a mod p, and it's just a vortex sum of a, which I proved earlier. So thus, if we multiply a by an integer multiple k, or multiplied by an integer k, it's already there. By k, we have k times a equals to k times a factor of p plus r1. Yes, we have this, and we multiply that inside. We're going to have k times a factor of p plus k times r. So note that k times a factor of p, really this out like that. So k times factor of p is just a factor of p still, because for example, i.e. 2 times 9 equals 18, and 18 divided by 2 is equal to 9 is the whole number. So in other words, yeah, if you have 2 times any factor of p, you could just still go, for example, 3 times 9, you just multiply, this is a factor of 9, but you could always divide by 9 and it always goes evenly, just cancel. So it does not matter. So if you multiply factor of p, it's still going to be a factor of p, and then since the remainder is what governs the vortex sum and the mod function and the remainder, yeah, that's all it is. So we don't need to look at this k value. So this k times a, this just becomes this over here. So we replace the k, it just becomes a factor of p. So k times a equals a factor of p plus k times r1. So that means it's a new remainder. So k times r1, yeah, this one, assuming it's greater than p, we could also write this as a factor of p plus a new remainder r2. So we could write this one here, that's just the remainder part, we just reduce that further. So then r2 is equal to new remainder equals to just k r1 mod p, which is just the vortex sum of k times r1. So that's what we have. Yeah, so this vortex sum is for this remainder part here, but again, this remainder, we could write this as a factor of p plus r2, and then we could just throw that back inside this full function, this k times a, so the k, the multiple. This one is k times the first vortex sum, which was over here, which is for this a value there. Yeah, so that means if you just replace this k times r1, that's over here. Yeah, that's this whole side there. So then what we have is here factor of p, which is this part, and then plus factor of p plus r2, which is this k times r1 when we could reduce or rewrite it like this when we keep reducing it until we get a remainder. And so what we have is this, but we also note that factor of p plus a factor of p is still equal to a factor of p. So again, all we want to do is get the remainder. So for example, i.e. 9 plus 9 equals 18. 18 divided by 9 is 2 is a whole number. And again, when you add stuff, for example, 9 plus 9, you could always divide by 9 because they just cancel. It just becomes 1 plus 1 is 1, 1. And this equals to 2. Yeah, so thus we can write this part. Yeah, we can write this whole part right here, k times a. This just replaces factor of p plus factor of p. It's still just going to be a factor of p. So ka equals factor of p. Yeah, anyways, hopefully you like my next level derivation skills right here, or deriving skills. So yeah, in future videos I may do a more formal proof, but again, this is pretty next level. So k times a equals factor of p plus r2, and r2 is a new remainder for this ka. And then this we could just solve it by ka equals ka mod p, which equals the vortex sum of k times a. So thus, yeah, notice this is the r2 is the exact same as this one here, like that. We already solved that for in a different method. So thus, the vortex sum of ka is equal to the vortex sum of kr1, and we know that r1 is just equal to the remainder equals the vortex sum of a. So it equals the vortex sum of a. And k times a equals factor of p plus r2, and kr1, yeah, because the kr1 equals factor of p plus r2. That's what we solved over here. So kr1 is factor of p plus r2. And then we have ka equals factor of p plus r2. So these are the exact same stuff here. And when we're dealing with remainder, these have the same remainder, so they're going to have the same vortex sum. So thus r2 equals vortex sum of ka equals vortex sum of kr1. And again, k times r1 is k times vortex sum of a. So in other words, vortex sum of k times a equals vortex sum of k times vortex sum of a. Or we could write this in mod form, or ka mod p, which gets the vortex sum of ka, equals to k times, then there's a mod p, which is vortex sum of a, and then the mod p is going to be the vortex sum of, or the remainder of k times the vortex sum of a. So yes, I'll go over the mod. This is just a mod identity, a modulo, a multiplication identity, which I'll cover in a bit. So yes, it's fascinating stuff. So in other words, the vortex sum of k when you multiply a number here, the vortex sum of this multiple of ka is equal to a vortex sum of just k times the vortex sum of a. And there was a remainder. So, for example, and this will be very, very useful, and this is actually pretty much the causation of most vortex math patterns, as I will go over soon, or we'll discuss in a bit. So, for example, consider the number 17 in base 10 and multiplied by 4. Yeah, so we have 17, v equals vortex sum, 1 plus 7 equals 8, and this is vortex sum. So now if we have 17, this also, you could write this down as 17 equals to 10 plus 7, and then this is base 10, so then break the 10 into a 9 plus 1, move this 1 over to the other side, so we'll have a 9 plus a 1 plus 7, add these up, this is going to be 9 plus 8, where we have factor of 9 plus a remainder. The remainder is 8, that's the vortex sum, it's less than, it's a single digit. Yeah, so we have 17 mod 9 equals to 8. And yeah, you can just type that in. Let's just verify this. Equals 8. Yeah, equals remainder equals vortex sum. So we're all good right here. That's for the number 17. But now we have k equals 4. We're going to multiply 17 by 4. So if we multiply 17 by 4, we get 68. 68 like that. V equals, then do the vortex sum. 6 plus 8 equals 14. Do that again. V equals 1 plus 4 equals 5 equals vortex sum. And also you could break this up into its parts. So we know this 9 plus 8 is 17. So if 4 times 17 equals to 4 times 9 plus 8. And then break that down, we got 4 times 9 plus 4 times 8. So 4 times 9 is just going to be a factor of 9. A multiple of a factor of 9 is still a factor of 9. Equals factor of 9 plus partial remainder. And that's because this is going to be greater than 9, so we have to reduce that again. But nonetheless, so we have a partial remainder right here, 4 times 8. But here, if we just take the 4 times 17 mod 9, this equals to 5. So in other words, we could find the remainder like using the mod function of this 4 times 17, or we could just look at this partial sum 4 times 8, which is just 4 times the vortex sum of 17. So in other words, 8 times 4 or 4 times 8 equals to, let's put this 4 times 8, put that in front, just so it's in line with everything, because we have the 4 times 17 right there. 4 times 8 equals to 32. V equals 3 plus 2 equals 5. Yeah, so then, and then we have 32 mod 9 equals 5. So in other words, multiplying the vortex sum here, and then doing the vortex sum gets the same as just as multiplying by this and taking the vortex sum. So this is true for any base, and this is this is where we understand that everything we're used to is all base 10, especially the built-in calculators. So this is true for any base. So for example, let's look at base 8 right here. 15 in base 8, the vortex sum is 1 plus 5 equals 6. So that's a vortex sum as you add these digits. And then we have, but then if you want to write this in a remainder form, we're going to have 15 base 8 equals to 10 plus 5. But now the 10 is its relative value based on base 8, so it's going to be 7 plus 1 plus 5. And then we move this 1 over to this side, so we're going to have a 7 plus, plus 1 plus 5, like that. So in other words, we have, this is the vortex of 1 plus 5. 7 plus 6, add those up, equals to a factor of 7 plus remainder. 7 is the highest unique digit in this base 8 system, or 8 minus 1 is 7. Yeah, so that's what we have. 6 is the remainder. That's a vortex sum right here. But then now, if you want to use the mod function, this is built in base 10. So we're going to have to go convert this to base 10. 15 in base 8 is equal to, well, relative value of 10 is 8. So 8 plus 5 in base 10 equals to, well, add those up as 13. And then we're going to have 13 mod 7. This equals to, 6. So equals remainder equals vortex sum. So fascinating stuff. So now we're going to multiply by 4. So we can multiply this 15 by 4. So 15 times 4 in base 8 is equal to, well, we know it's 10 plus 5. 10 plus 5 times 4. And then, so when we multiply this inside, we have 10 times 4 is 40. Then we have a 5 times 4 right here. But then we can't just calculate that directly because this is, again, built in base 10. So to do that, we want everything in 8s. And 8 is equal to a 10. Remember, an 8 base 10 is 10. So we always think of the relative value and then convert it into a number 10. So we're going to break this number 5 into 2 plus 2 plus 1. Yeah, so that's just 5 right here. 2 plus 2 plus 1 equals 5. And the reason we're doing that is because we have a 2 times 4 is 8. So 40 plus 2 plus 2 plus 1 times 4, we're going to have this 40 plus, and then 4 times 2. And then right here, which this one's already done, it's already there. We're going to have a 4 times 2 equals to 10 in base 8. Remember, the value is 8 in base 10, but again, we want we want the base, we want them all in 8s for base 8. We're dealing with base 8, so an 8 is a 10. An 8 in base 10 is a 10 in base 8. So this is going to be 4 times 2 is 10, plus 4 times 2 is 10, plus 4. So we're going to have a 40 plus 10 plus 10 plus 4. You could just add these up normally because you don't get beyond the number 8 right here, or 7. We don't get greater than 7 in any of these digits. So we're going to get a 40 plus 10 is 50, plus 10 is 60, plus 4 is 64. So you have 64 right there. And now let's just write that down right here. So what we have is 15 times 4 in base 8 is equal to 64. And then take the vortex sum v equals 6 plus 4. And then again, we can't just add them up normally. So we have to go 6 plus, break the 4 up into 2. So 6 plus 2, this is an 8, but isn't actually a 10. It's in base 10. It's going to be 10 plus 2, so equals 12. V equals, I don't know why it keeps popping up this right here. But anyways, we get a 12, then V equals 1 plus 2 is 3 equals the vortex sum. So that's doing that manually. And now we have 15 times 4. Yeah, 15 times 4, this is the manual way, but now if we write it in our factor of 7 plus remainder form, we have 15 times 4 equals to 7 plus 6 is our 15. That's right here. 15 is equals 7 plus 6. And then, so 7 plus 6 times 4. And then 4 times 7, that's a factor. You just multiply these out. 4 times 7 is a factor of 7. And then plus 6 times 4. So we have a factor of 7 plus a partial remainder, because again, we've got to reduce these further. So what we have, that's a 6 times 4. So in other words, 15 times 4, we'll deal with the partial remainder inside here. That's just that's the next part. So, but now if we want to write this in base 10, so 15 times 4 base 8 equals 2, well, you can just add these up. This is 7 plus 6. Yeah, you can just add those up, or you could also look at this. We already calculated this one. This is already 13, like that. So this is going to be 7 plus 6 is 13. Just add them up normally in base, because everything is base 10 by default, especially in my brain. So 13 times 4 base 10 equals 52. There you can just see that it's true, equals 52. Alright, so that's 52. And then 52 mod 7, this equals to 3. Like that. Equals vortex sum. So now if we look at this partial remainder though, this partial remainder just states this is a vortex sum of 15 times it by 4. So we could just calculate that instead of doing the 15 times 4 at vortex sum. So 6 times 4 base 8 is equal to, and again we can't just multiply normally, so 6 is equal to 3 times 2 is 6. So then we're going to look at this part right here. 2 times 4 is 8, so we'll just replace it with a 10 in base 8. So 3 times 10 is 30. And now we can calculate the vortex sum of it. So 6 times 4 base 8 equals 30. V equals 3. It's 3 plus 0. Yeah, so that's doing the manually, just multiplying it and then taking the vortex sum. But we could also do, we could also use the mod function by converting to base 10. So 6 times 4 base 8 is just equal to 6 times 4 base 10, because both these digits are included in base 10. So this just equals to, this equals to 24. Equals 24, like that. Let's erase that. But you could also write this as 3 times 8, because this is 30. So in other words, instead of going 3 times 10 is 30, we could go 3 times 8 is 24. So they're all the same thing. And then you go 24 mod 7 is 30. So yes, all of these are equal, every single one. And yeah, so it's true for any base, but any base besides 10 is very, very out of the box. Yeah, out of the box thinking. You gotta and you gotta just make sure that each step you're doing correctly and not just assuming based on the usual base 10 adding and subtraction and number system, etc. So thus it is much easier to determine the vortex sum of the remainder, especially when the multiplied number gets very large, such as in the following base 10 example. Yeah, because again, what this says is we can just take the vortex sum initially and then multiply it, as opposed to multiplying it and then doing the vortex sum. Because the vortex sum can only be a number between between 1 to the base, so it's very, very small. I mean, base minus 1, so it can only go 1 to p, or the modulus. So thus it is much easier to just determine the vortex sum of the remainder, especially when the multiplied number gets very large, such as in this example. Let's go right here. I'm going to go, let's say we have number 64, like this, and let's multiply 64 by 4. We'll do this manually just to show in case you don't have a calculator or whatnot, or you just want to do it in your head. So it's, again, it'd be tedious. So if you multiply 64 times 4, this equals to, well, 4 times 4 is 16. Add the 1 there. 4 times 4 is, 4 times 6 is 24. Add the 1, so give it 256, like that. And now if we take the vortex sum here, V equals, well, 2 plus 5 plus 6, this equals to, well, this is going to be 7 plus 6. 7 plus 6 is going to be, well, 10 plus 3 equals to 13. Like that. Equals 13, but instead we could have just done this one right here, the 64. If we just did instead go V equals, for the 64 is 6 plus 4 equals to 10. V equals to 1. 1 plus 0. And now we multiply this by 4. Times 4, this equals to, well, 1 times 4 equals to 4. Oh, this one we forgot to add this one up. V equals 1 plus 3. Yeah, so we're still not done that one, and we finally got it. 4. But this one already there, 4. So this one is just, this one you can just do it in your head. 6 plus 4 is 10 is 1, times 4 is 4. This one you have to do, multiply this manually. 64 times 4 is 256, add up every single one, add up again, and then add up again. And these are the exact same thing. So yeah, so now you understand how powerful this one is. This is super, super simple and easy. Yeah, and more importantly, if the vortex sum is the same as a previous multiple, then a pattern arises. And that's because if you're doing a series or a sequence of patterns or vortex sums, and you're using the same multiple, and then if the same vortex sum arises as a previous multiple, that means we already know what it's going to be when you multiply it, because we've already done it before. So and because we don't need to care about what this number 64 is multiplied by 4, we don't care if it's 256, whatever. All we care about is this number 4. So if we have this number 4 showing up again, or another number or a similar number showing up, then a pattern arises, and I'll illustrate that soon. And this is basically the causation of most vortex math patterns. And this can be seen visually by considering the following vortex sums. So let's say you have number a, and then the vortex sum is equal to 1. And let's say a times k, the vortex sum is equal to 2. And then you a times k, so you multiply it by another k, v equals to 4, and let's say you multiply it again by k, and then the v equals to 8, then you multiply again, it equals to 7, and then multiply again equals to 5, and you multiply again equals to 1. And now we don't care anymore about what this actual vortex sum is. We know it's going to, the next multiple is going to be 2, because we already know that the vortex sum of a times k, v equals to 2. Remember, multiplying this by k gets this, but you could have also multiplied this, right, or 1 times k. V equals to 2. So these are the exact same stuff here. So we could have got to this 2 from just multiplying this the vortex sum of a. So in other words, we already know what this one is, and we already know what this one is. This one's going to be based on this number 2, so we don't care what these big numbers are. So even though this number gets super large, it does not matter. It's going to be dependent on the remainder, or the vortex sum. So in other words, the next one's going to be 4, the next one's going to be 8, the next one's 7, next one's 5, next one's 1, next one's 2, etc. Pattern repeats indefinitely regardless of how big this number is. So note that I used the typical 1, 2, 4, 8, 7, 5. So yes, 1, 2, 4, 8, 7, 5. 1, 2, 4, 8, 7, 5. Doubling pattern, in other words, k is equal to 2. So yes, 1 times k, 1 times 2 is 2. Now, i.e. k equals 2, pattern referenced by Marko Rodin. This is the main one right here, and I'll go over it later in this video as well. So thus, even though there are infinite amount of numbers and they get super large, there are only a finite number of single-base digits, or single-digit base numbers. In other words, we can only have from 1 to 9 for the vortex sum, or 0 to 8 for the remainder, or the mod function. So thus a pattern is almost always expected. Yes, you're always expecting a pattern. So that's absolutely fascinating. This is the causation of it. So yes, absolutely magical. Almost always expected. This is right. Let's bold that. That's pretty amazing. So thus, or we could just go move forward now. So now modulo multiplication identity. I alluded to this earlier as well. So the above concept of, quote, multiplying a number and its vortex sum result in the same vortex sum can be generalized as a modulo multiplication, quote, identity, or formula stating 2 sides are equal. That's just identical. 2 sides are identical. Let's call it an identity. So since the vortex sum is the specific case of mod base minus 1, this is excluding the part where it's equal to 0, then you just set that equal to the base minus 1. Then we can write the following vortex sum example in its equivalent modulo notation. So for example, if we have number 25 like this, multiplied by 4, this is going to be, I'll just write it like this, times 4. This is 25 times 4 is just 100. You can just go 4 times 5 is 20, put a 2, 4 times 2 is 8, and then that's 8 plus 2 is 10. Or, just 25 is a quarter times 4 quarters is 100. So this is going to be v equals to 1, like that. Or you could go right here, v equals to 2 plus 5 equals to 7 times by 4. So for smaller numbers like that, or for some special cases like this where it's all even, it's sometimes it's easier just doing the multiplying this 25 by 4 than getting the vortex sum. This is going to be, so then that's 7 multiplied by 4. We're going to have, 4 times 7, let's go times by 4 equals 2, or actually make it a bit more uniform. This equals to 7 times by 4 like that. This equals to, 28. And then v equals to 8 plus 2. Then this equals to 10. V equals to 1, like that. So these are the same as expected, like that. These are same. Or we could write these as, or you could just write these as 4 times 25. Remember, you can just get the mod function of it. Mod 9 is base 10. So mod 9. Again, if I don't specify which base, it's going to be base 10. So equals to, this is going to be, 4 times, let's write this in as equivalent mod function, because that's the vortex sum, or that's the remainder. It gets 1, and 4 times 25 mod 9. So 25, the vortex sum of 25, over here is going to be 25 mod 9. So 4 times that. And then I'll put this all into a bracket like that. Whoops, mod P, or mod 9. Yeah, now here I just added the mod 9 there. So, and we could double check our results. We just go 4 times 25 mod 9, using the built-in base 10 calculator here. So equals to 1 right there, mod 9, and as expected. And then if we go 4 times and then bracket 25 mod 9, close bracket mod 9 equals to 1. And yeah, so we can actually generalize this for any integer multiplication and for any modulus. So we could write this as a times b, capital B, mod c. So it doesn't need to be mod 9, just anything, because we're not taking the vortex sum here. We're just doing general modulo identity. This equals to a times b mod c. So the multiplication of these, the modulo of it, is equal to a times the modulo of b, or b relative to c. So b mod c, close bracket, mod c, like that. Or you could also do this way, because again, it's all multiples, and these just find the remainder when you're dividing by c as the modulus. So this is going to be the same as when you multiply a mod c. So if you multiply that instead, and this is going to be, or we multiply both, a mod c times b mod c, and this is going to be all mod c. Oops. Mod c. And in fact, you could do the other way around too, because again, multiples, doesn't matter which one you're modding. You could do mod the other way. You can go right here. This is going to be a mod c, and then times it by b. I guess times by b, close bracket, mod c, like that. Yeah, so that's what we have here, and we can see we could calculate this in an example just to illustrate this. So basically, if you have a number a equals to 11, b equals to 22, c equals to 7, so a different modulus right there instead of 9. So we'll have, let's say if we have 11 times, so a times b, or 11 times 22, then mod 7, that equals to 4. You can just do this calculator, equals 4, like that. That gets to, yeah, so this is this part right here. I mean, that's the first one right here. A times b mod c. That's the first one, and then, or you could also go 11 times this right here, so a times b mod c. So 11 times 22 mod 7, and then mod 7 of the entire thing equals that. The next one to multiply both, a times b, so 11 mod 7, or a mod c, and then times b mod c, or 22 mod 7. And then all of that mod 7 equals 4. Or you could go 11 mod 7 and then times 22. So a mod 7, or a mod c times b, and then mod c, or 7 equals 4. So yes, these are all the exact same thing. Yeah, and again, the reason is because these gives integers right here. So for example, if you have a times b mod c, now you could just apply the same identity to, like the same one right here, to this one, where now we multiply, we multiply this one, or we consider that this a is being multiplied by this integer b mod c. These just give integers, so this can be considered as an integer. They're all integers. So that's the new integer that you're multiplying it by, or the new k. So k, and then this is going to be now a times k, like that. You can just take the a mod of this one. This is going to be our k, etc. And now you could apply the same thing here, or this one you can start from this one, and then the one that's k is going to be, well, this is going to be our k, like that. So as opposed to, yeah, so you could either, this one is considering this is a k, and then you get that. But anyways, yeah, it's pretty straightforward. Okay, I'll just delete that. So yeah, so anyway, so thus the modulo of a multiplication of integers is the same as the modulo of the multiplication of either or both modulo of the integers. Hashtag moduloception. Alright, now let's go further, and let's now look at or discuss modular arithmetic. Yeah, so since the quote vortex sum of a number is equal to the remainder or mod base minus 1, what we are actually doing, let's put a bracket, comma. What we are actually doing is termed, quote, modular arithmetic. Here is the mainstream definition of modular arithmetic, and with an example using a typical 12-hour clock used in most countries. So here's a modular arithmetic on Wiki. Modular arithmetic. So in mathematics, modular arithmetic is a system of arithmetic for integers where numbers where numbers, quote, wrap around when reaching a certain value, called the modulus. The modern approach to modular arithmetic was developed by Carl Friedrich Gauss in his book Disquisitiones Arithmetica, published in 1801 or 1801. So a familiar use of modular arithmetic is in the 12-hour clock, in which the day is divided into two 12-hour periods. Yeah, so if the time is 7 o'clock now, then 8 hours later it will be 3. In other words, 7 a.m. or 7 p.m. goes 3 a.m. or 3 p.m. Yeah, 7 if you add this by 8 hours. Yes, to get to 12 o'clock, it's adding by 5, and then add another 3 for 8 hours. So a simple addition would result in 7 plus 8 equals 15. Yeah, but the clocks wrap around every 12 hours. So because the hour number starts over after it reaches 12, this is arithmetic modulo 12 in terms of the definition below. The 15 is congruent to 3 mod 12. Yeah, congruent or the same. So you could go 15 mod 12 is the same as 3 mod 12 or so on. So quote 15 on a 12-hour clock is displayed as 3 on a 12-hour clock. So anyways, here's a modulo right here. So if you have 9 o'clock right here plus 4, you're going to go up to 3. Yeah, you're going to go 3 and then plus 3 and then plus 1 right there. So it gets to 1 o'clock. So you restart at this 12 o'clock right there. Yes, you can just write this as 12, like that, 12, and reset. So timekeeping on this clock uses arithmetic modulo 12 right there. And yeah, remember using the mod function, the 12, if there's or the remainder, it gets to 0, but you could consider this as 12, so 0 or 12, like that. So in base 10, we are dealing with modulo or mod 9, and thus for any number greater than 9, yeah, any number greater than 9, we restart the clock back to 1 and keep repeating this cycle. We can see this by considering the number 13 in base 10. So if we have 13, Vortex M is v equals 1 plus 3 equals to 4. Or you could write this as 13 mod 9 equals to 4. And then you could also write this in our usual notation. 13 plus 10 plus, 13 equals to 10 plus 3, which equals to 1 plus 9. So there's that 9 there. Move this 9 and move the 1 over to the other side. So you have 9 plus 4. So you got equals factor of 9 plus a remainder. So basically what we're doing is casting out this 9. Or just removing it out there because we're going to wrap around it. So we're wrapping around the remainder. So we can draw this out. The remainder is 4, so we should actually get 4 there. So we can wrap this around a circle. Yeah, so we can draw this out around a circle with 9 at the top. Yeah, so we're going to look at right here. So number 13 equals to 9 plus 4. So we could you could just start at the 9 and go to the 4. Yeah, let's do that right here. So you can go from the 9, it goes all the way to the 4. This is going to be plus 4, like that. And we get to the 4. Here, just put it over to this side. Or we could also write this as, well, just subtract 1 on both sides on this 8. And subtract 1 here and add 1 there. So we could go 8 plus 5. Or we could go from here, put this in red. And then if you add 5 right here, this goes all the way across here. So this is plus 5. Whereas this one is plus 4, so go from 9 to 4. Or you could even go further. And let's say we have, write this in green, or this equals to, just subtract 1 more, 7 plus 6. So we can go from here, 7, and then this one would go all the way into, move this around. This one would be 6. So we go 2, we would go plus 2 across here, then plus 4. So it's always 4 there. Yeah, it's always 4 from the 9. Yeah, so this is plus 6 like that. Or we could do either one like that. Let's move this around. Yeah, so it's a better circle there, and then move this plus 6. And then plus, this one is plus 5. Like that. Yeah, so thus what we have is modular arithmetic allows for reducing all integers regardless of size down to a specific amount of numbers or integers such as 1 through 9 for base 10 or modulo 9. So yeah, this is the main one. is, we reduce any the size 13 just goes into number 4 for this modular arithmetic clock right there. So now let's take a look at vortex doubling patterns. Yeah, so the main pattern in vortex math is that doubling can obtain a repeating vortex sum pattern. In this section, I'll go over the main vortex doubling patterns. So let's look at the main one right here. The first one, 1, 2, 4, 8, 7, 5 pattern. Recall that the reason why this and most vortex patterns arise is that multiplying a number yields the same vortex sum as multiplying the number's original vortex sum. Consider the following example. Again, just to drive home the point, it showed it as I proved earlier. So if you have 13, so yeah, let's say we have the number 13 like this, and multiply this by 3, for example. 3 is going to be, well, 39, or it is 3 times 3 is 9, and then 3 times 1 is 3, like that. V equals 2 right here. V equals 3 plus 9. This equals 2. Yeah, we could add these up, but this is a factor of 9. That's a factor of 9, and we're doing it base 10. So this is going to be equal to 3. So this should be equal to 3, or you could just continue further. This is going to be equals to 12. Yeah, so this should be just 3 there. So this should be 12. And then this equals a V equals 1 plus 2 equals to 3. So yes, as expected. Like that. It says 3 is as expected. I'll just circle this. Or you could go here, V equals 2, 1 plus 3 equals to 4, and then times it by 3. This is going to be, times it by 3 is 12. And this V equals to 1 plus 2 equals to 3. So these are the same stuff. These are same. Or here I just put always same. So always same, like that. So yes, keep this ingrained into your brain. So if we have a number 13 or any number, then the vortex sum of it, if you take the vortex sum of it, for example, here's 4, then if you multiply the number or the vortex sum, the resulting vortex sum is the same. So if you take the previous, so this number gets this vortex sum, or you could have just multiplied its earlier vortex sum, and then take the vortex sum, gets the same thing. So keep that ingrained into your mind, because then it'll make things much easier. So consider the pattern of doubling from the number 1 and taking its vortex sum. So let's look at here from the same Excel sheet as earlier, and again, you can download it, view it, and so on. And this is from the worksheet doubling, but I have many more worksheets that likely won't even show. It won't show in this video or in other videos, because a lot of them were just me exploring different patterns and so on, seeing what I could find with Vortex Math and other stuff like Fibonacci sequence and prime numbers and so on. So yeah, download it and see the extra worksheets and see what you can learn from them. Anyways, let's go further. So if we have this table, so I have a count the numbers from 1 to 24, so there's 24 numbers here, and I double from 1. So if we have 1 times 2, and then 2 times 2 times 2 is 4, and so on. Yeah, then 2 times 2 times 4, or 4 times 2 is 8, and so on. I don't know why my Excel sheet's blown up. This OneNote's blown up. So 8 times 2 is 16, and so on. And then here's the vortex sum is on the right. And I also put a chart just to show the patterns repeat. And the vortex sum of 1 is just 1, and equals to mod 9. So you just put mod 9 in the calculator of this, it automatically calculates it. Now we have 2 mod 9 is 2, or vortex sum is that. And here's 16, V equals to 7, like that. Equals to 1 plus 6 equals to 7. And then after that, you can multiply 16 times 2 is 32. And then 32, V equals to 3 plus 2 is 5, and so on. Notice that these numbers are getting super large, get 5. But again, we can just take the previous vortex sum, and we get the exact same one. So the vortex sum of this is 1, so we can multiply that by 2, and so on. 2 is 4, and so on. And then 4 times 2 is 8, and then 8 times 2, this times 2 equals to 16. V equals to 1 plus 6 equals to 7. So we could have just done that. It goes to 7, and then the next one is going to be, well, times it by 2 equals to 14. V equals to 1 plus 4 equals to 5. So you notice that, yeah, it gets to there. Then the 5 one multiplied by 2 is equal to 10. V equals to 1. And then after this one, multiply by 2. So once we restart it, we restart from here. It goes to 2, goes to 2. So in other words, we don't even care what this left side is. Yeah, so these numbers get super large, but we could always go with the previous vortex sum and multiply it. So instead of here, 128 times it by 2 right here gets to 256. Let's write this better. Times by 2, 256, and this is v equals to 2 plus 5 plus 6. That's going to be, well, 7 plus 6 is going to be 13, and then plus 1 plus 1 plus 3 is 4. But anyways, I don't know why my OneNote's not working. Yeah, so anyways, basically if you multiply any one of them, take the vortex sum, you're going to get all the way, you're going to get this number, or you could have just gone from the previous vortex sum. So in other words, this pattern keeps repeating, and we don't need to care about how large this number is. And we could see this is true for the number 5112, just double check that it's the same one right here. So 5112, v equals to 5 plus 1 plus 2 equals 8. And then if we multiply 2 times 12, that equals to 1024. V equals to 1 plus 2 plus 4 equals 7. Or you could have just gone multiply this by 8. I mean, multiply it by that too. Or, just go or 8 times 2 equals 16. V equals 7. So yeah, 1 plus v equals to 1 plus 6 equals 7. So yes, so we could have just gone multiply the vortex sum as opposed to multiplying the full number. And as a double check of the vortex sum, let's sum up the digits of the 24th number. So this is a really big one, show that the mod 9 calculation works. So this is 8 million, and then 388,608. V equals 8 plus 3 plus 8 plus 8 plus 6 plus 0 plus 8. This equals 2. 41. V equals to 4 plus 1 equals 5. Or you can just use the mod 9 function, which Excel does, and absolutely amazing. That's actually amazing. Let's do hashtag amazing. Alright, so now the pattern 124875 always repeats itself, and then it keeps going indefinitely. So 124875, 124875, and again, because once we get to this 1, we already know what the doubling 1 is, goes to 2. We already know doubling 2 is goes to 4, so we just keep going on and on forever, regardless of how big this number is. And now let's keep going further. So now let's look at the 3636 pattern. So the 36 pattern, or 3636 non-stop pattern, doubles from the starting point of 3. So we have doubling from 3. Here's the same Excel sheet and doubling worksheet. So we have 1. So yeah, the doubling 1 again is the same count all the way to 24 numbers, and then we have 3 doubles to 6, and then 6 doubles to 12. And then 12 doubles to 24, and so on. And then you take the vortex sum, or the mod 9, v equals 1 plus 2 equals to 3, and so on. Or you could just, and it keeps going on non-stop. Or you could just take the previous one, so multiply the previous 3 times 2 is 6. Or you can go 6 times, then once it's 6, you just use the previous one. So 6 times 2 is going to be 12. V equals to 1 plus 2 equals to 3. So non-stop. And then the 3 multiplied again is gonna be 3 is gonna be 6, and then the 6 is gonna go to 3. We already know it doubles to 3. The vortex doubles to 3, and so on non-stop, regardless of what these giant numbers are. These ones, if you add them up, they're gonna be their corresponding one. But again, the pattern always repeats 36, 36, 36. And here's a double check of the 24th number, and it sums to. Well, you start off. This is multiplying. This is doubling from the 3. So this number here is 251. Let's see how many 3s there are. 3 here. So 25,165,824. V equals 2. Add up every single digit. 2 plus 5 plus 1 plus 6 plus 5 plus 8 plus 2 plus 4. V equals 2. 33. 33. V equals to 3 plus 3 equals 6. Or you could go this number mod 9 6. Absolutely amazing. Or you could also do this one here. Because remember, this also equals to divided by 9. So all it does is take the remainder. Divided by 9 equals to... Actually, this calculator, this number is too big for this divided by 9. So we have to take something smaller. So if we take something smaller, let's say 3072, it should get a 3 or a repeating 3. 3072 divided by 9, this equals to 3.144, or 341.333. So there's that 333, and that's exactly this 3 right here. Right there, that's the 3 over there. Or you can go, let's go 3072 mod 9 equals 2. And this should be 3, yeah. So you just do that. Let's put a note. See, that's fascinating stuff. Or I would just keep that in there. Just wanted to include that. So yes, dividing by 9, it gets that repeating one, or dividing by the modulus always gets that repeating number. Absolutely fascinating. So now the pattern 3636 repeats indefinitely. Fascinating stuff. So let's go. The next one is the 9s that repeat forever. The 9 patterns doubles from the starting point of 9. Note that since the mod 9 function returns the remainder of a number divided by 9, and the remainder, so it returns a remainder when you divide a number by 9, and since all multiples of 9 are factors of 9, the remainder will always be equal to 0. Thus, I've set the Excel function to output the number 9 whenever the remainder, or mod 9, equals to 0. Yeah, remainder equals to 0. Let's see this. Equals 0. Let's write when the remainder or mod 9 equals to this auto calculator. Yes, remainder or mod 9 equals to 0. So here's the same worksheet doubling, and now here we double from 9. So 9 times 2, they're all factors of 9, so the mod's always going to be equal to 0. And then times 2, 9 times 2 is 18. 18, yes, v equals to, v equals 1 plus 8 equals to 9. That's over here. So yeah, so the mod 9, if you do it, it's going to be 0. Everything's going to be 0 there. So we're going to have to set it to 0. So if it's 0, set it to 9, and so on. So all these ones are they're all factors of 9. So the remainder is always going to be 0, 0, 0, and so on. So we just set the Excel to equal to 9. So it's a double check. Let's consider the 24th number. And 24th number here is, this one is, let's see, that is 75 million. So 75 million for 497,472. Add these up. 7 plus 5 plus 4 plus 9 plus 7 plus 4 plus 7 plus 2. This equals to 45. Yeah, this equals 45. And then v equals 4 plus 5 is 9. And then if you write this mod 9, this should be equals to 0. So yeah, just space equals 0. So yeah, it's fascinating stuff. So now let's look at the next section of this epic long video. So let's look at symmetry of number systems and how it causes the doubling patterns, or the specific doubling patterns that we were looking at. So as explained earlier, patterns in vortex sum, or vortex sums, like here, will almost always arise because multiplying a number will yield the same vortex sum as will multiplying the number's vortex sum itself, which itself is a single-digit remainder regardless of how large it is. So as for the particular patterns that arise, they depend on the starting point of the doubling sequence and the level of symmetry of the base number system itself. The base 10 system has 9 non-zero single digits, and thus when viewing the modular clock, modular 9 or modulo 9 clock vortex circle, it is clear that the numbers 1 through 9 are symmetric about the 9 vertical axis, or the what Marko calls the primal point of unity. Anyways, or something like that. So we have here. So here's the 9. This is going to be symmetric about this right here. When you draw this like that, symmetric about the vertical axis. This is going to be, I don't know why my OneNote keeps jumping up like that. Symmetric. All right, symmetric. So symmetric about that vertical point. So these are pretty much the same, but on the flip side of them. All right, so now recall that the remainder of a number or integer is equal to its vortex sum. So number equals factor of 9 plus remainder, and remainder equals the vortex sum, or the mod 9 for base 10. So for example, 13 equals 9 plus 4 equals to 9. Yeah, this is equal to factor of 9 plus 4, and then v equals 13. V equals to 1 plus 3 equals 4 equals remainder. So if we extend this to negative numbers, we could write each of the single-digit numbers 1 to 9 in the same terminology as above, when looking at negative numbers. So here we have a 9 plus 4, but we're going to write here now as a using a negative number. So we could write 1 equals 9 minus 8 equals to a factor of 9 plus remainder, where the remainder is negative. So negative 8 there. And also we could write 2 as 9 minus 7, 3 as 9 minus 6, and 4 as 9 minus 5. And then 5 is going to be the flip side, 9 minus 4, 6 minus 3, 7 minus 2, and 8 is 9 minus 1, and 9 is just 9 minus 9 is 0. Actually, no, we got that wrong. This should be minus 0. Yeah, 9, otherwise it's 0. So 9 equals 9 minus 0. Yeah, and this could be plus or negative. It doesn't matter. So that's why, yeah, 9 is symmetric. It's the, yeah, there's no other number there, so it's always going to be the same there. So going further, so note that the numbers 1 to 4 are the exact, or the equations, or better yet, note that the numbers 1 to 4 are written in the exact same equations as that of the numbers 5 to 8, except just rearranged. So these are, in fact, the exact same equations as these, as their corresponding ones. For example, this 1 equals 9 minus 8. It just rearranged 8 minus 1. Let's bold this so that we know how we're comparing the two. So for example, we can write 1. Yeah, for example, the number 1 right here, let's just write these down. So we have 1. This equals to just 9 minus 8. So yeah, 9 minus 8 is just 1. This could be rearranged as, well, if we just take this 1, move it over to this side, and take the negative 8 and plus it to this side, what we end up having is a 8 equals to a 9 minus 1. These are exact same stuff. And then likewise, if we go 2 equals to 9 minus 7, and then make this negative, make this positive, this becomes 7 equals to 9 minus 2. And likewise, keep going, we go 3 equals to 9 minus 6, and then move the 3 to this side, make a negative, move the negative 6 to this side, becomes positive. This becomes a 6 equals to 9 minus 3. And likewise, we write 4 equals to 9 minus 4. I mean, yeah, 9 minus 5 is 4. So move this, this becomes negative, move this becomes positive. This becomes 5 equals to 9 minus 4. And now plotting this on the circle shows that we get, notice the symmetry right here, that the ones that are similar to, the ones with the exact same equations are parallel, or I mean that are in line with each other, so they're mirror pairs of them. So 1 equals 9 minus 8, 8 equals the rearranged formula of 1, which is 9 minus 1. Yeah, keep going further. So yeah, so this 1 equals 9 minus 8, same as 8 equals 9 minus 1, and then 2 equals 9 minus 7, same as 7 minus 2. That's this one right here. So let's write this down. This equals 2. Let's move this away. Unclick that. So 9 minus 2. I don't know why. Why not? It keeps jumping. 9 minus 7. 7 equals to 9 minus 2. Then 6 equals to 9 minus 3, 3 equals to, this is 9 minus 6, like that. And likewise over here, this is equal to 9 minus 5, and then this equals to 9 minus 4. So yes, these are just all symmetric pairs like that. And I'll just draw this mirror. So this perfect mirror like that. This is like a mirror where those are the exact same, but it becomes negative. One becomes negative, one becomes positive. These are pairs. These are the exact same equations, just as a different negative sign. Yeah, like that. Same as over here, pairs, and then pairs exactly across. Yeah, now since these numbers on the right side, these are just the same thing as these ones, but and the equations are just rearranged. And also you can note that if you look at the right side, it's plus 1, plus 2, plus 3, plus 4. And the left side includes these 9 minus 1, 9 minus 2, 9 minus 3, 9 minus 4. So if we're looking at a modulus clock right here, a modular clock, this could be considered as going left side, reverse, and this could be considered as going plus 1, or just put a negative for different increments. So this is going to be plus on the right side, and this can be considered as going backwards. Yeah, so this is clockwise, and that's why it's called clockwise. So it'd be clockwise, going positive on the clockwise direction, and this is the other one is counterclockwise. Yeah, so yes, fascinating stuff. There now, yeah. So since the numbers on the right are the same but rearranged equations as the numbers on the left, so the numbers on the right. Yeah, numbers on the left. We expect that vortex doubling any of the numbers 1 to 4 will mirror the vortex doubling of the corresponding pairs 5 to 8, and in fact, just doubling it as it is, it will become the mirror image of it. So if we have 1 equals 9 minus 8, now we double it, just times 2 on both sides. We're going to have this equals to 2, which equals to 9 times 2 is 18, and then minus 8 times 2 is 16. Then we have 18 minus, and we could write the 16 as our usual into parts, so 10 plus 6. because remember this 18 is a factor of 9, so just leave it as is. So we have this 16 is 10 plus 6. So we have 18 minus, and then break up the 10 plus 6 for base 10, 9 plus 1. And then we could get rid of this 9. So we just subtract this as well. 18 minus 9 minus, and then bracket 1 plus 6. That is that 16, break it up. And now we're going to have, then we subtract 18 by 9, we'll have 9, yeah, equals to 9, minus 7 is a factor of 9, minus 7, but in this case it's exactly 9. So doubling is the same as vortex doubling. So what we have is there, yeah, thus we could write 1 equals 9 minus 8 doubles 2, 2 equals 9 minus 7. So we expect that that doubling any of the numbers 1 to 4 will mirror the vortex doubling of the corresponding pairs 5 to 8. For example, here, if I draw this in red, this right here doubles to here. This is doubling. So we expect that it happens here as well. So we expect this to double here, and in fact that is what happens. So this is the pair of 1 equals 9 minus 8. This is exactly the same equation. These are exactly the same equations, so these should be doubling to here. Double. Or I'll just put it times 2. Like that. So yeah, so these should be exactly the same. And in fact that is what happens. So likewise, if we have 8, which equals to a 9 minus 1, mirror pair of 1 equals 9 minus 8, that is exactly the same equations. So multiply by 2 on both sides. This equals to 16 on the left. 8 times 2 is 16, which equals 18. And then 9 times 2 is 18. Minus 1 times 2 is 2. So if 16 equals 18 minus 2. So let's look at this left side now. So 16, again, in our usual, is equal to 10 plus 6, which equals to 9 plus 1 for base 10, and then plus 6. Move this 1 over to the other side. We have 9 plus 7, or 1 plus 6. So we have 9 plus 7 over there. And now we could write these both. So this 9 plus 7 is equal to 16, which equals to 18 minus 2. So write those down together. So 9 plus 7 equals 18 minus 2, which becomes, and then we could move this 9, so subtract it over to this other side. So subtract 9 on both sides, so we'll have 7. 9 minus 9 is 0, so we just have a 7. 7 equals to 18 minus 9 minus 2, and then 18 minus 9 is just 9, so it equals 9 minus 2. In other words, so that's what we have is 8 equals 9 minus 1 doubles 2, 7 equals 9 minus 2. Yeah, so that's what we have is vortex doubling 1 or 8 involve the exact same but rearranged equations because they are mirror reflections of each other. So in other words, 1 equals 9 minus 8 doubles to 2 equals 9 minus 7, and 8 equals 9 minus 1 doubles to 7 equals 9 minus 2. And also you can include here 8 times 2, so if you double this equals 16, number v equals 1 plus 6 equals 7. So which is expected, because again, this 9 there, just move it around. For the vortex sum, you ignore it. But yeah, so you can write it in terms of negatives, so it would be 9 minus 2 if you're including negative numbers. And yeah, we could see this, in fact, is the exact same mirror reflection. We can just look up here. So 1 equals 9 minus 8 doubles to here, 2, which equals to 9 minus 7. And then this 8 doubles to 7, as well as note the 9 minus 1 doubles to 9 minus 2. So even the remainder is double exactly as is. So then here is 9 minus 8, 8 doubles to 7. Oh, vortex doubles. And look, this is exactly the same mirror pair. So that's absolutely fascinating. Yeah, so going further. So in both cases, note the negative remainder, which doubles according to the expected vortex sum and is a mirror pair. For example, for the first one, we have 1 equals 9 minus 8. This doubles over to, well, right here, doubles. Now let's write it, let's go times 2, this times 2 over here, and then this one, then this scenario comes down, this goes over to, let's put it like that, 9 minus 7. This is the vortex doubling. Or here, I'll just change up the arrow, so it's, we're doubling the entire equation right there, it doubles over to here, so 1 equals 9 minus 8, so that's over here, doubles to 2 equals 9 minus 7, and here it is, and note this right here, I'll draw this in red. This goes to here. This 8 is just number 8. 8 doubles to 16. V equals 1 plus 6 equals to 7. Like that. So then even the mirror pair of this doubling right here, the 1 is the mirror pair of 8. It also, the remainder is also doubling according to its mirror pair. So 1 mirror pair of 8 the negative of it as its remainder doubles to 7, same as 1 doubles to 2. And likewise, if we have here 8 equals to 9 minus 1, so this right here. And again, note the negative 1 goes to negative 2. So 8 equals to 1 minus, or 9 minus 1. Like that. And then over here, this goes over to, this doubles to, I'll put this arrow right here. This red is indicating both of these actually. Put this in the middle somewhere. And yeah, so this will double all the way to over here, like that. This is going to be our times 2 doubling. A equals to 7 equals to, this is going to be 9 minus 2. Where in this red one, so the negative remainder just goes down to here. Negative 1 times 2 is negative 2. Or just, yeah, the 1 times 2 is 2. So in other words, the mirror pair of 8 is 1, and then 8 could be written as its negative remainder, as using the negative remainder there. And then doubling the remainder goes to negative 2. So what this means visually, because remember I told you that it goes negative is counterclockwise, positive is clockwise. So basically we have direction right now. Yeah, it has direction or polarity. So this means that the clockwise positive numbers, you have vortex circle, has an equivalent mirror image counterclockwise negative numbers of vortex circle, or negative, positive or negative. Negative vortex circle or positive vortex circle, or negative numbers vortex circle. Let's put the positive. Alright, so this means that if we're considering, so the basic one is just everything goes in positive. So this one right here is going to be plus 1, this can be considered as plus 2, and this is going to be plus 3, plus 4, plus 5, plus 6, plus 7, plus 8, and then this one right here could be actually a plus or minus. We could just leave it like that. So if we go clockwise, this is going to be positive, and it's going to be clockwise plus, like that. Or if we go in the reverse direction, if we draw this in red, the reverse direction, whoops, here, so we draw this in red. So now reverse, remember this 1 has, so the 1 has its equivalent negative 8, and that doubles to negative 7. So in other words, we're going in the same thing, but in the reverse direction. So here, we're going to go, this is going to be equal to negative 1. Actually, yeah, it's negative 1 because this one has its negative over there, but here, so the 8, if we just include this negative remainders, so it equals negative 1. So like this, we'll just write this as negative 1 here. And then then likewise it doubles over to the 7. Remember the 7 has a 9 minus 2, so that goes to negative 2 there. And in fact, they're all like that too. So for example, if we go back to our little chart here, so there's a negative 1, negative 2, negative 3, negative 4, and it goes to negative 5, negative 6, negative 7. So all it is the exact same, but going in reverse. Thus we're going to have, here's negative 3, this is going to be negative 4, and this one's going to be our negative 5. Everything has its conjugate pair, or just a pair, or polar pair, or polar opposite. So yes, this is going to be, so this can be viewed as going in reverse. So let's go and draw this in red, or should I draw it right here? I'll draw it like that. And this is going in reverse. So this is going to be counterclockwise, is minus, like that. So that's pretty fascinating stuff. So simply put, we could state that the path taken on one side of the circle has an exact mirror reflection on the other side. Because remember, these are exact same equations, but with a negative sign. So in other words, if we start here and we double, it goes here. This is going to be our times 2, or doubling, like that. Or just put it times 2. So if we vortex double, this is going to be times 2, it goes to here. So what that means is we're going to have a reflection over here. This doubles to here, and we know that 8 vortex doubles to there, so this is going to be our times 2, like that. And likewise, if we go again, so if we go here 2, if 2 goes to here, let's say 2 goes to here, doubles. So this also doubles like that. That means, and we know that the pattern is 7 has to go to 5. And this one is going to go like that. And we know that already. 7 times 2 is 14, 1 plus 4 is that. So they are times 2. So they're exactly mirror images. And this also means that, well, if we have here, if this 4 doubles to 8, so this 4 doubles to 8, this is going to be our times 2, then 5 is the exact mirror reflection, 5 has to double to the 1. So this goes all the way back there, and now we're set. Now we're basically cycling back and forth nonstop. So in other words, these are cycle pairs, or cycle mirrors, I mean. So we could just put a line across here, and there's our mirror reflection. Mirror reflection. These are exactly mirror reflections. So whatever we do to the right side happens to the left. So we double this one, goes here, and this one, since this one goes back to 4, 4 goes to 8, 5 goes to 1, now we have a cycle. This is a cycle. And it continues on forever. Yeah, and here I just added, and thus what we have is the 1, 2, 4, 8, 7, 5 pattern. So here's 1, 2, 4, and then goes to 8. 8 does exactly what this one does, so it has to go to the 7, and then the 7 it has to go to the 5 because 2 goes to the 4, and we just have a giant cycle like that. So now this mirror reflection can be seen more readily by assigning polarity to the bases quote unique numbers 1 to 4, or the single digits. So we have so the unique ones are just the ones on the right. So 9 goes to 1, 2, 3, 4 plus plus 1, 2, plus 1, plus 2, plus 3, plus 4, and then the left one is going to be minus 4, minus 3, minus 2, minus 1. So these are exactly mirror pairs. I don't know, all it is stating which direction you're going around this modular clock. Hashtag amazing. It's pretty amazing stuff, guys. So having established a doubling mirror reflection pattern for the doubling 1, 2, 4, 8, 7, 5 pattern, this concept can be expanded to 3, 6, 3, 6, and 9, 9, 9, etc. patterns. So 3 doubles to 6, so we have 6 doubles, and then likewise 6 doubles to 3, 1, 2, or 6 times 2 is, I'll just write this here, 6 times 2 equals to 12, and then v equals 1 plus 2 equals 3, and then the cycle keeps repeating. So it's always 3, so it's always going to be 3, 6, 3, 6. But you can see this visually here if we look at the mirror pair. So we go here, mirror. So this means mirror like that. Whatever we do on the right side, we have to do to the left. So if we go here, 3, we start from here and double. 3 times 2 is 6, like that. So we get to here. So this is going to be our times 2. But this also means that now if we go from here, let's draw this. If we draw this in red like that from 6, so that means 6 has to go to here because it's exactly mirror. Because if 3 goes to this left side horizontally, this has to go there exactly, and we know that 6 doubles to 3, and so that has to go there. So in other words, it just goes back and forth based on the symmetry of this number system, and that 3 happens to double to exactly 6. And if it does, that means this one has to go there as well. And then for the 9 pattern, or 9-1 is the easy one. 9-1 is just on the top. Since it's the modulus over there, 9 times 2. I'll go here. 9 times 2. This is the same thing as writing. Whoops! I don't know why this keeps doing this. Okay, this goes 9 times 3, 9 times 4, etc. 9 times 5. Well, actually, I gotta erase that because we're doubling only. So this is gonna be 9 times 4, etc. Then this doubles to 9 times 8, like that. This always doubling, and etc. Dot dot dot. These are still factors of 9, so they're always gonna be themselves. Factors of 9. So in other words, it's always gonna be 9. So v equals 9. Yeah, I don't know why this is jumping. V equals 9, like that. And you can also see this visually, that if you have 9 here and you add 9 to it, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. If you add it left side, 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't matter which side you get to. Add or subtract, you always get to the top of the modular 9. Yeah, so note that, as I just showed, that 3 and 6 are mirror reflections of each other, and 3 doubles to 6, thus 6 also doubles to 3. So, and also 3 times 2 in base 10 equals 6. 6 times 2 is 12. V equals 1 plus 2 is 3. And also all multiples of 9 are factors of 9, and thus 9 mod 9 equals 0. And so we just set it to, note that the vortex sum is still 9. So we set the mod, the remainder 0 equals to 9 for the vortex sum, or the modular clock, like that, so 9. Yeah, so and also, here 9 doubles to 18. 18 is just equal to 9 plus 9, factor of 9 plus remainder. And you could view it as 18 plus v equals 1 plus 8 equals 9. This would be actually termed vortex remainder, because the remainder still divides evenly by 9, so it's vortex remainder. But anyways, know that the modulus, in this case 9, always vortex doubles to itself regardless of what it is. Although, Yeah, it's actually it's not just this 9. Any modulus, double it. It's always going to be itself, because the remainder is all based on dividing by the modulus, so it's whatever the modulus is. So we're dividing by 9. These are all factors of 9. If it's a different base number system, we're going to be dividing by that. So then we're going to be looking at factors of 7, 8, 2, etc. So let's go further. Yeah, so note that the modulus, in this case 9, always vortex doubles to itself, regardless of what it is, whatever it is. Although we have thus far covered symmetry of the base 10 system, the same symmetry concept applies to all number systems in general. Consider the base 4 system. So if you have base equals 4, the modulus is this equals base minus 1, or mod or modulus, which equals to 3. And then single digits are 0, 1, 2, 3, but for the modular clock, we'll only look at 1, 2, 3. Yeah, so we know that 1 doubles to 2, so thus 2 has to double to 1 in its mirror pair, as I'll show. Because you can see here, yeah, so 1 equals to just 3 minus 2. That's the modulus. So then 2 has to, yes, 2 is equal to 3 minus 1. So this means that the 2 has to double to 1. And you can see that 2 doubles to 10, or 4. But 4 is the modulus, so we said that is equal to 10. So V equals 1, or 4 mod 3 for base 10. Yeah, or in base 10, we have 4 mod 3 equals to 1. Yeah, this V equals 1 plus 0 is 1. So going further, 1 equals to 3 minus 2, writing it in its modulus subtracted by a number, which equals to, again, factor of 3 plus remainder. Here's negative remainder. 2 equals 3 minus 1, factor of 3 plus remainder, and it's negative. And then if we have this first term, 1 equals 3 minus 2, double it, double both sides. This equals to, it's going to equal to 2. 1 times 2 is 2. Then we have a 3 times 2, that's going to be 6 in base 10. But let's just leave it as is, because we're dealing base 2. And then we'll have this negative 2 times 2, that's 4, or we'll replace it with a 10. So 3 times 2 minus 10. And 3 times 2 equals to 3 times 2 minus, and then write this in its equivalent terms using the modulus 3. So if it's equivalent base 2, base 4 term. So it's going to be equal to this 3 plus 1 there. Then move this 3 out of there. So we get a 3 times 2 minus 3. 3 times 2 minus 3 is just going to be, well, 3. Yeah, so we're going to have 3 times 2 minus 3 minus 1 equals to 3 minus 1. So thus we have 1 equals 3 minus 2 doubles 2 as expected. 2 equals 3 minus 1. So this doubles to its mirror pair over there. Well, in this case, doubles to its mirror pair. Doesn't always have to be different number systems. This is going to be like the 3, 6, 3, 6. But yeah, doubles to over here, where the likewise expected one is going to double to it. Its pair is going to double to the mirror reflection of this one. So likewise, 2 equals 3 minus 1. If you double that, equals to this 2 times 2 is 10. So this is going to be, let's write this 2 times 2. We'll just leave it like that. 2 times 2 is going to be 10. And then equals to 3 times 2 minus 2 times 1 is just 2. And then this 10 is going to be equal to, like that. Or for more completeness, I'm just going to write this as 2 times 2 equals to that. And then this 2 times 2 equals to 10. Yeah, just write it like this. 2 times 2 is equal to 10 in base 4. Then write the 10 as 3 plus 1. This equals to 3. Yeah, so this is going to be this equivalent for the number 10 for base 4. So again, 3 times 2, multiply this inside. Actually, no, that's not multiplying inside. That's this part right here. So this 2 times 2 is equal to 10. This is from this top part right here. This equals to that. So we're going to have 3 times 2 minus 2. And then this becomes, move this 3 on the other side, subtract on both sides. So we'll have a 1 equals 3 times 2 minus 3 minus 2. In other words, this 3 times 2 minus 3 is going to cancel. It's going to be equal to 3. So we're going to have 3 minus 2, like that. So 1 equals 3 minus 2. Thus 2 equals 3 minus 1. This equation doubles to 1 equals 3 minus 2, which is as expected. And we'll show that visually as well. And also now look for the base 3, or the number 3, the modulus in base 2 doubles to 3 times 2. And again, this is going to be 2 plus 1. Can't just, we can't just multiply. It's going to be greater than the modulus. It's going to be greater than 4, the base. So we're going to write this as 2 plus 1. So we have 2 times 2 is going to be 10. Then 2 times 1 is just 2. So we'll have 10. So equals to 12. 10 plus 2 is 12 in base in base 2 or base 4. This is not base 2. This is base 4. Or yeah, I'll just remove this. We don't need this base there. This is, yeah, so that's base 4. Yeah, it's 3 doubles to this. We're all dealing with base 4. So then this equals to 12. Yeah, so 3 times 2 equals 12 in base 4. V equals 1 plus 2 equals 3. And then 3 times 2 in base 4 converted into base 10. That just equals to 6. Like that. Yeah, this equals to 6. Because you can just multiply 3 times 2. And then 6 mod 3 equals 0. V equals 3. In other words, the mod of the multiply 3, double 3 is always itself. So 3. Yeah, so we have here 3 doubles to itself. 3 times 2. This is going to be the same thing as 3 times 4, 3 times 8, etc. These are just going to be factors of 3. So then V equals to 3. It's always going to be 3, etc. Then here, if we have our plus 1 or just our 1, remember you could write this as 3 the modulus minus 2. So 3 minus 2 is just 1. And then here, we could write on this other side, we could write this as 2 plus 2. Just get all the polarity and everything. This could be plus or minus. Doesn't matter. Whatever you do, it's always going to be itself. And then you're going to have this as plus 2. This equals 2. You could write this as 3 minus 1. 3 minus 1 is just 2. And now if we double, let's just do some doubling. So if we double this, yeah, this doubles to here, and that's its mirror pair. Because remember, the symmetry line of symmetry is right here. Let's try this a bit better. Yes, this is the symmetry line, or this is our mirror. Like that. And then notice right here, so that's a doubling. This has to, I'll just put a multiply. This times like that. And this 2 doubles over to this side. Doesn't matter. So if you have this 2 like that. Yeah, this 2 like that. Yeah, so if you have 2 multiplies it here, goes to 4, which is just 10. V equals to 1. So in other words, back and forth. It's exactly like a 3-6 pattern. So in other words, we're just going to get a 1, 2, 1, 2, 1, 2 pattern. Yeah, so here we can write this as a pattern. Let's write this as pattern for the 3 one. 3, 3, or just a 3, 3, 3. Etc. Dot, dot, dot. And then this one here, we're going to have our other pattern. We're going to have a pattern of 1, 2, 1, 2, 1, 2, dot, dot, dot. And likewise here, now if you look at the negative side, here is the negative 1. We look at so we could just view the negative 1 times 2 is going to double to negative 2, like that. This is doubling there. And likewise, the mirror is going to happen as well, the same thing. So back and forth. Negative 2 times 2 is going to be negative 4, which is, or negative 10, V equals 1, negative 1. Yeah, and here I'll just write this down as well. Note the doubling pattern. So if you have 1, and then 1 times 2 is 2, and then 2 times 2 is 10 in base 4. Yeah, this V equals 1, and then if you double that, 10 times 2 is 20, V equals a 2, and then 20 times 2, that's going to be 100, because remember it's 40 in base 10, but we're dealing with base 4, so we can't go, there's no number 4 in base 10, we just go add another 0. So 100, that V equals 1, and then likewise the pattern goes on. 1, 2, 1, 2, 1, 2, non-stop. So this same symmetry concept and mirror reflections works for all number systems as well as for, or I'll just reword that, for all number systems and for all multiplication factors beyond just doubling. So yes, you don't need to just double, you can do a bunch of other stuff. So let's go continue further. So factors that govern Vortex patterns. Yeah, so let's look at factors that govern Vortex patterns in general. So now to expand further on the above section on symmetry that we've been dealing with. So this one here, let's remove this. Yeah, just remove that. So to expand further on the above section on symmetry, here are a few other factors that govern the vortex patterns that arise. So even and odd base number systems. The base 10 and base 4 systems covered above the ones that I just showed over. This is base 4, and the earlier ones are base 10. It's like that. So the base 10 and base 4 systems covered above are both, quote, even, but their corresponding mod 9 and mod 3 are, quote, odd. When the modulus, when the, quote, modulus is odd, then the corresponding, quote, vortex circle or modular clock is symmetric about only the modulus. Yeah, so when the modulus is odd, that means we have even base number system. So here is base 8. Let's go base 8 right here. And this would be 7, so it's an odd. And look at how it's symmetric. It's going to be written like this. 1 goes to 2, goes to 3 here, and you just move it down. So the corresponding number here is going to be, well, 3 is going to go to 4. 2 is, yeah, the next one's 5. Corresponding here is going to be 6, like that, just mirror reflection. Then if you have our base, let's write a base 6 right here. So even base, odd mod. So we're going to have 1, 2, this is going to be 3, write it in symmetric form, 4, like that. So now if we draw this in red, let's go to our doubling pattern. So 1 doubles here, times 2, and then this is corresponding pattern is going to have 6 times 2. It's going to be like that, times 2. And we could see this as well. If we go 6 times 2, this is going to be v equals 2, and write this in base 10. 12 mod 3, or 12 mod 7. 12 mod 7, the difference is 5. So that's a very quick way to solve it. The difference right here, the remainder would be 12 divided by 7. You're going to have a remainder of a factor of 7 plus 5. That's the difference between it. And likewise over here, double this one. I got 1 times 2 is 2. 4 times 2 in base 6. This would have to be there by symmetry. So again, we'll just do a symmetry like that. These are pairs. So whatever you do to the right or left, you do to the other one. So you multiply, you do the same thing. So pair, pair. And you can see this as well. So the 4 times 2, this v equals to the vortex sum is the same as doing it in just a mod like this, using the base 10. And this would be 4 times 2 is 8 mod. Yeah, this is going to be 8 mod 7. I mean 8 mod 5. 8 mod 5. The difference is 3. So the remainder is going to be 3, like that. Yeah, so there it is exactly. And yeah, so we have it's symmetric about only the modulus when we look at it in this vertical system like that. So there's a symmetry like that, only about the modulus when we split it in half, like that. So here we'll write mirror. And there's only the modulus number, mirror. Like that. Yeah, so notice in this one, base 8, base 6, both even, odd, and then you have odd modulus, and then if you draw a line straight down from the modulus, it's only symmetric about the modulus, like this. So that there's no other number right here, but that's not the case for odd base numbers, which I'll get to in a bit. But so thus, in general, even base numbers have symmetric vortex circles shown as below, and so let's say you have base equals n, which is even, and then you have p equals n minus 1, and it's odd. So then what you have is here, we'll have p. If it's odd, yeah, let's say it's odd. So that means when you draw this vertical line like here, there's no other number going to be there. Because when you divide it by 2, it doesn't divide evenly, so you're going to have to draw, if you're trying to draw the symmetric vortex circle, you're just going to have it, so it's going to look something like this, 1, 2, 3, etc. And then dot, 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 keeps going on. And then over on this side here, this is going to be p minus 1. And then here's going to be p minus 2. And then here's going to be, let's just line it up with here, p minus 3. Let's write this here, p minus 3. And then, yeah, just line those up. And now we have over here, just line this up, it's going to be like this, this, and this. Where this number here is, it's not going to be a number across here. So this is our mirror. And there's yeah, no number here. Let's write no, or here, no number. And here, just to remove that circle so it doesn't look like a 0, I'll just put a dashed box like that. So no number over there. Yeah, and here I'm just going to write, yeah, so p is odd. This is going to be even base, or base equals to even, just to here. Write it there, and like that. And now let's look at odd base number systems. Yeah, so for odd base number systems, we have an even modulus. Thus, a vortex circle will be symmetric by the modulus and 1/2 of the modulus, and the number 1/2 of the modulus. For example, here let's say we have base 9, let's say we have base 9 like this. So if you have base 9, the modulus is going to be, well, 8. So, yeah, 1 and 9 divided by 9 minus 1 is 8. And now if you want to draw a perfectly symmetric vortex circle, we're going to have to, or make it all evenly spaced. This is 8. 8 divided by 2 goes to 4 evenly. So that means we're going to have a number here if you want to make it like our typical vortex circle. There's going to be number 4. Now here we're going to have a number 1. And here we're going to have a number 2. It's going to be perfectly symmetric like this. Then 3. The next one's going to be, well, here 5. Then we have 6. Like that. And the next one's going to be, well, 7. Like that. Yeah, so that's our vortex circle. All of these are evenly spaced. And now if we want to make, let's say, another one, let's say base 7. Another odd one, just to illustrate this. Base 7. So if you have base 7, the modulus is going to be 6. And then half that. Half this goes all the way across here. This is 3. So we're going to have a 1, make it all perfectly symmetric. 2, like that. And this is, yeah, perfectly symmetric. This one's going to be 5. And this is going to be 4. Like that. Yeah, so thus in general, what we have in general base or in general odd base number systems, in general, odd base number systems are as follows. So if you write this down in generic form, so let's say we have a base equals n, it's odd, and then the modulus is equal to n minus 1 equals to p, so that equals to p, and it's even. So that we're going to have an even modulus. So this means here, p, this is going to be even. Yeah, let's just draw this out. This is going to be even. So this is going to be even. And just write it here and big right here. So we're going to have a base. Yeah, base equals to odd. So base is odd, then the modulus is even. Let's write that. Base equals to odd. Then just underline that. I don't know why it keeps doing that. Like that. Alright, so we have p like that. Then we're going to have at the center, it's going to be mirrored all the way down across with half of it. This is going to be p minus 2, p divided by 2, like that. And then, so this the first term is always going to be 1, you always have 2, depending on the size of the number system. And then the reverse of this one is going to be, well, p minus 1, or the mirror image. Then p minus 2, like that. And then we're going to have dot, let's say it keeps going on, like that, and like this. But then we could also, we know what the pattern is from the bottom. The pattern of the one to the right of this is going to be, well, p divided by 2 minus 1. Then to the left of it is going to be p divided by 2 plus 1. And then we're going to have over here p over 2 plus 2, etc. Dot, and then dot. And then eventually it's going to coincide with those. But these are all going to be, equivalent. If you go from here, p minus 1, p minus 2, you're eventually going to have it over here where these are just going to equal to these. But you can start from the bottom or the top up. Yeah, you can start from the top down or bottom up, which is fascinating. So then the next one here is going to be over here, p over 2, p divided by 2 minus 2. Like that. And next dot, and then let's say another one, symmetric, like that. And it keeps going on. So yes, very fascinating stuff. So it's symmetric about these two numbers. So let's go further. So the main difference between odd and even base number system is that the odd base number systems have a vortex circle that's symmetric about two numbers, so just like this, p and p over 2. An odd base number system has an even modulus. This means that doubling the number p divided by 2, so right here, if you double this, it just goes to p. So it becomes equal to p, which are also the numbers that the circle is symmetric about. So if you double this one, it's going to go over here. If I draw this here, doubling from here goes to the modulus times 2. And then the modulus, whatever you double the modulus, is always going to be the modulus. Yeah, so doubling isn't the same as for even base number systems, which have an odd modulus. So let's go further. This means that doubling right here becomes the same. So we can see this for the base 9 and base 7 vortex circles. So let's say from base 9, if you start from 1, so for number 1 multiplied by 2, or vortex double goes to 2. Then 2 multiply this. We're gonna just cut it like this, cut straight across. So this goes straight across like that. Goes to 4. And this is multiplied by 2. But then this one, 4, goes straight to the modulus. Like that, goes straight to the modulus. And then this one here, this doesn't go back to the 1. This just goes to the modulus still. This is times, yeah, so we'll go 8 times 2. No, this one here is actually, we're just going to put like this, v equals to. V equals to 8 always. So v equals to, or vortex sum is always going to be 8 when you double. Or I'll go times 2, v equals to 8 times 2, v equals to 8. So yeah, so you're always going to be stuck there. It doesn't go back to the 1. Similar for the base 7, you have an even 6 like this. So if we to double from there, we just start from the 3. And then this one goes up to the 6. This is our times 2. And this one here, again, this goes to itself. It does not go back to the 3. So this is going to be, 6 times 2. Let's write this like this, 6 times 2, v equals to 6. Just a factor of 6. Yeah, so notice these patterns, if we were to write them down, what we end up having. So for example, for base 9, 1 doubles to 2, which doubles to 4, which doubles to 8, and 8 just doubles to itself since it is the modulus. So then we were going to have a pattern of 1, 2, 4, 8, 8, 8, 8, 8 non-stop. So it's not like the usual patterns we're dealing with, usual doubling patterns for the base 10 or the other base, the even bases. And base 7, 3 doubles to 6, which always doubles to 6 since it is the modulus. This just goes to itself. So we're going to have a pattern of 3, 6, 6, 6, 6, 6, dot, dot, dot. So thus for odd base number systems, there's an additional pattern that doubling the midpoint, the midpoint number gets, quote, funneled to the modulus hashtag. Interesting stuff. This is actually similar. If you were to, for the base 10, if you multiply by 3 instead of double, so you tripled, then 3 would go to 9, which becomes the modulus, and so on. And the pattern would be, well, 1 times 3 is 3, 3 times 3 is 9, and then you get a 1, 3, 9, 9, 9, 9, 9. So anyways, but this is in particular is for doubling. So size of the number system. There's another factor that governs the pattern. So this was part of this section. Yeah, so factors that govern vortex patterns was even odd base number systems, and then the next one's going to be the size of the number system. So another factor that governs the types of vortex patterns that arise is the size of the number, the base number system. The bigger the base, then doubling will have more numbers in the pattern before the quote mirror reflection. Consider the base 18 vortex circle doubling pattern. So here, if you have base 18, that's even, so we're going to have an odd modulus, and there's a mirror reflection all the way down. And I have this already pre-written down. So that's the mirror, and now let's start doubling from 1. So here we double, we get to, well, 2. This is just times 2. And then what happens here? 2 becomes to 4. And let's catalog this pattern right the whole time. So pattern like this, and we're gonna have a 1, 2, 4, and then 4 goes to 8, like that. So we have 4, 8, and then this is going to be, and now the 8, well, 8 times 2 is 16, so this always goes up to the very top like that. That's 16. So remember, this is base 17, so I have 16 there, 15 all the way there, so we have 17 numbers in this modulo 17 circle. So what we have now, the next number is 16, and again, this is written in base 10 notation, just for convenience. So this is going to be base, this is number 16. And here, I just wrote it down, written in base 10 notation, as I mentioned earlier in this video. We'll just convert everything to base 10 notation for convenience. So we have 1, 2, 4, 8, 16. And now the expected pattern, well, this is a mirror pair. I'll just draw this in green. This is a pair. So that's a pair. So then this one has to, well, mirror this exact same thing. So 16 has to double over to here, to 15, which is 1 that goes to 2. Like that, and this is the pair, like that. I'll draw this pair. The next one's going to be over here, so this should be a skipped one, and should go over there. So pair, and then one more is over here. These are pairs. Pair, like that. So what we're going to have is this 15 is pairs with 2, so 2 goes to 4. That means 15 has to go to the pair of 4, which is 13, I mean. And then likewise, this has to go all the way to 9. So vortex doubling goes to 9, and then 8, since 8 goes to 16, 9 has to go to 1. So this has to go to 1. Let's draw this straight across, like that. Yeah, here I just move these pairs away. So it goes back to the 1 and then repeats the cycle. So let's keep writing our down. 16 goes to 15, 15 goes to 13, and 13 goes to 9. And then likewise, this is going to go to 1. And then we've our pattern has started repeating. So it goes to 1, dot, dot, dot. So I'll just leave it at the 9 to indicate that's the pattern, and then it starts repeating. Like that. Yeah, so what we've just done right now is determine the doubling circuit or doubling pattern from starting from 1 for the base 18 without actually having to calculate what the actual vortex sums were, or multiply 16 times 2 or 15 times 2, etc. We just directly used the symmetry of the vortex circle and the base number system, and we got this, and we can double check that this is in fact correct. This is 1, 2, 4, 8, 16. 15, 13, 9. So we can double check that the mirror reflection does indeed obtain the correct doubling pattern. So if we have 1, 2, 4, 8, 16, 15, 13, and 9. So we start from 1. Then we double 1. 1 times 2 is 2. And then double 2. 2 times 2 is 4. And then 4 times 2 is 8. And then 8 times 2 is 16. And then 16 times 2, well, this will get to 32. But I'm just going to convert this into directly... Or just, yeah, you use the base 10 notation for the whole thing. That's why we have the 16 as opposed to some other random letter A, B, C, D, F, or whatnot. So anyway, so we can go 16 times 2 is 32, but V equals to 32 mod 17. That's the mod P is the mod 17. And you can just directly calculate it using the base 10 notation and the calculation. So this equals to 15. And likewise, 32 times 2... Yeah, this V equals to 64, so 32 times 2 is 64, but the vortex sum is V equals 64 mod 17, which equals to 13. And you can see this right here. Or you could multiply this 15 by 2, this previous vortex sum by 2, and then V equals to 15 times 2 is 30. So V equals 30 mod 17, and you can calculate that. That's exactly 13. This fascinating stuff. And then 64 times 2 is 128, or V equals to... the vortex sum is going to be 128 mod 17. You get the remainder of 128 divided by 17. That equals 9. Or 13 times 2. V equals to 26. Yeah, 26 mod 17 equals 9. And you could, you could just calculate this. Automatically show it equals 9. Likewise here, you could do the previous one, 13 right there. So many ways of calculating the vortex sum. It's always going to be the same, and you can just use this the same mirror reflection of this symmetry there, which is absolutely fascinating. So then going further, so 128 multiply this one times 2 is 256, or V equals to 256 mod 17. You get the remainder equals to 1, and you can see this, and it restarts. Or you could have just gone 9 times 2 is 18. 18 mod 17 is 1. Yeah, 18 mod 17 is 1. So it's fascinating stuff. So then it just restarts right now. So in other words, we have our 1, 2, 4, 8, 16, 15, 13, and then 9. And it goes back to 1, which confirms our pattern. Yeah, so we derived it just from using this this vortex circle. Just using the symmetry of the base number system, we were able to get the doubling circuit or doubling pattern. And we didn't even need to do anything else. We didn't even need to do any calculations over here. So it's absolutely fascinating. So the base 18 vortex circle, vortex circle, this is similar to the base 10 vortex circle in that there is an exact mirror reflection of the doubling circuit. But in the, so you can see the exact mirror. So you go run 2, 4, 8, and then this has an exact mirror 16, 15, 13, 9. Yeah, but in the base 18 vortex circle, there are more numbers skipped in the doubling pattern. For example, if you look at here, so it goes 1, 2, and then it skips to number 3, goes to 4. But then here we skip 5, 6, 7, then goes to 8, then goes to 16, and etc. But even though these are exact mirror reflection like that. So it has more numbers skipped than the base 10. So the numbers 3, 5, 6, 7. It's right here. 3, 5, 6, 7, and its reflection and its mirror is 10, 11, 12, 14. So let's go here. Yeah, so the numbers are 3, 5, 6, 7, and their mirrors 14, 12, 11, and 10. Let's just double check. So 3 is 14, 5 goes to 12, 11, 10. Yeah, 5, 6, 7, 11, 10. Yeah, and their mirrors 14, 12, 11, 10 are skipped in base 18. But if you looked at base 10, only the 3 and mirror 6 are skipped in base 10. And again, in both cases, we're ignoring, let's write. In both cases, the modulus is skipped. But yeah, so skip, but again, that's not relevant for this one here. So if you look at the base 10, this is going to go to 1, 1 goes to 2. 2 skips number 4. I mean, not number 3, so it skips it like this. So it skips it. So that this one is skipped over there. Yes, the number 3 and 4 are skipped, and then the 4 goes to the 8. 4 goes to the 8 like that. And then the 8 is a mirror pair with 1, so it just goes to there. And this skips to 5, the 6, like that. So we have, and then this cycles back, like that. Then we have our pattern. Exactly, we could just calculate it. We could just look at this and just find the pattern instantly. It's going to be 1, 2, 4, 1, 2, 4, 8, 7, and 5. And then this 3, I'll just draw this for completeness. Pair. Then we have another pair like that. Those are pairs and pair like that. And then so the number, I'll draw this in blue maybe. So this one here, so these are skipped. So let's put an arrow like that. 3 and 6 are skipped. Like that. So yes, this one has less numbers skipped. This one has more numbers skipped over here, and then you're gonna have room for different or more patterns inside, because you can start from the 3, you can start from the 5, 6, 7, etc. As opposed to the base 10, everywhere you start besides the 3, 6, or 9, they're already part of the circuit. So if you start at 2, you're gonna have to go follow this cycle. If you follow this 1, it's gonna follow the cycle 4, 5, 6, 4, 5, 7, 8. Yeah, the only ones that are different are 3, 6, and 9. So now let's go further. So note that not all base number systems have a direct one-time reflection before the cycle repeats itself. So consider the base 12 number system, which has several mirror reflections before the cycle repeats. So here's base 12, and I've already drawn out the vortex circle. And then we have also, it goes from 11, and it cuts down the mirror between 5 and 6. And then notice right here, notice here, this 5 and 6, actually I want to make a note here. So 11, if you 11 minus 1 is 10, then divide by 2 it goes to 5, and then or 11 plus 1, and then divide by 2, so it's 12 divided by 2 is 6, like that. Then we can just write that in our general, even base number system. So here, if this is odd, then you can write the one to the right of it is going to be, well, p minus 1 divided by 2. This one here to the right of it is going to be p plus 1 divided by 2. And again, that's because p divided by 2 does not divide evenly into it. So anyways, let's keep going further. I just wanted to make a note. And yeah, you could see that for all the other ones too. Let me just see the one here. So this is even, yes, base 8, so odd is 7. So we'll have 7 plus 1 is 8, divided by 2 is 4. 7 minus 1 is 6, divided by 2 is 3. And likewise here, 5 plus 1 is 6, divided by 2 is 3. 5 minus 1 is 4, divided by 2 is 2. So 4 divided by 2 is 2. So yes, fascinating stuff. Let's keep going further. Alright, so let's look at our base 12 number system here. And now I've added the pairs in green already. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it cuts down the middle like that. And now let's start our doubling circuit right here and see what happens. So if we have 1, let's draw this in red actually. Now let's draw this in red. I'm going to write this here 1. And so our pattern starts off at 1. Next one here, we're going to multiply by 2. This is going to be our doubling pattern. 2 goes to 2. And then here, 2 is going to skip here. But notice here, this goes to 4. This goes to 4, the doubles here. But now notice the 4 isn't at the bottom here. It's not at 4. So it's not over here. And again, let's look at the even number again. Let's go back to the even number, because I'll discuss this later. So the even number right here, or the other one, or even this one right here, either or. But if you look at this one here, p minus 1 divided by 2, if you multiply this by 2, it goes to p minus 1, which is the mirror pair of 1. But that's if it's the bottom right number. But for the base 12 number system, we have it over here, which doesn't go over there. So I'll show you what happens. Yeah, let's go back here. So 4, it doesn't go to the top left, so it's not the bottom right. So if you have 5 here, 5 times 2 goes to 10. But instead we have a 4 times 2 goes to 8, like that. 8 over here. Yeah, it goes to 8 over here, but now there's the mirror pair of 8 is 3, but we don't know what that, we haven't calculated doubling of that, but we can though. So 3 times 2 goes to 6. What that means is, well, so that means that we don't need to do the vortex sum of 8, 8 times 2, and because we could just do it from the 3 and then use a mirror reflection. So 3 over here, I'll draw this in light red like that, 3 goes to 6. That means the 8 has to go to its mirror pair, which is 5. So there's the green dash. So then this, this 8 goes straight across over here. So yes, I just drew it over there. So basically, we could use a mirror reflection of the smaller numbers, the 1, 2, 3, 4, 5, the positive small numbers. Otherwise, this one's negative ones. Instead of actually having to calculate 8 times 2 and then taking the vortex sum. So we just use a mirror pair of 3 over here, and then I'll just erase that just to make it clear. So just make it less messy right here. But notice here we crossed the mirror reflection twice now. So we've already gone once. Now we're going back here, and now the 5 times 2 is just 10, and now we're crossing it again. So 3 times. So it's not a direct one-time mirror reflection. So not all of them have it. This one has just one cross. It goes like here. It crosses once, and then the next time it crosses, it's back to its cycle. Same as the base. Which other bases? Yeah, the base 18. Let's go back to the base 18. Yeah, so notice here, 18, it crosses once. It goes from 8, goes 16, it crosses once, and then the next time it crosses, it's repeating its cycle. So yes, it does a direct one time before the cycle repeats. Yeah, so now back to here, it goes to 10, and now 10, where will 10 go? Well, 10 has a mirror pair of 1, 1 goes to 2, so that means 10 has to go to 9, like that. And then the 9 has a mirror pair of 2 right there, and the 2 goes to the 4, that means 9 has to go to the 7, like this. This has to go to the 7, and then the 7 has to go, well, wherever the 4 went. 4 went to 8, 7 has to go to 3. So then this goes across there. Oops. Let's draw this again. Oops, I don't know why my OneNote keeps doing that. So it goes like that. So there's a 3, and then 3 goes to the 6, which we already illustrated earlier. 3 goes to the 6. And notice the 6 is the mirror pair of 5. And let's just keep track of this one, write this down. So 4 goes to 8. 8 goes to 5. And then we have 5 goes to 10. And then what's the next one? 10 goes to 9. Then 9 goes to 7. 7 goes to 3. And then 3 goes to 6. And then 3 goes to 6. And then we know that 6 is a mirror pair of 5. 5 goes to 10. That means 6 has to go to the 1. So now the 6 goes all the way back to 1. There's the cycle. And there's our cycle. Repeats. Or, cycle. Repeats. Yeah, so there's the pattern. That's the pattern we expect, and we can double check as well to see that this is in fact true. Yeah, so again, for this pattern right here, we were able to get it with just using the symmetry of the number system on this modular 11 clock, or this vortex circle, a vortex 11 clock. Or just a vortex circle for base 12 with modulus 11. So when, yeah, notice the pattern 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. So we can double check this again. Again, we didn't even need to do any calculations besides the simple doubling from the right side, which has a full number on the left side without having to reduce or digit sum or vortex sum further. So now double checking the vortex circle doubling pattern. Yeah, we can go, so here's the pattern. So 1, 2, 4, 8, 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. So 10, 9, 7, 3, 6. We go from 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2, this will become 16 in base 10 notation. And again, we're just converting it all and writing it all in base 10 number systems, as I stated earlier, instead of writing this as letter A or whatnot. And then this would be, actually no, this wouldn't be, yeah, this would be A, this would be B, this would be letter B for the modulus. But anyways, just write it as 10. So, because it's greater than the base 10 system, the modulus 9. So again, so we'll go here. So 8 times 2 is 16 in base 10, and then we're just going to calculate that directly. So V equals 16 mod 11 equals to 5. Equals 16 times 2, V equals 32 mod 11 equals to 10, like that. Or you could just go multiply the previous vortex sum. So 5 times 2 is just 10. 32 times 2 is 64, or V equals 64 mod 11 to get the vortex sum is 9. Or you can go right here, 10 times 2 is V equals to 20. And then mod 11 is equal to 9. So V equals to 20 mod 11. Again, this is base, writing in base 10 notation for the base 12. And furthermore, you get 64 times 2, V equals to 128. Mod 11, you get 7. So we're getting the exact pattern. Or you can go 9 times 2 is 18. Mod 11 equals 7. So V equals to the vortex sum, or digit sum. Then keep going further. 128 times 2 is V equals to 256. Gets really large. Mod 11 is going to be 3. Or you could go 7 times 2 is 14. Mod 11 is 3. And likewise here, 256 times 2, V equals to 5112. Mod 11. Again, 2 times 256 is 512. Mod 11 equals to 6. Or you could just go 3 times 2 is 6, using the previous vortex sum. And then going further, 5112 times 2, V equals to 1040. 1024. You can see that right now. It just equals and equals to directly that. But that's why. But we're taking the vortex sum. So V equals 1024 mod 11, and that equals to 1. So the cycle repeats. Or you can just go 6 times 2 is 12. Mod 11 is 1, and number 12 and base 10 is just 10. Or I'll just write this here. Or just to show that different base number systems, or 6 times 2, this equals to, this is base 12, equals to, I'll just put equals to 10 in base 12. So that's fascinating stuff. And then V equals to, let's put this bracket 12, V equals 10, V equals to 1. Yeah, so 1 plus 0 is 1. So anyways, I just wanted to include that because yeah, I've just jumped straight to using everything in modular, in base 10 notation. But here just to illustrate if you're using different base number systems as well. So anyways, going further, so we have the pattern 1, 2, 4, 8, 5. So 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. 10, 9, 7, 3, 6. Same thing here. 1, 2, 4, 8, 1, 2, 4, 8, 5, 10, 9, 7, 3, 6. So yeah, 1, 2, 4, 8, 5, 10, 9, 7, 3, 6, which confirms the vortex circle doubling pattern. Which is actually pretty amazing. Going further, the base 12 number system is quote messier than the base 10 or base 18 number systems, because the doubling pattern jumps across the mirror several times before restarting the pattern at 1. So yes, it has it's several times. It goes back and forth. So it cuts from here once, then goes twice, then 3 times, and then it goes to 4 times, 5 times, and then so 5 times before the cycle repeats at the 6th time. So it's 6th cycle. So yes, I'll just keep going further. Yeah, also I want to make a note, the next level use of the mirror pairs to find a doubling pattern of numbers from the left side, which otherwise would need to find a modulo / vortex sum / remainder of it. So for example, number the 8, I just went straight to the look at mirror pair of 8. So mirror pair of 8 was 3, and then you could just 3 times 2 is 6. So then 8 has to go to 5. Just want to illustrate that use again, because it wasn't in a direct doubling circuit that we calculated. We just looked at it and know that we could do that. Yeah, so if you look at the pairs right here, 3 doubles to 6. Whoops, yeah, I don't know why this keeps happening. 3 doubles to 6. This is a times 2. And then likewise, for the mirror pair, 8 has to go over here. 8 times 2 is, this has to go there. Like that. And this is, again, the mirror is in the middle. And I'll just write mirror. So everything is exact mirror reflection there. And also note that for the red. So note that 8 times 2, this V equals to, well, 8 times 2 is 16. And I just write mod 11. That's for the modulus. And you can see the difference here. 16 divided by 11, the remainder is going to be 5. This equals to 5. Yeah. I'll just write V equals to, doesn't get confused with 8 times 2. V equals to 5, like that. And it confirms our 5 right there. And this is, yeah, circles that, check mark. Like that, hashtag. It's actually pretty amazing stuff, guys. Hashtag amazing. Amazing patterns. Anyways. Alright, so now let's look at another factor that governs the patterns that arise in Vortex Math. So let's look at synchronization of doubling pattern with size of base. So the reason why the base 10 and base 18 number systems had a simplified one-time mirror reflection, while the base 12 number system had multiple mirror reflections during one cycle, is that the base 10 and base 18 number systems are, quote, synchronized with a doubling pattern starting from the number 1. So this is base 12. Let's go back up here. So notice the base 12 here, it's not synchronized. Well, what I mean by that is that the number 4 here, once you get to the last or the largest part of the doubling circuit, 1, 2, 4, instead of jumping to here where the mirror pair, it jumps to some random number here, 8, as opposed to 8 being here. And I'll illustrate that in a bit. But notice the base 10, it goes 1, 2, 4, and all of a sudden jumps to 8, and it's paired with this 1. So that it just repeats exactly the same on the right side. So it reflects one time. And likewise with the base 18, notice the one-time reflection. Where the 8 goes to 16, where 16 is a pair with 1. And that just mirrors to the right side. So it just goes down and goes up like that. As opposed to the base 12, which went all over the place. Yeah, such as this one here, crosses many times before it gets to the 1. So let's go further. Before this jump right here, this goes to the 10. Once it got to the 5, then it finally has a full mirror reflection, and then, but it already had crossed out many times. So anyways, let's go further. So what I mean by this is that the vortex doubling pattern jumps from the bottom right side of the vortex circle directly to the top left side, which is the quote mirror pair of the starting number 1. Alright, of the right side of the vortex circle. And then directly to the top left side, which is the mirror pair of the starting number 1. And you don't need this comma, just leave that. So in fact, this happens whenever the bottom number of the bottom right, or written better, whenever the bottom right number is part of the doubling pattern. So if you have the doubling pattern, just here 1, or just the overall doubling. So 1, then 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 64 times 2 is 128. So it's 128. So now let's look at the scenarios where this arises, where it's part of it. So this number 1 is part of the base 4 system at the bottom right. So if you have the base 4, here's 3. Let's see how the doubling pattern will occur. So this base 4, this is part of the doubling pattern. So if you double this one, it's gonna go once across the cycle, and then doubling this one is gonna go directly back. This is times 2. So it crosses once, and then the next time it crosses, it's repeating the cycle. So times 2 like that. And that is because, again, this bottom right number is 1 is included here. Now if we look at base 6, the next largest one is when it's 2. So the first one is 1, the next one would be 2, and that is when we have a base 6, where it's just 5 is the modulus, goes 1, 2, so this is the bottom, so this is the bottom right. And then if you double this one, it goes to here, which is the mirror pair is 1 there. So we start from here, we double here, times 2, goes to here. Now this jumps right to there where the mirror pair is the starting point. So in other words, the next time it crosses, it's going to go back to it. So this is the mirror pair of 2, so that this is going to go directly across here, and this is going to jump across. So we've crossed once. Now the next one is 1, 2, and then 4. So that's going to be, base 10, because you have 1, 2, 3, and then 4 here, and it doubles up to the 8. So 4 jumps right to the 8 there. And again, starting from the original doubling from 1, let's just jump right here. This is a mirror pair with 1. So whatever it does here, it does it to the other side. So 1, 2, this is times by 2, jumps to the 4, and then the 4 goes to the 8. 8 follows the same pattern on the right side, so we're going to go all the way to, this is just going to go to 7. And then 7 goes to the 5, and then it crosses once again, directly back to it. Now if you look at base 18, the next number is 8 right there. So in other words, the bottom right number, if it's number 8, if it's synchronized with the doubling pattern, so 8 doubles up to, for the base 18, all the way to 16, which is the top left. So in other words, if we start from here, it goes to here, this times 2, times by 2, so it's synchronized with this doubling pattern. The 4 goes all the way to the bottom here, all the way to here. And then this one goes up top, and this just mirrors that other side. This goes to 15, 15 goes to, let's just write this a bit neater. 15 goes to wherever the 2 went, so which is the 4, so this goes the mirror pair of its 13. And then the 13 goes to the 9, because that's the 4 goes to the 8, that means this has to go to here. And then the 9 has to go to the 1, because the 8 went to the 16. So we've cycled once. And then, yeah, so we cross it again the next time we cycle. So we've only crossed one mirror reflection before cycling back in. And now if we look at a really big one, number base 34, this is the next one here, because notice the numbers get bigger and bigger. So that is, it goes 1, 2, 4, 8, and then 16. Yeah, so if it's 16, that's going to be on the right side. 16 doubles to 32, and then just add the modulus would be 33, so the base would be 34. So we'll go right here, 16 times 2 equals 32. Then we'll have modulus. Mod equals 33, so base equals to 34. Just keep adding to it. So base equals to 34. So this one is if you want to synchronize with the 16. And the next one here, 32, would be using the 66, 64, and then modulus 65, so 66 base 66. This would be here. I was right here. Base 66. So that's base 66 synchronized. The next one, the 64 is going to be, well, 1, 2, 8, etc. This is going to be 1, 2, 130, and so on. So you can just see the pattern. So here, let's look at the base 34. So we have 33 is the modulus, and then we have, yeah, it took me a while to write this down, just write it before making the video. So 1, 2, 3, 4, all the way to 16. 16 doubles all the way to the top, which is a mirror pair of 1. So it doubles to, let's erase this a bit better. 16 doubles all the way across there. And then this is going to be 32, and that's going to mirror pair from the 1. So that means it's going to cross once the next time. So this is right from here to there, and we're going to mirror this. So this is the doubling pattern, doubles to 2, 2 goes to the 4, 4 goes to the 8, 8 goes to the 16, like that. Let's draw this a bit closer. And then this, the left side is going to mirror the right side, so it's going to go 31. 31 is going to cross the 30. Same thing here, cross the 3. And then the 4 goes to the 8. This is a mirror pair. This one has to go to the 25. Like that. And then likewise, the 25 goes to, well, this goes to, 8 goes to 16, so 25 goes to the 17. And this goes right here, like that. And then the 17 goes exactly where the 16 was, the mirror of it. So 16 goes to 32, 17 has to go to the mirror of it, which is 1. So yes, there's a cycle repeats, and then 1. So the next one, yeah, you can see it's going to be, yeah, the next one's going to be base, 66, and so on. So you can see here, the base, if it's number 1, the base is going to be, well, times 2 plus another 2. Yeah, which is base 4, and then this one here, if we get the 8, or actually, no, get the 4, this one times 2 is 8, plus another 2 is base 10. And so on. So yeah, you can see the next one's going to repeat the exact same thing. So wherever the 16 goes, it goes to 32. That's going to be the bottom right number. Yeah, and yeah, it's pretty amazing stuff. And also, I'm just going to write down the pattern. So here, and we'll do a double check soon. So the pattern for this one, we have, well, starts at 1, then 2, then goes to 4, 8. Let's go, this is going to be 8. This is going to be 16, and then goes to 32. So 1, 2, 4, 8, 16, 32, then goes to 31, and goes to 29. Again, this is base 34 in base 10 notation, so that we don't need to deal with letters and so on, and other symbols. 29 goes to 25, then 25 goes to 17, and then this goes back to the 1. So as a double check for base 34, so we have the pattern 1, 2, 4, 8, 16, 32, 31, 29, 25, 17. So we could do our usual 1, then we have 1 times 2 equals 2, 2 times 2 is equal to 4, 4 times 2 is equal to 16, 8 times 2 is 16, 16 times 2 is 32, and then 32 times 2 is going to be greater than our 34, equals to, I'll write V equals for proper terminology. Yeah, so we have this 32 times 2 is 64, mod 33, and equals to 31. You can see mod 33, 31, so which is correct there, 31. The next one has to be 29, so you can see 31 times 2, V equals the vortex sum is 62. 31 times 2 is 62. Mod 33 equals 29. And there's our 29. Then the next one's going to be V equals 58 mod 33 equals 25. You see the built-in calculator, 25. Then 25 times 2, times 2, v equals to 50. 50 mod 33 equals 17. There's 17. Then the next one is 17 times 2. V equals to 34. And here, here I just use the previous ones just because it's rather do that than the other way. So we get the 31. You could do either way. So 31, just use the previous vortex sum. Then 29, multiply that, and you're gonna get 25. And then you use the previous one, 25, and use a 17 times 2 is 34. Mod 33 is 1. And there's the 1, 2, 4, 8, 16, 32, 31, 29, 50, 25, 17 pattern confirmed. So absolutely amazing stuff. Alright, so now the reason that the bottom right number for even base number systems always vortex doubles to the top left. And again, yeah, keep note this for base number systems that we've been dealing with. Always vortex doubles to the top left mirror pair of 1 is because of the following. Or better yet, for synchronized, for even base number systems, for even base synchronized. This is the key point because not all of them have it. Actually, we don't even need to include that. This is the bottom right always goes to the top left. Yes, this is. But if it's synchronized, if this happens to be part of the doubling pattern 1, 2, 4, 8, 16, 32, etc. So yes. But for even base number systems, they always do, and the reason is for the following. Consider, so if you have base equals n and it's even, and let's say the modulus is going to be just base minus 1 equals p, and this is going to be odd because this is even. So then mod divided by 2 can't divide cleanly because the mod is an odd number, hashtag mod is odd. So in other words, p divided by 2 rounds up to p plus 1 divided by 2, and rounds down to p minus 1 divided by 2. And you can see this, for example, i.e., for example, if you had mod 9, this is base 10, this is divided by 2, it goes to 4.5, which rounds up to 5 or 4 rounds, like that. Or you could just view it as 9 plus 1 divided by 2 equals to 5, or 9 minus 1 divided by 2 equals 8 divided by 2 equals 4, like that. Yeah, so the bottom left number, this is going to be equal to the rounding up, and the bottom right is equal to the rounding down. So this bottom left number equals p plus 1 divided by 2, and then bottom right is p minus 1 divided by 2. So we have p minus 1 divided by 2 doubles to, well, p minus 1. This is just a 2, so it always doubles to the top left, which is the top left number and mirror pair of the number 1. And now we can draw this out. So this is the modulus p, and this is for base n. Yeah, I'll just write base n. This equals to p plus 1, and p is just equal to n minus 1. So this is going to be the number 1 here, and then the mirror pair here is going to be p minus 1. This is a pair, and then likewise if you split the mirror down here, so these are pairs like that. Then the bottom right number is going to be, well, here is going to be p minus 1 divided by 2. This one's going to be 2, dot, dot, etc. And likewise, whatever this side's going to be, p minus 2, and goes on, like that. So this is going to be p minus 1 divided by 2. That's bottom right, and bottom left is going to be p plus 1 over 2. Now if you double this one, if you double this, p minus 1 times 2 just becomes p minus 1. Like that. This is just times 2. So yes, you can just see this easily. P minus 1 times 2 times 2. 2's cancel. This equals to p minus 1. Yeah, so thus, to get the simplified one-time mirror reflection, the doubling pattern needs to be, quote, synchronized with the base number system, and the size and which base you're dealing with, so that the bottom right number is part of the doubling pattern numbers. Or just doubling numbers right here. So for example, if you have doubling pattern 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, then the bottom right number, which equals to p minus 1 divided by 2, has to equal to one of these numbers in order to be quote synchronized with it. Yeah, so it's part of the doubling pattern, i.e. equals to a number in the doubling pattern. That should be pretty clear anyways. So it has to equal to 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. So it has to equal one of these numbers. And then the bottom left number, Now this is going to be the top left, not bottom. So the top left number is going to be over here. That's going to be mirror pair of 1, and that's p minus 1. So p minus 1 is going to be, well, just multiply this by 2. Equals to 1 times 2 is right here. So let's go times 2, and so on. Yes, 1 times 2 is 2, 2 times 2 is 4, the other one's 16, then yeah, 4 times 2 is 8, 8 times 2 is 16, and then 32, 64, 256, etc. Then the mod, or the modulus, is going to be p, you just add 1 to it, that's p, equals to, well, just add 1, just plus 1. Plus 1. So you add 1, so we're going to p equals to, well, 2 plus 1 is 3, 4 plus 1 is 5, so 3, 5, 9, 17, 33, 65, 256. And the corresponding synchronized base number systems are base equals n, which equals to just p plus 1, equals to 4, 6, 10, 18, 34, 66, and 258. And yeah, so the ones we went over was 4, 6, 8, 10, 18, 34. Yes, fascinating stuff. Now going further, another factor is we have to take into account is odd base number systems. They can't synchronize with doubling pattern. Yeah, so the above, quote, synchronization of the doubling pattern and the base number systems, yeah, synchronization of the doubling pattern with, with the base number systems were done only for even base number systems. This isn't the case for odd number systems because when the bottom right number of a vortex circle is even, then the top left or mirror pair is odd. Yeah, this means that we can't double an even number on the right side to get an odd on the left side. Because if you look at doubling patterns 1, 2, 4, these are all even numbers besides the first one, and we're excluding the trivial base number, the odd one, if it's just base 1, so it's 1, 1, 1, 1 only. Yeah, so we're just ignoring that one. So these ones are all even, and even when we if you have an odd one at the bottom right. Yeah, we already showed that that is for a even base number. That's this one right here, like that. But if it's just 1, then there is no circle. Anyways, that's for another day. Alright, so let's take a look at what I mean by this. So if we look at base 7, this one is the number 2 at the bottom right is part of the doubling circuits. That's 1, 2. There's the 2. But this is a odd base number. That means the modulus is even. And this one divided by 2 is 3. So this one here, and the number right to the left of it is odd. So if we multiply 2, or double the 2, 2 doubles to here, to 4, instead of this one. So it's not this one. I'll draw an arrow, we'll move this away, times 2, like that. And draw an arrow, or a dash, this one here, like that, and it's not this one. Not that. Just put a big X on it. No. It doesn't go up top to the mirror pair. So instead just goes to here, and then the 4, yeah, the 4, this is a mirror pair of 2, so that this one is just going to go back and forth. Oops. So, yeah, it doesn't cycle back. Whereas this one right here just cycles down right here. Just times by 2. 1, 2, and then it just cycles back and forth. So there's a break in here, it never goes back there. And now if you look at the next one, 2, 4, so this is 4, base 11. Then the 4, the multiplies by 4, it goes to the 8. Oops. This times 2 goes to the 8. It does not go to the 9. So it does not go to the 9. And here if we have 1, 1 goes to 2. The 1 goes to 2. And then 2 goes to 4. And then what we have is the 8 goes to the 6. Like that, and then this is a mirror pair of 4, so this is going to go to the 2. And now we have a cycle, but it cuts off the 1. So in fact, these ones we have a cycle. This is always the case. Yeah, and we could see this with the next base up, which is going to be base 19. So just added this one here just for clarity. And then then I'll go over general one, next one. So if we go, so 1, 2, 4, 8. So the pattern is 1, 2, 4, 8, 16. So the next one is going to be 8. So the 8 is going to be at the bottom right, and this is going to be 4. Move this. Like that. So base 19, that's odd, and then minus 1 is going to be 18. That's even, and then 18 divided by 2 is 9. So we have a 9 over there, and then it goes 1, 2, 3, 4 all the way to the 8. And then it goes 10, 11, 12, 13, 14, etc. all the way to the 17. And the bottom right number is 8. 8 doubles to, well, 16. It doesn't go up to the top right because it's an even number, and you can't get an odd number by doubling. So it goes like that, and it goes to the 16, and the 16 is mirror pair with 2. So again, the 1 times 2, like that. Start get the, and notice the, once again, the 1 cuts off from the doubling pattern. 1 times 2 is 2. 2 goes to 4. 4 goes to 8. And 16 has to follow to the other side, so this 4 goes to the, 16 goes to the 14. And then again, there's a 1 cut off. The 14 goes into all the way to the mirror pair of wherever the 4 went. 4 went to 8, so the mirror pair is 10. 14 goes to the 10. Like that. And then 10 just goes wherever the 8 goes, 16, so this goes to 2, the mirror pair of it. Let's fix this up. Yeah, so let's just draw this up again. Yeah, so this goes back to it like that. And again, the 1 is cut off. So it just goes back to the 2 goes to 4, 8, and this is cut off. So this is cut off. Or 1 is cut off. It's always cut off. Here's 1's cut off from the pattern. 1 is cut off. And again, 2 does not go to the top left. It goes to the wherever the 4. Yeah, which is 1 minus, it's 1 less than the top left. Alright, so now let's go further. And yeah, so again, this because it's even and this one's odd, the bottom right is even, top left is odd, you can't get there ever. You only go 1 less than this one, so 5 minus 1 is 4, etc. So here, 9 minus 1 is 8, this one is 7 minus 1 is 16, so it always goes 1 less than it. And so on. So now let's look at in general. So if we have base n equals p plus 1 is odd, then what we'll have is we'll have the top, the modulus is going to be even. So the modulus is even. That means here if we draw this all the way down to the bottom, so even, you could divide this cleanly. So this is going to be p divided by 2. And then the number to the top left is going to be, well, p minus 1. Like that. And then this is just 1 here, the mirror pair of it. Mirror pair of 1 is just that. And here, smooth things around, make it a bit more spaced. So there's the 1, the mirror pair of it is over here, like that. And this to the right of this number here is p divided by 2, and then minus 1. P divided by 2 minus 1. To the left of it would just be over here, p over 2 minus, plus 1, like that. And then, so the number next to it after this one is going to be 2, and then the mirror pair of it is going to be like that, ... Mirror pair is just p minus 2, like that. And now if we double this one is going to be doubling 2. Well, let's just calculate this out. So this is going to be times 2. And that's going to equal 2. Well, the 2 will just cancel. Well, here's moving this over here. Let's see if we get this all done. So times by 2 on everything there. So p divided by 2 times 2 is going to be p. And then negative 1 right there times 2 is just 2. Yeah, so we just have p minus 2. So in other words, this goes to p minus 2, which is right here, which is a mirror pair of 2. So the 1 is always cut off. Yeah, so it goes over to there, and again we have 3, 4, etc. The next one, p minus 3, p minus 4, all the way to here, where they coincide with this formula. So let's put a times 2 like this. Yeah, so times 2. And the mirror pair of this one, p divided by 2 minus 1, is over here. So that's a mirror pair, and then so what we're going to have is, I'm just going to draw this in green actually. So this part here is the mirror pair. This has to multiply all the way to exactly this. In other words, we have, if you have times by 2, let's multiply it by this as well. So times by 2 here, 2 times 2, or put it somewhere else, times 2, this equals to, just multiply this inside, p over 2 plus 1 is multiply the 2, so p over 2 times 2 is going to be p, 1 times 2 is just 2, equals to p plus 2, and this is v equals to 2, the remainder. This is a factor of p. V equals to 2. It goes all the way up to here. So yes, fascinating stuff. And then this one right here, I'm just going to circle this in blue and say this is cut off. It's cut off from the doubling pattern. So yes, this is fascinating stuff right here. So let's keep going further. So again, note that cycle that is it's a perfect mirror reflection outside of the 1, or almost perfect if you, yeah, just because it cuts off the 1. So nonetheless, notice how the doubling pattern almost has a perfect mirror reflection except for the starting number 1, which gets lost in the pattern. So we start from 1 and it just disappears. Or let's just draw this red for this. Draw this red. So this doubles to here times 2, and then all of a sudden this goes to this is 3. That'll be 4. We'll just keep doubling. Yeah, let's erase that again. Let's start that again. So this 2 goes to the 4. This will be a 3 there somewhere. So just leave it like that. It goes to a 4, and then the mirror pair of it is going to be, well, across here. This is p minus 4. And then the next one is going to go to an 8 somewhere, assuming it's not 8 or whatnot, goes to an 8. And the next one, let's just say, goes to that 16 or whatever, just to generalize it. It's going to be p minus 8 over there. Yeah, so this doubling pattern goes to there, goes to here, just goes to the mirror pair. Then this goes to here, this goes to, etc., wherever this is, and it goes all the way back up there. But again, this 1 is cut off. Again, it's cut off from all of these too. So the 1 gets cut off, 1 gets cut off, 1 is cut off, and so on. And now let's just double check the base 19. Doubling pattern is the big one, and I'll just show that it's, again, you could do this. I can do this in my sleep now. So we have 1. Yeah, so note the pattern here is going to be 1. It's going to be from 1, 2, 4, 8, 16, 14, 10, and then 2. Then it starts repeating. So 1, 2, 4, 8, 16, 14, 10, 2. So yeah, then it starts repeating and the 1 is cut off. So we start off from 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is, well, 32. That's bigger than our base, base 19 or 8. That's bigger than, modulus 18. So bigger than modulus 18. So we just use v equals 32 mod 18 equals to 14. Again, you could just calculate, auto calculates. So and then you just multiply this now. Instead of doing the 16, you just multiply the 14 and 1 after. 14 times 2 is 28. V equals 28 mod 18 is 10. And then 10 times 2, just take the next one. So v equals to 20. 20 mod 18 is 2. You can see the difference. 20 divided by 18 is remainder 2. And then, yeah, so we have the pattern confirmed. 1, 2, 4, 8, 16. 16, and then 14, 10, 2. So 1, 2, 4, 8, 16, 14, 10, and then the 2 just repeats. It's going to be 4, 8, etc. Confirms the vortex circle pattern. Yeah, so note that the cycle, repeats at the number 2, again, while cutting off the starting number 1. This is as expected since the doubling across, or since doubling across the mirror axis, or mirror reflection, lands on the mirror pair of the number 2. For example, here, if you jump across to here, so this one you double it, it goes to p minus 2, which is the mirror pair of 2. All these 8 doubles to 16, which is the mirror pair of 2. 4 doubles to 8, which is the mirror pair of 2. 2 doubles to 4, which is the mirror pair of itself, which is 2. So yes. And so this is pretty amazing stuff, so that deserves a hashtag amazing stuff. So another factor that we're going to look at is the starting point of pattern. So another factor that governs the vortex patterns is at which point we start the doubling or other multiplication pattern. Yeah, so the base 10 number system has 3 doubling patterns. That's 1, 2, 4, 8, 7, 5, or 3, 6, 3, 6, or 9, 9, 9. And they all depend on which is the starting point of our doubling pattern. So the main one is, let's draw this in red, is starting from 1. So if we start from 1, we're going to get 1 to 2, 2 goes to 4, and then 4 synchronizes above to 8, mirror pair of that one. It's going to go exactly this, just mirror pair that. And then 7 goes to the 5, like that, and the 5 goes to the 1, like this. Oops. Let's try that again one more time. Okay, there it is, yes. So it goes to there, that's starting from 1. And then if we start from the 3, so if you start from 2, it just goes back into the same cycle. So if we start from 3, it's not part of that cycle, it goes across. Let's try that one more time. I don't know why it keeps doing that. So it goes to the 6 right there, and then the 6 is the mirror pair of it, so it just goes back and forth, like that. Now let's put a times 2 like that, so we're all doubling. We're all times 2, and then the last one is if it's just at the 9, well, it's just a modulus, so it just keeps at itself, so that's it. Doubling and multiplying the modulus is itself. Yeah, so thus what we have is, well, the usual 1, 2, 4, 8, 7, 5 pattern is because a doubling sequence is, quote, synchronized with the base, so you have numbers all on the right side, then it flips to numbers all the way to the left, and then it cycles back in one direct reflection before the cycle repeats. So in the 3636 pattern is because the number 3 doubles to its mirror pair, which is 6, and the number 9 always vortex doubles to itself because it is the modulus by which the base number system is governed. Yeah, so thus every modulus of every base number system vortex doubles to itself. We can also see this by viewing the doubling of p as adding one full cycle to the modular p clock, thus returning to itself. So for example, if you have here p, so there's a base n equals p plus 1, so there's modulus p, then you have, let's say, 1 here. I'll just move it out of the way so that that's p, that's 1, this can be p minus 1, and so on, this can be 2, and then this left side is going to be p minus 2, and so on. So if you cycle this across, let's just draw this in red. So if you add p to it, we're going to go all the way around, and then back to the p. So p goes 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way into, well, plus p, goes one cycle, or plus p. It goes one cycle, and it goes back to itself. So the modular clock is always the same. Or I'll just say of mod p clock. And just for completeness, you can also write this as over here, let's just double this, times 2 is going to equal to, if you multiply it, we get, well, 2p, which equals to, you get this equals to just p plus p. And what we could do is, the interesting thing we could do is, well, we can add 1, so we could go p plus 1, and then we'll subtract on the other side p minus 1, just illustrate some cool stuff. So this p plus 1, depending on whatever the base number system is, this is just 10. So in other words, this equals to 10, and then plus this p minus 1, like that. So now if we take the vortex sum, this is this p minus 1 is going to be, it's going to be included in the digits. So the number is going to be equal to, it's going to look like something like this, 1 digit, and it's going to be p minus 1, like that. These are digits. Yeah, I don't know why I'm doing this exercise, but it's pretty interesting. So this is p minus 1 digits, or then you could take the vortex sum of it. So you can just do v equals, so you add the digits of 1 plus p minus 1. This equals to, well, the 1's cancel. Equals to p. And there is our vortex sum. Alright, and now when viewing a bigger base number system, or a bigger base system such as base 16, we can derive several more vortex patterns depending on the starting position. Remember, the base 10 skips to 3. You only have the 1, 2. It only has the 1 or the 3 starting positions, because if you start at 2, it's the same thing as starting 1, it's the same cycle. But the only unique ones are from the 1, 2, 4, 5, 8, 7, or 1, 2, 4, 8, 7, 5. That's 1. Then you have the 3, 6 is 2, and then third one is 9. So if we start off with a bigger base number system, we will have the following patterns. So such as the base 16, and we'll start at different points. So let's start off at 1, and I'm going to write down patterns here. Write this in black because we're going to have several different ones. So patterns, write this. Yeah, so I just wrote patterns there. So let's start from the 1. So 1 doubles to 2. So, so the modulus of base 16 modulus 15, and it goes like this. Yeah, so 7 is there, and that is the 15 minus 1 divided by 2. So 14 divided by 2 is 7, and then 15 plus 1 is 16 divided by 2 is 8. And then it just goes all around like that, 15 numbers. So 1 doubles to 2. So let's write our pattern, 1, 2, and then 2 goes to the 4. Alright, 2, 4, and then 4 goes to the 8. 4, let's cut it across like this, so it cuts through the mirror like that, so 8. 8 goes to, the 8 goes to, well, we can just look at the mirror. The 7 will go to the 14. 7 goes to 14, so that means that the 8 has to go to the 1. So this is the mirror pair of it. I'm just going to look at this like that. So it's a mirror pair. So we're just going to go straight where this one goes to the 14. So this one goes straight to the 7. I mean, straight to the 1. So 7 goes to 14, so 8 has to go into the 1. So this is the cycle. So that's one pattern. Yeah, now if we draw in green, we could just look at the mirror pair of this. So this is mirror pair, it cuts off short. So this is going to be a 14 starting from here. So we're going to have a 14. 14 goes, mirror pair is 1, so it goes to the 13. Where 1 goes to 2, and then this is going to go to the 4, which is 11. 11 like that. Yeah, so these are pairs. And then the next one is 11 goes to, well, the pair of 4 goes to the 8, so then 11 has to go to the 7. So this has to go straight to the 7. And then 7 goes to the 14, so that the cycle repeats. Like that. Alright, so now let's start a new number. Number right here is a 3, so let's start at the 3. 3 doubles to 6, so we can write it like this. I'm just going to cross it like that, cross it all the way to 6. So 3 goes to the 6. And now, yeah, these are all times 2. I'm just going to write these all as times 2. So these are just times 2. Everything's times 2. And then the green one, this is also times 2. And times 2 like that. I'll put this in green. Yeah, just added that in green. And this one's going to be times 2 in blue. And then the 6 times doubles all the way to 6. I mean, the 6 doubles to 12. Let's write this like that. I don't know. Why does it keep doing it? So here, just fix that up. Just pause the video and fix it. I don't know why it wasn't working. So again, so the 6 goes to the 12. Notice the 12 is a mirror pair of 3. So now this 12 has to go where the 3 went, which is a 6. This goes to the 9. Again, this is 12. So this goes to the 9. And then the 9 is mirror pair of 6. 6 goes to the 12, so 9 has to go to the 3. So now we have an actual cycle. Yeah, just pause, add it there. So we actually have a cycle that is symmetric about this 15. So this is going to go back to, this is 9, and then it cycles back. And now the next pattern, let's just look at the 5. So the next one is not filled as the 5. 5 times 2 is 10, and it's its own mirror pair. So this goes to 10. Yeah, let's go slowly before the computer messes up. So this is the own mirror pair, so that means it goes back to itself. So in other words, we're having a 5, 10, like that, and it just repeats back and forth. 5, 10, and then the last one, let's just draw this in black, is the trivial one is just 15, just by itself. 15 by itself, which is the modulus. Yes, and now we can double check these patterns, and also here I forgot to made a mistake here. This is not 2, this should be 14 and 13, yes. So the mirror pair of 2 is the 13 over there, so 14, 13, 11, and then it goes to 7, and it goes back down over there. So let's just double check the pattern. So the first one, 1, 2, 4, 8, double check the patterns, 1, 2, 4, 8, so we have 1 times 1, then 1 times 2 is 2, 2 times 2 is 4, 2 times, 2 times 4, let's rewrite that. Yeah, rewrite that. 4 times 2 is 8, and 8 times 2 is, 16. V equals 16 mod 15, because it's mod 15, equals to 1. Like that. So there's the pattern. It's confirmed. 1, 2, 4, 8, and then 1. So 1, 2, 4, 8 pattern is confirmed. The next one is a mirror pair, 14, 13, 11, 7. So 14, so we have 14. 14 times 2 is V equals to 28 mod 15, equals to 13. So yes, you could just calculate this. First equal. Yeah, just erase it, equals 13, like that. And then, going further, so then 13, just multiply the vortex sum of it. So 13 times 2 is 26, but V equals the vortex sum 26 mod 15, which is 11. And then 11 times 2, the vortex sum of it, you could also multiply 26 by 2, but anyways, you could always just do this. So 11 times 2 is V equals to 22 mod 15, and it's 7. The difference is 22 minus 15 is 7. Which is the remainder, equals 7, and 7 times 2 is 14. So we have the pattern 14, 13, 11, 7, and then, 14, 13, 11, 7, and it goes back to 14. So 14, 13, 11, 7 pattern confirmed. Next one is 3, 6, let's scroll up here. So the next one's 3, 6, 12. So it goes to, starts from 3, goes to 6, goes to 12, goes to 9, and goes back to 3. So we have, and also before we get to just completeness, put this in gray for the times 2 for the 5. Like that, 5 goes to 10, 10 goes to 5, and so on. Alright, let's go further. So yeah, the 3, 6, 12, 9 pattern, so it's 3, and then 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, that's greater than the mod 15, so V equals 24 mod 15, and using base 10 calculator, but it gets the right answer for base 16, as I explained earlier. This equals to 9, and you could calculate this, equals to 9, and it should be popping up. Yeah, I don't know why it's doing this, let's do it again. Equals to 9, yeah, so 15 equals to 9, and then 9 times 2, multiply the double the vortex sum, so 9 times 2 is 18, V equals 18 mod 15, that's going to be 3. So we have our pattern starts back at the cycle. So 3, 6, 12, 9, 3, and then this pattern is confirmed, or you could just remove this 3, because it's That's the pattern. So like that. Yeah, because it goes back to the 3 to start the cycle. And then the next one is the 5, 10. So you look at the 5, 10 in gray. So 5 times 10, 5 times 2 is 10, which is a mirror pair. So it has to be itself. So 5, 10. And then after that, it's 15. That's just trivial. So let's go to the 5, 10. So 5 times 2 is 10. And then, yeah, so 10 times 2 is, well, 20. V equals to 20. Mod 15, that's going to be 5. So 5, 10 pattern confirmed. And the modulus one, that's trivial. Just keep that. Yeah, just keep that for yourself. I already showed that the modulus, whatever you multiply it by, is always going to be the modulus. So yes, pretty amazing patterns there. And now let's look at another factor that governs the patterns, and that is the multiplying factor or multiplication factor. So far, we have only looked at doubling or multiplying by a factor, or a multiplying factor of 2. If we use other multiplying factors, we expectedly get different vortex patterns. So consider the patterns of multiplying by 3 for the base 10 system. So I'll write this as, so let's draw this in black, base 10, like that. Here, just fix that line up. So anyway, now if we multiply by 3, and we'll start off from 1, and we'll change the starting position as we go along. So let's just write patterns here first. We're going to have multiple patterns. I'm going to write patterns. These are base 10, like that. Alright, so if we start from the 1, and then we multiply by 3, so we're going to go, well, 3 goes to, 1 times 3 goes to there. 1 times 3 is just 3. And now the next one, well, if we multiply by 3, yes, pattern's going to be 1, then 3. Then 3 multiplied by 3 goes to the 9. And now the 9 always going to be, whatever we multiplied by, it's going to be itself. So we're going to have a 1, 3, 9, 9 pattern. Yeah, 1, 3, 9, 9, 9, etc. Dot, dot, dot. So it cuts off. So it just gets funneled into the top, and that's it. And then it has a mirror, so you can mirror it if you start from the 8. So if you mirror to the other side, this is going to be the mirror. So then the 8's going to do the same thing. So we're going to go from 8. 8's going to go to the mirror of, 8 times 3 is going to go to wherever the 1 times 3 was. 1 times 3 goes to the 6. So 8 times 3 goes to the 6, like that. Times by 3. And yeah, so this is going to be 6. And then this one has to go funnel to the top. So it's going to go funnel exactly as its mirror 3. So this is going to be 9, put 9, 9, 9, signaling that we are going, funneling back to the 9s. And now let's start from the 2. So we have start from here from the 2. 2 times 3, that is going to be, well, 6. So we know 6. Oops. So yes, I don't know why it keeps doing this. So it goes to the 6. This is going to be times it by 3. And then if it goes to the 6 we already know goes to the 9. So this goes straight up to the 9. So this is going to be 2, 6, 9, 9, 9, dot, dot, dot. Fix this up a bit. And then likewise, a mirror pair of 2 is going to be the 7. It's going to do the same thing but on the reflection. So it's going to be 7 like that. Starting from here, right in gray. 7's going to go where, so the 2 and the 6, so then the 7 has to go to the mirror pair of 6, which is 3. Let's draw this better, like that. This is going to be our multiplied by 3. So 7's going to go to 3, and then 3 goes to the 9. So yes, it just cycles like that to the top. It's going to be 9, and then the 9 just always goes to itself. Dot, dot, dot. And now the next ones are these 4 and 5s. There's a mirror pair, so we're going to have pairs as well. So let's draw this in black. So 4, like that, is going to, 4 is going to go to, well, we know that 4 times 3 equals to 12. It's all base 10, so we just automatically sum it up like that. And then vortex sum is 1 plus 2 equals to 3. So in other words, 4 goes to the 3. So 4 goes to the 3, and then the 3, well, is just going to funnel straight up to the top, like that, to the 9. So it's going to go 9. Every single one of these is funneling to the top. Dot, dot, dot. And this is what we expect, because the 3 is a factor of 9, so you're multiplying by 3, so you should eventually get up there. And likewise for the 5 is a mirror pair. This is a mirror pair. Dot, 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 dot. This is going to go to the 6. And 6 is going to, then this is going to go all the way to the top, like that. So yeah, let's just write this down. It's going to be 5 goes to the 6, goes to the 9, goes to the 9, goes to the 9, dot, 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 put another dot. And the trivial one is just a 9 by itself. So 9, dot, dot, dot. Yeah, 9, 9, 9. Let's leave the 9 by itself, so it's just by itself. So the modulus always itself. So yeah, so this is some pretty fascinating stuff here. But yeah, it always funnels into it. Because again, it's a 3 is a factor of 9. It's 3 times 3 is 9. And we expect that, and I'll get to that in a bit. So let's double check just one of the vortex doubling patterns and its mirror reflection. So let's look at 1, 3, 9, 9, 9, 9. It's over here, and its mirror one is going to be, well, 8, 6, 9, 9, 9. So so we have 1, then 1 times 3 is 3, 3 times 3 is 9, and 3 times 9 is 27, v equals, this is base 10, so we just multiply directly like that, v equals 2 plus 7 is 9. And it just keeps going on and on, so 1, 3, 9, 9, 9 pattern confirmed. Next one is 8, 6, 9, 9, 9, so 8, mirror pair of 1. So we have 8 times 3, v equals 24, mod 9, just different ways of calculating it, the same thing. So it's going to be, or 2 plus 4 is 6. So we calculate right here, space, just delete this, and then just press space and automatically calculates. So you could use different ways, and then we're going to multiply the vortex sum. 6 times 3, or 6 times 3 is going to be 18, v equals 1 plus 8 equals 9. So yes, it's always going to be 9, and if it's a modulus, it's always going to be itself. So 8, 6, 9, 9, 9 pattern confirmed, and so on. Note that all the tripling patterns of the base 10 system quote funnel towards the 9. So we have 1, 3, 9, 9, 9, then we have 8, 6, 9, 9, 9, 2. Then we have a 2, 6, 9, 9, 9, and then which is in its mirror pair 7, 3, 9, 9, 9. Then we have a 4, 3, 9, 9, 9, and 5, 6, 9, 9, 9. Also notice this one here. Let's just double check we got them right. So yeah, here. So there's a 1 mirror pair is 8, 2 mirror pair 7, 4 is mirror pair of 5. And notice that everything's a mirror pair. 6 is a mirror pair of 3, 3 is a mirror pair of 6, and 4 is a mirror pair of 9, of 5, 9 is a mirror pair of itself. 1 mirror pair of 8, 3 mirror pair of 6. So everything is mirrors. Yeah, so I'll write that here. So note the mirror pairs in each of the single digits. So 1 and 2, 3 and 6. 9 is itself, so 9, 9, 9. And then a 2 and a 7, 6 and a 3, and then a 9, 9, 9. Then 4 and a 5. 3 and a 6, and then 9, 9, 9. So amazing. So this is actually part of the polar number pairs series, or section, which I'll cover later in this video, which is again all fascinating stuff. And again, the quote funneling is mainly because a multiplying factor of 3 is a factor of the modulus 9. So 3 times 3 equals to well, just 3 squared equals to 9. So the odds of funneling are pretty high because you're eventually going to get a factor of 9, or just a multiple that gets straight to the 9. Yeah, so let's try instead the base 12 system, and let's start this one here. So you have this as modulus 11. Let's write this in the middle. Yeah, so we write that in the middle. Yeah, just move this here. So we'll start from here. So 1 triples to 3. So we have 1 and then 3. 3 triples to 9. Like that. And then 9 is mirror pair of 2. So then this is a mirror pair of 2. 2 would double or triple to 6. That means 9 has to triple to 5. Like that. Yeah, so this would go straight across there. So that should be a 5. And now here, mirror pairs isn't going to help because the 5 times 3 or 6 times 3 is going to be greater than the modulus 11. So what we could do is just multiply this by 3. Like that. This is going to equal to v equals to 15 mod 11 in base 10 notation. So 11, this is going to be differences, well, 4 is a remainder. 15 divided by 11 has a remainder 4. And so this is going to go straight to the 4, like that. Like that. And then 4 times 3, well, we know this is going to be 3. This is going to equal to, let's write it normally, I'll move the other one up. This is going to equal to, well, v equals the vortex sum. Equals to 12 mod 11, and that's going to be 1. Yeah, the difference is 1. So this goes straight up top to the 1. Oh, how should I draw this? I'll just draw it like that. Or better yet, just curve it in. Like that. And this is going to be, again, times by 3. Here, just move everything around, and then this is going to be 4. Yeah, it just goes to 1, actually. Yeah, so we can just leave it actually like that. Make it a bit closer in. or a bit further out. Okay, so now the next one is this, look at the mirror pair of this, mirror pair of 1 is just 10, so everything's going to be the same thing. Let's write this in green. Here, just fix that color scheme again. So this is going to be 10. The next one's going to go wherever the 1 went to 3, so this is going to go to 8, like that. And then 8's going to go to, where's this one go? 3 went to 9, so 8 has to go to 2. Like that. It's going to be 2, and then the 2 has to go to wherever the 9 went to 5. So that means this has to go all the way to 6. And then the 6 has to go wherever the 5 went to 4. So this has to go to the 7, so the opposite of that. Draw this a bit further out. Just fix this up. So this goes all the way there, and then this is going to be 6 goes to the 7, and the 7 it goes wherever the 4 went to 1, so 7 has to go to 10. So this has to go to 10, and we've covered all the numbers except the modulus. So yeah, that goes back, and then obviously the other the trivial one is just the 11. And yeah, like always, you can double check these patterns. So let's double check the patterns here. So we have the 1, 3, 9, 5, 4. And mirror 10, 8, 2, 6, 7, and then there's that 11 always. So we could have, so 1, and you multiply 1 times 3 is 3, 3 times 3 is 9, and 3 times 3 is, 9 times 3 is 27 in base 10, but it's base 12, so again you go V equals 27 mod 11, this equals to 5. And then we'll have the 5 times 3, just take this one and multiply that, it's going to be 15, so the vortex sum of it is multiplied instead of the 27. Anyways, V equals to 15 mod 11, that's 4, you see the difference is 4. And then 4 times 3, V equals to 12 mod 11, that equals to 1. And there's the cycle repeats. So 1, 3, 9, 5, 4, and then let's look at the 10 one. So we have 10, 8, 2, 6, 7, 10, 8, 2, 6, 7, and you can see 10 times 3 is V equals to 30 mod 11, which is equal to 8. Just calculate this, automatically calculates 8. 8 times 3, V equals to 24 mod 11, that's 2. And then 2 times 3, just always multiply the vortex sum, just because it's a smaller number. 2 times 3 is 6, and then 6 times 3 is V equals 18 mod 11, which is 7. And then 7 times 3, V equals to 21 mod 11, that's 10. So the cycle repeats back to the 10. The vortex of 10 is going to be this one right here. So we'll have 10, 8, 2, 6, 7. Yeah, so 10, 8, 2, 6, 7. So 1, 3, 9, 5, 4, and mirror 10, 8, 2, 6, 7 patterns confirmed. Now let's try multiplying a factor of 4 and for the base 16 system. This one has interesting results. I didn't realize until actually making this video. So let's look at the, let's start from the 1. So we got the 1. So let's start from here. So we're going to times it by 4. 1 times 4 is going to be, well, 4. This is going to be times 4. So we have 1 and then 4. And then now if you multiply 4 by 4, that's going to be, well, this equals to, V equals to 16 mod 15. So 16, let's put this, here, put this as times. V equals 16 mod 15, and this equals to, well, just 1. That's the difference. So 15 goes in once, and there's a remainder 1. So in other words, this goes straight back to it. So there's a pattern. It's just 1, 4. So this cycles back, and it keeps going on and on. Now let's look at the other patterns. So start from number 2. 2 times 4 is 8, so it goes like this. This is going to be our times 4. So we have 2 goes to 8. And let's solve this one. So we have 2, this one's going to be multiplied by 4. This equals to, well, V equals to, if 4 times 8 is 32. And then this equals to, well, 32 mod 15. This equals to, well, if you look at this, 32 mod 15, 15 goes in 32 twice, and there's going to be remainder 2. 15 times 2 is 30, is remainder 2, so this should be just 2. So this actually just ends up going backwards then. So this goes back. Like that. Yeah, so just put it like that. So we have the pattern 2, 8. So that's it. So now let's look at the pattern from 3. So 3 times 4. Yeah, 3 times 4 is going to be this right here. Yeah, this is going to be 12. So this is times 4. So we have 3 and 12. Yeah, and also notice that we're multiplying by 4, where 4, note, 4 squared equals to 16, which is the base. So this is why we expect, this is why it's not surprising we're getting these very interesting patterns where they just cut off right away. So that might be a reason why 4 squared is just 16, which is the base 16. So let's look at this. So this goes 3 times 12, and then here if we multiply this by 4, well actually we don't even need to multiply by 4. We already know that this is the mirror pair. So this has to go straight back to it. So yes, I just go straight back. So that's just 312. Now the next one is going to be very interesting here. I'm going to draw this in gray. So number 5. So if we draw this number 5 like that, 5 times 4, this v equals to, well, that's just 20 mod 15. And then 15 goes into 21, so there's a remainder of 5, so the difference is 5. This just equals to 5, so it's equal to itself. So that's just it, it's just 5. So in other words, it's just going to be 5, 5, 5. It's like the modulus, similar to the modulus right there. This is also 15. And then now let's look at the number 6. So 6, see what this would be. 6 times 4 is going to be, well, v equals to 24. 24 mod 15. This is going to be, the difference here is 9. So that's just going to be 9. So 15 goes into it once, and there's a remainder 9. So it goes all the way to, so this 6 goes to right here, which is a mirror pair. So just go straight back to itself. This is times 4. Yeah, so this is just going to be 6 and 9. Like that. And then last one, 7 here, that's just a mirror pair of 2, so it just goes straight over there. Yeah, so let's just write that anyway. So 7 has to go, because 7 is a mirror pair of 8, so it has to go wherever this 8 goes, which is 2, so 7 goes to the 13. Like that. I'll just put this in maybe, I'll do this also in gray. So here's, or just a green pencil mark like that. So this is going to be up like that, and this goes to the 13, and it's going to go back to it as well, exactly like this 8. It's going to be 7 and then 13. Yes, and going further, so we have the 15 right there. I'm also going to write, so the 15 modulus repeats itself. I'm going to put this here, 15. But also notice that the mirror pair of 5 is 10, so this also has to repeat itself, like that. So I'll just go 10. I'll just put a mirror 10. I'll just put a 10 like that. And then plus the rest of the mirror pairs. Let's write. Then this one right here plus mirror pairs. Mirror pairs, etc. Yes, I'm not going to solve those. Those are pretty straightforward. For example, if the 1 goes to the 4, the 14 would have to go to the 11, and so on. Or we could just write that down actually, because it's just one more. Actually, everything else is circled already. So this would just go here, would go to the 11, and then it goes back down to it. So let's put an arrow back. It's times by 4, like that. So we have 14 goes to 11, and then put this right here, 14 and 11, like that. Yeah, and here, I'm not going to double check everything else, but what I'm going to do is just look at the ones that repeat itself. So note that the number 5 and its mirror pair 10 repeat just like the modulus 15. So if you take 5 times 4, v equals to 20 mod 15 is 5. And likewise, 10 times 4, v equals to 40 mod 15. This is just equals to 10, you can see. So it's always going to be equal to 10. And then likewise, 15, the modulus times 4, v equals 60 mod 15, which is equal to 0. But then you set that equal to the modulus in Vortex Math, so v equals 15. So lastly, since Vortex Math is mainly done with the base 10 system, let's see the patterns that arise from multiplying by different factors. So here's base 10 with a multiplying factor of 4. Yeah, so let's start off from the 1. So we have 1, and then 1 times 4 is just 4. So it goes to 4. Then 4 times 4 is, well, this is going to be times 4. This equals to 16. Remember, it's base 10, so we don't need to do the mod. We can just sum up the digits. This is just automatically 16. This is all already in base 10 notation. 16v equals to 1 plus 6 equals to 7. So this goes to the 7, like that. And then the 7, oh, the 7's going to go to wherever the 2 goes. So let's just draw the 2 instead. I'm going to go with the 2. This is the mirror pair of it. So there's a mirror pair of 2, and yeah, so instead of timesing 7 by 4, we just times 2 by 4. 2 by 4 is going to go right to the 8. Times it by 4. So we have a 2, 8. And then this, so that means the 7 is going to go, well, wherever the 2 went, the mirror pair of it. Mirror pair of 8 is 1, so it goes like this. So it goes to the 1. And this is going to be, I'll just put this times by 4. So this goes, back to the 1, so 1, 4, 7. So that means this 8 goes to wherever the 1 went, and 1 goes to the 4, so that means 8 has to go to the 5. I got the mirror pair of it. And then that means that the 5 has to go to the mirror pair of where the 4 went to 7. 4 goes to 7, that means 5 has to go to 2. Yeah, so 5 has to go to the 2. Whoops. Let's try that again. Yeah, so 5 goes to the 2 like that. And then, yeah, 2, 5, 2, 8, 5. And it just repeats non-stop. But since there's a mirror pair there, we can just put it like this instead. I'll just put the 8. 8, yeah, so from here, 8, 5, 2. So the mirror pairs line up. So 1 lines up with 8, 4 lines up with 5, 7 lines up with 2. And then lastly, if you look at this 3 right here, 3 times 4, this is going to equal to 12. And this is v equals to 1 plus 2 equals to 3. So in other words, 3 is just by itself. So yeah, so just 3 repeats non-stop. So that means 6 has to repeat non-stop. And then likewise, 9 also repeats non-stop. Because number 3 is a mirror pair of 6. So 3, 6, 9 just repeat. So that's very fascinating stuff. It's just, yeah, it's fascinating stuff here. And I'm not going to be double checking these just because I'm pretty, well, gotten pretty good at this and I'm pretty sure these are right. If I make any mistakes, let me know. But anyways, expanding to more multiplying factors or multiplication factors, yeah, however you want to state it. Yeah, we can see that there is a repeating cycle of the vortex patterns themselves. So the table below shows the resulting vortex sum pattern starting from number 1 and with multiplying factors 1 to 30. So here's this is the same Excel sheets from the worksheet multiplying factors. So here are the numbers. You have 1 to 30, the multiplying factors. And then we have, this is to count how many numbers there are. Now we start from the number 1. Now the number 1 times 1 times 1 times 1 is always going to be just 1. And then we have our doubling right here. So this is going to be our doubling. 2, yeah, so we have 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. V equals 7. And then, yeah, so you just have our usual 1, 2, 4, 8, 7, 5, 1 doubling pattern. And then we have this, then we go for the third one. So 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is always goes to 9. Then the next one is 4, the one we just calculated. So 4, we have 1 times 4 is 4. 4 times 4 is 7. And then 4 times 7 goes to v equals to 1. And just keeps going on and on. 1, 4, 7, 1, 4, 7. Then for the 5, we have 1, 5, 7, 8. 4, 2, 1, 5, 7, 8. And for the 6, we have 1, 6, 9, 9, 9. And we've already calculated that part here. Actually, no, never mind. We didn't calculate that. You can see that right here. If 1 times 6 is 6. 6 times 6 is going to be 36, which is 9. V equals 9. And, yeah, so we can keep going. So 1, 6, 9, 9, 9. And the 7, yeah, so this is going to be 1 times 7 is 7. 7 times 7 is going to be v equals to 4. Yeah, so 174, 174, 174, etc. Then for the 8, we get 1, 8, 1, 8, 1, 8, 1, 8. And then the 9, everything's just going to be 9. 1 times 9 is 9. So 9, 9, 9, 9, 9. And then it repeats back to the 1. So we have it repeating right here at the 10th increment. So it repeats. Like that. Yeah, so it just repeats from there. And then we get our usual pattern. So it's exactly the same. And it repeats all the way until the next part right here. So this is 9 numbers right here. So it repeats. Let's put this again. It repeats and then it repeats again at this part right here. So in other words, we're going to have from 1 all the way, so we have 1, 0, and then all the way to 1, 18, so that's going to be 9 as well, so including this. So I have 1, 2, all the way to 8, plus a 0, so it's 9 increments. So every 9 repeats, and then goes to 19, is going to be, so the next one, then it repeats at the factor of 9 right here. So this one, so it repeats there. So there's the 1, there's 28, so there's 27. Just repeats again and again. And here's zoomed in of that. Alright, so zoomed in of it, here's the multiplying factor. Yes, this is just a bigger size of it. So it goes from 1 all the way like this, 1, 1, 1, 1, and then it repeats at the 10th one there, 1, 1, 1, 1, 1. And yeah, so multiplying factor just expands from the 11 to 30. So again, it repeats every, so there's going to be 9 patterns, and then repeats on the 10th one. So it goes to 11. Actually, this 11 is, yeah, forgot this part right here. So there's going to be 8 numbers here, 1 to 8, and then plus this include this part right there. And then it repeats as well here at the 19. It just keeps going on. And yeah, so this repeats to 28. It's going to be, this is going to be 1, 1, 1, then 1, 2, 4, 8, 7, 5, and then etc. So note that the pattern cycles every 9 increments of the multiplying factor, and then starts over on the 10th increment. So for example, if we have multiplying by 1, we get our 1, 1, 1. Multiplying by 2, we get 1, 2, 4, 8, 7, 5. Multiplying by 3, we get 1, 3, 9, 9. Multiplying by 4 is 1, 4, 7. Multiplying by 5 is 1, 5, 7, 8, 4, 2. Note that this is the reverse of the factor 2 pattern. So the usual doubling one is multiplying by 5, and in fact, this is just our halving pattern converted into multiplying by 5, as I'll explain later. So we have this 1, 5, 7. This would be 1 there, and then 1, 5, 7, 8, 4, 2, 1. 1, 5, 7, 8, 4, 2, 1 is exactly the reverse. If you go backwards, it's going to be 1, 2, 4, 8, 7, 5, 1. That's just a doubling pattern. And also then we have 1, 6, 9, 9. Then multiplying by 7, 1, 7, 4. Note that this is the reverse of the factor of 4 pattern. So here, right here, factor multiplying by 7, 1, 7, 4. This one, next one is 1 there, so 1, 7, 4 backwards, or 1, 4, 7. It's going to be reverse of 1, 7, 4. And then multiplying by 8, we get 1, 8. Dot, dot, dot. Multiplying by 9 is 9, 9, 9. Yeah, dot, dot, dot. And then the multiplying by 10 repeats at 1, 1, 1 right here. So the 10 repeats 1, 1, 1, 1, 1. Non-stop. Now, in fact, this is expected since the 10th increment is equal to the modulus plus 1 for whichever base number system. And in this case, it's the 9 plus 1 for base 10. So, in fact, this is always the case because multiplying a number by k plus p is just that number multiplied by k plus a factor of p. What I mean by this is if we have a number like this, let's just say we have a integer right like that. Yeah, whichever number this is, let's say we're going to multiply by k plus a factor of p or plus a modulus p like that, or a factor of it. So we're going to get multiply this inside, so a times k. Then we're going to have a plus right here. This is going to be a times p. And then this is going to be this can be considered as our remainder. I mean, this is going to be considered as our factor of p. This is our factor of p. Yeah, factor of p, and this is a remainder. Just have it in the other direction. This is going to be our remainder. Like that. So this equals to as well. This is going to equal to, I'll just write the factor of p in front, just because it's our usual. So this is equal to a factor of p. This is, just a times p is just a factor of p. So just factor of p plus ak. I just write this remainder like that. Yeah, so that's what we have is thus we could just write this as right here v equals, or just put this in ak in front, so a times k plus p. V equals to the remainder, which is just, or the partial remainder until you keep reducing it. And then v equals to a k. So in other words, multiplying a number by k, or an integer by k, is the same as, it has the same vortex sum as multiplying the number by you're multiplying the number by k plus p, the modulus. Because again, that's just a factor of p. Even if you have 2 times p, etc., it's still going to be a factor of p. So in other words, here, in our case, the k is just 1. So k is just 1 in our case. And I'll just bold this. Yeah, so what this means is if we look at that table again, just so if we have a multiple right here, for example, let's say 3, or let's just go over here. Or let's go over here. So if we have a 3, if you multiply this number 3 by 3, we will get 9. But if you multiply 3 by 3 plus 9, that's going to be 12. So then in other words, you're going to multiply by this 3 by 12. That goes all the way over here to 12. It's going to be 9. It's going to be the exact same ones over here. It's 9 and 9. And I'll just illustrate that right here. So the following examples illustrate this for base 10 or mod 9. So if you have 1 times 4 equals to 4, Then if you have 1 times 4 plus 9, this equals to 9 plus 4, which just equals to, well, factor of 9 plus remainder, which this is going to equal to 13, v equals to 4. So yeah, you can just write it like that. Factor, yeah, the factor of 9 just goes away, or you could just even just calculating it out, it can be 9 plus 4 is 13, v equals 1 plus 3 is 4, and you can just sum those up. And for another example is just, yeah, if you have 3 times 7 equals 21, v equals to 2 plus 1 is 3. But if you have 3 times 7 plus 9, so you add the modulus to it, this equals to 48, v equals to 4 plus 8, so you just automatically calculate. So you can calculate it, and you'll see 4 plus 8 equals to 12, which v equals to 1 plus 2, which equals to 3. So it's the exact same thing. Or you could just break it up into its remainders. So 3 times 7 plus 9 equals to 3 times 7, yeah, multiply this inside, plus 3 times 9. In other words, you get a remainder plus a factor of 9, v equals to the remainder, which just equals to that 3 times 7 equals 21, and you got to reduce it further, v equals 2 plus 1 is 3. So yes, fascinating stuff. And here I quickly just updated this to match this look as well. This is a better illustration. So yeah, 1 times 4 plus 9 is equals 13, v equals 1 plus 3 equals 4. Or you could just go 1 times 4 plus 9 equals 1 times 4, plus 4 times 9 equals remainder, plus factor of 9, v equals remainder, and it's just equals to 1 times 4. The remainder is 1 times 4 equals 4. And yeah, this is the exact same. So this is the same for any other base, such as base 4. So if you have base 4, and then mod is 3. So if you have 11 times by 1, this just equals to 11. Yeah, well, yeah, 1 times 11 just itself. V equals 1 plus 1 equals 2. So if you have 11 times 1 plus 3, so the modulus is 3. This equals to 11 times, well, 10. 1 plus 3 is just 10. So in other words, we just increment another 0, so 1, 1, 1. Yeah, 1, 1, 0, v equals to 1 plus 1 equals to 2. And again, that is in, yeah, this is base 4. So 1 plus 3 in base 4 is 10. So yeah, this just equals to 2. The 0 doesn't affect it. And likewise, if you have 11 times 1 plus 3, you could, you could just write this out, expand it out. So 11 times 1 plus 11 times 3. So we get a remainder plus a factor of 3. So v equals Vortex times just a remainder, which equals to 11 times 1, which equals 11. V equals 1 plus 1 equals to 2. Alright, so now that we've covered all the doubling patterns and multiplying patterns, now let's look at vortex halving patterns. So after adequately covering doubling and multiplying patterns in general, or a bit more than adequate, it's pretty in-depth. In this section, we will review the main halving patterns presented by Marko Rodin. So we have the 1578442 pattern, and note again the main base 10 doubling pattern. Yeah, so yeah, we'll cover this. This is the halving pattern, it's just the reverse of the doubling, or 1, 2, 4, 8, 7, 5 going backwards is 1, 5, 7, 8, 4. We have 1, 5, 7, 8, 4, 2. So anyways, note again the main base 10 doubling pattern. We have 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and add up the digits. 1 plus 6 is 7. Then 7 times 2 equals 14, or v equals 1 plus 4 is 5. 5 times 2 equals 10, v equals 1. And then we get our 1, 2, 4, 8, 7, 5, and then pattern, and then next repeats at 1. And now here's the halving pattern, which ignores the decimal place and the zeros, and is in fact just the reverse of the doubling pattern. So we have here, so if you have 1 divided by 2 is 0.5, and then v equals, we just ignore the decimal place and the zeros, v equals 5, and then 0.5 divided by 2 just equals to 0.25, and then v equals to 2 plus 5 is 7. And you can see here, this equals, so just calculate it automatically. Then 0.25 divided by 2 is 0.125, equals 1 plus 2 plus 5 equals 8. And then the next one, 0.125 divided by 2, you can see you get this big number, equals 625. V equals 6 plus 2 plus 5 equals 13. V equals 1 plus 3 equals 4. Just add those up. And then going further, we get this 0.0625 divided by 2 is 0.03125. Notice the 5s everywhere. It's all just multiples of 5. 0.03125. V equals 3 plus 1 plus 2 plus 5 equals 11. V equals 1 plus 2 equals to 2. And then going further, the next one, 0.03125 divided by 2 equals 0.015625. V equals 1 plus 5 plus 6 plus 2 plus 5. You add up these digits, and then this equals to 19. You can just double check for space. V equals 1 plus 9. Put a space between here. Then, yeah, this equals to 10. V equals 1. So, yes, we have our 1578421 1 pattern, which is again the reverse of the doubling 1, 2, 4, 8, 7, 5, like that. That's fascinating. So note we could have just half the resulting vortex sum each time, just as with the doubling patterns. So instead of going with the full number here, we could always just go take whatever the vortex sum was and then divide it by 2. So in this case we have, so we could have just done that. So we could have got 1 divided by 2 is 0.5, v equals 5, so just divide by 5, and divide 5 by 2. 5 divided by 2 equals 2.5, v equals 2 plus 5 equals 7, and 7 divided by 2 is equals to 3.5, v equals 3 plus 5 plus equals 8, and then 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. And then we get our usual 1, 5, 7, 8, 4, 2, and then repeats again at 1. And we can go further and we can calculate more terms using Excel or Microsoft Excel or any other spreadsheet program by first multiplying the halving result by 10 to the power of 13. I just put a 10 to the power of 13 to get a really big number, or base to the power of a very large number to remove the decimal places automatically. Because otherwise when you're dividing it, you're getting these big decimal places. So if you calculate it, or if you multiply it by 10 to the power of a really big number, you'll just move the zeros to the other side, and zeros, they're not included. Yeah, the zeros just get removed in the mod function. They're not, they don't affect the vortex sum or the remainder. Yeah, and I'll show that. So to remove the decimal places so that we can take the mod 9 to get the remainder or vortex sum. So basically here 1, so if you start out at 1, halving, and I was halving times 10 to the power of 13. So 1 times really big number, we get this, and then mod 9 of this one, this is a base 10, equals to just a 1. And then 0.5 times big number, you get 5, and then all these random zeros, and then the mod remainder is just going to be 5 when divided by 9, because again, everything is just, the zeros, they're just equal to factors of 9 plus 1. So this could be 99999 plus 1, and then times by the 5. So all that matters is that remainder. So going further, or actually better yet, let's just write that down, actually, it's pretty interesting. So let's say if you have, for example, 0.5, and let's say times it by a big number, so times by 1,000, this equals to, this will just move the decimal place to the right, 1, and then 2, and then 3. So we're going to have a 500. So 0.5 times 1,000 is 500. And then v equals here, this would just be equal to, well, 5. But we're calculating using the mod function in Excel. So this would equal to, well, 5 times 100. And then 100 is equals to 5 times, well, 1 plus 99. So in other words, we have 1 plus 99. This equals to 5 times 1. Yeah, 5 times 1 plus 5 times 99. This is just a factor of 9. Factor of the modulus 9, and this is going to be a remainder. Yeah, so then the vortex sum is going to be equal to just a remainder. Remainder, which in this case is 5 times 1, just equals to 5 times 1 equals 5. So yes, basically, yeah, we just multiply that like that. And again, the reason is because we're going to calculate the mod function, so we'll have it 0.5 times by, for example, 500, or for example, 1,000, or you could do 1,000, or you could even do 10 to the 13, etc. Let's put this 10 to the 13. Like that, and then this equals to, yeah, do that, and then we'll mod it. Mod 9 equals to, this would just be 5. Because this just gets a remainder. Or I'll just, for completeness, or just for clarity, just move it down here, or we could write it like that. Or this, so then this one would be 0.5 times 10 to the power of, this is 3. Like that, that's for the 10,000. Mod 9 equals 5. Yes, they're all going to be, it just calculates the remainder. Equals the remainder. So all of them are going to be equal to the remainder. This equals remainder, so 10 to the 13. So here I just put multiply by 10 to the 13, just so that we can eventually get a full number at the 14th count over there. This is going to be a remainder. Like that. Alright, so anyways, going back to this Excel sheet or this Excel table, so notice here 1 divided by 0.5 is, 1 divided by 2 is 0.5, and then vortex sum is 5. or the mod 9 is 5, and then when you multiply by a big number, so you get just a bunch of zeros. And then 0.5 divided by 2 is 0.25, add the digits up, it's going to be 7, 0.125, then eventually the 14th one you get 0.000, you have 3 zeros, 1, 2, 2, 0, 7, 0, 3, 1, 2, 5, add up all those, or just multiply by 10 to the 13th, so we get all the decimal places gone. So 1, 2, 2, 0, 7, 0, 3, 1, 2, 5, and then the mod 9 of this is going to be 5, or the vortex sum, just add those up. And as expected, the pattern continues indefinitely. And yeah, going further now, the difference between doubling and halving is, well, is that halving, or multiplying in general, depends on the base number system. So when we double the number 1, we get 2, or more generally, we get 1 plus 1. To account for all number systems, including binary. There's no number 2, it just goes to 1, 0. Yeah, but with doubling or any other integer multiplying factors, the quote value of the resulting number is the same for all base number systems. Thus, even though the resulting number notation is different, doubling always means the same thing in all number systems. So 1 plus 1, this is just doubling. So equals to 2 in base 10, but 1 plus 1 equals to 10 in base 2, but these are equivalent. So 2 in base 10 is equal to 10 in base 2. So these are just equivalent. On the other hand, halving or dividing in general depends on the number system for its value. So so if you have 10 divided by 2, this equals to 5 in base 10, but 10 divided by 2 equals to 1 in base 2. So that's going to be half of that. So 1 plus 1 equals to 10. And then, but if you have base 12, so when you half that, that's going to be, well, it's going to be half of the base. So 10 divided by 2 equals to 6, or yeah, 6, which equals to base 12. I mean, in base 12. So 10 divided by 2 equals 6 in base 12, but the values, yeah, these are not the same. So these values in base 10 value would all just be the same, 1, 5, 6. These are all just base 10, but the values are not the same. So what I mean by that is 5 in base 10 is not equal to 1 in base 2, and it's not equal to 6 in base 12. But notice here, when we double, 2 is base 10 is equal to 10 in base 2. But these values are not the same right here. In fact, the relative values are just that, well, 1, 5, and 6. So yes. Note that in the above examples, I used the earlier concept of the number 10 as a, quote, placeholder to transition the count beyond the base number of single digits. Yeah, so the number 10 is the transition holder. Just remember that one there. So note that, yeah, so for example, base 2 is 1, 10, and then 1, 1, 1, 0, 1, 0, 0. Base 4 is 1, 2, 3, and then it goes to 10, and then it goes 1, 1, 1, 1, 1, 2, 1, 3, etc., then 20. Base 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also, yeah, recall base 16 is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes A, B, C, D, E, F, and then it goes to 10 once it repeats at this is the 16th digit. Yeah, 16th digit when you ignore the 0. If you include the 0, this would be the 16th digit. But anyways, now going further. So using the same concept, we can derive the following sequence for any general base number system. Yeah, so what I'll do here is I'll make a little column right here. I'm going to call this count. So count, this would be just base 10 notation for the count. But then for any, but the derivation is going to be for anything else. So let's say count to 0. Let's put it like this. So from the, let's say our count is 0, and then what we have is, well, 1 divided by 2. You could write this as 1 divided by 2 to the power of 0. Or actually, I will do that after, just to show you. I'm going to write this. So we have our starting point number 1. Yeah, so that's our starting point number 1. Then our next one, this is our count 2. I'm going to go with 1 divided by 2, like that. So 1 divided by 2 is the same thing as writing 1 divided by 2 to the power of 1. And I'm going to convert this into the general halving for any number systems. What I'm going to do is I'm going to multiply this by 2. We'll include that 1 after. So I'm going to multiply this by, multiply by 10 over 10. So we're not changing anything. This just equals to 1. So you're multiplying by 1, so the same thing. So now we're going to move this over to there, and then move the 2 over to there. Just switch these places. So we'll have a 1 over 10 times it by a 10 over 2, like that. Yeah, so that's what we have there. I'm going to put this in bracket. So this 10 over 2, it depends on the base number system. And this one for Vortex sum, we exclude those. But anyways, let's go further. So the second count is going to be 1 over 2, like that. So this is going to be, well, 1 over 2 times it by 1 over 2, or halving. And this equals to, well, just 1 over 2 squared. Well, actually, before I even get to that, I'll just illustrate this. So 1 over 2, this is gonna be equal to, well, 1 over 2 times 1 over 2, but 1 over 2 is this. This is 1 over 2. So we can just throw those inside. So this is gonna be equal to 1 over 10, like that, times it by 10 over 2. I'll just get rid of this bracket for now. And then times it by 1 over 10 times 10 over 2, like that. Yeah, so what we end up having is just using it in power notation. This equals to, well, the like ones, 1 over 10 times 1 over 10, that just equals to 1 over 100, or 1 over 10 squared, and then 10 over 2 times 10 over 2. You could just use that in this square notation as well. So this is going to be equal to 10 over 2, 10 over 2 squared, like that. Yeah, and here quickly just move things around, move the column around, and then also put this arrow. This equals to this left side multiplied by the 1. Yeah, so this is 1/2, this is 1/2. So multiplied together, we get this one. And now I shift this over so that we could write these all in powers. So 1 over 2, this just equals to 1 over 2 squared. 1 over 2 times 1 over 2. So 1 over 2 squared. And this one here is going to equal to 1 over 2 to the power of 1. So that the count lines up with the power. So to see the 1, see the 1 and 1, 2 and 2. And then this one here, we could also write this in general. So 1 over 2 to the power of 0. This 2 to the power of 0 is defined as equal to 1. So this just equals to 1, like that. And then the next one, we could see the pattern that arises. This is going to be, well, 1/2 times this one right here. And you can see this one right here, actually. So if I put this in a bracket, this is, or just leave that, yeah, actually keep the bracket like that. This equals to, or actually keep it there. I'm going to set this equal to 1 over 10 power of 1 times it by, this is going to be 10 over 2. Power of the power of 1. So yeah, it's not changing anything. And this one too, this 1 equals to 1 over 10 to the power of 0 times it by 10 over 2 to the power of 0. You can see the pattern. It's all the exact same thing. And yeah, these 10 to the power of 0 cancels. All we're left is 1 divided by 2 to the power of 0, which equals 1. And then likewise, you see the pattern that arises. The next one, when you half it, is just going to be 1/2 times it by it's going to be 1/2 times it by this, where 1/2 equals to 1 over 10 times 10 over 2. So we just increment this by another 1. So we're going to have 1 over 2 to the power of 3 is equal to 1 over 10 3, like that. You got 10 to the 3 times it by 10 over 2 to the power of 3. And then in general, if you just go like here, dot, 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 to the kth term, we get, or the kth count, we have 1 over 2 to the power of k equals to 1 over 10 k. And then now we have a 10 to the power of 2 k, like that. And we can circle this. So notice what we have. We essentially have a division, 1 over 2, or a halving, and converted into a multiplication when we ignore this one here for the vortex sum. So 10 over 2 to the power of k. This is a multiplication, depending on the number system. Yeah, so note that although I made the left count column in base 10 is base 10 notation, the general kth term derivation is in the same notation for any base number system. So yeah, this k term, doesn't matter what base number you're using, so it's going to be equal to this in general, how this formula is. So for convenience, as done throughout this video, I will convert the above general halving formula into its equivalent, but in base 10 notation. So if you have base 10 and base n, so base is n, and then in, this is in bracket n base 10 notation, so that we don't need to deal with letters like A, B, C, D, E, F, etc., or jumping to 1, 2, 3, all of a sudden to a 10, and so on, so in base 10 notation. So that means we could just convert directly. We could have 1 over 2k. This is going to equal to 1 over nk, where n is equal to the base, but instead of putting a 10, we'll just put it in the base 10 equivalent. Yeah, so then we'll have 1 over nk times it by n over 2k, like that. Yeah, so for example, if this is the base 12, so if n is 12, the base 12 system, this is going to be a multiplying by, well, 12 over 2 is 6. So yeah, remember, if it's base 12, so 10 over 2 is 6, so or you could just go 12 over 2. Yeah, so in base 10 notation. Yeah, so thus the value of each halving term depends on the number system n and the operation n over 2. So again, this, if you're halving it, it's going to depend on whatever this is. In base 10, n is equal to 2. So let's go further. So this is actually, we're just converting it into a multiplication here. So converting halving into multiplication. The above derivations effectively turns the halving formula into a multiplication formula because the division 1 divided by 10k in placeholder notation or 1 over nk in base 10 notation doesn't affect the vortex sum of the number, but rather just moves the decimal place or increments the number of zeros. For example, consider the base 10 number system. Yeah, so for base 10, we have, well, n equals to 10, and we'll just write this as 1 over 2 to the k. Just scroll up here, 1 over 2k equals 1 divided by n to the power of k. But in our case, yeah, n is equal to 10, times it by our 10. So so basically we're taking the general one, 10 over 2 power of k, and then 10 is the same in, so base n is 10, and also in general it's 10. It's 10 over 2, and then this is going to be k, and again this does not affect vortex sum. Let's write down, does not affect vortex sum, so that 1 divided by 10 power of k, vs, does not, I'll just write it full, it does not affect vortex sum. Yeah, so that's what we could do is, just write this, remove that, and also note that the 10 over 2 power of k, that equals to, well, that just is 5 in base 10. So, in other words, we've converted 1 over 2 to the power of k into a multiplication 5 to the power of k. Yeah, so thus the halving formula is now transformed into a multiplication formula with a multiplying factor of 5. Yeah, so it's basically this 1 over 2 to the power of k just equals to 1 over 10 power of k times it by whatever this 10 over 2 is. In base 10, it's equal to 5, and then in vortex sum, we remove this entirely, this 1 over 10 to the power of k. So thus, what this means is if we're going to halve from starting from 1 divided by 2, it's the same as multiplying by 5. So, and then if you do it the second time, 1 divided by 2, it's going to be equal to, yeah, it's going to be, the second time is going to be 1 over 2 to the power of 2, and then you just have it equals to 1 over 10 squared times 10 over 2 squared, where then this one doesn't doesn't account for the, it's not affected, does not affect the vortex sum. So all we're going to do is multiply by 5 squared, 5 squared. So let's take a look at this. So we can analyze this further by seeing the pattern on a vortex or modular circle. So I'm going to write this here. So let's start off from here. So 1 like that. And then we're going to multiply this by 5. Yeah, when we multiply by 5, we get, well, over here, 5. This is going to be multiplied by 5, or 1/2. So, or you're going to half it or multiply it. And there's our pattern. Let's just write our pattern. Keep track. So we have 1, then it goes to 5. Next one we expect is, well, it's going to be, we expect it to go to the 7 because it's reverse the doubling. So this one's going to be, well, let's times it by 5. Let's go times by 5 equals to, or yeah, equals to 25. Then you sum up the digits. V equals to, well, 2 plus 5, and then equals 7. So this would go straight to the 7 like that. Yeah. And then the 7 one multiplied by that by 5. So we're going to have this by 5. And then this equals to, going backwards, 5 is going to be 35. Like that. And then this is V equals to, I'll just fix that up. Let's write it down, left to right. Yeah, this is going to be 7 times 5 equals to 35. V equals to 3 plus 5, which equals to 8. So this goes back here. Again, the mirror image of this one over there. Yeah, so the next one, you can just draw this dashed line like that. So mirrors there, 1 goes to 5, 8 has to go to 4. And yeah, it's multiplication, and so we just have our usual mirrors. And then the 4 goes straight to the 2. Mirrors here's the mirror there. And this goes straight to the 2, and then the 2 goes over here. Everything just mirrors like that. So 1, 5, 7, 8, and then 4, 2, and it goes back. So it's reverse of the doubling. Alright, and as a double check right here, we can go, yeah, there's the pattern 157842, and yeah, 157842, let's just multiply by 5, so 1, and then we have our 1 times 5 is 5, 5 times 5 is 25, v equals to 2 plus 5 is 7. 7 times 5 is, yeah, just, you also multiply just from now on. 7 times 5 is 35, v equals 3 plus 5 equals to 8. And then right here, 8 times 5 is 40, v equals to 4, just sum up the digits, and then 4 times 5 right here is 20, v equals to 2, 2 times 5, v equals to 10, and then we have this v equals to 1 over there. And then there's our 157842 pattern, so 157842 pattern confirmed, and is the expected halving pattern. Yeah, so that's what it was earlier. And now let's determine the halving pattern, or determine the halving pattern of the base 8 number system. So if we have base equals n equals 8, that means n divided by 2 in base 10 notation equals to 4. And yeah, so halving pattern equals multiplication by 4 pattern. So if we start over here, this means that let's start from the 1, and let's multiply by, or yeah, divide by half. Is the same thing as going right here, because remember, it's not going to be equal to 0.5, because 0.5 is based on base 10. This is base 8. So then it's going to be half of 8, which is 4. So it goes over to here, and we'll write this as 1/2, or I'll go times 4, or 1/2, like that. Or just put it on this other side. So it's either 1/2 or times 4, it's the same thing. So he goes over here, 1 times 4 is 4, and then 4 times 4, let's times this by 4, equals to, well, this is going to be v equals 16 in base 10 notation, mod 7. And the difference here is going to be, well, this should be, well, let's see, 7 times 2 is 14, so the remainder is going to be 2. This equals to 2. So this will go right here. There's the pattern. And now this one, well, 2 divided by 2 is just going to be 1. Yeah, so you can go 1/2, yeah, or times 4. So 1/2 is going to go to 1, so there's a cycle, or times 4. And we can even do times 4, and what we'll get is this equals v equals to 8. 8 mod 7, and 7 goes in once, and the remainder is 1. Equals 1. It's just pretty fascinating stuff. So going further, we can show that that halving is always, or in general, always the reverse of doubling. So we can show that halving is in general always the reverse of doubling by considering the following. Let's just say we have a number a, or integer a, and now we're gonna let's say we're gonna half this one. So if you half it, this equals to, well, a times 1/2, like that. Now this has a vortex sum that's equivalent to the vortex sum of, well, a times 10/2, like that, which depends on the base number system. Yeah, so now if we take this number right here, or this vortex sum, and then let's double this one. Okay, let's double this. So we have over here a times 10/2, and let's double it. So we're going to multiply it by 2. This is going to go over here, times it by 2. If you multiply by 2, the 2's just cancel. So 2's just cancel. All we're left with is a 10. A times 10. But then the 10, this does not affect the vortex sum. This just adds another 0. And this is again, yeah, this is another 0. And this is just the transition holder. So we're going to write this as, yeah, does not affect vortex sum. Affect vortex sum. So multiplying it does not affect it, even dividing doesn't. Vortex sum. So then this is going to be v equals to a. So here, I'll just box this out like that, and this like that. Yeah, so that's what we have is they're just in the reverse direction. So thus a goes to a times 10/2. This is a vortex halving. And reverse as well as a doubling. So times by 2. Times by 1/2 or times by 2, it's the same thing, like that. So let's just remove this times. So yeah, halving or doubling, same thing. But in this reverse direction. So this goes backward, this goes forward. Let's just circle this. Oops. Let's try this again. Alright. There's perfect. Yeah, so essentially, since multiplying or dividing, as we derived earlier, by the number 10 placeholder doesn't change the vortex sum, then halving is always equivalent to doubling in vortex math patterns. Or does it, don't need a comma there. Since it doesn't, since multiplying or dividing by the number 10 placeholder, all it does is add another 0 or subtract another 0 or move the decimal place. It doesn't change the vortex sum by definition. Then halving is always equivalent to doubling in vortex math patterns. So for general base number systems, we have the following halving and its reverse doubling pattern. So if you have a base p plus 1, and here I've made it like this, where you have the modulus p. Now to the right of it is 1, to the left of it is p minus 1. And then the bottom left, I have it as 10 divided by 2, yeah, which is as expected. So going back here, so the 10 divided by 2 is over here is a 4, so 8 divided by 2 is 4. And then for the base 10, it's going to be in 10 divided by 2 is 5. Yeah, so here's 10 divided by 2 is 5 there. So bottom left always. Let's keep going further. Yes, it's bottom left just because it's p divided by 2. Yeah, when you divide that by 2, it goes straight down the middle, but then here's increment 1 divided by 2. It goes over to the base number of it, so 10. So what happens here? So let's say we have 1 there, and I'm going to write the patterns. Let's double, or let's half this one. So I'm going to half it. So halving goes to, by definition, 10 over 2. So that is going to be our 10 over 2. I mean, yeah, this is, our halving goes straight to the 10 over 2. Thus, we could write our pattern. So we start from here 1, then it goes to 10 over 2, whatever the vortex sum of that one is. And then the next thing this is going to go to, this will go, let's just say generally it'll go, just pick a number there. Say it goes over here where it's going to be 10 over 2 times it by 10 over 2. So writing it as a multiplication. Like that. Yes, write it like this, 10 over 2. Like that, and then this equals to 10 over 2 squared. Just put it squared like that. So then the next one is going to be in this pattern, 10 over 2 squared. Then let's go one more. So let's say one more, it goes over to here. And let's say this number, the vortex sum is where you had the multiplication, 10 over 2 to the power of 3. Like that. So then it goes to 10 over 2 to the power of 3. Alright, so that is halving, and now let's start doubling, and let's start from here, so 10 over 2 to the power of 3. So then we'll put that over here, and it's because again it's going to be the reverse of the halving. So then this one we're going to go this way. So when you multiply this one, it's going to go backwards where you came from. So this is going to be times by 2. So that's going to be over here 10 over 2 to the power of 2. So yes, this one is going downwards. I'll view this one like this. So this one is going downwards. And then the other one is going to be going, yeah, this is going to be times it by 1/2. Like that. Yeah, or better yet, just move it around and move this down straight here. So that's the 1/2 pattern. And the green one here goes to here. This is 10 over 2 squared. And then the next one's going to go just backwards in time here. So 10 over 2. Like that, so it's the exact reverse of it. So this is going to be start going down, and then the last one here, this goes to the 1. So this would go to the let's go like this. Yeah, this goes straight to the 1, like that, and it's going to be 1. So it's reverse of it. So you could write this as like this. It's going to be our times by 2, and this one is the 1/2. Yeah, and here's, yeah, the starting point's the same. So we have this 1 over there. Let's draw this in black. So it starts there. I mean, yeah, it ends there. This one starts there. So it's just going exactly reverse directions. So yes, yeah, fascinating stuff. Now let's do an example with the base 10 number system. So here, let's do this right here. So let's start from number 1, and we're going to half it. So halving number 1, again, for base 10, we'll write this as 10 over 2. Equals to 5. So we're going to be multiplying by 5. Goes like this to the 5. And here I'll just write patterns there. So it goes to the 1, and then it goes to the 5. And we know that already 5 times 5 is 35. It goes to the 7, like that. Then 7 goes to 7 times 5 is 35. Goes to the 8. So we're going to have 1, 5, 8. Yeah, 1, 5, 7, 8. And then this goes to the 4. We know that this one is just a mirror image of this 1 goes there. 1 goes to 5, so then that means it has to go to 4. And then this goes like that, 2, and it goes back like that. This is going to be 4, 2, and then 1. And now the reverse direction has to occur. This is going to be in 1/2. It's going 1/2. So then the reverse has to be starting from here, 1. So we ended off here. Let's say, so we're going to start from here. So we're going to start off from the 1. A circle in black to know where we're starting off from. Yeah, or to make it similar to this one. This is where we ended off of. Let's just circle the bigger one. So this is where we started off. This is where we ended off from. So this is where we're going to start. And when we do that, yeah, notice what happens. It just goes down. Or we could actually include both. So this is where it ends. This could be where it starts, like that. So it starts there, ends there. So we could write this as actually the end point. So this can be, this is the starting point. So we could do this. This is the starting point. You just make it like this. So starts, ends in square, and it will go square for ending. Oh, whoops, not the 4. Yeah, it ends right there, and then this one's gonna be where it starts. Yeah, for the 2, and then it's gonna end over there where there's the 1. So anyways, let's go. This is the green. So this starts at the circle, ends at the square. That means the doubling has to start at the square and end at the circle. So we're gonna go from 1, doubles to 2. This times by 2. Let's just draw this. This is 1/2, like that. And then the 2 goes to the 4. So we'll have a 2. Then 4, yeah, so 1, yes, so this is going to be in reverse, 1, 2, 4. Next one has to be 8, and you can see that this is going to go straight to the 8. 2 times 4 is 8. 8 goes to the 7, and then the 7 goes into the 5, and the 5 goes all the way back to the 1. So we're going to get this is going to be 7, 5. So yes, it's like we're going upwards. So it's like we're going up in reverse, and this is going to go back to the 1, and this is where it's our starting point of the original. So, yeah, so this one is halving. This is doubling, and doubling is just reverse of the halving. All right, yeah, it's pretty amazing stuff. And now let's go further and exercise our halving ability. So lastly, let's determine the halving pattern base 12, and then double check our results and see that it is in fact the reverse of doubling. So what we'll do here is this is the pattern for base 12. So we'll have here 1 divided by 2. 1 divided by 2 has to go to the 6 because, well, we know that 12 over 2 is equal to 10. Equals to 6. That's in base 10 notation. So this is going to be, halving is equivalent to multiplying by 6. Like that. So the pattern is going to be, well, 1. Let's put this in the middle. So we're going to have 1, and then 6. 6 goes to, well, multiply 6 by 6, so 6 times 6 is going to be equals to 36, and 36 mod 11, so 11 goes into it cleanly 33, then a remainder 3. This is going to be V equals, not equals, just for proper notation, it's going to be 3. And then 3 right here, 3 times 6, V equals to, well, 18 mod, or make some room, I'll just move it down here. So V equals 18 mod 11, which equals to 7. Yeah, so this equals to 7, like that. And just move this away. Here, just move this over there, so it's going to be 7. And then let's move this 3 goes to this 7. It's down here. Like that. Oops. Let's do this again. Whoops, again. One more time. Yeah, here I just paused and just moved over, drew the line myself. And also here I made it straight as well because I just realized what you could also do is, remember this goes to 7, but you could also do this just in bracket 3, or I'll just put a note like here. Yeah, note right here, we could do 3 divided by 2, this is base 12, this is going to equal to 1.6 as opposed to 1.5, because remember that's 5 would be base 10. This is going to be base 12. So then V equals to here, 1 plus 6 is 7. It's just fascinating stuff right there. Yeah, and here I just move this over to that side. And yeah, so going further, so 7 right here, we could do 7 divided by 2. That's going to be, what would that be? 7 divided by 2 is equals to, is going to be equal to 3.6. Phi equals 3 plus 6 is 9. Equals 9. So yes, you could just do that. In fact, it is the exact answer. So I'll move this around like that. 9. And the next one is, yeah, next one's going to be, well, 9 times 6 is 54, I think. Or you can also divide this by 2. So 9 divided by 2 equals to, what would this be? This would be 4.6. So in other words, phi equals 4 plus 6 equals to 10. So this would just go straight to the 10. And then the 10 divided by 2 is just goes straight to the 5. And now we have our mirror symmetry right here. So these are pairs right here, and then the 5 can go to wherever the 6 went. 6 went to 3, so then the 5 has to go over to the 8. Let's keep track of our numbers. This is going to be 10, then it's going to be 5, then it's going to be 8. Whoops. Then it's going to be 8, and then the next one is going to be from here, wherever the 3 went, 3 goes to 4. This one fills up every single number besides the modulus. Amazing. This goes to the 4, and the mirror is 7. 7 goes to the 9. That means this one has to go to the 2. So put this as 4, and then 2. That's it, because the 2 divided by 2, yeah, 4 divided by 2 is just 2. Yeah, we don't need to do the mirror. We can always do it many ways. 2 divided by 1 is 1. And this is the halving pattern. Yes, that's a pretty fascinating example here. Now, there's even the division there. And so we can double check the pattern as well as look at the doubling sequence and show that it's a reverse of halving. So we can double check the pattern 1, 6, 3, 7, 9, 10, 5, 8, 4, 2. So 1, 6, 3, 7, 9, 10, 5, 8, 4, 2. That's correct. So 12 divided by 2 is 6. So it's going to be a multiplication of 6 of 1. And then we'll have 1 times 6 is 6. 6 times 6 is 36 mod 11. That's the vortex sum. It's going to be 3. And you can again calculate this. Yes, erase and press space, and it's 3. And then 3 times 6 is going to be v equals 18 mod 11. That's going to be 7. There's a 7. And then you have 7 times 6 v equals 42. Yeah, and then mod 11 is going to be 9. And then 9 times 6 v equals 5. You have 54. Mod 11 is 10. And there's a 10. And then 10 times 6 v equals 60. Mod 11. And you have 5. Then you have 5 times 6 v equals 30. Mod 11 is 8. And then 8 times 6 v equals 48. Mod 11 equals to 4. And then 4 times 6 v equals 24. Mod 11 equals to 2. And so on. And 2 times 6. Yes, so 2 times 6, multiply that, v equals to 12, mod 11 equals 1. So we've just repeated the cycle. So 1, 6, 3, 7, 9, 10, 5, 8, 4, 2, 1 pattern confirmed. And as a double check, the doubling is the reverse of this. So the doubling should be going backwards. 1, 2, 4, yeah, so 1, 2, 4, 8, 5, 10, 9, 7, 3, 6, 1. And then it keeps repeating. So we go 1, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, so 1, 2, 4, 8. And then 8 times 2 is 16 mod 11, which is 5. And then 5 times 2 is 10. 10 times 2 is 20, mod 11 is 9. 9 times 2 v equals 18 mod 11, which is going to be 7. There's a 7. And then 7 times 2 is 14, mod 11, it's going to be, the difference is 3. And there's 3, and then 3 times 2 is 6, mod 11 equals to 6. You could just use mod 11, or you could just leave it as that. Just leave it like that, 6. Because, yeah, mod 11, the remainder is, yeah, you're just modding the remainder. So 6 times 2 is going to be 12, v equals 12 mod 11, which is 1. So the cycle is repeating. So yes, 1, 2, 4, 8, 5, 10, 9, 7, 3, 6, 1, confirmed and is a reverse of halving. So fascinating stuff. Note that the same reasoning applies for division of any integer in general, besides just halving. And note the comparison also, I just realized I'm making this video. Note the comparison between the numbers 1 half, or 1 over 2, in base 10 and base 12 when written in decimal notation. So base 10, you have 1 half equals to 0.5, v equals to 5, the vortex sum. But then base 12, 1 half is equal to 0.6, and v equals to 6 right there. So yes, you also have to account for the base number and so on. So fascinating stuff. And now let's go further. And now an interesting part here, because most of these that we're dealing with were even base number systems, base 12 and so on, base 10. But now let's, there's a question that arises. Vortex halving doesn't work for odd base number systems, question mark. Yeah, I don't think it does. So far in this section, I've looked at even base number systems in which the division 10 over 2 is a whole number. For example, in base 10, 10 over 2 is 5. In base 12, 10 over 2 is 6. But in base 6, 10 over 2 is 3. Recalling that halving has the same vortex sum as multiplying by 10 over 2, let's compare with the odd base 5 number system. So, because 10 over 2 governs the halving pattern, and it converts it into a multiplication. So 10 over 2 equals to 5 over 2, or actually I write this for more accuracy. So base 5, 10 over 2 in base 5 is equal to 5 over 2 in base 10. And equals to 5 over 2 in base 10. Or actually, better yet, this is it will get a bit confusing. So this is all in base 5. So 10 over 2 in base 5, you could write this as 4 plus 1. So that's because the highest digit is 4, the highest single unique digit in base 5 system. So then we'll have divided by 2. This would equal to, well, 4 divided by 2 is 2, and then 1 divided by 2 is just 1 half. So in other words, 10 over 2 does not get a whole number. It gets 2.5, which is, again, this half. If you multiply 10 over 10, you're going to get the scenario, this can be just a decimal place. So you're not actually solving anything. So what I mean by that is, if we compared with, if you write that in base 10 notation, so 10 over 2 base 5 is equal to 5 over 2 in base 10, and solve this equals to 2 half. So it's not a whole number. So in other words, if you were writing this all in base 5 notation, or just writing this base 5, or just base 5, base 10 notation. So we have 1, 2, 3, and then goes to 4, and now we're going to half. Let's do the halving. So we have 10 over our 2 in base 5. This is equal to, this equals to, not sure what this equals. This would equal to 2, 2 plus 1 half. Or you could write this as 2 1 half, and we have this 1 here. So this 1 is equal to, well, it's going to, 1 divided by 2 goes to where? So it goes to where? So number turns into multiplication. So we have this right here. I don't know why it keeps doing that. Yeah, like that. So this goes in between this. Is this 2 1 half? So 1 half equivalent to multiplying by 2 1 half. So this doesn't make any sense. So it's not a whole number, so I'm not sure how to handle this in Vortex Math. And likewise, if you multiply this by 1 half, I'll actually move this above, multiply by half or start doubling. So this is the halving. And now if you multiply it by, do you go here? This is going to be times 2, question mark. So that, because if you multiply by doubles, it's going to be, well, 2 1 half times it by 2. This would equal to, this is 2 1 half, I'll put in a bracket. This is just equals to 2 plus, like this. This is just in fraction form. I'll just put this bracket. This is fraction form. Fraction form, and it just means 2 plus 1 half. So this equals 2 plus 1 half times 2, which equals to 4 plus 1, like that. So this would cancel, this would be just 1, 4 plus 1, and v equals to this factor of 4 plus remainder of 1, so v equals to 1. So just that doubles to there, that's correct, but what is this number? There's no number on this vortex circle. So thus it is not clear which integer to assign the halving vortex sum, or even if how that integer doubles to the number 1. Yeah, because well, if we have this written as a fraction form 2.5, this can double there, but that's not a whole number, so I don't know what to do with that. Unless if you multiply by 2, this equals to that. Interesting, this incoherency is in line. Yeah, it's in line with the non-cyclic doubling pattern of the base 5 vortex circle, which I covered earlier sometime in this video. Basically, if you look at this base 5, this is, or I think I covered in base 5, but in this video. But anyways, so if we have here, yeah, actually I know I didn't cover this earlier, but notice what happens here. If you start from 1 and then you double, this would go right here. This would go to the 2. So doubling goes to the 2. It's times 2, but then this one, because this is an odd base number, the modulus is even, and then the halfway point is part of the doubling sequence, so this will jump straight to it, as is the modulus part of the doubling. So this goes to 4, and now this just becomes, well, 4. It doesn't go to 1 anymore. So there is a break in this. So I'll do this right here. Break in pattern. And this is in line with, so this incoherency is in line with this break in pattern here, so it's in the doubling pattern as well, so break in pattern right there. Like that. But interestingly, if you go half from this side, so if you go half 4, it goes also in reverse. This is going to be half. And then this one right here is half, like that as well. So 4 divided by 2 is 2. 2 divided by 2 is 1, and then this one right here is a break. So we don't know where it goes. So this one goes, yeah, I'll just do I'll do a break. This would be like, or just put an arrow, yeah. This would be a gap, and then the doubling one, that's halving is the green, and this one's going to be a break. Yeah, so a break right there. Or a gap. Or just let's see if this will look better like that. So break right here. So yeah, this break in the pattern, I just change it up again. Just made it like this is much simpler. So this break in the pattern is due because this due to the odd base number, which doesn't have a coherent halving definition. So you can't split up the 5 into 2 whole numbers. So that's why you're gonna have a break in this pattern. And that, yeah, coincides with that, as well as going further. So note the patterns first, the doubling, 1, 2, 4, 4, 4, 4. So 1 here goes there. The 1 doubles to 2, doubles to 4, and 4 as a modulus is always itself. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is v equals to 4. Yeah, v equals to 8 mod 4. So yeah, v equals 8 mod 4, which is the remainder 0, but then that's why you have to set it, or the mod is 0, so you have to define it as 4. So as modulus v equals 4, and then 8 times 2, just multiply this, or you can multiply that, doesn't matter. V equals 16, mod 4 equals 0, v equals 4. Then you can also do 16 times 2, v equals 32, mod 4 equals 0, v equals 4. So yes. And then halving, note the halving we have 4, 2, so we have 4, 2, 1, and then what? So 4, 2, 1, and then 1 over 2 is question mark. 4, we have 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2 is question mark. Interestingly, this video is pretty long, so I'm just losing my voice. So interestingly, when halving the doubling pattern prior to its vortex sum, yeah, we get the following pattern. So if we double this one here up to 32, so then if we halve it before taking the vortex sum, and then do the vortex sum of that, so we'll have 32 divided by 2 is v equals 16, mod 4 equals to 0, v equals to 4. 16 divided by 2, v equals 8, mod 4 equals to, v equals to 8 mod 4 equals 0, and then v equals to 4, vortex sum. So 8 divided by 2 is v equals to 4, mod 4 equals 0, v equals 4, and now we take the vortex sum of this, 4 divided by 2 is equal to 2, 2 divided by 2 is equal to 1, and 1 divided by 2 is equal to question mark. So in other words, we have it in the reverse, dot, 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 4, 4, 4, etc., then 2, 1, and then 1/2, and then 1/2 is the question mark. Yeah, this also means that halving a number does not always yield the same result as halving the vortex sum, and then, yeah, taking the vortex sum of that, which is again due to the even modulus number, which can be halved evenly. Yeah, for example, here, let's write number 16. This is in, again, base 10 notation, but we want it in base 4. So this would equal to 4 times 4. So in other words, we have a 4 times it by a, well, factor of 4. Factor of 4. And then the vortex sum is just 4 because it's just a modulus. So this is in base 5. So remember, the other one's just writing a base 10 notation, but we want to get base, base 4. So that v equals to 4. But now, if we want to half this one, so we're going to take this and we're going to half it. If you half it, we get 8. And now we take the vortex sum of this one in base 5. This is going to be, well, this is going to be 2 times 4. So yes, you just divide by 2, and this is just going to be, well, it's another 2 times factor of 4, which equals to 4 like that. That's the vortex sum of it is 4. But if you half this one right here, so half it, I'll just put the half. So if you instead went from the vortex sum and then you half this one, you're going to get 2. And these are not equal like that. Yes, and let's go further. So furthermore, from the earlier section on quote odd-based number systems can synchronize with doubling pattern, we can now see even more clearly why the starting number 1 is always cut off from the doubling pattern. So recall here, I just took a screen grab of it. So number base 7, if you have, this is odd base 7, so the 6 goes, there's an even number there. So now if you have 1, 2, and then it just cuts off the 1. Because there is no number that you can get to over here, because it's because 1 doesn't have a even or this number 1 doesn't have an easy way to half it. Yes, in other words, there's no way of getting to the 1 because we haven't defined it properly. Because 1 divided by 2 for odd-based systems, you're gonna get a, well, it's gonna be not a whole number, so it's gonna be somewhere in between here. So for example, 1 divided by 2 goes somewhere here. Oops, let's draw this in green. So it's going to go somewhere here. 1 divided by 2. So then you're going to need to double some number here. Like that. It's a question mark. So that question is, how are we going to get to that? Yeah, see, this is the base 11. So number goes like this and it cycles around in here. And then base 19 cycles like this. And it goes back in here. So the 1's always cut off. So the 1 is cut off here. This is just a general base n equals p plus 1 equals odd. So p is even, cuts it in half like that. And then, the 1's always cut off because there's no way for it to get to. It's somewhere over here. Like that. Let's just erase this. So yes, so that's beyond just the quote synchronization issue. Odd number systems don't have a coherent definition for halving, which is required for the doubling to bridge the gap back towards the starting number 1. So we need somehow to get back to this number 1. And there's no whole number between these two. Or this 2. So 9 and 10, what are we going to get to? 9.5 goes somehow to get up to this 1. So, don't have a coherent definition. So if you can think of a coherent way to define halving for odd-based number systems, please let me know. And interestingly, that can be extended to, well, even based number systems for different division factors like 3, 4, 5, etc. that don't divide even. So I discussed this further in a section below, quote dealing with dealing with quote irregular division. I'll deal with that later in this video. So now let's look at the powers of 10 pattern. And so after going through the exhaustive analysis of the halving patterns, let's bring our attention to the quote powers of 10 pattern, which is associated with halving. Recall the full formula for the conversion of halving to multiplication discussed earlier. So if we have our halving, let's just go 1/2 in general, 1/2 to the power of k, so whichever part of the sequence. This equals to, we can just multiply the top and bottom by 10 to the power of k, so this equals to, well, 1 over 2k times by 10 to the power of k, divided by 10 to the power of k, and then this equals to, just move this over, just shift these around, so this is going to be 1 over 10 to the power of k, and then this is going to be 10 over, 10 to the power of k over 2 to the power of k, and you could just take the k's out, so 1 over 10k, same thing as writing it as 10 to the power of k over 2 to the power of k. Like that. So I'll just put it together right here. So 1 over 2 power of k, this equals to 1 over 10 power of k times this is you actually forgot this, just move these out. It's the same formula as the other side. So this is going to be 10 to the power of 2 over k, like that. Put these together, 10 to the power of k, and circle this like that. Yeah, so going further, so in the earlier section we had ignored the 1 divided by 10 to the power of k, since it doesn't affect the Vortex Math pattern or Vortex sum pattern. So yeah, we just define it as not being included in the Vortex sum. But if we include the full term, we get the following halving formula in base 10. Yeah, halving to, let's go, alright, halving to multiplication. Yeah, in base 10, which is again 10 over 2 equals to 5. So that means you're going to multiply by 5. So this 10 over 2 is going to be 5 in base 10. So we could write this as 1 over 2 to the power of k. This equals to, let's write the full term, 1 over 10 to the power of k, times it by 10 over 2 k. This equals to just 5 in base, this equals to 5 in base 10. So this is going to be equal to 1 over 10k times by 5 to the power of k. Which equals to, well, we'll write this as this, 5 over 10k, and this is going to be k like that. Yeah, so now if we plot this this on the vortex circle, plotting this all out, we get the following vortex circle by including these 10 to the power of k there. So we're going to have here, if we start off at 1, so 1 goes down here, this goes to the 5, and this 5 right here, I'm going to put this beside it. V equals to, well, this is going to be 5 to the power of 1 over 10k. I'm 10, 1. And this number 1, we're going to write this as equaling to just 5 to the power of 0. And this is going to be 10 to the power of 0. So that's the starting point right there. Goes over to here. And then this 5 goes to the 7. So 5 times 5 is 30, 5 times 5 is 25, which is v equals 2 plus 5 is 7. So this is going to be our v equals to 5 squared, and then this is 5 squared over 10 squared, and then the 7 goes over to here. 7 times 5 is 35, 3 plus 5 is 8, and so then v equals 2. This is the same as doing the vortex sum of this one, and excluding this 10 over 3, so 5 cubed over 10 to the power of 3, and yeah, we're just including that for the just for the notation. So we'll see the pattern for the powers of 10, and then this goes around like that, and this is our v equals 2, and this is just a mirror image of yes, this 1 goes to the 5, 8 has to go here, 4 is v equals 2. This is going to be the same as if you multiply this 5 by 4, power of 4, and then take the vortex sum. And then this is going to be our 10 to the power of 4. And then the 4, half that goes to the 2. This, or you could have done the, just do the multiplication. So this is going to be 5 to the power of 5 over 10 to the power of 5. And then this one goes, it goes to the 1, which was, it starts at 5 to the power of 0 divided by 10 to the power of 0. Or it could also continue with the series. So that's going to be, well, v equals to, it's all the same thing. This is going to be 5. I'll put this in green, 5 to the power of 6 over 10 to the power of 6, like that. And then the next one is going to be, once you go backwards again, it's all going to be following the same thing. V equals to 5 to the 7, like that, 10 to the power of 7. Likewise, this one's going to be v equals to 5, 8 over 10, 8. And this one's going to be v equals to 5, 9, 10 to the 9. And then goes down here, v equals to, they're all equivalent, 5, 10, 10 to the 9, 10 to the 10, like that, and then it goes up to here, v equals to 5, 11. This is going to be 10 to the 11, and then the next one is going to be, let's put this as, a new one right here. This is going to be just our 5, 12, 10 to the 12, like that. Yes, and now note the patterns here. Notice that the powers of 10 cycle every 6 powers. So you have 5 to the power of 0 is the first one, then goes to 5 to the power of 6 and 5 to the power of 11. This one 5 to the power of 5 goes to 5 to the power of 11. This is 5 to the power of 12, not 5 to the power of 11. Yeah, we're looking at the powers of 10. So either or, the powers of 5 or the powers of 10, they all go to they all go by 6s. So 0, 6, 12, 10 to the power of 5, it goes to 10 to the power of 11. 10 to the power of 8 goes to 10 to the power of 6. 10 to the power of 2 goes to 10 to the power of 8. And 10 to the power of 3 goes to 10 to the power of 9. These are all separated by 6. So all these powers separated by 6. 1, 7, 4, 6. And now let's plot the corresponding powers of 10 on the vortex circle. So we have the 9, 3, 6 like that. And now let's put the powers of 10 only. So 10 to the power of 0 is over there. And then the next one is going to be over here, 10 to the power of 1, like that. And then 10 to the power of, let's just draw this like that. 10 to the power of this one, that's the 5, goes to here, 10 to the power of 2. And now this one goes over to here, 10 to the power of 3. It's increments by 1. And then this one goes down here to the 4. This is going to be 10 to the power of 4. This one cuts to the 2, 10 to the power of 6. Like that. So I mean 5, we just skip one. And then the next one here is going to be, this goes up here. This is going to be 10 to the power of 6, like that. And then, yeah, obviously, so then it's going to go 10 to the power of 12, etc., dot, dot, dot. So 10 to the power of 6 goes over to here. And this is going to be 10 to the power of 7. Yeah, it's separated by 6. This is going to be 10 to the power of 8. This is going to be 10 to the power of 9. And this one's going to be 10 to the power of 10. They're all separated by 6. This one's going to be 10 to the power of 11, separated by 6, and goes to the 10 to the power of 12, like that. Yeah, so note that these increment by 6s, the powers on each side. But then if you compared with this mirror pair, they're separated by 3. So 10 to the power of 0, 10 to the power of 3, 10 to the power of 6 is 10 to the power of 9. And likewise, 10 to the power of 2 is 10 to the power of 5. So they're separated by 3s. So yes, I know the symmetry in that the left and right mirror pairs are separated by every third power. So if we have 10 to the power of 0, we have 10 to the power of 3. And then, likewise, the next one, 10 to the power of 6, is separated from that because it cycles back to it. This is going to be equal to 10 to the power of 3 plus 3. So separated by 3 on this one. And now this 10 to the power of 2, yeah, it's separated by a third power as well. So this equals to 10 to the power of 5, which equals to 2 plus 3. 10 to the power of 2 plus 3. Like that. And then the next one here, 10 to the power of 1, this is 10 to the power of 4. This equals to 10 to the power of 1 plus 3. And yeah, these are the pairs. Let's put a dashed line for the pairs. Pairs like that. All the way to here. And then there's the pairs like that. And just write down pairs or pair. Alright, so now, yeah, so we see that it's separated by thirds. And that's pretty much the bulk of the powers of 10 pattern. So let's list the number of zeros associated in this pattern. So we have 10 to the power of 0 is defined as equal to 1. Let's put this like this. Here, let's put it by definition, just for math terms, because when you're dealing with this 0 there, 10 to the power of 0, it's usually, usually always defined as equal to 1. So now 10 to the power of 1 equals to 10. And then 10 to the power of 2 equals 100. 10 to the power of 3 equals to 1,000. You could use a built-in calculator, press space, 1,000, and there's a comma there. So 10 to the power of 4 equals 10,000, 10 to the power of 5 equals 100,000, and then 10 to the power of 6 is 1 million, and the vortex cycle repeats it. So 10 to the power of 6 right there. Then the next one's going to be, you add another 0. So 10 to the power of 7, you have 10 million, and then 10 to the power of 8, 100 million, and then 10 to the power of 9, 1 billion. Like that. So yes, fascinating stuff. And then there's dot, dot, dot cycles for the next 3 pairs, and then so on. So note that the typical convention of adding a comma every third 0. So if you have 1, 10, 100, this is just usual convention. Then we have 1,000. Yeah, so comma right here indicates cycle repeats. So the 3 zeros. So we have, yeah, and notice that it repeats back to the 1. Then you add another 10, and then we have 10,000. Yeah, so we have 10,000 and 100,000, and then at 1 million is so the comma indicates we repeat by adding another 3 zeros. So basically we go 1, 10, 100, and then we repeat back to the 1. 1, 10, 100, and then all it does is state initially we have, this is just 1, 10, 100, then the next one's going to be 1,000. So 1,000, 10,000, 100,000, and then 1 million, 10 million, 100 million, and then 1 billion. So thus, adding a comma after every third 0 matches the symmetry of the mirror pairs, which are also separated by every third power. Thus, we obtain the expected powers of 10 vortex pattern, which is right here. I have the cycle already drawn in, and there's the 9, 3, 6. And now we're going to have a 1. So that's the that's the starting number 1 there. and then the next one here, it's going to go down here. This is going to be our 10, and then it's going to go over to 100, like that. And then the next one is going to repeat after the third, so this is going to be 1000. So 1, comma, dot, dot, dot. So in other words, this lines up. We'll put this in like that. This lines up with that. And then the next one is, it's going to be 10,000. So let's go cycles down here. 1, 2, 3. And there's the in the red. So this is the 10 and matches with that one. And the next one is going to be 10 to, this is going to be 100,000. 2, 3, and then the next one here is going to be 1 million. Let's put a, well, we can't put a comma. 1 million, and then we have, yeah, just 1 million like that. And yeah, the cycle keeps repeating, so I'll have the 0 like that. I mean, circle the 1, circle there, circle the 100, and the 100's right here. So yeah, it just keeps repeating. This is going to be 1,000, the next one's going to be 10,000, and so on. So it's going to go pretty much forever. So then dot, 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 next one as well. And then the next one here, this one's going to be, we'll just write this one here, 10,000. 10 million. 1, 2, 3, 2, 3, like that. And circle the 10. And yeah, dot, dot, dot. So the next pair as well. So yeah, it's all going to go. Then next one's going to go to 100,000, and then 100 million. This is going to be 100 million, and the next one's going to be 1 billion. Yeah, so if instead we used a different convention, because this convention of adding a comma every third zero matches up with the vortex circle, which the powers of 10 are separated from the mirror pair every third, or the full cycles are separated every sixth one, like that. So 10 to the power of 0 to 10 to the power of 6, or you have 10 to the power of 3 plus 3, and this is going to be 10 to the power of 3, so it's separated by 3. Yeah, separated by 3 on its mirror, or separated by 6 on its full one. Yeah, but so if instead we had a different convention, yeah, if we use the convention of adding a comma every second 0, then it would not match up with the vortex circle. So if we had 1, 10, and then 1, comma, 0, 0, that's 100, but this case is going to be, actually, yeah, so this will just be called 100, I guess. So comma indicates cycle repeats, and then the next one's going to be 1000. Yeah, so 1000 or 1000. The next one's going to be 1, whatever this would be called. There's going to be 4 zeros. That's our usual 10,000 now has 2 commas. And the next one's going to be over here, 10, and then 0, 0, then 0, 0. It looks like binary, but it's not. So this one's going to be, next one's going to be, this is 3 zeros, 6 zeros. That's 1 million, but we're going to write this as 1, and then 100th, or whatever you want to call it. So yeah, 1, 0, 0, and then 0, 0. So if we had that every second comma, we're going to have our 9, 3, 6 circle like that already drawn in. We're going to have a 1. And the next one's going to go down to 10. And the next one's going to go down to, well, 1, comma, 0, 0. And then after that's going to be 1, 10, 0, 0. And notice that these don't match. And the next one after that's going to be 1, 0, 0, 0, 0. And then after that's going to be 10. 0, 0, 0, 0, and then after that's going to be, well, it's going to be 1, and then comma, 0, 0, and then 0, 0, and then 0, 0, like that. Yeah, that's how many? That's 6 zeros, and this is our 5 zeros, 6 zeros, and 4 zeros, 3, 2, 1, and yeah. So these don't match up. So the 1, there's a 10, so they don't line up, and then when we have a 10, we have a 1. So it's a different pattern, but it's not the matching up one. So if we have a 10 here, we get a 1. And likewise, there's a 1 there as well. And there's a 10 there. And yeah, so these don't match up. I'll write 10 versus 1 don't line up. So yeah, note that the convention of adding a comma every second 0 doesn't line up with the mirror pairs for the base 10. But we can still make this new comma convention match up by changing the base number system, such as the base 6 number system, in which case 10 divided by 2 is equal to 3, or halving becomes tripling. So in other words, what we'll have here is this 1, I'll put this in red, Let's put that in red. So 1 divided by 2 goes to the 3, like that. This is 1 divided by 2, and we can just write that down right here. So 1 divided by 2 is equal to, or in general, 1 divided by 2k is equal to, this is going to be 1 over 10. K times it by, number our formula, it's going to be 10 over 2. K, again, this is base 5. This is base 6, so this equals to 3. So this is going to be 3k over 10k, like that. Yeah, so we start off at 1, and then half it is going to go over to here, which is just equal to 3 over 10 power of 1. And this v equals 2, and then it goes up to, so the, halving it goes here, and then this halving it goes to, well, just multiplied by 3. 3 times 3 is 12. Yeah, and then we could do 12 mod 5. Actually, 3 times 3 is 9, and then, so 3 times 3 is 9, and then 9 mod 5 is 4, so it goes up here. I'm just going to put the, and you could also go from here. This is a mirror pair of this one, and it's the reverse of doubling. Or you can just look at this one, it's a mirror pair of this one, 2 goes over to here, so that's halving. So this one has to go over there, and then likewise the 4 divided by 2 just goes to the 2, like that. So that's the pattern. And then this 4 is v equals to, well, you put it on this side, so 3 to the power of 2 divided by 10 to the power of 2. And this goes here. This 2 is the vortex sum of, taking the vortex sum of this one, 3 over 10 to the power of 3. And here, just change up the colors here. So that's the formula for base base 6. Mod 5. So now this the next one's going to go over to here. This is going to be this is the same thing as writing 3 to the power 4 over 10 to the power 4, like that. Or the starting one is also, remember, that's also equal to 3 to the power of 0, 0 over 10 to the 0, like that. And so 3 to the 0 separated by 2 from this mirror pair, and then also look at this 3 to the power 4 separated by 2 over there. And likewise, you draw the commas in the correct place. So this one goes to here. This is halving. Halving goes like that, and then this goes up here. Now we'll do the commas, and then this goes back here like that. So this starting one is our starting one. Now the next one's going to be 10, 0 if you just include the powers, and then the next one's going to be 10. So 10 comma or 1 comma 0. So there's 2 zeros on this one. That's 1 comma, and then the next one's going to go down to 10 comma, and then the next one over here is going to be, well, a 1 0 0 comma 0 0, like that. And again, notice how they all match up. So this I'll just draw this in green. So this matches up with this and this. And this matches up with this. So yes, matches up. Let's put that here. Oops. Or just fix that up. I don't know why it keeps jumping. So anyways, fix that up, just write matches. So 10, 10, there's a 1, 1. And they all match up too. Let's say match. And note also that the base 10 and base 6 systems are, quote, synchronized with the doubling and halving patterns. Thus there's only a one-time mirror reflection before the full cycle, when starting from 1. So before the full cycle repeats. So for example, here it just jumps in once. It goes 1, 2. This is synchronized with the doubling pattern. This is 2 was part of it, as similar to the 10 is part of it as well. So 1, 2, 3, and 4 over here. So this is the 4, or this is the let's go back to the number one. Let's go back to the normal pattern there with the 1, 2, 3, 4, 5. So all the way over here, yeah. So this is synchronized with it. So this just mirrors once. So it's synchronized with the halving or doubling. So 1, 2, 4, right there, and it goes to the 8. But if we had something that didn't synchronize, what we could have is something very, very messy. Yeah, so base 10, base 6 are synchronized, unlike the earlier base 12 number system, which is a lot, quote, messier when you're halving or doubling. It's not synchronized. So a recall here just copied it from earlier. So this is the halving pattern goes to 1 over 6. No, it goes 1 goes to 6 and so on. And now if we draw our draw our pattern right here. This is first let's just write this here. This is the halving is going to equal to 1 over 2k equals to, in this case, is going to be this is just going to be, let's write this fully. It's 1 over 10k times 10 over 2k, like that, and this equals to this is going to be equals to 6 for base 12. So that's going to be 6k over 10k, and we're just going to ignore that. Just include only the power. So this 1 is just power of 1. The next one's going to be, well, power of 10, and then the next one it goes over to the 3. So it goes to the 3 right here. So we're going to have a power of 100. So yeah, notice it gets a lot messier. Then the 4 goes over to here. Let's add a comma right like that. Yeah, and then the 7 goes over to the 9. Which is going to be a 10,000. Yeah, it's going to be a 10,000. And then the 9, the 10 goes over here. It's going to be 100,000. And then, let's see what happens here. The 10 goes down to here. This is going to be 1 million. So yeah, it's not lining up. And to be 1 million. And then the 5 goes to the 8, which is going to be a 100,000. I mean, 100 million, yes, it's going to be, this goes over to there, it's going to be 10,000, actually, 10 million. Let's put a 10 million there. Then the 8 goes to the 4, which is 100 million, like that. So yeah, it goes back and forth many times. So then the 4 goes back to the 2, so this is going to be 1 billion. And let's do another 1, 2, 3. Here's made this smaller and shrunk it, and just box that in. Alright, and now the 1 over here, the 1 billion goes to the 10 billion. 1, 2, yes, so it goes from 1 and 10, so it doesn't even alternate. Yeah, it alternates with its own self. And this is going to be 1, 2, 3, and let's just double check we had it all right. This is going to be 1, 10, and then goes to 100. 3, and then 3 goes into the 7, 1,000, so that's correct so far. And the 7 goes to the 9, that's 10,000, and the 9 goes to 10, 100,000, and then the 10 goes to the 5, 1 million. This goes to there, 10 million. This 5 goes to the 8. Then 8 goes to the 4 is 100 million. 4 goes to 2 is a billion, and this goes to 10. It goes to the 1 is 10 billion. So yeah, so it's a lot messier. And yeah, it doesn't line up. 1, 2 to 10 doesn't line up. Then you have 100 and you have a 10, and so on. And you have a bunch of these inside. So there's no. It's not as simple as these ones. So compare that with the base 6 and base 10, which were much simpler, and they line up. So the 10 matches there. Yeah, so the 10 lines up, the 1 lines up, and so on. And then for the base 10. For the base 10, we have, so the 10s line up, 100s line up, 1s line up, and so on. Yeah, so thus synchronization and the convention you're using for the commas govern how they reflect, and so on, when you're doubling or halving. Yeah, I mean, when you're halving, and then you only consider the powers of 10 that you initially ignored in the vortex sum. It's just fascinating stuff. Alright, so now let's continue further. Now look at general division to multiplication vortex conversion as opposed to the just a halving to multiplication that we were dealing with. So although we have focused on halving, which is just a specific type of division, i.e. divide by 2, we can generalize to the division of any integers. For example, in base 10, if we divide by 5, then we expect it can be converted into a multiplication of 2. So for example, if we have 1 divided by 5, we could do the exact same thing as before. We just multiply top and bottom by 10, 10 over 10, and then switch these up. This equals to, this is going to be a 1 over 10, times it by a 10 over 5. So in other words, we've converted this 1 over 5 as now 1 over 5 division as a multiplication of this 10 over 5, and then if we look at the powers of it, it's going to be 1 over k. 1 over k equals 1. Etc. So we could write this or 1 over 5k is equal to 1 over our 10k, and now we have a 10 over 5, like that, to power of k, and just circle this. Yes, and where again the 1 divided by 10 power of k does not affect the vortex sum, so it doesn't affect it. So for taking the vortex sum, this would just be equal to v equals to over here, 10 over 5, okay, like that. Yeah, and likewise, the division 10 divided by 5 depends on the number system, and for the base 10 system, it is equal to 2. So 10 divided by 5 is 2. So we could write, just go right here, base 10. This division 10, where the 10 is a placeholder, divided by 2 is equal to 5. I mean, divided by the opposite of it, actually. Let's fix that up. I mean, 10 divided by 5 is equal to 2. So it's opposite of the doubling goes to multiplying by 5. So in other words, we have 1 over 5k, which equals to 1 over 10k, times it by, this is going to be our 10 divided by 5. That equals, so let's put it for completeness, 10 over 5k, like this. This equals to 2. This equals to 1 over 10k times by 2k, like that. And again, this doesn't affect vortex sum, doesn't affect. Yeah, this doesn't affect vortex sum. Just type it all there, and then then this means it's v equals to 2k. Yeah, and you could sum it up or summarize it as here: 1 over 5k. V equals to 2 to the power of k. This is vortex sum, like that, which we have to reduce this one further. Yeah, and I want to make a note as well. So in both cases, a division, and again in base 10, 10 divided by 2 and 10 divided by 5 yielded an integer or whole number, and in fact is preferred. Yeah, so we got a whole number. We can do vortex math. We can define a division much easier than if it didn't have a whole number. And these would be, as expected, reverse of each other, which is just, this is just halving. This is just going to be, division by 5. Actually, no, these aren't. No, actually, they are, because this one is a halving, and then this 1 over 10 divided by 5 is equal to doubling. So that's 2, which is the reverse of halving. So thus, in general, if we have a division of d, then it can be converted into a multiplication of 10 divided by d, and whose value depends on the number system. Yeah, so what you have is a 1 over d, or 1 over d to the power of k. This would just equal to 1 over 10 power of k, or in this case, this is just multiplying, dividing once. Then we're going to have it a 10 divided by d, like that, and again, just leave it like that, where the vortex sum is equal to 10 over d, like that, because this doesn't count as the as part of the vortex sum. Or you could write this again, or 1 over dk, and yes, in general, as part of the series, 1 divided by 10 power of k times it by 10 over d, k, like that. V equals to 10 over d, k. And I'll box these two general ones out, and this one like this. And yes, vortex sum doesn't account for this 1 over 10 power of k, and so on. Yes, and as usual, which this right here can be written as, or written in its equivalent base 10 notation for convenience, again, because every calculator is base 10, and every counting, default counting system is base 10 and in most calculators, and this OneNote and my brain. So for convenience, where n is the base in base 10 notation. So we could write this as 1 over d power of k equals to 1 over n power of k times it by 10 over, not 10, so this is the placeholder, n over d, k, like that. Yeah, and for example, using the base 12 number system, a division by 3, or division of 3, actually I'll write that better, a division by 3 yields the same vortex sum as the multiplication 12 divided by 3 is equal to 4. That's number, this is going to be n. Yeah, 12 is n, so n divided by 3 is going to be 4. So in other words, we can go from here, so we'll write this, draw this out in red. So here's the base 11 system, so we start off at the 1. Yeah, so if we were going to divide by 3, this is the same thing as multiplying by 4. So in other words, we're going to go straight to here, where this is the 4, like that. Yeah, so 1 divided by 3 would go to the 4, would be just 10 divided by 3 equals to 4 by definition in base 12. So yeah, or 12 divided by 3 is 4. Now the next one is, this is 1/2 like that, and it's equivalent to, there's 1/3. Let's put it like this, yeah. 1/3, or you could also do times by 4, or times by 4. It's the same thing. So times by 4, or put or 4x, like that. So times by 4 or 1/3. And then this is going to be here, so times this by 4, this v equals to 16 mod 11, which equals to 5. So in other words, this is going to go straight to here. Circle this, and now the 5 is going to be times by 4. Yeah, 5 times 4. It's multiplied by 4. This v equals, vortex sum is going to be, well, 4 times 5 is 20 mod 11, like that. This equals to 9, like that. So this jumps all the way to the 9, like that. And now the 9, well, we can easily solve this one. This is 9 divided by 3. This is, yes, we can either go 9 divided by 3 equals to 3. So it should go straight to here, like that. Or you could just multiply it by, or you can multiply by 4. Or you can go 9 times 4, which equals to 36. So v equals to 36. Mod 11, and then mod 11, that's going to be, 11 goes into it 3 times, so 33, and then there's remainder 3, so equals to 3, like that. So yes, that's correct as well. And then the 3 right here, you can, this goes back, 3 divided by 3 is going to go, well, just, 3 divided by 3 equals to 1, so it just goes straight back to it, and let's just put an arrow like that. Yeah. Like that, or you could also multiply by 4. V equals to 12 mod 11, 11 difference is just 1, like that. So yeah, it's fascinating stuff. And yeah, this is pretty amazing stuff, and it deserves a hashtag amazing. Yeah, hashtag amazing stuff. Whoops. Yeah, like that. Yeah, pretty amazing stuff. And yeah, all this glitches, this OneNote application, I might have to get a new Surface Pro. Anyways, let's continue further. So dealing with, quote, irregular division. So in this section, we will examine several examples of, quote, irregular division scenarios which depend on the base number system and are not as clear-cut as previous division scenarios we have thus far examined when looking to obtain vortex sums. So let's look at this example here. Example 4, halving in base 5. So recall from the previous section titled Vortex Halving Doesn't Work for Odd Base Number Systems, in which we went over halving of the odd base 5 number system. So if you have base 5, let's just half it right here. So base 5. So we have 1 over 2. Is going to be equal to, well, you could do our usual multiply the top and bottom by 10. This is a placeholder notation. This equals to, switch these around, 1 over 10 times it by 10 over 2. And then this equals to, yeah, if you want to divide it, because this doesn't divide cleanly. So 10 divided by 2 does not divide cleanly. So we could write this in just the base 5 unique digits. So we could write this as 1 over 10. Times it by, this is going to be, well, 4 plus 1 over 2. So 10 is just 4 plus 1 in base 5. And now, yeah, we have a scenario here where the 2 divides into 4 evenly into 2. So this would be 1 over 10 times it by, well, we're going to have a 2 plus a 1/2. Like that. Yeah, so thus we have a scenario right here, thus 1/2 is equal to, well, 1 over 10 times it by 2 plus 1/2. So in other words, these are equivalent in there. If we have this 1/2 in there, then we have the 1/2 in there again. So we have a continuous loop. Yeah, so thus we have a continuous loop since the term 1/2 or 1 over 2 occurs inside the formula for itself. So yeah, there it is, and there it is again. Interestingly, if we feed back the 1/2 term, we get a continuous repeating pattern. So if you write this all, just expand this all. It's basically long division in a different base unit, or just manual division in a different base number system. So base 5 as opposed to our base 10, which we're accustomed to. So this equals to 1 over 10 times it by 2 plus 1/2. Let's just expand this out. So multiply this 1/10 inside. So this equals to 2 over 10. Yes, like a 2 over 10 plus, and then we have a 1 over 10 times it by 1/2, like that. So we just expand this out of the bracket. Yeah, and then where this term right here, we could just feed this one back inside it. So to feed this term inside the other term right there. So let's just feed back in. So this feeds back in there. So we get 1/2 is equal to 2 over 10 plus 1 over 10 times it by, and then we have a giant feedback loop, so 1 over 10 times it by 2 plus 1/2, like that. Yeah, so now if we expand this inside, this is going to be equal to, let's just put it over here, so this is going to be equal to 2 over 10. So now this 1 over 10 times it by 1 over 10 is 1 over 100, and multiply that inside further, or let's just expand this here and then do the second step after. 2 over 10 plus, this can be 1 over 100 times it by 2 plus 1/2, like that. Yeah, so now we have then multiply this 1 over 100 inside, so we get a plus 2 over 100, and then plus, this is going to be plus, yeah, fix that up. So now this 1 over 100 goes over there. It's going to be 1 over 100, and now we have that same 1/2 there. So 1/2 never goes away. Yeah, so we have this term right here, it just never goes away, so we always feed this back in with this term. And then what we're end up going to get is, you can see the pattern, is this going to be equal to 2 over 10 plus 2 over 100 plus, and then it's going to be 2 over 1,000, and then so on, plus dot, dot, dot. And in decimal notation, we're going to get 1/2 equals to this is going to be 0.2, 10 over 10 is 0.2, and then this is going to be, well, plus 0.02. So we'll just add another 0, add another 2, and this is going to be another 2 like that. And then it's going to go dot, 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 continues, so dot, dot, dot. This is again in base 5. So yeah, this is just equal to, let's put it over here for completeness, 0.2 plus 0.02 plus 0.002, and then plus dot, 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 and add up all the terms. And yeah, we just get this 0.222 repeating nonstop. Yeah, so now when we look at the actual quote value of the division 10 divided by 2, we discover that the repeating decimals are a result of the number system itself. So for example, 10 divided by 2 in base 5, this is equivalent or equal to 5 divided by 2 in base 10. But if you're writing in base 10, the division 5 divided by 2, this equals to 2.222. But in base 10, this is 5 divided by 2 is just 2.5, so it doesn't repeat. So it's fascinating stuff. This one is 0.222 continuously, and yes, absolutely fascinating. And yeah, you could just go, 5 divided by 2, space equals 2.5 with the calculator. And in fact, we can calculate this out by just going over here to just a random base calculator. So change the base to 5. First number is 10. 10 divided by 2. Calculate 2.222, and so on. So yes, just a quick double check of our work. So yes, this is some pretty fascinating stuff indeed. So now the question we have to ask is, what quote vortex sum should we assign the repeating fraction 0.2222? Should it be 2? Because it's just the 2 everywhere. And how do we connect it to the vortex circle? So remember the base 5, you have that break in the pattern from 1 to 4, because you can't get there. Because here's a doubling, 1 doubles to 2, 2 doubles to 4, and then 4 halves to 2, 2 halves to 1, but there's no way of connecting these two, because 4 times any integer is always 4, and 1 divided by 2 is 0.2222, which is, we don't know which one it is. So hashtag many questions. So yes, if you have a way to define it, let me know, a coherent way to define it. Alright, so now let's look at another example. It's example 6 of the overall example series, but the second example of this irregular division. So example 6, converting division by 4 to multiplication by 7 in base 10. So another quote irregular division is one that we are actually able to convert into a multiplication, without any repeating decimals or so on. So consider the division 1 divided by 4 in base 10. So we have base 10, so 1 divided by 4. Do our usual multiply top and bottom by 10, times by 10 over 10, switch these around, this equals to 1 over 10, times it by 10 over 4. And now here what we could do is write this 10 into a multiple of 4, which is 8. multiple of 4, so it's going to be 1 over 10, 8 plus 2, just to simplify it out. And so we can divide this out. Now 4 goes into 8 twice and goes into 2. It just becomes like this. So 1 over 10 times it by, this is going to be 2 plus 2 over 4. This one right here can simplify to 1 over 2. So this equals to 1 over 10 times it by 2 plus 1/2, like that. So this 1/2, we have this, but this doesn't this doesn't repeat, because we can actually calculate 1/2 of 10. So yes, the difference in this case is that 1 divided by 2 is equal to 0.5 in base 10. Thus, we don't have a continuous loop. And we can write this out as, well, 1 divided by 4 equals to 1 divided by 10. And this is going to be 2 plus 1/2, which equals to, just expand this out. So this is going to equal to 2 over 10. And then times it by, or 2 over 10 plus 1/2 is going to be 0.5. And then divide this by 10. So this is going to equal to 0.2 plus 0.05, which equals to 0.25, like that. Yeah, so 1 divided by 4 is just a quarter, or 0.25, but since we are interested in the vortex sum, we can convert a division by 4 into a multiplication by 7, or even 25. Remember, that's vortex sums. There's 25, you could add the 2, is 2 plus 5 is 7. Or you could just do it more formally, slightly more formally. So 1 over 4, this equals to 1 over 10 times it by 2 plus our 1/2. But now we have a 1 over 10. Let's convert that to 10 over 2. So we could do that by, well, multiplying this again by another 10 over 10. So that we're not changing anything. We're just dividing it by another 10 times by 10, because the 10 divided by 10 is just 1, so we're not changing anything. And we're going to write this as 100. So 10 times 10 multiplies together like that. And then this is going to be, so then multiply this top inside. So you multiply this one just with this 10 and this one inside. So this is going to be 20, just basic arithmetic. Yeah, let's write this again. So it's going to be 20 plus 10 over 2. And we know that this doesn't affect vortex sum. It's right here, because we're only interested in the vortex sum, doesn't affect vortex sum, like that. So then basically we have this this right here. This one we know is equal to 5. Yeah, so we could have 1 over, yeah, we'll get rid of that 100. So this just becomes 20 plus 5. Yeah, or V equals. V is a vortex sum, 20 plus 5, and this side there you can either go 25, but then notice the digits, they never add up. They never combine, so we could just go V equals 2 plus 5 equals to 7, like that. Yeah, so you can just start there. So it's a multiplication by 25, like this, or reduce it even further to a 7. So yes, so in single digits, and yeah, that is the correct one. We could also do it in a different way, or we can go 1 over 4. So start off at this point, V equals to 20 plus 5, and then start doing our usual, writing this as 2 times 10 plus 5. And then this equals to, this one right here is going to be our 9 plus 1. So this can be 2 times 9 plus 1 plus 5. And now multiply this inside, and then we're going to get this equals to a 2 times 9 plus a 2 plus 5. Where again, this is the factor of 9. And this one is the remainder, like that. And that's, so in other words, this V equals 2, just get rid of it, 2 plus 5 equals to 7. So yes. So yeah, you can do either or, fascinating stuff. So yes, let's write that down as well. Fascinating stuff over here indeed, guys. So we can see this visually on the vortex circle, and similar to the halving pattern, similar to halving. Yeah, similar to halving. Dividing by 4 is the reverse direction of multiplying by 4 when we're dealing with vortex math. So let's look at here. So here is, we start off at 1. So 1, and then we're gonna divide this by 4. is going to be the same as multiplying by 7. So we go across here. This is going to be 1 over 4 or multiply by 7, like that. So 1/2 or that. So we should get here. And likewise, or let's just solve this one first. So we can do it many ways of getting the vortex sum. So 1 divided by 4 is equal to 0.25. V equals 2, just ignore the decimals, 2 plus 5 equals 7, like that. And now if you multiply this by 4, so 7 times 4, to get the reverse direction, this is going to be equal to, or actually put the 7 times 4 over here, so we could go 7 times 4, this equals to 28, V equals to 2 plus 8 equals to 10, V equals to 1, like that. And just move it over there, this is going to be times it by 7. Times it by 4, like that. And so it's a reverse direction. And now the next step is, well, 7 divided by 4. 7 divided by 4 is same as 7 times 7. So it should be actually going across here. So it's going to go to the 4 because 7 times 7 is equal to 7 times 7 is 49. V equals to 4 plus 9. And remember, 4 plus 9 is a factor of 9, so it's just going to equal to the 4, or you could just keep going. 13, V equals 1 plus 3 equals to 4. So so you could have just stopped there. Anyways, this equals to 4. Or we can go in reverse direction, so from here it should go straight to here because 4 times 4 is equal to 16. V equals to, again, it's base 10, so we can just easily sum up the digits. Equals to 7, like that. And then lastly, 4 divided by 4 is just, well, 1. Just go straight up there. So we are dividing by 4, like that. And that's 1/4. And it's going to be the reverse direction. 1 times 4 is just straight here. So this is our times by 4. And this is, 4 times 1, like that. And likewise here, our 4 divided by 4 is this part right here. 4 divided by 4 equals 1. So yes, many ways of going around, and it always goes back to the same thing. So yes, that's some very interesting stuff. So now let's continue further in this epic long video. So now let's look at another example. This is going to be example, this is actually example 6. I got these mixed up. So this is example 6. This one is supposed to be example 5 of the overall document. Alright, let's keep going further. Alright, so now let's continue further in this example 6. So division by 7 in base 10 pattern. In base 10 gets this pattern. Get ready like that, then space, put the pattern here. So we get a 1, 4, 2, 8, 7, 5, and then starts repeating again at the 1 pattern. So in previous examples, I'll just erase this 1 there. In previous examples, the base 5 division 1 divided by 2 yielded an infinite repeating decimal. Or decimal number 0.2222, which doesn't have a clear vortex quote conversion, but for the base 10 division 1 divided by 4, we were able to convert it to a vortex multiplication of 7. Or right here, vortex multiplication. Conversion. In this example, the base 10 division 1 divided by 7 is not as clear in either respect. And you can see it's a combination of both. So if we have a 1 divided by 7, this equals to our usual, I'll multiply top and bottom by 7, 1 over 10, divided by 10, and switch over the bottom, like that. Switch these over, we get a 1 over 10, times it by 10 over 7. And now we could break this up into a factor of 7 here, or multiple of 7. So this is going to be 10 is equal to just 7 plus 3 in base 10. So divide this by 7, like that. So what we end up having is, now break this up, it's going to be 1 over 10, or just multiply it inside. Actually, divide inside. So 7 divided by 7 is 1, plus 3 divided by 7 doesn't divide evenly, so it's just going to be like that, a 3. Alright, so now expand it further, so we're getting a 1 over 10, times it by 1 is just 1 over 10, and then a 1 over 10 times 3 over 7, that equals to, we could write this as 30. Actually, no, we'll get to that after. This is going to be 1 over 10 times by 3 over 7. So we have a cycle back in, but it's not exactly 3 over 7. It's going to be 3 times 1 over 7, so you can put that back in. But we could do our usual multiply top and bottom by 10, so we get a 1 over 10, but on the other side. So 1 over 10 plus a, so keep in mind the pattern 1, 4, 2, 8, 7, 5. So it's going to be 1 over 10 plus a 1 over 10 squared, because we multiply top and bottom, times it by, now it's going to be a 30. Divided by 7. So all we did was multiply top and bottom by 10, like that. So now this right here, 30, we could divide that in, it goes in cleanly at 28, so that's 7 times 4 is 28. So you could write this as 1 over 10 plus, write this better, 1 over 10 plus 1 over 10 squared. Now we get a 28 plus a 2. Yeah, 28 plus a 2. Oops. Yeah, and then divide that by 7. Yeah, I think the OneNote's glitching because the file's getting pretty big. This video is pretty epic. So we have that. So 7 divided by 28 is just 4. So we can expand this out. This is going to be 1 over 10 plus 1 over 10 squared. And then we have a 28 divided by 7 is 4 plus a 2 over 7, like that. Yeah, so expand this further. We get a 1 over 10 plus a, now multiply this inside, so we're going to have a 4 over 10 squared, like that, and then plus a 1 over 10 squared times 2 over 7. Yeah, so we got the first two numbers, digits in our pattern, so 1, 4, 2, 1, 4, and now so we have a 1, 4. Now we keep doing the same thing. We're going to get a, let's write this all out, and you can see the pattern arise. Yeah, so this equals to, we're going to get a 1 over 10 plus a 4 over 10 squared. And then the next thing, we're going to do the same thing, multiply top and bottom of this by 10. So that we get a 1 over 10, let's move this away, 1 over 10 cubed times it by 20 over 7, like that. And now to save time, so this 20 is the same thing as writing 14 plus 6. Yeah, which 14 is a multiple of 7, which is, 2 times 7 is 14. So then you divide that out, we're going to get a 1 over 10 plus 4 over 10 squared, plus now we get a, so the next one's going to be, this is going to be divided by, 14 divided by 7 is 2, so you can see the pattern. And then multiply that inside, 10 over 3. Then plus, the same stuff right here is going to be, to follow the same thing. So we multiply it inside. So we have this right here, 28 plus 2, divide this out and separate it, so we get a 28 divided by 7. 28 divided by 7 is 4. So 4 divided by 10 squared, and then plus a 1, plus a 1 over 10 squared times 2 over 7, or just get it over here, 1 over 10 cubed times 20 over 7. So this is going to be 1 over 10 to the 4 times it by, and this is the remainder, so 6. The other one is 2 becomes 20, 3 becomes 30, and so on. And 1 becomes 10. Yeah, 1 is already shown there. So we're going to get a, this is going to be times it by a 60 over 7. Let's write it here, 60 over 7, like that. And now multiple of 60, just to save time, is 56. Which is 8 times 7. 8 times 7. This one is 2 times 7 there. So anyways, so we get a 56 plus 4. So then 8 times 7 is a new one. So we're going to have a 1 over 10 plus a 4 over 10 squared plus a 2 over 10 cubed plus a, this is going to be a over 10 4. So we repeat the same pattern, it's going to be 8, and then plus 1 over 10, 5, and the remainder is 4. So we have 4 times 10 times by 40 over 7. You see, you can see the pattern. 40, this one is going to be, 35 is the next multiple. 35 plus 5, and the multiple of this one is 5 times 7. So yes, you can see the pattern, where the patterns are rising 1, 2, 4, 8, 7, and then 5. Actually, I got this wrong. It's not 7. It's going to be 5. Yeah, let's just erase this. Yeah, this is actually 5. Yes, it's 5, then it's 7. Yeah, 8, 5, 7. Yeah, so this is going to be now, follow the same procedure, 1 over 10 plus 4 over 10 squared plus 2 over 10 cubed plus 8 over 10 4. And then plus, this is going to be 1 over, yeah, this is to the 5. 1 over 10 to the 5, and then, I mean not 5, this is going to be 5, plus 1 over 10 to the 6, times it by 50. So you multiply top and bottom by 10, and the remainder is 5, so there's going to be 50, and 50 breaks up into 49 plus 1. And now we repeat the cycle. This is going to be a 7 times 7. And then let's write this down one last time. 1 over 10 plus 4 over 10 squared plus 2 over 10 cubed plus 8 over 10 4. Yeah, hopefully you enjoy this exercise in algebra. And then plus 5 and 10 to the 5 plus, and then it's going to be 7 over 10 to the 6, like that. 5, 10 to the 6, and then we're going to get a 1 over 10 to the 7, yeah, times by, and the remainder is 1 over 7. Okay, so the cycle repeats again. I'm just going to circle this one right here. Yeah, cycle repeats. Actually, this is supposed to be a 1 over, yeah, so you multiply by 10, so like that, 10, or before doing that, just go 10 to the 6, and then remove that 1. So yeah, cycle repeats, and so on, and you start off from here, or you can just put it like this, or just write it as the following this pattern above there. So this is going to be 10. And yeah, so this cycle repeats. I'm just going to circle this and write cycle repeats. The cycle repeats. And then when you add these up, yes, the cycle repeats there, and then add these up in a decimal form. It's going to be 0.1. This is 0.04, so it's going to add up like that. Next one's 2, next one's 8, next one's 5, next one's 7, and then this is going to repeat, and you put a line above, overline like that for repeating, and the next one's 1, 4, 2, 8, 5, 7, and dot, dot, dot. It's going to keep repeating. Yeah, so thus we have a repeating pattern as opposed to just a repeating single digit pattern. This is repeating a full-on pattern there. So 1, 4, 2, 8, 5, 7. And yeah, so 1 divided by 7 equals 2. And you could put in the calculator here. Yeah, if I delete and press equals and then space, it automatically calculates to 1429. So it rounds up. So 1429, but it's actually over here. So it's actually 0.142857. Yeah, I always get the 7 and 5 mixed up. And then 142857, 142857, etc. And the repeating term is 142857. So the question is, what should we do with the vortex sum? Should we add all the terms of just one cycle? So in other words, 1 divided by 7, if we v equals to 1 plus 4 plus 2 plus 8 plus 5 plus 7, this equals 2. Yeah, this equals to, oops, let's go over here. Equals to 27, v equals to 2 plus 7 equals 9. So should we do that? Yeah, so put a question mark like that. So should we do that? 9, or just leave it like that. And then 27 mod 9 is 0, v equals to 9. Set it as 9. This would mean that 1 divided by 7 converts to a multiplication of 5, but then it means it is a factor of 9 and the vortex circle just goes right to the modulus. Right to the modulus, which also means that multiplication of 7 doesn't reverse to the number 1, but rather is always 9. So for example, if we start like that, if we have 1 divided by 7, v equals to 9, like question mark for example, and then this 9 right here, yeah, this 9 right here, actually I'll just put this in red, so that so now if we want to get the reverse of this one, the reverse would be times by 7, so then times by 7 just go back to itself. Yeah, so it does not reverse back to the 1, because 7 times 9 is just going to be a factor of 9, so it's always going to be the modulus. And basically, yeah, so times by 7, not reverse of 1 divided by 7. We have 1 divided by 7, v equals 9, etc. Yeah, so yes, multiplying by 7 is not the reverse of halving by 7 if you set that vortex sum equals to 9 based on adding the adding up the cycle, the digits of the one repeating cycle. Or should we just convert it to the multiplication of 4 to align with the previous example? Because we know that dividing by 4 is a multiplication of 7. So would the reverse be true? Dividing by 7 to be a multiplication of 4? Should we do that instead? And yeah, so those are questions that we can ask ourselves. But thus it is not clear what to do with a division by 7. Yeah, so thus it is not clear what to do with a division by 7, but let me know what you think if you got some better ways of doing this. So anyways, let's go one last example in this section. So example 7, summary of base 10 division to multiplication conversions. And here's just a summary of all of them. For completeness, let's catalog each division to multiplication conversion for the base 10 numbers 0 to 9. So 1 divided by 0 is undefined or infinity. V equals question mark. Because yeah, 0 goes into 1 infinite times. Right, so undefined. So 1 divided by 1 is just 1. 1 divided by 2... Yeah, 1 divided by 2 is equal to 0.5, which you could just write it as v equals to 5. So 1, divided by 2 it becomes a multiplication to 5. 1 divided by 3, you get 0.333, so we're not sure what to do with that. 1 divided by 4 is 0.25, which again, you can sum the digits of v equals to 7. 1 divided by 5 is equal to 0.2, and v equals to 2. So yeah, we could just convert. Divided by 5 is the same as multiplying by 2. Divided by 4 is same as multiplying by 7. And 1 divided by 6, you get a 0.1666, and you can calculate this as well. Space equals to, 0.6667, it rounds up, it's actually 666 like that, ... Yeah, so v equals to question mark. So 1 divided by 7, we get our 142857, and it keeps repeating 142857, v equals to question mark. And then interestingly, 1 divided by 8, we get 0.2, which becomes 0.125 right here. And v equals to 8. You could even just add up the digits. 1 plus 2 plus 5 is 8. So so that's interesting because dividing by 8 is the same as multiplying by 8. So we have right here, the last one, 1 divided by 9 is the usual 0.111, just the remainder repeating. V equals to question mark, so we don't know what to do with that. So only ones we know what to do is, well, 1 divided by 1 is the same as times by 1, and 1 divided by 2 is 5. Same as multiplying by 5. 1 divided by 4 is same as multiplying by 7. 1 divided by 5 is same as multiplying by 2. And 1 divided by 8 is the same as multiplying by 8. So the same process used in the previous examples can be used to determine the above calculations. Note that dividing by 8 is equal to multiplying by 8. So you have 3 divided by 8 equals to 0.375 equals to 3 plus 7 plus 5 equals 15. And then v equals to 1 plus 5 is equal to 6. Yeah, here's just an example. Here's just 3 divided by 8. You can calculate this out right here. So let's erase this. Yeah, as you can then you sum the digits up, you get 15, like this, equals 15, and add them up, you get 6. Or you could just go 3 times 8 is equals to 24, v equals 2 plus 4, and this is going to be equals to 6. So it's the same thing, hashtag nice. Alright, so now let's get on to the last section before the summary and conclusions, and that is polar number pairs and addition. So the quote polar number pairs are the same as the mirror pairs discussed earlier in the section Symmetry of number systems causes the doubling patterns, but instead of multiplication we focus on the addition. So consider the following Excel spreadsheet which increments each number of the base 10 vortex circle by itself and then calculates the vortex sum or mod 9 of it. So we have here's the vortex circle in base 10. So we have the 9 on top, 1, 2, 3, 4, 5, 6, 7, 8. So what we have here, if I increment we'll just start from here. So increment 1 by 1, we get 2. Vortex sum is just 2. And then 2 plus 1. So we have here 2 plus 1. This is just 1 plus 2. 1 plus 1 is this one, and then the next one is going to be, the next one you just add another one, so this is just going to be our plus 1 like that. So we plus 1, it goes 2, 3, 4, 5, 6, 7, 8, 9, 10, then the vortex sum is going to be accordingly at the bottom, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and it repeats back to the 1. But here we add 8, so if we add 8 to these, this is plus 8, so we get a 16, 8 plus 8 is 16, plus 8 is 24, plus 8 is 32, etc. And you take the vortex sum, you get a 7, 1 plus 6 is 7, 2 plus 4 is 6, and then we get a 5, so we get a, this is going backwards. This is plus 8 this way, plus 1 this way, but in fact this is actually going minus 1. So you're subtracting by 1 here, minus 1, all the way to the left. Likewise here we get 2, 4, 6, 8. So we're adding plus 2, and then you get this vortex sum of 2, 4, 6, 8, and this is 1. Then it's 1 plus 2 is 3, 5, 7, etc. But then if you go this way here, you're adding 7. So 14, yeah, this is going to be plus 7. Like that, we get a 7, and then this is 1 plus 4 is 5. And then 14 plus 7 is 21. 21 is 2 plus 2 is 3. So yes, we get that. But this is in fact going reverse. This is going -2. Like that. So yeah, this is going plus 2, this is going -2, this is going plus 7 there. In fact, this one's going -7. If you look at it, yeah, this is actually going -7. So you do 8 minus 7. Yeah, 8 minus 7 is 1. And here, likewise, if you get to the 9, you can see it. So 9 minus 8, etc. And then the next one here for the 3. Yeah, so the 3 is the same thing. You get a plus 3, so 6, 9, 12, 15, and then they always get to a 3, 6, 9, 3, 6, 9. So the 9 so 6 is vortex times 6, 9 is vortex times 9, 12 is 3, so 1 plus 2 is 3, and 15 is 1 plus 5 is 6, etc. And then this one going backwards is, yeah, this is 6, 6 plus 6 is 12, plus 6 is 18, so we get backwards here, plus 6, and this becomes the same thing as 6 minus 3 is going to be, 3. It's going to be, and then 3 minus 3, using the vortex circle, goes back to the 9. Notice 9 minus 3 is 6. And this one here is you're adding 3. At the same time, it could be considered as minusing 6. So you have the 9 minus 6 is 3. Yeah. And so I'll show that it's always, These are all, basically, if you're adding plus 3 here, you're going to be subtracting 3 here. If you're adding the mirror pair on this side, plus 6, it's going to be subtracting it on that side. So if you're going to look at just the positive here, so if you're adding to the right side, plus 3, it's the same as adding its mirror pair on the other side. And in fact, if you look at this, if it's minus 3 this way, that means it's plus 3 this way. So in other words, this whole thing is just a continuous loop, which I'll cover. Because here, if you plus 6, but then if you include this 9 there. If you include the 9 over there. Yeah, and then lastly we have over here, this is the 4, so we're adding 4, 8, 12, 16, you're adding just plus 4 this way, and likewise here you're going to be subtracting by 5, adding 5 this way. So we have 5, 10 plus 5 is 15, and then when you take the vortex sum, you get 15 is 6, then you get 20 is 2, etc. And the same as subtracting by 4, so you get 5 minus 1 is 4, and this one here is going this way. You can be subtracting by 5, because if you look at 8, 8 minus, if you go 8 minus 3, 8 minus 5 is 3. So yeah, that's what we will be getting, and so every single one here is -4, is going to be plus 4 this way. So now if we include the number 9 in the middle of each mirror pair, we can see that the mirror pairs are in fact continuous loops. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice here we have a 1, 2, 3, 4, 5, 6, 7, 8, 9. The whole way is continuous on this side, both sides. Now let's do this here. So the whole thing is continuous this way. You're adding, the vortex sum is adding plus 1. Let's put it like that. So plus 1 this way, or you could go minus 1 on the other side. And then this one here is going to be, well, we have this 1. You can see from here 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, then plus 2 is going to be 9, then 1. And then 1, 3, then this one is 2, 4, 6. So this is going to be a continuous loop this way. Or both ways, depending on which one you're adding or subtracting. So this is plus 2 that way. The next one's going to be 3, 6, 9, 3, 6, 9, 3, 6, 9, so it's plus 3 this way. And then the last one here is 4. So we have this 3 plus 4, 7, plus 4 is going to go to 8, 9, 1, and then 2. And yeah, so we can get plus 4 like that. And let's make a space here. And in fact, we can go even further than this. We can see that, in fact, notice how the corresponding vortex circles increment via addition or subtraction of the starting number 1 to 9, or its mirror, subtraction, or addition, respectively. Equivalent. So it's so if you're adding or subtracting, you're going to be subtracting or adding its mirror pair. So for example, or it's an equivalent mirror pair. Yeah, it's a mouthful, but this will make sense here. So if we look at the vortex circle here, so the main one in bold, so we start from here. We have from 1 to 9. 1 to 2 is plus plus 1, or you could view it as minus 8, because if it's this way, yeah, you could go minus 8. So 1 minus 8, if you go around the vortex circle, you're just going to go, yeah, so a full loop around would be, all the way around would be 9, so you're just subtracting 8 and you go to the 2. And likewise, you can see this minus 8 over here. So this right here, minus 8. Or minus 8 or plus 1. Yeah, so you're going to be adding, adding or subtracting, and then you're going to do the reverse, subtracting or adding its equivalent mirror pair. So 1 is a mirror pair of 8 and so on. So you're going to add plus 1 minus is 8. Yeah, plus 1 minus 8, it goes all the way around like that, goes to the 4, goes to the 6, goes to the 7, goes to the 8, goes to the 9 like that. And this is true for any of them. You could even see over here this 2. So 2 plus 2 is 4. 4 plus 2 is 6. Yes, you can see 2 plus 2 is 4. 4 plus 2 is 6, then goes to 8, and then goes to loops around, goes to the 1, and so on. But we'll look at another one. Let's look at the 7 one right here. So the 7 over here. This is going to be a minus 2. And the equivalent of minus 2 is going to be, well, the reverse plus 7. So 9 plus 7 as a factor of 9. So we're going to get to 7. And then continuing further, this one would go to the minus 2 again is going to go to the 5. Yeah, this is its equivalent. You can see the numbers 1, 2, 3, 4, 5, 6. I mean 1, 2, 3, 4. Let's add these up. These are 5 digits. So the next one's going to be 3. Yeah, this is exactly in line with it. And then you're going to subtract by 2. We get a 1 like that. Subtract by 2. It's going to get a 9, then a 1. Oops, let's loop it all the way around. 9, then it goes to 8. So that's this one right here. And then the 8 subtract again goes to the 6. 6 goes to the 4. And then 4 goes to the 2. And then 2 goes all the way to the 9. Like that. And let's do one more. Let's look at the 3 over here. So every single one works like this. So 3, let's draw this actually in blue. Yeah, so the 3, we can either go plus 3, so or 9 minus 6. Like that. And then plus 3 again is going to go to the 6. Or you can subtract by 6 and it goes around. Yeah, it loops around to 3, then goes up back to the 6. And then, yeah, so 6 again plus 3 is 9. 9 plus 3 goes to the 1. 9 plus 3 is just 3. It's going to be a factor of 9 plus 3. And then 3 plus this is going to go to the 6. Like that. Yes, this is pretty amazing stuff. And 6 goes to the 9. 9 goes back to the 3. 3 goes to the 6. 3, 6, 9. 3, 6, 9. Yeah, so it just loops amazingly. Every single one of these does the exact same thing. And then it starts again at the 1, 2, 3. Notice the 1, 2, 3, 4, 5, 6, 7, 8, 9. And yeah, we could go in the reverse direction as well, because again, it's plus 1, minus 8. Other one's going to be plus 8, minus 1, etc. So we can go in the reverse direction. Let's look at what the first one is right here. Let's draw this in red. This one is minus 1, or you could do a plus 8. Right there. So minus 1 or plus 8, where again 9. Yeah, 9 plus 8 would just be a factor of, that factor of 9 plus 8, so just it's 8, vortex sum. And then again, this is subtract by 1, 7, goes to 6, goes to 5. 5 is right here. And then 5 goes into the 4, and then goes like that. I think, yeah, we have that. Actually, I made a mistake here. This one is a 4 goes to, plus 1 there. And it goes to the 5 again. Yeah, so my bad there. And then, so 3 goes into the 2, 2 goes to the 1, and then this goes over there. And likewise, we can go over to this 1 here. So there's a 1, 2, 3, 4. So the next one is, you could even just go in reverse direction this way for this one. This cycles always repeat. It's going to be a plus 1 or a minus 8. And this is going to go into the 2, 3, 4, and the 4 goes all the way to the 5 right here, to the 5 there, and then the 5 goes into the 6, 6 like this, 6 goes to the 7, 7 goes to the 8, and then 8 goes to the 9. Yes, amazing stuff. And yeah, so again, the reason for these patterns, or quote polar number pairs, is once again due to the symmetry of the number system. Consider again the mirror pairs written as a difference or subtraction of the modulus 9. So here's the mirror. So it's a mirror like this, so mirror reflection. And if you write it as a difference or subtraction of 9, so 1 equals to 9 minus 8, where this 8 equals to 9 minus 1. So again, it's mirror pair. So this is plus 1, this is minus 1, this is plus 8, this is minus 8. So exactly the same thing. The right numbers are the same, or just reflection of the left. It's going to be 9 minus 7. This equals 9 minus 6. This equals 9 minus 5. This equals to 9 minus 4. 9 minus 3 equals 9 minus 3. Yeah, set that equals 9 minus 3. This is 9 minus 2, etc. So yeah, notice the mirror pairs. Negative 2, plus 2, plus 7, minus 2, 7, etc. And again, these are the exact same equations. So these are same equations, just rearranged. Same equations. Because you could just see the 4, you move the 4 to this side, so minus 4 on this side, and then plus 5, yeah, minus 4 both sides, plus 5 on both sides. This cancels, so just move this over here, it just becomes positive. So we get a 9 minus 4. Yeah, if you move this over here, we'll get a 9 minus 4 equals 5, and move for the 5 over there. And yeah, so note again that the equations are the same for each mirror pair, but rearranged. For example, 1 equals 9 minus 8, just get one of the examples, 9 minus 8. This is the same thing as writing, we'll move this 1 over to this side, move this negative 5 over to this side. Yeah, so then we just get the exact same thing. So these are the same thing. We get a 8 equals to 9 minus 1. It's the same exact thing. It's the same thing, but rearranged. So yeah, one is dealing with positive 1, one's dealing with negative 1, and one's dealing with negative 8, one's dealing with positive 8. Yeah, so since these are the same equations, this effectively means that adding or subtracting a number yields the same vortex sum as subtracting or adding, respectively, its mirror pair. Consider the following example, because this is just with subtraction, and 9 minus 8 it gets converted to a 9 minus 1 as a mirror pair. So consider the following example to illustrate what I mean by this. So if you have 4 plus number 6, this equals 2. Let's write this number 6 in its equivalent number. So number 6 is equal to 9 minus 3. So equivalently, you could write it using its mirror pair. So that means we could just convert them using its mirror pair. So they're effectively the same thing. So 4 plus 6 is equal to 4 plus 9 minus 3, like that. And now just move the 9 out and move the 4 inside. This equals to a 9 plus a 4 minus 3. So in other words, we get a factor of 9. Yes, factor of 9. Then we get a remainder here. Remainder is 4 minus 3. So in other words, the vortex sum remainder. Yeah, so then basically this means that 4 plus 6, v equals to the remainder, which is just 4 minus 3. Let's put 4 minus 3. So in other words, this number right here, this number is plus 6. Put it like this. So plus 6, and then this one right here, minus 3, we get mirror pairs. But then it's so if we're adding, if we're adding or subtracting, we get subtracting or adding respectively. So yes, the order matters. So plus 6 gets a minus 3, and these are again mirror pairs. Mirror pairs. Like that. Yeah, over here, just move it over here to this side so to save some vertical space. So I'll keep writing more. So yeah, these are mirror pairs. Or we could have also done, the other way. Or we could have gone 4 plus 6. This equals to, instead of writing 6 as a mirror pair, we could write 4 as a mirror pair of negative 5. So we can have 4 equals to a mirror pair of, yes, or just write it as a difference of 9. So 4 is equal to 9 minus 5, like that, and then just add our plus 6. And now get rid of the 6 and move this over to this side, so we get a 9 plus a 6 minus 5. And again, this is a remainder, like that, and this is going to be our factor of 9. Factor of 9. So factor of 9, and then the remainder, and the remainder is what governs the vortex sum. So then this one here, rearrange this so that it's 6 plus 4. V equals to 6 minus 5. So, and again, this right here, plus 4, and this minus 5, these are mirror pairs. And then these are mirror pairs. And yeah, let's just solve these actually. So 4 minus 3 is equal to 1. Vortex sum of both is equal to 1. And so basically you can add 4 plus 6 the same as 4 minus 3 equals to 1. And 6 plus 4 same as 6 minus 5, which equals to 1. And these are, again, all the same equations because, yeah, these are just rearranged. Yeah, so what this means is that that incrementing the numbers on the right has a mirror reflection of subtracting from the numbers on the left when you look at the mirror pair. For example, so if you have the vortex circle here, so yes, if you increment this number right here to the right by 1, let's go. So we're going to go increment by themselves. So we're going to have next one's going to be 2, next one's going to be 3, next one's going to be 4. Yeah, I'll just draw this like this. So if you increment by plus 1, which is the equivalent of subtracting from its mirror pair. So if you plus 4, for example, then it's minus 5. If you plus 1, or you could do minus 8. So plus 1 or minus 8. Yeah, then the next one's going to be 6, and then 7, and then 8. And again, then it goes 9, then it goes back to the 1. Whoops. It goes back to the 1. Then it wraps around, it goes back to the 1. Because again, we're doing vortex sum. So 10 goes to 1. Let's read this again, 1, like that. And then on the mirror pair on the other side, this one, if you're adding 8 on this side, is the same as subtracting 1. Because remember, when you add or subtract, it's the same as subtracting or adding, respectively, the mirror pair. So let's go backwards, this one. So this one going backwards, let's do this backwards. This equals to, this is going to be this is going to be plus 8 or minus 1. So if you're plusing 8, then you're going to have to subtract 1 as well. So then this one you can just subtract 1, so it'll be 7, 6, 5, 4, 3, 2, 1, and then next one's 9. And then let's just go one more to line up back to it, so we get back to the 8. So yeah, so we have that. And then likewise for this 2, so if you add 2, just keep drawing a line like that. So if you add 2 plus 2, or minus, this is going to be minus 7. Yes, so plus 2 or minus 7, this is going to be 4, 6, 8, then 10 becomes 1. And then, yeah, the next one, plus 2 is going to be 3, etc. Let's go dot, dot, dot. Or let's just do this. Let's do a few more. So 5, 7, 9, and then 2. Yeah, so it lines up with a 9 there. Then there's a 1, 2, just to double check. And then the next one here is going to go on this side. Oops, let's draw this better. So this is going to be, yeah, this, if you're adding 7, so matching this number, so adding 7 is the same as minusing 2. So we get 7, then we go to 5, then we go to 3, then we go to 2, and then 2 goes 1, then 9, like that. And then the next one's going to be, actually no, I made a mistake here, so it's 3 minus 2 is 1. Yeah, and then the next one's going to be 9, then 8. And then it's going to go to 6, then it's going to go to 4, go to 2, then it goes to 1, then 9, and then 7. So yes, there it is. So then it goes up 7, 8 there. So it lines up with that. Let's do the next two here. So we have, this one's going to be plus 3 or minus 6. So if we do that, it's going to go to 3 plus 3 is 6. And then 9, then goes back to the 3, wraps around 6, 9, and then yeah, 3, 6, 9, etc. And yeah, it just lines up. And then the next one's going to be, well, let's just see how these line up. So this lines up with this. Let's just move it around. Okay, let's just see how many digits. So here we have 1, 2, yeah, this is going to be 10 digits. So this we need to get to 10. So 3, 6, 9, 3, 6, 9, 3, 6, 9. So we need one more. This is going to go to 3, like that. So yes, it lines up. There's a 1, 2, 3. And then next one here. Let's just go with this one first now. So on the left side, for adding 6, the same thing as subtracting 1. So plus 6 or minus, it's subtracting 3, so it's mirror pair. So you add 6, same as minusing 3, and this is going to go to 6, then 3, then 9, like that, going backwards. Yeah, let's just add this again. So 9, this is 1, 2, 3, then it's going to go to 6, 3, so it's, then it's going to go to 9, so that's 6 numbers. We need 4 more. Then it's go to 6, 3, and then it's going to go to 9. These are, 9 numbers, 1 more is 6. Yeah, so 6, like that. 6 lines up with there, 6, 7, and then all the 9s line up. And then the last one here, so for adding 4, you're going to be subtracting 5, and vice versa. Just write it here, plus 4 or minus 5, and then this is going to be 4 plus 4 is 8. Then plus 4 is going to be, goes to 9, and then 1, 2, 3. Like that, and then the next one's going to be 7. 3 plus 3 plus 4 is 7, and 7 goes to 8, 9, 1, 2, and then it goes to 2 plus 4 is 6. And the next one's going to go to 7, 8, 9, then 1. Then the next one's going to go to 5. The next one's going to go to 9, and after that's going to be 4, and that's 10 numbers. And yeah, you can see it's 10 numbers. This is going to be 5 numbers, and then 5 there. And there's the lines up 1, 2, 3, 4. 1, 2, then 1, 2, 3, 4, and there's a 9's line up too. And the next one's going to go. This one's going backwards. This is either plus 5 or minus 4. So let's just do the minus 4 because it's just a 5 minus 4 is 1, and then minus 4 is going to be. Well, yeah, minus 4 or plus 5, so let's add 5 here is going to be 6. So you can do either or. So yeah, so 6, and we get minus 4 here is going to be 2, and then we can plus 5 is going to be 7. So yeah, that's much easier instead of having to wrap around. So then we can go minus 4 is going to be 3, and then plus 5 is 8, and then minus 4 is going to be 4. Yeah, and then plus 5 is 9, and then plus 5 is going to be, or minus 4 is going to be 5. And then there's the 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Then there's the lines up 5, 6, 7, 8, 9. And there's the 1, 2, 3, 4, and then lines up 5, 6, 7, 8, 9. And yeah, so you could either plus 5 or minus 4. And again, it doesn't matter which one you use. If you have to wrap around, you have to wrap around. Or you could just use the other one to not wrap around, which is fascinating. Yes, and yeah, this is pretty much the mirror or the polar number pairs. But here I included the 3. Marko Rodin didn't include the 3 and 6, but I did. And yeah, because it doesn't matter which one you're using. It's just a mirror. The numbers on the right mirror the numbers on the left. So note that adding or subtracting numbers may require, quote, wrapping around a vortex circle or modular arithmetic clock, or we can simply subtract or add respectively. Again, if you're adding or subtracting numbers, you could subtract or add their mirror pair. Respectively, it's mirror pair. Yes, and we can see that right here. So let's say we have the number 1 here, and then we're gonna add, or let's just say, yeah, we're gonna add, or we're gonna let's do it instead. Let's subtract. So let's subtract by 8. So if we subtract by 8, we're gonna wrap around this. So it goes here once. To the 8 is 1. To the 9 is 1. And goes all the way back down over to here, and this is going to be over to here, and this is going to be minus 8. Yeah, so minus 8, we wrap around this 9, so we go once here, then go 7. 7 after that, so 9 minus 7 goes up to here, which is to 2, or we could have just done the plus 1. So we could have just avoided that and just go plus 1, which is its mirror pair. So mirror pairs like that. And you can see it as well over here. Let's say we have 7 right here. Well, let's draw the 7 in green or red. So let's say we have 7 and we add 3 to it, or let's just add 4 to get back to the 2. So if we add 4, it's going to wrap around. So 1, 2 there, and then 2 over there. This is going to be plus 4. It gets to the 2. Or we could have just subtracted by 5. So, or we could have, so this wraps around the 9, gets over there, or you could go 7 minus 5, which is 2. Like that. So its mirror pair is -5. So plus 4 or -5. So we could have just gone there, we could have wrapped around the 9, or we could have not wrapped around the 9. So that's fascinating stuff. Alright, so continuing further, note also the mirror reflection symmetry of addition or subtraction. So for example, here's the modulus, again, modulus 9 for base 10. So just draw this down here. That's a mirror like that. There's the pairs and so on. Let's draw this in red on this side. So if we start from this 1 here, if we add 1, it goes over to here. So this is plus 1, or it's mirror pair minus 8, which you wrap around. Then it has an exact mirror pair on this side here, and this one's going to be, I'll just draw this in actually just keep it in red. So this next one's going to be mirror pair is going to go down straight to here, which this one is minus 1 or plus 8. So plus 8 or minus 1. So notice the exact symmetry then. Because if you're adding 1 there, you're going to subtract 1 there, so it's going backwards. And then likewise here, let's just use a doubling pattern. So this one right here is plus 2 or minus 7. This one right here is going to be plus 7 or minus 2. And minus 2, you know that already, it goes to the 5. So this is going to be plus 7 or minus 2. So notice the exact symmetry. These are exactly mirrors of each other. And then likewise, this 4 right here, if you add 4, it goes over there. This one is plus, I'll put it somewhere. Yes, I'll put it over here. So this is plus 4 or minus 5. And yeah, I just moved it over to there. And on the next one here, this plus 5 is the same as minusing 4. So you get all the way across here. So notice the symmetry. This is going to be plus 5 or minus 4. So yes, we just do a minus 4. And we get straight to there. Just put an arrow here. So yes, plus 5 or minus 4. Yeah, so thus incrementing a number by itself has a mirror reflection. So if you 1 plus 1 there, or any other number. So incrementing a number, actually I just make it more general. So thus adding or subtracting a number has a mirror reflection. So even if you have here, if you plus 4 on this side, it's equivalent, if you have, so 3 plus 4 goes to 7. It's the same thing as, same thing as 6 minus 4 goes over to the 2. So yes, if you have 3, plus 4 goes to 7, and then look at the mirror pair, 6 minus 4 goes over to the 2. Yeah, so 7 and 2. Yeah, so those all line up. Lastly, if we write each polar pair as a difference of the modulus 9, we could see the corresponding vortex circle pattern or vertical symmetry arise. So what I'll do here is I'm going to write, so from the 9, I'm going to put the 9 in the middle, like that. Then the number 1 here on the right side is going to be, well, 9 minus 8. Just write it as a difference of 9. And then when you add 1 to it, it's going to be 9 minus 7. Then it's going to go 9 minus 6. And so on. And this is going this way. This is going, plus 1 or minus 8. Like that. So yeah, when you have 8 right here, negative 8 plus 1 goes to negative 7 because you're adding 1. So this is from the negative side, you're adding 1. Negative 7 plus 1 goes to negative 6, and so on. So this goes over to that side. And on the left side of this, we have the number 8, which is 9 minus 1. And then this is next one's going to be, well, 9 minus 2, because you can go, it's going to be plus 8 or negative 1. Then it's going to go 9 minus 3, like that. And I'll put an arrow like that. This is going to be negative 1 or plus 8. Or I'll just do the other way around. So plus 8 or negative 1. So you could do either or. So yeah, adding 8 on the left side is the same as adding minusing 8 on the right side, or plus 1 on the right side is the same as minusing 1 on this side. And then let's go to the next one. So we have 9. Then we have a 9 minus 7 for number 2. Then we're gonna adding it by 2, so it's gonna be 9 minus 5, and then 9 minus 3. These are negative numbers, so they go downwards. And this is gonna be plus 2 or minus 7. And then going backwards here, we're gonna go 9 minus 2 for the 7. And then then it's gonna be we're gonna subtract by 2, 9 minus 4, like that, and then we're gonna go 9 minus 6. And note these are all mirror pairs of each other. So we have 9 minus 4, this is 9 minus 5, it's just the 5 and 4 mirror pairs. And just put an arrow like this. This is going to be plus 7 or minus 2. And then let's go another one here. So 9, let's move this in the center. In the center like that. So this one's going to be the 3, so 9 minus 6. Like that. And then if we write it one at a time, so 9 minus 6, and then this one's going to be 9 minus 3. So notice it's always going to be the mirror pair. So when you write this one here, it's going to be plus 3, so it's going to be 9 minus 3 like that. This one's going to be minus 3, so it's going to be 9 minus 6. So they're always going to be mirror pairs. Because you're always doing the opposite of the other one, so it's going to be mirror pairs like that. And this one's going to be 9 minus 0. Because then you get to 9. This is going to be plus 3 or minus 6. This one's going to be, put an arrow like this. This is going to be plus 6 or minus 3. And then the next one right here, this is going to be minus 3. So 9 minus 9. And remember, yes, this will go to 0, but remember when you're dealing with the modular clock, this one just goes back to itself. So that's just 9. And this 9 minus 0 is also the same as the 9. Like that. So yes, mirror. And then the last one here, we're going to go 9 minus 5 is 4. 9 minus 4 is 5. And then when you're adding 4, it's going to be 9 minus 1. Like that. So I'll draw an arrow here. This is going to be plus 4. Or minus 5, like that. Yeah, so this one right here, so we can either plus 4 here, then wrap around the 9, or just go simply 9 minus 5, 9 minus 1 minus 5, so it's going to be 9 minus 6. So just subtract by 5 there. And likewise, here is going to be 9 minus, this is going to be, draw this arrow, this is going to be plus 5, or minus 4. So if you subtract by 4, it's going to be 9 minus 8. And then we can, this one we can subtract by 4, but if you're subtracting, negative 8 minus 4 wraps around, or you could just plus 5, so that's just going to be negative 8 plus 5, or just 8 minus 3, which is going to be, 8 minus 5, this is going reverse, so that's going to be 3. So the difference is of 8 and 5 is 3, so it's going to be negative 9 minus 3 like that. Yeah, so notice what we have. So we have on this right side 9 minus 8, and then the one below it's 9 minus 7, then we have 9 minus 6 and 9 minus 5, then it wraps around to 9 minus 4, 9 minus 3, 9 minus 1, 9 minus 2. So in other words, we have a vertical symmetry like this that wraps around into the vortex circle and makes it, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is, 1, 2, 3, 4, 5, 6, 7, 8. And this is going to be plus 1 like that. So this is on this side is going to be plus 1, or you could do your other, plus 1 or negative 8, or you could go backwards the other way. So plus 1 or negative 8. And likewise here, this one right here is going down. So 9 minus 7 is 2. The 9 minus 5 is going to be 4. So 2, 4. Yeah, it's just, this one negative 7, then the negative 5, negative 3. So you're adding 2, and it wraps around all the way to here, which has our vortex circle here. So this is going up as well by 2. So 9 minus 1, and then when you're adding 2 to it, it goes over to adding 2 or subtracting by 7. So you get this 8, and then you get the so keep adding 2. So 6, negative 6, negative 4, negative 2, and so on. So this is going to be wrapping around this way. This is going to be this is plus 2 or negative 7. And likewise over here, this is going to be the 3. So notice this one is the 3. 9 minus 6 is you're adding 3, and it wraps around all the way across here. Yeah, negative 6 plus 3 is going to be negative 3 like that. So this is going to be our plus 3, or its mirror pair, minus 6. So yes, it's just wrapping around. So we have this, and the next one's going to be obviously plus 4 or negative 5 and so on. Yeah, and this is actually some pretty amazing stuff. So I'm going to put this deserves a hashtag. Amazing. It's amazing symmetry right here, guys. Like that. So now if we extend the vortex sum increments further, we can see that they cycle back after 9 increments, thus forming a continuous horizontal loop, as well as a symmetry, as well as the symmetry of the polar number pairs. So if we have here, so 9, and then put the 9 on top where the modulus is, and then 9 in between, like here, so they line up horizontally, and then we could wrap around vertically. So we have this 9 minus 8, 9 minus 7, 9 minus 6, etc. Then this is going to be our plus 1 or minus 8, then the next one's going to be plus 2 or minus 7 and so on. But notice that these are exactly the same formulas on the left side. So once you keep extending this 9 minus 1, 9 minus 2, 9 minus 3 all the way to 9 minus 8, the next one below is going to be 9 minus 7, and it's going to be 9 minus 6, 9 minus 5. These are exactly the same equations here. So in other words, this right here, these are exactly the same, and this extends this way, and then it repeats again after this 9 minus 8. So let's go here. It's extended past over there, and then it starts repeating as well here, and it keeps going to the right. So notice, so then we can circle this right here, and then this is going to be all the way to the 9 over there. So these are the exact same, and then it just starts repeating. So this and this are the same. And yeah, also notice the polar pairs or mirror pairs. So if we have over here the -1 over to this side, we're going to have the over here, this is going to be our negative, no, 8. Yes, if we have 1, we have 8. We have, if we have here 6, we're going to have 3. So these are all pairs. This one's 2, this one's going to be 8. I mean, this one's 2, this one's going to be, no, this one should be 7. This is wrong. That should be 7. Because this is the 9 minus 4 is 5, so this is plus 5 or minus 4. So -3 minus 4 is 7. Yes, and then but then we have it right over here. So -7 plus 5 goes to -2. So yeah, that's correct. So it should be 7, like that. Yeah, and here I quickly just paused the video and just updated this this table right there. Just it's from the same Excel sheet. I'll put a link soon. Yeah, so just continue for this. These are left and right side are just all pairs. So I'll just put it like this. Pairs. Yeah, so there's the difference from 9, all these are just pairs. So 7 goes to the 2 over here, 3 goes to the 6, and so on. Yeah, notice how they start going backwards as well. 7, then it becomes 2. So yeah, we had 2, 7, then this goes 7, 2, and then this should be a 6. Then this is 6. Then it's going to go back to the 3. This is 1. And then it goes to the... I know this is 8. Then this is 1. This is 1. This is 8. Yes, now let's go further. So let's compare now the vortex values with the corresponding notation as a difference from the modulus. So the actual vortex values is just subtracting. So 9 minus 6 would be 3, etc. And note that 9 minus 0, v equals to the same vortex sum as 9 minus 9, v equals to 9. So here I have 9 minus 0, 9 minus 0, or here again it depends on which way you did these addition or subtraction. So for example, here I got it to the 9 minus 9. Yeah, so here I have 9 minus 6, and then I subtracted by 3 gets 9 minus 9, or if I added 6, it would have gone to 9 minus 0, so it's either or. 9 minus 0 itself, so everything's just, those are always going to be modulus 9. So if it's a modulus subtracting by the modulus, or subtracting by 0, it's going to be the same exact thing, so v equals to 9. So here's the same Excel sheet, the worksheet is polar number pairs, so here is the updated in difference form, the updated vortex polar number pairs in difference form. And then if you just include all the numbers inside, you get the this is 9 minus 8 is 1, 9 minus 7 is 2, and then we get this 1, 2, 3, 4, and then it goes up 5, 6, 7, 8, and then it goes 2, 4, 6, 8, and then it goes all the way around 1, 3, 5, 7, and so on. And recall, yeah, above in this this pattern here. So notice that it goes from +1 or -8 around like this. Then it goes to +2 or -7, +3 or -6, and the next one's going to be +4 or -5, and so on. And yeah, so it's always going to be following that pattern. So let's go continue further. So since the vertical symmetry or corresponding vortex circles increment clockwise as follows: +1 or -8, +2 or -7, +3 or -6, +4 or -5. +5 or -4, +6 or -3, +7 or -1, or +8 or -1. So it goes all the way backwards. So once it gets to this point here, this is going to be subtracting by 1 or +8. And this one here is subtracting by 2 or +7. So what we could do is we could thus view the corresponding vortex circles by their simplest form by only considering the numbers plus or minus 1 to 4. Yeah, so in other words, we could go write it over here. So start from here. So this is going to be a +1 loop, +1. This one's going to be a +2. And notice the loop 1, 2, 3, 4. It loops all the way to the 5. And this one right here, let's draw this a bit better. Yeah, let's draw this a bit better. Yeah, so +2. The next one's going to be over here. is plus 3, like that. And then this goes, 3, 6, 9, then goes back to the 3, goes over to here, and then these all just loop back to 9. 8 plus 1 is 9, 7 plus 2 is 9, 6 plus 3 is 9, and then next one here is going to be our plus 4. Yeah, so there's the 4, 4, 8, and then it goes 3, 7, like that. Goes, wraps around there. And now, this is, the next one's going to be plus 5 or negative 4. So we'll look at the negative one. So this is going to be negative 4, like that. And this goes around, whoops, all the way around. Yeah, just fixed that up there. So yeah, it goes, wraps around there. And the next one's going to be minus 3 or plus 6. So minus 3, 6, 3, then 9, and then 9 minus 3 is 6. It goes around like this. Let's go slowly so it doesn't glitch. Because again, this OneNote file is pretty giant, so apologies for the glitching. So negative 2, and then this goes 7 minus 2 is 5, and then it goes 3, 1, and it keeps going on. Let's go that one more time. I'll just fix that loop around, and then go there, and then let's get this 8 is going to be, this is going to be negative 1. And yeah, this goes back there, and this wraps around there. So this is plus 1, 2, plus 1, plus 2, plus 3, plus 4. Then it goes to minus 4, minus 3, minus 2. And then the next one here is just you could consider it as plus or minus 0. Yes, right here is in black, plus or minus 0, and then the next one's going to be our plus 1. And yes, it just starts repeating again. So yes, there's some pretty amazing patterns here. Or instead of using the negative numbers, because remember the negative number, the opposite of that is going to be either plus 4 or minus 5. This one's going to be plus 5 or minus 4. So, or we could simply view only positive increments, but in opposing cycles. In opposing directions. So here is these are just the positive numbers here: plus 1, plus 2, plus 3, plus 4. This is the same one as in black here. But now instead of going this negative 4, negative 3, negative 2, we can go only positive increments, but in opposing cycle directions. So this is minus 4 this way. That means it's going to be plus 4 the other way. So 4, 8, and then it goes to 3, and then 3 plus 4 is 7, etc. So this is going to be like this in red, and plus 4. So we're just going to go opposite cycle. And then it goes, loops around there to the 9. And likewise here, the next one's going to be plus 3. So 3, 6, 9, etc. So yes, like that. Yes, it gets to the 6 there. The next one's going to be plus 2. We have a 2, 4, 6, 8. It goes all the way to 9, then it should be a 1. Let's continue further, like that. That's going to be, this goes to the 1. And then plus 1 here. This 1, 2, 3, 4. And loops all the way across. Let's see if we can cut this up. And then 5, 6, 7, 8 all the way there. And then again it loops over to the 9. And some pretty amazing stuff. And this deserves a hashtag fascinating stuff. Let's keep going further. So different base number systems. So in the above section we analyzed the base 10 system, but we can extend this to all base number systems in general. So consider the base 6 number system. So the modulus is 5. You have 1, 1, 2. So not a just fix that up. So we have 1, 2, 3, 4, and then the modulus 5. And you can write this as a difference of the modulus. This is equals to 5 minus 4. This equals to 5 minus 3. And notice the pairs. Again, everything's the exact same thing. Right there. This is going to be equal to 5 minus 1. And then this is going to equal to 5 minus 2. Again, where these pairs are over there. And let's just write pair and write the symmetry line. Let's just draw the symmetry line straight down the middle like that. So yeah, it's all the exact same thing, but now the modulus is p. And so we could do pretty much exactly the same thing. So similarly, adding or subtracting a number yields the same vortex sum as subtracting or adding, respectively. Again, the order matters. It's polar pair. So for example, if we had 2 plus 4, this is base 5, so this equals 2. You could write this as 2 plus, and then write 4 as its polar pair. The difference of 5 minus 1, which equals to move the 5 out, move the 2 inside, we get a 5 plus a 2 minus 1, like that. And where this is a factor of 5, the modulus, and then this right here is just the remainder, which is what governs the vortex sum. Yeah, so that's the remainder. So then this means that 2 plus 4 v equals 2, and then this is going to be 2 minus 1. So let's write 2 plus 4. 2 plus 4 vortex sum is equal to, equal to 2 minus 1, where this is the plus 4. This is the minus 1. These are the mirror pairs, like this, and these are mirror pairs. You guys put it like that, mirror pairs, and this just equals to 1. Or you could have done the other way. You could have gone, just move it around. 4 plus 2 equals 2. 4 plus, and the mirror pair of 2 is going to be 5 minus 3, which equals 2. Move the 5 out, move the 4 back in, so this equals to 5 plus 4 minus 3. Like that, same thing. So then this v equals to 4 minus 3, that's the remainder, and that is the factor of 5. This equals to 1. Yeah, so we could go like this, 4 plus 2. And here quickly just pause, added this factor of 5 there for completeness, make it exact same as that. There's a remainder, so 4 plus 2, v equals to 4 minus 3, and then where this 2, so this plus 2, and then we have the minus 3, like that. Yeah, these our mirror pairs, like that. Mirror pairs. So adding 2 is the same as subtracting from its mirror pair. This equals to 1, which is the exact same thing that we expected here. So yes, you could just do the same on either or. And yeah, so these are all exact same thing. All we're doing is replacing the modulus 5 in base 10 with modulus 10 in base 10 with the number 5 with modulus 5 in base 6. So yes, all we're doing is replacing that with the modulus because you remove the factor of the modulus in the vortex sum and the remainder in the modulo formula and so on. So we can increment each polar pair in the same manner as before to get the expected increment and cycle patterns, but relative to the modulus 5. So if we do that here is in the same Excel sheet in the worksheet polar number pairs. So we do the same thing with the 5. So increment 5 on right or left. So just add 5. 5 is modulus, so add it on both. So we will have 5 plus 5 is 10. And then plus 5 is 15, plus 5 is 20. And then the modulus is always going to be 5, 5, 5. And likewise here, we add 1 here on this other side. So this is plus 1, or you could do minus 4. Yeah, so we get this 1, 2, 3, 4, 5. Then it goes 1, 2, 3, 4, 5. And likewise, over on this side, this is the same thing. This is going to be plus 4 or minus 1. So we get a 3. Yeah, so on these I've incremented it here. So 1 plus 1 is 2, 2 plus 2 is 3, and so etc. Then take the vortex sum. So then 4 plus 4 is 8. 8 plus 4 is 12. Vortex sum of 1 plus 2 is actually no, we have to take the mod because this is going to be base 6, so mod 5, so 12 mod 5. If 5 goes into it twice, 10, then the remainder is 2, so that's 2. And likewise here, 12 plus 4 is 16, and then 5 goes into it cleanly to number 15, so 3 times, and then remainder 1 there. So anyways, we subtract 1 here, it's doing exactly the same thing, we just take the mod of mod 5 now. And then going this way, we get a plus 3 or minus 2, so we get 3, then 1, then 4, then we get a 4, then 2, and etc. This one is going plus 2 or minus 3. So we get plus 2, 4, then we can subtract 3 there. Plus 3, plus 2, plus 2. So 1 plus 2 is 3, 3 plus 2 is 5, then you can subtract 3 because you don't want to wrap around. And then get to the 2, and then plus 2 is 4, etc. And then if you write this in a difference form, we get 5, 5, 5, and then we get 5 minus 4, 5 minus 3, and then we get a 5 minus 2, 5 minus 2 on the, 5 minus 1, 5 minus 2 on this side. So in other words, exactly the same thing. We get the vertical symmetry here. This is going to wrap around. This is going to be plus 1 like that. And this one here is going to be a... Yeah, no, this one, yeah, this is actually wrong. This should be 1, 5 minus 1. And then the mirror pair is 5 minus 4 there. So let's just fix this all up. Yeah, here I just go quickly just pause and fix that up. So this is going to be 5 minus 3, then plus 2 is going to be 5 minus 1, and then we can minus 3 over there and get to the 5 minus 4, just so we don't need to wrap around. Then we get plus 2. to get to the minus 2 there. And again, this is a 3, so 5 minus 3 plus 2 is 5 minus 1, and it wraps around like this way. This is going to be plus 2. This is or minus 4 or minus 3. It's readily plus 2 or minus 3. The next one is going to be, this is plus, this is going to be minus 2 or plus 3. So yeah, you could go minus 2 or plus 3. Yeah, because the 3 would just wrap around and so on. Yeah, so I'll just put it down here. The next one's going to be plus, this is plus 3 or minus 2. The next one right here is going to be plus 4 or minus 1. So you get this 5 minus 1, 5 minus 2, and again, they all wrap around, etc. So they all just wrap all the way around there. And yeah, likewise here, I just write it in its values form as opposed to the difference. You get this 1, 2, so plus 1. We get this plus 2. And we get this over here. This is going to be a plus 3 or minus, scrolling down, it's going to be minus 2, minus 1, etc. Then there's a 0 and so on. They also wrap around all the way to here and so on. Similarly, we can write the cycle in, we can write the cycle. Yeah, here, write the cycle in positive increments but in opposing directions. And here I just fix this up, just put some red for the minus ones, and then there's a plus for the positive cycle. And yeah, so if we could just use these only in positive increments, and we could just go with plus 1 here, plus 2 here. These wrap around to the 5, the 2, 4, then goes to 1, 1, 3, then 5. And then we can go again, likewise, exactly the same as the base 10, but in, now it's base 6. Yeah, let's draw this in red. So now we have a plus 2 right here, then plus 1 over there. And then, yeah, this wraps around this way. And yeah, it goes back to the 5, etc. So this is going to be plus 1, 1, 2, 3, 4. The other one is 2, 4, 1, 3. Yes, 4 goes to the 5, then 1, then 3. And now we can just generalize this whole procedure, but for any number system, so not just this base 6 or the base 10 earlier. And again, all we're doing is just going to change the modulus. The modulus governs everything, so the 5 governs this pattern like that, because you can write them as a difference of the 5, and then the base 10 is going to be difference of the 9. And yeah, so if we could just generalize it to any modulus p, so in general, and by simplifying the notation by only writing the left side as a modulus difference of the right side, for any base number system, we have the following polar pair or polar number pair cycles. And yeah, I'm only going to write the right side as a whole number, the left side as a difference of that whole number. As a difference of the modulus, including that whole number. So let's say we have a modulus p. Yeah, so we have a modulus p right there, and then the right side, yeah, we're going to have the first number is going to be 1, and then after that we're going to have a 2 and a 3 and a dot, and then we're going to increment this one on the other side. But first, let's just write this down. The polar pair of it's going to be 9 minus 1, like that, which is going to be, actually no, that's 8, that's for base 10. It's going to be p, just reverse of the 9. I'll get that mixed up. So we have a p there, let's write this in the middle, like that. Then we'll have p minus 2, the polar pair. Then this one's going to be p minus 3. So again, this is just positive, those are just negative, and then dot, it's always going to be the same thing. And then when you add 1 to here, we'll get a 2, and then add a 2 to this one, we're going to get a 4. Add a 3 to this one, we're going to get a 6, and then add a 1 again, we're going to get a 3 like that, dot. So this side we're going to have a plus 1. Or you could subtract by its polar pair, or minus a 9 minus 1. Which again, if you calculate this is just going to be negative 9 plus 1, where the 9 is the factor of, just a factor of 9. You have the negative sign, but for vortex sums, yeah, actually let's just write that down. So this is going to be a negative 9, and then plus 1. Yeah, and this negative 9 doesn't affect the vortex sum, so you're just going to go backwards one loop around wrap around the modular clock. So anyways, the next one's going to be, this is 2, 4, 6, dot. And again, we're just generalizing for any base number system. This is going to be plus 2, or you could write minus 9 minus 1. Or just for completeness, this is included as well. Or minus the polar pair, 9 minus 2. like that. So it's, again, it's just going to be negative 9 plus 2. And then next one here is going to be 9. Yeah, it's plus 9 like that, dot, dot, dot. And then we're going to write this as plus 3. Then we're incrementing it by 3 or subtracting by the polar pair, which is 9 minus 3. Like that. Then here we're going to have a dot, dot, dot. And then a dot, dot, dot. Let's make this a bit better. And let's just write this on the other side. So this is p minus 1. This is going to be subtracting by 1 or, subtracting by 1 or adding the adding itself, p minus 1. So we could write this down. The next one's going to be, well, p minus 2. And notice that they always match. There's p minus 2. This next one's going to be p minus 3. Like that. Yeah, so we have this p minus 3 there. So we're just subtracting by 1 like that. So we'll write a minus 1. Or we could do a... Yeah, you could write this, or you can add, it's right here, or plus 9 minus 1, the polar pair of, the polar pair of 1. So polar pair of 1 is 9 minus 1. Polar pair of 2 is 9 minus 2. So that's pretty much what polar pairs are. And you can do that likewise for the other ones. And then this one here is 9 minus 2. No, 9 minus 4, because we're subtracting by 2. Yeah, change that to a 4. Next one's p minus 6. Etc. Notice how they all match up. So 2, 4, 6, and then we have a negative 2, negative 4, negative 6. Dot, dot, dot. This is going to go to minus 2. Minus 2 or plus 9 minus 2. And then next one's going to be p minus, this is going to be 6 for subtracting by 3, p minus 9. Like that, dot, dot, dot. And then this is going to go all the way to 9 minus, it's going to be subtracted by 3. And again, dot, dot, dot like this, dot, dot, dot like that. And then likewise over here, we get this part right here is going to go, let's put it downwards like that. Or better yet, let's put it on top. So it goes downwards by plus 1. This one goes downwards by plus 2, so 2, 4, 6. And this one goes downwards by plus 3. Like that. And then this part right here is you can put a negative sign down here going down by negative 1, negative 2, negative 3. Or you can go upwards here to continue the loop, or let's just put it down here for just to match up with that. So negatives match up. So negative 1 goes down. So yeah, this is the vertical symmetry. Negative 1, negative 2, and then this is going to be subtracted by 3, like that. Or you can add its polar pair, or you can subtract its polar pair. So yes, so you always have these 9 minus 1, this one here, or plus 9 minus 3. Yeah, so thus, because we can write this in general for any modulus, thus the polar number pairs are a direct result of the symmetry of number systems in general. So yeah, it doesn't matter what you use, it's always going to be adding up like that. In which adding to the right by plus 1, if you go to the left plus 2, it's the same thing as subtracting 1 on the other side, and subtracting 2 on the other, and then subtracting 3, and so on. And then, yeah, minus 1 is the same as going plus 1 in reverse. So this is all going in one way, plus 1, or it's all going negative 1 in reverse, like that. It's just fascinating stuff. Yeah, especially when you include the modulus p there, then this would be plus 1 this side, and then this would be minus 1 on this side. And yeah, so going further, and now let's quickly look at odd-based number systems. So lastly, if the base number system is odd, then the only difference is that the number modulus divided by 2 is its own polar pair, or the number that is half the modulus is its own polar pair. What this means is, well, let's just consider the base 7 number system. So base 7, the modulus is 6, which is 7 minus 1. Now let's write our polar pairs. This one, you could write this as a difference with the modulus, so 6 minus 5. This one's going to be number 5 equals to 6 minus 1. 2 is equal to 6 minus 4. There's the polar pair of it. So these are polar pairs. Just write here pairs like that. This is a pair like that. This one's going to be 6 minus 2. So it's exactly the same thing we've been doing. And then, yeah, right here, 3, this equals to, well, 6 minus 3, which also equals to 3. 6 minus 3, yeah, it's equal to 3. It's the same thing. Actually, no, they're all the same thing like that. They're just rearranged. So you can't rearrange this one. Yeah, actually, I mean this one here. So this 3 and 3 are the exact same. Notice these ones are opposite. So 2, you have a 4, you have 1, you have 5. Yeah, so these right sides, it's always going to equal 1 anyways. They're equal. So you have the 1, you have a 5, you have a 2, you have a 4 there. And yeah, we're ignoring the modulus. This one here, that's also its own, but it can only be 6. It can only be 6, 6, 6, 6, etc. This one, it can actually alternate between 3 and 6, as I'll show. Yeah, so what this means is that since 3 is its own polar pair, then it means that if we add any number by 3, then it yields the same vortex sum as subtracting by 3. Because remember, you add or subtract a number is equal to, the vortex sum is the same as doing subtracting or adding, respectively, in that order, of, by its mirror pair. But since it's its own, so you just, if you add any number by 3, it's the same as subtracting by 3, which we can see via vortex circle modular clock. So if you have a number, so let's say you have here, and we're gonna draw this in here. So let's start from here. Yeah, let's change that to red. So if we add 3, let's just say we're from here, and we're gonna do a plus 3. So if we add 3, 3 plus 3 is 6. So this goes all the way to here. This is plus 3. And it's equivalent to the same thing as subtracting 3. So if you subtract 3, 3 minus 3 is 0, but that vortex sum is 3. So these are exactly the same thing. And it doesn't matter where you go from. Let's say you pick number 2 here. And now let's say you add 3. So add 3 to 2 plus 3 is 5. It goes over to there, so that's plus 3. It's the same thing as subtracting 3. So if you subtract 3, you just go around the clock. So so 2 minus 3, you go to 1, 2, and then you go subtract it backwards. So all it is going backwards when you subtract. And this is minus 3. So yes, it's exactly the same thing. Just split in half, and it goes in the same direction. And this goes to here. Yeah, so this would this would arise pretty much exact same patterns as the even ones, except you're gonna have plus or minus of 3 has its own polar pairs, and I'll show you what happens there. There's going to be an overlap. So calculating more terms of the polar pairs, we notice that the only difference is that the patterns cycle around an alternating sequence of 3, 6, 3, 6. So you have here. So if you have there's the 6 on top is the no, this is supposed to be a 6. Yeah, these are supposed to be 6 and 6. So let's just update this right now. Yeah, so here quickly updated it. So yeah, that's the modulus. So just put it in there so that it shows the continuous loop. So now here you increment by 1, be the same thing here. So this is plus 1. Or you could do a minus, it's polar pair minus 5. And then yeah, you have 2, 3, 4, 5, 6. The vortex sums are the same. It's going to be 1, 2, 3, 4, 5, 6. And this one is 7, and in base 10 notation, this cuts down straight to the 1. Or 7 mod 6 is 1. So yes, and then the next one is plus 2. Whoops. It's going to be plus 2, like that. This is going to be, I'll write it here, plus 2. Or you could write it as minus 4. And here, just move things over to the middle there. Now here, this one, I just put it going downwards. So that, because it's again, it could be plus. Yeah, this is going to be plus right here. I mean, the values here, you can see that the vortex sum becomes plus 3 or minus 3. Yeah, that's what the vortex sum does. But here's the, this is just the general, adding the 2. So 2 plus 2 is 4, plus 2 is, 4 plus 2 is 6, plus 2 is 8, and 10, 12, 14. But the vortex sum right here is always going to be this plus 2 or minus 4 there. So you have a 6 goes to minus 4 is 2. And then this one here, we're going downwards, but then this is this in here, I just incremented 3 by 3. So 3, 6, 9, 12, 15, 18, 21. And the vortex sum in base 7 is always going to be at this 3, 6, 3, 6, 3, 6, which is just same as going plus 3 or minus 3. Like, yeah, with this polar pair. And again, this one right here, we're going to be adding a plus 4. And then the vortex sum is just plus, we're going to be adding plus 4 or minus 2. So we have the minus 2, 4, 2, and then it goes to 6. Because 2 it goes to 1, then modular clock goes to 6. But here we just added 4 plus 4 is 8, plus 4 is 12, 16, etc. Then you take the vortex sum. And I'll go over this this part right here, which I pretty much skipped over, but it's pretty basic, and it's an addition modulo identity. So then the next one here, we're going to be incrementing by 5, or the vortex sum is going to be subtracting by 1. So 5, then goes 4, 3, 2, 1, and there's a continuous loop. So this way, going this way is positive 1, so there's the 4, 5, 6, 1, 2, 3, 4, 5. And going backwards, it's going to be 3, 2, 1, and then it goes 6, 5, 4, 3, 2, 1. Here's positive this way. 2, so 2, 4, 6, and then connects there, 2, etc. And then what we'll notice is, as I'll draw it later, so you have this 2 right there. This 2 goes down, 2, 4, and then goes to 6, and then goes to 4. I mean, goes to 2, goes to 4, etc. And yeah, we'll get to that in a bit. So now if you write it in this difference form, you have 6 minus 5, 6 minus 4, and then 3, 6 minus 2, 6 minus 1, etc. Where this one here is just 6 minus 3. I just write it as 3. This one's 6 minus, this is 6 minus 0. Just put it as 6. So whenever it's 6 minus 3, I just write it as 3, just because it's unique here. Then here's 6 minus 4, then you add 2, so you're going to add, so you'll subtract the negative. So 6 minus 2. And likewise here, you can see this 6 minus 5, 6 minus 4, then it goes to the 3. So this is going to be 1, 2, 3, and then this is going to be 4, 4, 5, etc. So yeah, we could just write this down. This is going to be a plus 1, and this is going to be a plus 2, and then notice how it gets here. So this is going to be, it's going to loop over to this side here. This is 6 minus 3, which is just 3, and then this one is 6 minus 4, 6 minus 2, then 6, then 6. And the next one here is 3, 6, and then the next one after that is going to be a 9, etc. there. So yes, plus 3, and so on. It's the same kind of loop. And this goes over here. We're going to add another 1, so it's 6 minus 2, and add another 1, 6 minus 1, and so on. And then add another 1, 6 over there. So it's all the same loops. And here, if I just include the values, so we have the 6. Yeah, so you can see here, this is going to be plus 1 or minus, just move it over, or minus 5. And then this side is going to be a minus 1 or a plus 5. Plus 5 or minus 1, etc. This one's going to be a minus 2 or plus 4. So yes, 4 plus 4, it goes to 6, and then another 2, it goes to 2, or you just subtract by 2. And then here you could add 4, it goes to 6, you could subtract 2, it goes to 4, you subtract 2, and then you could add 4, it gets to 6, and so on. And then notice the loops, it goes like that. 1, this is going to be plus 1, it's going to be plus 2, this is going to be plus 3, or minus 3, because 3 minus 3 goes to 0, which v equals to 6. Plus minus 3. And this goes to plus minus 3. Whereas this one is just plus 2. Then it goes to plus 1, etc. Goes up top. Like that. And then after that just goes back to this minus 2 there, or this plus 4. Or minus 2. Yeah, it's going to be a minus 2. Then it goes minus 1. Like that. And so on. Now, when we write in positive increments but in opposing directions, we see that there is an overlap at each third increment. So, for example, if you write this in positive increments right here, so plus 1, remember plus 2 here, so it's going to loop like that, 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 and it goes back to the 6, etc. Yes, so we have a 2, 4, 6, and then 2, 4, 6, here's a 1, 2, 3, 4, 5. And then the next one here, yeah, I'll write this one in blue. So here we can have a plus 3 or minus 3. Yeah, so plus 3 or minus 3. 3 minus 3 is 0. It goes to 6. You have vortex time is 6, or you could go 3 plus 3 is 6. And then add another 3 goes to 3. So you can go backwards or forwards. So you could write this like that. Backwards or forwards. And then this is, again, you can go backwards or forwards, and I'll put another arrow like that. This is going to be plus 3. It's going to be minus 3 or plus 3. Actually, we're doing increments of positive only. So plus 3 or minus 3, like that. And now if we want to get the reverse direction now for the other ones don't have a plus or minus. So now, if this is 2 going down is negative 2, so we'll add it as plus 2 on this side, so plus 2, and put it in red. Because there's 2, 4, 6. 2, 4, and yeah, it goes back to the 6. And then like right here is going to be our plus 1. Yeah, so that's the plus 1 there. Just change it, there. So 1, 2, and then it goes to 3. So notice it alternates to the 3 there. It goes up there, yeah. And the next one's plus 0. And yeah, you can just go plus 0 right here. Plus 0, and this one's going to be plus 1, etc. And if it's plus 0, it's going to go 6, 6, and the next one's going to be 6, and it'll be 6, 6. And then it goes all the way to 6 over there. Yeah, so now with this whole procedure, there's nothing unique about it for this number system, this base 7 system. It's just that the modulus is 6, so that it can divide cleanly by 2, so it goes to 3. And that means that the number 3 is its own polar pair. So all we do is get this alternating 3-6 pattern, and that adding 3 is the same as subtracting 3 when you're looking at the vortex sum. But there's nothing particular special about this base number system, and we're going to expand this to any odd base number system, as I'll illustrate right here. So this procedure is the same for all odd base number systems in general, as can be seen by the base 5 number system, in which the number 2 is its own polar pair. So here's base 5, so if it's odd base number, even modulus, and then 4 divided by 2 is 2, it divides cleanly into it. And then that means that, so we have 1, the polar pair of 1 is 3, so that now if we just increment by 1 on the, and then take the vortex sum, we get a 1, 2, 3, 4, then goes back to 1, 2, 3, etc. And then this is I'll stop at the 1 there. Yes, so it starts repeating. And this is our plus 1, or you could do its polar pair minus 3 for taking the vortex sum. And then this side over here, this one's going to be, well, 3, 2, and subtract by 1, then it goes to 4, then it goes to 3. Like that, where this right here, you're going to be adding plus, this is going to be plus 3 or minus 1. It's a polar pair. So you can add 3 or it's subtract its polar pair, which is 1. And notice that it all is one continuous loop. So you have 1, 2, 3, and it goes to the 4, 1, 2, 3, 4, etc. If you include that 4 there. Okay, and then now this one here, because it's its own polar pair, we do the same procedure. This can be add 2 or subtract 2 goes to 4. Then add 2 or subtract 2 goes to 4. Goes to 2 in the modular pair. Next one's 2, etc. And this is going to be plus or minus 2. Yeah, because it's its own polar pair. And now what this means is, now if we look at the corresponding vortex circle patterns, or the vertical symmetry, so we have plus 1 here goes to 1, goes to 2, goes to 3, and goes to 4, and then goes, well, yeah, loops back down to it. And then now, because this is number 2 is its own polar pair, we could plus or minus 2. Yeah, so write plus or minus 2 and put in a double arrow. So we can go either direction, and yes, we have it like that. It goes over there, back or forth, and this is going to be, again, this part is going to be plus or minus 2. And now if we write the negative or the reversed positive one, put this in red. So yeah, this is going plus here. The next one's going to be, well, plus 3. Or minus 1. Yeah, or yeah, if it's plus 3 or it's subtract its polar pair, which is this 1. And yes, but then we're going to look at the positive side only, so we get the 1 here. So if you write this in red, so plus 1. So 1 goes to the 2. And then the 2 goes to the 3. And then the 3 obviously goes to the 4 over there. And they all just cycle back and forth. And then as usual, this one here is going to be our plus 0. So yeah, it goes 1, 2, 3, and then plus 0. Or you could plus 4 or whatnot, then it goes resets back to the plus 1 here. And then there's the, there's 0 there. If there's 0 right here, then you add it, it's just going to be 0 there. So it could be 4, 4, 4, and then next one's going to be 1, 2, etc. So yeah, this is actually some pretty amazing stuff. So, and that deserves a hashtag amazing stuff. So now let's go into the last section of this video before I summarize. Before I do a summary conclusion of the whole video. So let's look at the modulo addition identity. So in the polar number pattern sequence, note that I had taken advantage of the fact that the addition of a number yields the same vortex sum as addition of its vortex sum. Yes, for example, here notice this is from, again, that same Excel sheet. It's a worksheet polar number pair. This is from the base 10 system. So if you look over here, the 16 is just 8 plus 8. And the vortex sum is 1 plus 6 is 7. But now here, so now the next one is going to be plus 8, like that. Yeah, so plus 8 gets to 24, and then the vortex sum is 2 plus 4 is 6, like that. Or we could have just done, or what I was doing is just using the vortex sum of it. So 16 goes down to here is the vortex sum of 16 is 1 plus 6 is 7, and 7 plus 8 is just equal to, 7 plus 8 is just v equals to the same thing. Let's write v equals to its polar pair, 7 minus 1, which is 6, like that. So I just look at it like that. Or you could go 8, or you could go 7 plus 8 is equal to 15. You just go 15, and then v equals to 1 plus 5 is 6. Yeah, and likewise here, just for every single one of them, same things here. So here, for example, this one, 4 plus 4 is 8, and then, 8 plus 8, just pick a random one, so 8 plus 4 is 12, and then here we have 12 plus 4, let's just pick this one here. 12 plus 4 is equal to 16, then you take the vortex sum is 7, 1 plus 6 is 7, or we could have just done this one, 1 plus 2 is 3, and then this one here plus 4, so we could have just done the addition of its from the vortex sum, as opposed to taking, as opposed to adding the number plus 4, then taking the vortex sum. We could have taken the vortex sum and then added the number, and then the vortex sum would be the same. Yeah, so consider the following example. Yeah, so I just took advantage that it is always the same. We could just take the vortex sum and just add to it, as opposed to actually looking at these numbers 3, 6, etc. You could just go beforehand, the numbers 5, so you add 4 is 9, as opposed to going 3, 6, and then add them up. That's going to be 9. Or 32 plus 4 is 36. Get to the 9. So consider the following example. We have, let's say, 4 plus 13. So this is equal to 17. And the vortex sum is going to be equal to 1 plus 6. And 1 plus 7 equals to 8. So that's what we could. That's what the long way is. Or we could have done this one right here. And notice that this right here, 13, v equals to 1 plus 3 equals to 4. So we know this one here, so we could just do sidestep 4, plus 13, v equals to, well, this is just going to be, this is just going to be 4 plus 4, or 4 plus 1 plus 3 equals 4 plus 4 equals 8. Yeah, like that. So we could have just replaced this with, this 4 is just the same as 1 plus 3. So we could have done that instead of actually calculating 4 plus 13. And we can derive this for the general case right here. So in the usual case, we can derive this as always. Derive that this is always the case. For example, if we have a capital A and capital B as integers, and we have A, B, C lowercase equal integer digits of number A. So then what we'll have is A equals to A, B, C. And notice that, remember before we could write this as a factor of 9. Like that, factor of 9 plus... And then it's going to be plus remainder, which is going to be our A plus B plus C. So exactly as before, where this right here is a remainder. Like that. Yeah, so that's a remainder. And again, it's just using our previous derivation abilities or notation. So then this is going to be just equal to the remainder. So V equals to A plus B plus C, which is just the remainder. And then, so that means, so if we have that, that means B... If we have so if we have integers b plus a, let's write thus. Thus, if we have b plus a, this v equals to, or I'll just write this as this equals to b plus, let's write the factor of a, so it's going to be equals factor of a, factor of 9. Yeah, factor of 9 or any other modulus p or whatnot. So let's write this factor of 9 like that. This is plus our ABC. This is just the remainder. Yeah, and then again, this ABC is just our vortex sum. Let's write this as vortex sum. So that means this is going to be v equals to, get rid of that factor of 9, doesn't affect the vortex sum. It's going to be a plus b plus c. It's vortex sum of A, like that. So then this means that the vortex sum of B plus A is equal to B plus AB, A plus B plus C, or in other words, B plus vortex sum of A. And I just bold this like that. And as usual, we could write this in just basic mod format or modulo notation because vortex sums, it just so happens to be the remainder, which just so happens to be the modulo function. So we can write this in mod 9 notation for base 10. So you could write b plus a, or capital B plus a, the integers mod 9 is equal to b plus a mod 9. Because remember, the mod 9 is just a vortex sum or the remainder when it's not equal to 0. If it's equal to 0, you just set it equal to the modulus 9. Or for any base number system with modulus p, and in a more general form, you could write a plus b mod p is just equal to a mod p plus b mod p mod p. All of this modulo p like that. Because this right here, this a mod 9 or a mod p, this gives an integer. So that means you're still doing an integer plus b, and b and a are just interchangeable. So they're both integers. This one you're going to get an integer. So you just apply that again with a b, and then you could just do both of them, mod p like that. And as a final example, we can see that we can apply the modulo addition identity in several different ways, all resulting in the same result, or same vortex sum. Or in this case, yes, same remainder. So 13 plus 17 are earlier. Actually, never mind. It's not the earlier example here, but we can. Yeah, it's just 13 is. But anyways, if we go 13 plus 17, then mod 9. It's the same thing as 13 plus 17 is equal to 30. So you could write 30 mod 9, and then this vortex sum is just 3 plus 0 is just 3, and then we have this mod 9 is equal to 3. So you just calculate it like that. Yeah, just delete this and press equals space. So yeah, it's 3. You could also just do it from here directly. Equals 3, yeah. But I'll just add 30 for the addition, and just to show us what we're comparing it with, we'll compare this with 13 plus 17 equals to 30, v equals 3, yeah, which is 3 plus 0 is just 3. So then we have 13 mod, yeah, we could do 13 mod 9, vortex sum of 13, which is going to be 4, 1 plus 3 is 4. And then you could go 17 mod 9, vortex sum is 1 plus 7 is 8. And you can see that this is true. You can see this true just putting equals here, and yeah, automatically calculates 4. And then this one right here, same thing. We go equals. This equals to 12. Actually, no, that's because it's calculating the before. So let's just put a decimal. Just put that like that, or put a letter X, just so it does not think it's a calculation. Yeah, just put X there. Now we do equals. 8, yeah, so this equals 8 there. Let's fix this up again, and then fix this up. Yeah, so then we'll have 13 mod 9 plus 17 mod 9, and then all of this mod 9, we get 4 plus 8, which is again 12, and then you get 12 mod 9 is 3. And then you could also go 13 mod 9 plus 17, and then this one's going to be, well 4 plus 17 is 21. It's 21 mod 9. I don't know why there's a bracket there. Yeah, just get rid of the brackets. 21 mod 9 is just going to be 3. And you can see 9 goes into 21 twice, 18. So 9 times 2 is 18, then you have remainder is 3. And lastly, you can go 13 plus 17 mod 9. It just equals to 13 plus 8. Yeah, because 17 mod 9 is 8. And then all mod 9 of it is going to be, this is going to be 13 plus 8 is 21. Yes. Yeah, 13 plus 7 is 20, then plus an extra 1, and then 21 mod 9 is 3. So yes, fascinating mathematics indeed. So now that we finally finished this epic long video, I don't know how many hours it is, I'll have to check once I compile all the parts. So summary, as per MES certified procedure, here's a summary of the concepts covered in this video, MES notes. I'll plan to streamline research and video production to avoid long downtimes before videos. The original Vortex Math video required more research, so I'm doing it in parts. This video is in regards to the basics of Vortex Math, and later parts will be about the Vortex torus geometry and more advanced Vortex patterns. So let's go over the introduction to Vortex Math. So Vortex Math, VM, or Vortex Based Mathematics, VBM as others call it, I just call it Vortex Math, is my first deep dive into, quote, number theory. Number theory or arithmetic is the study of integers or whole numbers and involving the basic operations of addition, subtraction. Here's put involve. So involve the basic operations of addition, subtraction, division, and multiplication. Marko Rodin claims that the number 1251 is the, quote, mathematical fingerprint of God. He converts the Baha'i religion. Put this just put a comma there. Yeah, so this I think that's the correct way of spelling it. So Baha'i religion's name of God, Abba, A-B-H-A, into numbers using the abjad number system. So 12 represents the start of a typical vortex doubling circuit, and 5-1 represents the end. And vortex doubling patterns involve multiplying and then summing the digits until a single digit is achieved. So you keep repeating that. So doubling from one pattern, we get the 1, 2, 4, 8, 7, 5. So we have 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, v equals 2, so that's my notation. 1 plus 6 equals to 7, so the vortex sum is 7. 16, then you could also go 16 times 2 is 32, v equals 3 plus 2 is 5. 32 times 2 is going to be, 32 times 2 is 64, v equals to, 6 plus 4, the vortex sum just added digits, equals to 10, v equals to 1. So then pattern, keep doing this, pattern repeats indefinitely, 1, 2, 4, 8, 7, 5, so 1, 2, 4, 8, 7, 5. and then 1, it keeps going on. Then you can also double from 3, and then you get the pattern 3, 6, 3, 6, etc. 3, and then 3 times 2 is 6, 6 times 2 is 12, and sum of digits 1 plus 2 equals to 3. And then you can also go 12 times 2 is 24, and the sum of digits is going to be, well, 2 plus 4 is 6. Yeah, just add that 2 plus 4 is 6. And then the next one is 24 times 2, you get 48. And then you sum those up, 4 plus 8 equals to 12. And then sum that up, 1 plus 1 plus 2 is equal to 3. And then the pattern repeats indefinitely, so you have this 3, 6, 3, 6, 3, 6, etc. And then if you double from the 9 pattern, so we get 9. The 9 times 2 is 18. And sum the digits, you get 1 plus 8 equals to 9. And then 18 times 2 is 36. Sum of digits, 3 plus 6 equals 9. And then pattern repeats indefinitely. You get the 9, 9, 9, 9. And put this in bold. The doubling patterns are the bulk of, quote, Vortex Math. And now the doubling circuits from the following patterns, when transcribed onto a circle, or the doubling circuits form the following patterns when transcribed onto a circle with the number 9 at the top. So you have 9 there. You get 1, 2, 3, 4, 5, 6, 7, 8, 9. So the pattern goes 1, 2, 4, and then the next one is going to be doubles to 8. 8 doubles to, well, 16, which is 7. And then 16 doubles to 32, which is 5. And then 5 doubles to 1. And then the cycle repeats. Or 32 doubles to, 64. And then 64, the vortex sum is 6 plus 4 is 1. And the next one is going to be, 64. It keeps going on and on. 64 doubles to 1, 2, 8. Then you add those up, you'll get a 2 plus 8 is 10, which is 1 plus 1 is 2. Then it goes 2, 5, 6, double that, 5, 12, 10, 2, 4, and 20, 48. And yeah, this is always going to be the 1, 2, 4, 8, 7, 5 pattern. You get that hexagon, and then you have the 3, 6, 3, 6, 9. We'll get to that in a bit. So halving. Actually, we'll get to that in a bit, but yeah, 3, if you double 3, it goes to 6, double 6 goes to 12, which is 3, it just goes back and forth. And 9 just goes by itself. That's why he has the triangle in the dashed lines, the red dashed line. So halving maintains a doubling pattern, but in the reverse direction. So if you half, you get 1 divided by 2 is 0.5, but if you sum the digits only the whole numbers 5, you get, so it's 5. Then divide by, then 0.5 divided by 2 equals to 0.25, divided by 2 is 0.125, and the pattern is the same as doubling, but in the reverse direction. I guess you go backwards, and this is going to be 2 plus 5 is 7, 1 plus 2 plus 5 is 8, etc. And it just goes backwards. So this goes backwards like that, and it goes non-stop. Doesn't matter how much you divide by half. I mean, you divide by 2, it's just still going to go backwards. Even these super large numbers all can be reduced into this infinity hexagon. So the, quote, powers of 10 arise when considering the halving decimal places. So those are decimal places to whatever you need to multiply to get it to a whole number. So 0.5 times by 10 gets it to 5. This one, for example, is 0.0625 times it by 10,000 gets it, so 4 zeros, get it out of there, so there's 4 zeros. And then that pattern lines up in which the hundreds line up with the hundreds, all because of the comma. So 1 comma, and then 1s, 10s line up. 4 doesn't matter what size pattern that you're doing. Whenever you use this halving pattern and look at the powers of 10, powers of 10 always line up with the hundreds, 100, 1, 1, and then 10, 10. And then yes, that's powers of 10. And then going further, so adding numbers or adding 1, 2, 4 by themselves and summing the digits yields mirror. Or instead, just remove that yield. So summing the digits mirror the same done to the 8, 7, 5 numbers. The corresponding pairs 1, 8, 2, 7, and 4, 5 are called the quote polar number pairs. You have the mirror pair like this. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. You're adding by 1. This one you're going to be subtracting by 1. 8, 7, 6, 5, 4, 3, 2, 1. Or you can add by 8. So 8 plus 8, 16. And then sums up to 1 plus 6 is 7 and so on. And likewise here, this one you can be adding 2, 2, 4, 6, 8. And then, this is the vortex sum. This one's going to be subtracting by 2. So 7, 5, 3, or 7 plus 7 is 14. And then the digit sum is 1 plus 4 is 5. And so on. This one's going to be 4. And you could also include the 3, 6 as I did later in this video. Or earlier in this video and then later in this summary. So we have the 4 plus 4 is 8. And then just keep adding it. Plus 4 is going to be 12. Sums to 3. And then this one here, 5 plus 5. Is going to be 10, or you could subtract by 4. And then 5 minus 4 is 1. And the next one here is going to be 10 plus 5 is going to be 15. 15 is 1 plus 6 is 7. I mean 1 plus 5 is 6. And yeah, so this is going plus 4 is going plus 5. The vortex sums are the same, but in a mirror reflection. So again, 1, 2, 3, 4, 5. This goes 8, 7, 6, 5, 4, 3, 2, 1. And again, this is from the other one, which I'll cover in a later video. So doubling 1, 2, 4, 8, doubling 1, 2, 4, 8, 7, 5 pattern in one direction. Or instead writing this, so writing the doubling 1, 2, 4, 8, 7, 5 pattern in one direction on a grid and another in the reverse direction while continuously interspaced with the pattern 3, 9, 6, 6, 9, 3 creates a blueprint for a torus. So if you have doubles here, 1, 2, and then the reverse you have 1, 2 in the reverse direction, and you can see this with 1, 2, 4, 8, and you have this reverse 1, 2, 4, 8, 7, 5, and interspaced there you have this 3, 9, 6, 6, 9, 3. And then this is the blueprint for the torus, and there's the, again, 3, 9, 6, 6, 9, 3, etc. You got doubling, and then doubling this way. So in other words, doubling and halving. And then if you look at the diagonals right here on this square grid, you get the, this numbers are adding up 1 to 9. So this goes 2, 3, 4, 5, 6, 7, 8, 9. And then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in the reverse direction as well. So we got 1, 2 in the blue. You got it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it goes 1, 2, 3, 4, 5. So alternates the adding as well, which he doesn't illustrate it in this one, but I'll cover it in a later video. So going further, Rodin claims resulting torus claims a resulting torus from this blueprint when you roll it into a torus demonstrates the winding of a coil. So you have these kind of patterns inside, and let's see the numbers here. So you have the 1, 2, 3, 4 goes in. You have 5, 6 that goes in, then it increments 1, 2, 3, 4, 5 outside. And you have the doubling ones in the red and blue, and so on, and some other patterns, I think. But anyways, so that's what he has. So Marko Rodin deifies, literally deifies the number 9 as the, quote, primal point of unity, and then reframes the yin-yang duality as 3, 6, 9 trinity, and states that, quote, spirit emanates from the center of mass outwards, and nature is a dynamic of contracting and expanding, but he doesn't expand on in detail what he means. So you have this 3, there's the yin-yang, 3, and he says this is 6, and then you have the 9 in between. And that's primal point of unity. And then you have the 9 with the triangle pointing on top. You have the lazy hexagon. That's what he refers to it, lazy infinity symbol. Oh yeah, lazy infinity symbol. Then you have the center point right here merging out, and that is the center of mass outwards. And it's not yet, so it's off center, and it's directly below the 9. And yeah, center spirit emanates. And you have vortex in and vortex out of this torus. So going further, yeah. So Marko Rodin's claims are, quote, reification, in which, or yeah, are examples of, quote, reification or fallacy of reification, in which abstract concepts like numbers are treated as being concrete real entities. Philosophical example: who are you? Not what your name is or what you do. Now that's a good question. So yeah, so I don't want your name or what you do for a living, what your job or whatever. I'm saying, who are you? Don't reify the label you give yourself, as Marko does with numbers. So Rodin also claims that designing electromagnetic coils to align with Vortex Math spiral patterns can boost efficiency and capabilities. Claims include space propulsion and cancer treatment. All right, but again, if you've been here at MES watching my videos long enough, you'll realize that hidden advanced tech include whatever you can think of. Anti-gravity, free energy, these are all real, but these claims are are dubious. Anyway, so many of Rodin's these claims to do with these Vortex Math and the coils, somehow with no details. That is dubious. So you got to put details, or else just no talking. So many of Rodin's websites and companies are no longer online or in operation. So I've had to view archived versions, and there's a lot of other websites. I didn't want to include those. But anyways, so overview of base number systems. The base, or radix, Latin for root, is the number of unique digits, including 0, used to represent numbers. So base 10, the number system is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so 10 of them. Incrementing past, the largest unique digit 9 is equal to 10, so 9 plus 1 is 10 in base 10. The number 10 is a transition beyond the unique base numbers 0 to 9, so and then count restarts 10, then you go 1, 1, 1, 2, 1, 3, 1, 4. Or 11, 12, 13, 14. Or 10, 10 plus 1, 10 plus 2, 10 plus 3, etc. Transition beyond 19 gets restarted at 20, and so on for 30, 40. So you get 18, 19, 20, 21, 22, and then it goes to 48, for example. Then 49, then it goes to 50, then 51, 52, etc. A transition past 99 restarts the count at 100. So 99 plus 100 equals and then 99 plus 1 equals 100. Likewise, 999 or 999 plus 1 equals 1,000, just as a transition past 3 of these, the biggest digit, number 9. And then transition further means adding more zeros. You have 10, 100, 1,000, 10,000, 100,000, etc. And you can write these in power notation, so 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, etc. And negative numbers work the same way, but in reverse. You get negative 10, goes to negative 9, negative 8, negative 7, etc. So you can just go the same thing. And the transitions here, 0, 1, 2. So if you go backwards, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then transitions to negative 10 there. So, and then, so base number systems in general follow the same conventions as in the base 10 system. So if you have binary, which is base 2, so you get 0, 1, so it's just 2 digits. And then the next one's going to be the placeholder 10. So then 0, 1, then 1, 0, then 1, 1, then 1, 0, 0, 1, 0, 1. And then base 4 is going to be 0, 1, 2, 3, so those 4 digits, including the 0. And then it goes to 10, so or 1, 0, then 1, 1, then 1, 2, 1, 3, then 100, then 1, 0, 1. And then base 16, this one, because it transitions beyond the conventional base 10, number 10, so it'd be beyond those numbers. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then it starts at A, B, C, D, E, F, so 16, including these 6 letter F, these 6 letters, 8F. And then it transitions back to number 10 or 1, 0, 1, 1. And then converting between number systems depends on the relative value of the transition number, quote 10. So for example, 10 or 1, 0 in base 2 is equal to 2 in base 10. But 1, 0 in base 10 is equal to 8 plus 2, which equals to 2 to the power of 3 plus 2. So 2 to the power of 3 is 8. Just getting these into relative value, which is 2. And then you can convert these 2 into 10. So that goes to 10 to 10 cubed plus 10 to the power of 1. This is base 2 now. And then that just equals to 1,000 plus 10. That equals 10. And also I made a base 10 to base X conversion calculator on Excel, and you could see that with a link there. And note that this Excel file is used throughout this video and likely in future parts. Or likely in future parts. And now going further, so summing of integer digits and the remainder after division. So the main aspect of Vortex Math is a continual summing of digits to get a singular digit. So MES convention, quote digit sum refers to the sum of digits. Quote V equals refers to a digit sum, so just write that for short notation. And quote vortex sum refers to the continual digit sum until a single digit is achieved. So dividing an integer by another integer results in a whole number, could be 0, and a remainder, which also could be 0, which can't be divided into wholly, if it's not 0. So basically, dividing a number, you're going to get a whole number plus a remainder. Division by the largest unique integer of any base number system results in a repeating decimal that corresponds to the remainder. So for example, if you have base 10, 1 divided by 9 equals 0.1111, and then base 5 is the same thing, 1 divided by 4 is 0.1111. If you have 2 divided by 9, it's going to be 0.2222, etc. Let's go further. So the modulo operation, even for base 5, so 2 divided by 4 in base 5, it should be at 0.222 as well. Going further, so the modulo operation is a process of calculating the remainder. The notation A, actually before we get to that, I just want to simplify this part here. So dividing an integer by another integer results in a whole number, could be 0, and a remainder could be 0, which can't be divided into wholly if it's not 0. In other words, A divided by B, these are both integers, equals to another integer C, a whole number, plus capital R, which is the remainder, divided by B, which can't be divided cleanly into it, unless it's 0. If it's 0, then the remainder is 0, and then it can be. But yes, and then the C also could be 0 if it's just going to be 0.111, etc., or 0 plus the remainder, so you have the 0 in the decimal place there. So anyways, going further, so the modulo operation is a process of calculating the remainder. The notation A mod n indicates the remainder of the division A divided by n. A is the dividend, and then n is a divisor or modulus. Many calculators have built-in mod functions, or many calculators have built-in mod functions, including the one in this, the one on this OneNote document I am using, or in this OneNote document that I'm using. So the vortex is the bold one here. The vortex digit sum is equal to mod of base minus 1, and this is very important. So the only exception is when the mod or remainder is equal to 0. It is assigned as the base minus 1 or modulus in Vortex Math. The mod is just the base minus 1. So if the remainder is 0, just assign it to equal to the 9. So in base 10, so you have 18 mod 9, and for example, this equals to 0. And then v equals to, just take the digit sum, 1 plus 8 equals 9. So you just sum that up. Yeah, which is this vortex sum 1 plus 8 is 9. So you just set it to 9, which is base 10 minus 1. This is always the case because any integer could be written as a factor of the modulus plus the remainder as a sum of the digits. For example, if you have base n and then modulus p equals n minus 1, and then you have single digits a, b, c. So the number, a, b, c like this equals to, you could separate this into its transition number. So a times 100 plus b times 10 plus c equals to now a times pp plus 1 plus b times p plus 1, because those are just 100 and this is 10. And then plus c. And then c, then you multiply this inside and move the a times 1 and b times 1 separate with the c. So we get a times pp plus b times p, then plus a plus b plus c. And then this is just a factor of p plus a plus b plus c. So we get this right here, a times pp plus b times p is equal to a factor of 9, or a factor of p. Yeah, just change it to a factor of p for general modulus. So then a plus b plus c equals remainder, and which also equals a digit sum. You're just summing the digits of this number. And then we repeat until digit sum is equal to vortex sum, or one single digit. And then the ABC, actually before we get to this part right here, so I forgot to write here. So repeat until digit sum is one digit, and then that is equal to the vortex sum. And then so ABC mod p, you could calculate, it calculates the remainder, and it's equal to the vortex sum. But when it's equal to 0, you just set it as the vortex sum. And most calculators are on base 10 by default, and as well as my brain. So it is often convenient to convert different bases to base 10 to determine the vortex sum using the base 10 mod function. Note, the base 10 mod function can calculate the base 4 vortex sum without requiring conversion, because the modulus 3 in base 4 is a factor of the modulus 9, which is base 10. MES note, unless stated otherwise, all numbers are by default in base 10. Yeah, so in this document and pretty much anywhere in life. And now let's get to the section on the main reason why vortex math patterns always arise, and that is that multiplying a number and its vortex sum result in the same vortex sum. So for example, if you multiply the number, take the vortex sum, it's going to get the same as if you multiplied its earlier vortex sum and then multiplied to get the vortex sum. So yes, and I'll explain this soon. I'll summarize this again soon. So this is due to the fact that an integer multiple of another integer can still be written as a factor of the modulus. Note that a factor f of a number n is a number that can be divided cleanly by n into another whole number. Yeah, for example, 27 is a factor of 9 because 27 divided by 9 equals 3, which is a whole number. And 9 is a factor of 3 because 9 divided by 3 equals to 3, which is a whole number. Yeah, so let's go to the integer multiple. So if you have integer multiple 7 times 9, this is a factor of 9 because, well, 7 times 9 divided by 9 is just going to be 7, and 9's always cancel. Or you could write 7 times 9 is 63, and 63 divided by 9 equals 7, which is a whole number. And also adding factors, and adding factors of a number results in a factor of that number as well. For example, factor of 9 plus factor of 9 is also going to be equal to a factor of 9. So for example, 9 plus 9 equals 18, which is the same thing as writing 2 times 9. So yeah, it's the same. It's just an integer multiple. So addition, the same numbers or same factors, you can always factor out a 9 and write it as an integer multiple. And also you'll have 18 divided by 9 equals to 2. Or you could go 2 times 9 divided by 9, 9's cancel equals 2. So yes, which is a whole number, and so that means this 9 plus 9 is a factor of 9. Alright, now let's look at the derivation for this multiplying a number and its vortex sum result in the same vortex sum. So if you have derivation n equals base, and you have p equals n minus 1, which is a modulus, and you have lowercase a, b, c equals any integer digit between 0 to p. This makes up the integers of the number system. And let's say you have a equals to integer, which is equal to a, b, c, the digits. And then you have k, which equals an integer. And now you have a, and you can expand this out using our previous placeholder number 10 placeholder notation. So we'll have a equals abc. So it's not a times b times c. This is the digits abc of this number of this integer a, and this equals to a times 100 because you could expand the 100. This is just the same meaning, plus b times 10 plus c, and this then you could replace this 100 as its biggest two digits of. The biggest possible two digits plus 1, that's the definition of this 100. So it's going to be a times pp plus 1, and then b times 10 is the same thing as writing b times p plus 1, and then plus c. Now if you expand these out, a times pp, and then you'll have a times pp plus b times p, and then the ones a times 1 and b times 1 move it over to the right side. So you have this a times pp plus b times p plus a b c, plus a plus b plus c. So in other words, we have a factor of p plus a remainder. So a equals a factor of p plus remainder, and we'll call that remainder 1. And now a, the vortex sum of it is the remainder governs it, so we'll have a vortex sum equals to remainder 1 when it reduced to 1 digit. So you repeat the same process until it's reduced. And then what we'll have here, a v equals to remainder 1, which you could also calculate the remainder as a mod p, and this equals to the vortex sum of a. Yeah, so keep that in mind, that's remainder 1. So now if you multiply this integer a by k, so you have k equals to k, k times a equals to k times, we'll just multiply this, expand this out, k times factor of p plus k times remainder 1. And note that k times factor of p, just a multiple of a factor of p, is also equal to a factor of p. So that means, we can replace this k times factor of p with over here, I'll get this ka equals to factor of p, and then we'll get to this part soon. And then next step is, well, look at this k times remainder 1. You could also write this out as k times remainder 1 equals factor of p plus remainder 2. And note this follows the same procedure as a equals a b c equals factor of p plus remainder 1. So you could always write these as a factor of p plus the remainder. Because you could just expand whatever digits this was of it, and then we'll get it to this notation. And if k times remainder 1 is a factor of p, then the remainder 2 would be 0. So yes, we have this right here. But then what this means here is that if you take the vortex sum of k times remainder 1, it's going to be this remainder 2, which is the remainder of this. This multiplying of this remainder 1. So k times remainder 1 v equals to remainder 2, which equals to, well, you could just calculate the mod k times remainder 1 and then mod p. And we know, we know what remainder 1 is. Remainder 1 is the vortex sum of a. So in other words, remainder 2 equals the vortex sum of k times, and then, because, this k times remainder 1 mod p is a vortex sum of this. So it's going to be k times vortex sum of a. That's remainder 2. And so now, let's expand this out. So we have remainder 1. K times remainder 1 equals factor of p plus remainder 2. So if you expand this all out, put it inside here. Put this inside here and this inside here. We get ka equals factor of p plus remainder 2. And note that factor of p plus factor of p equals a factor of p. So in other words, we can just write this as ka factor equals factor of p plus remainder 2. And then the remainder 2 is what governs the vortex sum. So ka v equals to remainder 2. And this equals to, you can use the mod function ka mod p, which equals to vortex sum of k times a. So that's what we have. Put these all together. So that's what remainder 2 is. Remainder 1 equals vortex sum of a. Remainder 2 equals vortex sum of k times remainder 1, or k times vortex sum of a there. And remainder 2 equals vortex sum of ka. So in other words, vortex sum of ka, this is remainder 2, is equal to vortex sum of k times, remainder 1 is this, vortex sum of a. So yes, there's the quotation marks. It's absolutely fascinating. So what I mean by this is, for example, 17v equals 1 plus 7 equals 8. That's the vortex sum of 17. And now 4 times 17, this equals to 68. And you can also calculate this as 6 plus 8 equals to 14. Do this digit sum again. 1 plus 4 equals to 5. Or we could have just multiplied 4 times the vortex sum of 8. 4 times 8 equals 32. V equals to 3 plus 2 equals 5. So yes, these get the exact same answer. And if the vortex sum is the same as a previous multiple, then a pattern arises. And this is a causation of most vortex patterns, or vortex math patterns. And here quickly just pause and update of this to make it look like the previous one. So there are now, there are infinite numbers, there are infinite amount of numbers, but only a finite number of vortex sums between 0 to p, which is the modulus. Thus, a pattern almost always is expected. For example, here if you have the number a, if a vortex sum of a is 1, then a times k, let's say we were given its vortex sum of 2, or you could have just gone to 1 times k, and then you'll get the same result. So 1 times k, vortex sum is 2. And then you can go, the next one, a, and multiply it again, so a times k, v equals to 4. And then the next one, 8 times k, v equals to 8. Let's say we were given these. And then the next one is 8 times k, times k is the next one. So vortex sum is 7. Multiply k by k again. We get vortex 5, then k again, we get vortex of 1. And now the next pattern, well, it's going to be 2. Because it starts right here. So we have the previous multiple right there, 1 and 1. Because even though this number is getting super large, a times k, etc., all that matters is that the vortex sum, we could have just multiplied it, and these are a finite number between the 0 to the modulus. So, in fact, since we're dealing with the vortex sum, and we're not going to have it 1, so let's put this from 1 to the modulus. Let's put this from 1 to the modulus, yeah, because you can't have vortex sum of 0. So vortex sum of 0, if the remainder is 0, you just set it equal to the modulus p. So yes, these can only be from 1 to the modulus p, so you're eventually going to get a repeating pattern. And then the next one is going to be 2, because we already know the vortex sum of 1 times k is 2. And then we already know for the 2 is 4, we already know the 4 is 8, etc. So it's going to go 2, 4, 8, 7, 5, 1, and this is the 1, 2, 4, 8, 7, 5 pattern, and this repeats indefinitely, and as expected, yeah, this k is equal to 2. K equals to 2, and a equals to 1. That's right, and k equals to 2. And yeah, a equals to 1 in this example. So this is a specific case of the following modulo multiplication identity. So if we have AB mod C, is the same thing as writing A times B mod C, and then mod C. And then, yeah, this is also equal to A times, you could also do it inside, A mod C times B mod C, and then all bracket times mod C. Or you can go just mod of the A mod C times B, and then mod C. This is a vortex sum 1c equals the modulus. For example, if it's equal to the modulus, if c is equal to modulus, then this is the vortex sum. So this is AB mod c is a vortex sum of AB. And this right here is A times vortex sum of B. And then we get the vortex sum of that. And that's, yes, same thing as what we were doing before. And then you can also do the vortex sum of both. And this equals the vortex sum of it. And that's because the vortex sum itself is going to be an integer. And then that integer multiple of this one, you could do a vortex sum of that, and so on. So you just go back and forth. So this is all modular arithmetic, which is pretty amazing. So example 25 equals to 2 plus 5 equals 7. And that's the same as writing 25 mod 9, which is 7. It's like that. Just delete and press space, it calculates equals 7. So the vortex sum is equal to 25 mod 9, or you can sum up the digits. So yes, this is the amazing part where it's connected to the mod. And then you can go 4 times 25. So if you multiply this number by 25, and then mod 9, you're going to get the answer 1. Or if you did 4 times 7, which is the 25 mod 9, and then mod 9 of that is the same thing, you're going to get 1. Yes, 4 times 7 mod 9, erase and equal, yeah, equals 1. It's just the same thing. So it's all modular arithmetic. So modular arithmetic is a system of arithmetic for integers that involves, quote, wrapping around a specific number called the modulus. The familiar 12-hour clock is an example of modular arithmetic with modulus 12. And since the vortex sum is equal to the remainder, or mod base minus 1, then it too can be viewed as a, quote, modular clock with modulus p equals base minus 1. So that's fascinating stuff. So let's continue further. So vortex doubling pattern. The main pattern in vortex math results from vortex doubling or vortex multiplying by 2, and it's the 1, 2, 4, 8, 7, 5 pattern is the pattern formed from doubling starting at 1 and continues indefinitely. So if you have 1, 2, 3, yeah, 1, yes, you have, this is just the count, is 24 digits. So you have 1, 2, 4, yeah, multiplied by 2. So 1 times 2 is 2, 2 times 2 is 4. 4 times 2 is 8, and then 8 times 2 is 16, etc. And here's the mod 9, which equals vortex sum. So 1, 2, 4, 8, and then this is 1 plus 6 is 7. 3 plus 2 is 5, etc. And it goes 1, 2, 4, 5. 1, 2, 4, 8, 7, 5, and it keeps repeating. And the 3, 6, 3, 6 pattern results from doubling from the starting point 3. Yeah, so we have here doubling from 3. Yes, it goes 3, 6, 12. 6 times 2 is 12. 12 times 2 is 24, etc. It keeps going on. And then if you take the mod 9 or the vortex sum, we'll get the 3, 6 pattern. So we get 3, 6, and then 1 plus 2 is 3. 2 plus 4 is 6. 4 plus 8 is 12, which equals to v equals 1 plus 2 is 3. etc. So you get the 3, 6, 3, 6, and it keeps going on forever. And the 9, 9, 9 pattern results from doubling from the starting point 9. Yeah, and we get this count 1 all the way to 24, and here is the mod 9. And there's the 9 times 2 is 18, 18 times 2 is 36, and you take the mod 9, we'll get 0 because they're all factors of 9, so the remainder is always going to be 0. And then, yeah, they're all just integer multiples of factor of 9, which is 9. Yeah, so multiplying that, and then the vortex sum is going to just be 9. So 9, then 1 plus 8 equals to 9, 3 plus 6 equals 9, 7 plus 2 is 9, 1 plus 4 equals 9. 2 plus 8 is equal to, well, it's going to be 10 plus 8, which is going to be 18, so 1 plus 8 is 9. So it keeps going on and on non-stop, it's always 9. The doubling patterns are a result of the symmetry of the number systems in general, and the vortex or vortex circle or modular clock is symmetric about the modulus. The numbers to the right have mirror reflections on the left when extended to negative numbers. So you can write this as 9, and then you can go 1, plus 2, plus 3, plus 4, or you can go backwards on this modular clock, negative 1, negative 2, negative 3, negative 4. It's just they're symmetric about this, and that is, so all the patterns arise because of this symmetry. And the numbers on the right can be written as a difference between the modulus 9 and the mirror number on the left, and then vice versa. These paired equations are the exact same but rearranged. So you could write these, this is exactly the same thing. 1 equals 9 minus 8. Same thing as just move this 1 on this side, move the 8 on this side. It's equal to 8 equals 9 minus 1. So you have the plus on this side, 1, 2, 3, 4. There's a negative 1, 2, 3, 4, like that. These are written as difference of the modulus. And note that this negative 1 goes counterclockwise. The positive we've defined as going clockwise. And these are the pairs, 8, 1, 7, 2. These are exact same equations, 5 and 4, exact same equations. And then there's a mirror just straight down from the 9. And then if you double this one here, so yes, a doubling pattern on the left side is a mirror reflection on the left. The modulus 9 can be viewed as its own mirror reflection. So if you have 1 equals 9 minus 8, if you double, we're going to get to 2, and equals to, 1 times 2 is 2, and equals 9 minus 7. If you double this one, vortex sum is going to be written exactly this. Or just doubling. So 18 minus 16, same thing as writing 9 minus 2. And then you'll have, this is going to be mirror image on this side. So we'll have 9 minus 1 equals 8. And then double that one here. This 18 goes to 16, and v equals to 7. And also you get these 9 minus 1 straight down like that. 9 minus 2 equals 7. But yeah, this one here, if you multiply 8 times 16, then we just move it around. 16 is equal to 9 plus 7. Move the 9 on this side. Subtract this, gets 18 minus 9. And here, yeah, we just get the 9. So this is, if you double it, rearrange, it gets exactly this. And it's exactly a mirror of this one. If you double this, same thing as doubling the 8, and we'll get to the 7. The vortex sum, we'll get to it. So the symmetry holds for all number systems and multiplication factors. So here's the base 9 right here. And if you have mirror reflection straight down here. And if you multiply 1 times 2 goes to here. And the same thing as multiplying 8 times 2 and getting the vortex sum. It's just mirror reflection. And then from here, 2 times 4 goes to here. Same thing, 7 times 2 goes to 5, which is 7 times 2 is 14. 1 plus 4 is 5. So just exactly mirrors. And this 4 goes up here, 5 goes up over there. And then for the base 4 system, you have modulus 3, and the same thing here. So we have a plus 1 equals 3 minus 2, and 2 is equal to 3 minus 1. These are pairs of itself. Just draw this triangle. And the multiplying the pair, the modulus, so you can consider as plus or minus, it's always going to be itself. So 3 times 2, 3 times 4 times 8, it's all factors of 3. V equals 3, pattern 3, 3, 3. This one here, multiply 1 times 2 goes to here. 2 times 2 goes to 4, but 4 mod 3 is equal to 1. So this just goes back to here. So we get a 1, 2, 1, 2 pattern. Or you could look at this negative side. So we go negative here, negative 1 times negative 1 times 2 goes to negative 2. The negative 2 times 2 is negative 4, which is just negative 1, the vortex sum, or the mod 9. Now going further, so factors that govern vortex patterns. Even base number systems have an odd modulus and results in a vortex circle that is symmetric about the modulus. Yeah, for example, here these are symmetric about the modulus there because they're even base has an odd modulus. Odd base number systems have an even modulus and results in a vortex circle that is symmetric about the modulus and modulus divided by 2. Yeah, we'll get to that in a bit. Vortex doubling patterns that involve doubling. Involve doubling there. Yes, fix that up. Involve doubling the number modulus divided by 2. Results in a pattern that quote converges. Yeah, that converges or gets quote funneled to the modulus. So here is this is just the even ones. Well, actually, we'll get to that in a bit. So if you have, for example, here. Actually, no, I didn't include that here. Yeah, just to summarize it, so I didn't include the images there, and it's too long for me to include it. But anyways, hopefully you understood what I meant if you just recap from earlier. So size of the base number system affects how many numbers are included or excluded in any particular vortex multiplication or doubling sequence. And Yeah, so that's the size of it. And quote, synchronization of doubling or multiplication in general with the size of the base number system allows for a single direct mirror reflection in the resulting vortex circle pattern. And synchronization of doubling pattern requires the bottom right on a vortex circle to vortex double to the top left to mirror pair the starting number 1. So you have here, this is base 4. 1 is part of the doubling circuit. This one goes to the top left, which is just a single number, 2. And this goes back here, mirror pair of itself. And then if base 6, you have 1, 2, and then 2 jumps over to the 4, and this mirror pair of 1, and 2 is part of the doubling circuit. And there's a 3 there. And yeah, this goes back, and it reflects once before the cycle repeats. And then base 10 goes 1, 2, and then 4 is part of the bottom right, is part of the doubling circuit, jumps to the 8, which is mirror pair of 1, and is exact mirror pair. And yeah, so the next one's going to be base 18, 1, 2, 4, and then jumps to the 8. Then there, and notice the size of the number system, and how many numbers are skipped. So this one, only this 3 is skipped on this first mirror there. And this one here, we skip 3, 5, 6, 7. This one, no numbers are skipped. This one is just 1 and 2. And yes, it jumps right there. One time mirror reflection before the cycle repeats from the 9 to the 1. Exact perfect symmetry there. Odd-based number systems can't synchronize with doubling patterns because we can't double a number on the right to get an odd number on the left of the vortex circle. In other words, yeah, doubling, you get the only odd number in doubling is 1. After that is going to be 1, 2, and then 4. Yeah, these are all even. Then you can't, when you multiply 4, it goes to an even number. So you can't get this 9. So this 9 is cut off. Yeah, so this 9 is cut off from the pattern, and then the cycle repeats. Notice the cycle repeats though when this is at the bottom right, but with cutting off the top and 1 in its pair. So it just goes like this. And then the same thing here for base 7. This odd base number. And notice the splits down in the middle there with the modulus divided by 2. So we get the 1, 2, and then it goes to the 4, and it goes back and forth like this. And this one, base 19, where even though this is 8 is over there at the bottom right, it jumps to the 16 because it's you can't jump to the odd number there, because if the base is odd number, the modulus is going to be even, and then the number to the left and right are both going to be odd. Or just the number to the left is going to be odd, so 17. So can't get there, so we have this 1 is always cut off. 1 and 17 is always cut off. Even though you start off 1, and it goes there, and it just cuts off. And then, yeah, so in general, if you have base equals n equals p plus 1 equals odd, yes, so the modulus is going to be even. And the base is equal to n equals to p plus 1 equals odd. So we'll have 1 is cut off, and you multiply by 2, goes to here. Let's say you have 4a, then we get over to here, which is p divided by 2 minus 1. Multiply this by 2, you're only going to get to, yeah, expand this out, p over 2 times 2. Cancels, the 2 cancels, we get, and then minus 2, so p minus 2 goes to here, and we don't go to p minus 1 because that's an odd number. And then yeah, likewise this goes down over here and eventually gets to this point here, which is p over 2 plus 1. That's p over 2 plus 1. Multiplied by 2 gets over to this, just cancels, we'll have a p plus 2, and then vortex sum is just 2, the remainder. That's modulus of, that's a factor of p. And yeah, it just jumps there. So yeah, the cycle is always there. The starting point of any vortex pattern governs a resulting pattern. Doubling or integer multiplying the modulus results in a vortex sum of itself. Yeah, and if the starting point is the modulus, then doubling or integer multiplying the modulus results in a vortex sum of itself. So, for example, 9 is always going to be 999. 18 multiplied by, for base 19 is always going to be, the vortex sum is always going to be itself, so 18, 18, 18. So different multiplication factors besides the usual doubling or multiplication by 2 results in different patterns. Multiplication factors that are a factor of the modulus result in the pattern, quote, funneling into the modulus. I'll just put often result in the pattern funneling into the modulus. And if you have multiplication factors, you also cycle after the modulus plus p increment. This is always true and for any integer k in general. So if you have a times k, v equals 2, we can write this as a factor of 9 plus remainder. And then if you write capital A times p plus k, you can expand this out as a times p plus a times k, which is just going to be a factor of p plus remainder. Or just more completely, because this is ak, this is ak, this is going to be just factor of p plus plus remainder. So we can write this as, just expand this out, factor of p plus factor of p, and also make this the lowercase r. So remainder, and then this is this part is just this ak over here. And we also know that factor of p plus factor of p is just factor of p. So a times k equals to, a times p plus k is equal to factor of p plus remainder. And these are the same remainders. In other words, a times p plus k, vortex sum is the same as vortex sum of ak, which v equals to the remainder. So yes, it does not matter. If you're adding, incrementing by the modulus, you're going to get back to the starting point. So here's the multiplying factors for base 10, starting from 1. So 1 times 1 times 1 times 1, it always goes 1. 1 times 2 is 4, 8, and then vortex times 7, 5, etc. But then for the 3, it's a factor of 9. So we start from 1. 1 times 3 is 3. 3 times 3 is 9. And yeah, it just goes 9, 9, 9, 9, 9. And then 4, we get 1 times 4 is 4. And then 4 times 4 gets to the 7, and 1, 4, 7, 1, 4, 7. The 5 is going to go into 1, 5, 7, 8. Multiply by 5. 1 times 5 is 7. 1 times 5 is 5. 5 times 5 is 35. 3 plus, it's 25. 2 plus 5 is 7, etc. And then you go 8, 4, 2, 1. It's actually the reverse of the doublet. So 1, 2, 4, 8, 7, 5, 1. And it goes reverse, so 1, 2, 4, 8, 7, 5, 1. And then it repeats. And then the 6, which is comprised of 2 times 3, which that includes, yes, 2 times the factor of 9, which is 3. 2 times the factor, 2 times the number 3, which is a factor, or 9 is a factor of. So 9 is a factor of 3, then you have 2 times 3. So that's why we have this 1 times 6 is 6, and then 6 times 6, 36, it gets to 9, you get 9, 9, 9, 9, 9, 9. And then likewise here, 7, we get 7 times, 1 times 7 is 7, and then 7 times 7 is going to be 49, which is just 4 plus 9, which is 13. 1 plus 3 is 9, or you could cast out the 9, it'd be 4. Yes, 4. 174, 174, and it's the reverse of the 4. And then this is going to be 147, this is going to be 174. 1471. Then it goes backwards. Then goes 1741, which is the same thing as 1741. And then the 8, this is going to be 1 over 1 times 8 is going to be just 1 times 8 is 8. 8 times 8 64. 6 plus 4 is going to be 10, which is 1. So 1 8 1 8 1 8. And then the 9 is just 1 times 9 is 9. So it's just going to go funnel right to itself. It's a factor of 9, 9, 9, 9, 9. And then the pattern repeats because this is going to be p plus 1. This is going to be 10 equals to 9 plus 1. So that's the modulus. Plus 1, p plus 1. K is 1 in this case, p is 9. And then this is going to be 1. Notice the pattern starts repeating. 1, 1, 1, 1, 1. The next one's going to be 1, 2, 4, 8, 7, 5, etc. It's just fascinating stuff. And it keeps repeating every 9th. So you're going to have 9 patterns and then repeats on the 10th. Every single one. And now Vortex halving patterns. So halving is a similar process to doubling, but involves... involves leaving out the decimal places. So yes, halving, similar process doubling, but involves leaving out the decimal places. So if you have 1 divided by 2 is 0.5, which v equals to 5, and then just remove the decimal place 0 and 1. And then 0.5 divided by 2 is 0.25, you get 2 plus 5 is 7. And then likewise, 0.25 divided by 2 is 0.125, and then we get 1, 2 plus 5 is 8. And notice these are just multiples of 5, so 5 times 5 is 25, times 5 is 125, etc. So it keeps doing this. And you're going to get this pattern 1, 5, 7, 8, 4, 2, 1, and it's in fact the reverse of doubling. So you get the 1, 5, 7, 8, 4, 2 pattern, repeats indefinitely and is reverse of the doubling pattern. Regardless of how big these numbers get or how many digits they get or how small they get. But they just ignore the zeros, add these up. 1 plus 5 plus 6 plus 2 plus 5 equals 19, and then 1 plus 9 equals to 10 equals 1. And you could have just also done the reverse, so 8, or just done it with the vortex sum. So 8 divided by 2 is 4, 4 divided by 2 is 2, and then 2 divided by 2 is 1. So halving the resulting vortex sum also results in the same pattern. So we have 1 divided by 2 is 0.5, which v equals to 5. 5 divided by 2 is 2.5, which v equals to 2 plus 5 equals 7. And then 7 divided by 2 is 3.5, and then 3 plus 5 is 8. 8 divided by 2 is 4, 4 divided by 2 is 1, 2 divided by 2 is 1. 1, and then we start back at this 1. So 1, 5, 7, 8, 4, 2, 1, etc. pattern repeats indefinitely. Here, just remove that 1 just so we have the full patterns. 1, 5, 7, 8, 4, 2 pattern repeats indefinitely. And unlike doubling, the quote value of halving or dividing in general depends on the base number system. So doubling is just 1 plus 2 equals to 2. That's in base 10. Or you could write that as 10. 1, 0 in base 2. But halving, 10 divided by 2 in base 10 is going to be equal to, it depends on the base number system, so you have to write this in base 10, equals to 5, which is not equal to 10 divided by 2 in base 2, which is equal to 1. Because binary is just 2 digits. So 10, this represents 2, And then 2 represents 2 in base 10. So here, divide by 2, you're going to get 1 for base 2, and then 5. So they're not equal. So halving involves dividing the number of unique base digits. Yeah, for example, 10 base 10, there's 10 unique digits. 10 divided by 2 is going to be 5. Or 5 plus 5, it gets over to 10. And then base 2 is going to be, there's 2 unique digits. Either a 0, 1, or just there's going to be... there's going to be, well, when you divide it into half, you're going to have just a 1 plus 1, and that makes up its number 10, 1, 0, which is, again, the number of unique base digits. So value of 10 divided by 2 governs halving for each base number system, and can convert halving pattern into a multiplication pattern. So you have 1 divided by 2k equals to 1 divided by 10k times 10 over 2 to the power of k. Yes, in other words, we divide. So this halving, whichever part of the sequence you're at, you could just multiply 10 over 10, or 10 to the power of k over 10 over the power of k, so it doesn't change anything. And then just move this around, we get this 1 divided by 10 to the power of k times 10 over 2 times to the power of k. So in other words, this 10 over 2 is a multiplication, and based on the number system. In the base 10 system, halving is equivalent to multiplying by 5, since 10 divided by 2 is 5. In base 8, halving is equivalent to multiplying by 4, since 10 divided by 2 is equal to 4. And since the division by 10k, so this division 1 divided by 10k, 10 power of k, is ignored when taking the vortex sum, then halving is in general the reverse of doubling. Yeah, reverse of doubling. So halving or multiplying by 10 divided by 2 is equal to 5. Yeah, 10 divided by 2 is equal to 5 in base 10. So in other words, so halving or multiplying by 5. So, because again, we ignore these 10 to the power of k, so we ignore the decimal place and so on. So halving is going to be in general reverse of doubling. So we have this 1, 5, 7, 8, 4, 2, 1 pattern. And then the doubling pattern, just the reverse of that. So we go 1, 2, 4, 8, 7, 5, 1. Because yeah, halving and doubling are interlinked. And it goes backwards. So odd-based number systems don't have an integer value for halving, so it does not appear they're able to, quote, vortex half properly. So 10 divided by 2 in base 5 is just, you could write this in 4 plus 1. Divided by 2 equals to 2 plus 1 half. So yeah, that 1 half again. So they don't know what to do with that one. And 10 divided by 2 in base 11, for example, this equals to 10 plus 1 divided by 2 equals to, divide this out, equals to 5 plus 1 half. So there's always this extra half. So do you have any suggestions for dealing with this? So yes, what are we supposed to do then? So it doesn't divide cleanly into it. And then the quote powers of 10 pattern arises when plotting the ignored halving divisor 10 to the power of k onto the vortex circle. So the convention of adding a comma after every third zero coincides with the 3 halving terms on the right and left sides of the main 1, 5, 7 and then the 8, 4, 2 pattern. So we have this this doubling one. We get 1, 2, 4, 8, 7, 5. Oh, actually, no, this is going reverse. So we get 1, 5, 7, 8, and then it goes to 4, and then 2, 1. Yeah, but since the convention is adding a comma after every third zero, and we keep incrementing a 0, so we have 1, goes to the 10, the next one's going to be 100, next one's going to be back to the 1. So this is paired. And then this one is going to go back down to here to the 10,000. Then we have 100,000. 100,000 lines up with this. And then we have 1 million lines up with this. If the convention was adding a comma every second term, then the base 6 number system would provide this symmetric pattern. Yeah, so instead if you added every second, notice that the pattern here lines up where you have 2 numbers on the right of the doubling sequence, and then you have 2 numbers on the left, and you're adding a comma every second one. So we go 1 of equals to 3 power 4. Actually, no, that's on the other side. So 3 to the power of 0 divided by 10 to the power of 0. This just equals to 1 over 1. And then you half it. It's going to go to 3. That's because it's this base 6. And in base 6, it's a 10 divided by 2 is going to be equal to 3. Or 6 divided by 2 is 3. So yes, halving is multiplying by 3. So you go to 3 here. Or 3 to the power of 1 over 10 to the power of 1. Then it goes to the 4. And then it goes to here, to 2. And it goes back. Yeah, back over there. And then if you just take the 10s, you get the 1, then it goes to 10, then it goes to 1 again, matches, and then it goes to the 10 here, and this is 10 dash 00. Then it goes to the 1 here, 1, 0, 0, 0, 0. So in other words, 1, 10, and then we have 100, and then we have 1000, then we have 1, this is 10,000 actually. I'm trying to see how this is 10 hundreds. Or how you would say it in words. But yeah, so notice the lining up. Same thing as this one here. This is every thirds. This is every 2. Because 2, you gotta get something that has 2 on the right side and 2 on the left side of the doubling sequence, or the halving sequence. It goes half over here, 1, 10, 100, 1, 0, 0, 1 and 3 zeros, and then 1 and 4 zeros, but then you're adding a comma there. So anyways, that's power of 10. So in general, a vortex division can be converted into a vortex multiplication, and which also depends on the base number system. Yeah, so we have over here, so in general, a vortex division can be converted into a vortex multiplication, and which also depends on the base number system. So if you have 1 divided by 10, 1 divided by divisor d, to the power of k, this equals to 1 divided by 10 to the power of k, times, and you have, again, there's a 10 to the power of k, so it doesn't change anything. So times it by 10 divided by d to the power of k. Then you remove this 1 divided by 10 to the power of k. It doesn't account for the vortex sum, so v equals to 10 divided by d to the power of k. So yes, so this division is now converted into vortex sum with the multiplication. So all that matters is 10 divided by d, and it depends on the number system, and this is the k integer, whichever part of the series or the sequence you're at. So some cases arise, in which the base number system doesn't divide cleanly and results in either repeating single digits, repeating pattern of multiple digits, or multiple divisions before obtaining a whole vortex number. So here's a summary of base 10 division to multiplication vortex conversion. So we have 1 divided by 0 equals to undefined or infinity, v equals to question mark. So yeah, don't know what that would be. 1 divided by 1 is just 1. So 1, yeah, dividing by 1 is the same as multiplying by 1. 1 divided by 2 equals to 0.5, or v equals to 5. And that is a multiplication of 5. So 1 divided by 2 in base 10 is the same as multiplying by 5 for vortex sum purposes. 1 divided by 3, we get 0.333, and v equals to, well, question mark. We don't know what that is. It's repeating decimal. And then 1 divided by 4 is 0.25. Sum that up is 2 plus 5. So you could also multiply by 25, but that's a big number. So we'll multiply by 7, which is single digit. So 1 divided by 4 in base 10 is the same as multiplying by 7. 1 divided by 5 is the same as multiplying by 2. And then 1 divided by 6, we get this 0.16666, v equals to question mark. And then 1 divided by 7, we get the 142857 pattern. And it keeps repeating, v equals, don't know, and it repeats this 142857. So just repeat this one repeats single digit, this repeats single digits. And then 1 divided by 8 is 0.125, v equals to 8. So dividing by 8, same as multiplying by 8. You can add this here, 1 plus 2 plus 5 is 8. And yes, that's a very interesting part here. And then 1 divided by 9 is 0.1111, v equals to, well, question mark. And yeah, so now let's look at the last section, which is polar number pairs and addition. So polar number pairs are just the same as the mirror pairs, but the focus is on addition instead of multiplication to derive patterns. So incrementing the right side by themselves results in subtracting by itself on the left side, and vice versa. So if you have this 1 here, the vortex circle of base 9, 1, 2, 4, 8. You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you increment on the right side, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then next one's 10, but then vortex sum is 1. So it's the same as plus 1 or minus 8, which is a mirror pair. And then this left side, if you have 8 plus 2, 8 plus 8 is 16, v equals to 7, and then 16 plus 8 is 24, v equals to 6, etc. But then if you look at the vortex sum, it's just subtracting by 1. So if you have plus 1 here, you subtract 1, or plus 8. Or this is minus 8. For example, 9 goes to the 8. So you can do either or. And this one here, we're adding by 2. So 2, 4, 6, 8, 1, 3, 5, 7, 8, 9, 2. So you get this 2, 4, 6, 8. And or you can subtract by 7, which is a mirror pair. And then now 8 divided by 8 minus 7 is 1. And here is the same thing. 7 plus 7 is 14. 1 plus 4 is 5. Or you could just go minus 2 for the vortex sum. 7 minus 2 is 5. Minus 2 is 3. Minus 2 is 1. And then you could also plus 7. Or it goes to 8, or you could wrap around. It goes to 1 minus 2 goes to the 9, and then the 8 wrap around the 9. Yeah, it goes to 8. And likewise for the 3, for this 6 right here, you can just subtract by 3 to get to the vortex sum. So 3, or you can add 6. So it goes 6 minus 3 is 3. 3 plus 6 is 9, and 9 minus 3 is 3. And on this right side, 3 plus 6 is 9, plus 6 plus 3 is 9. And plus 3 is 12, v equals to 3, etc. 3, 6, 9, 3, 6, 9. Or you can subtract. This is 9 minus 6, this is 3. And at the bottom here, we can add 4 or minus 5. So we get 4 plus, so we could add here, 4 plus 4 is 8. Plus 4 is 12, v equals to 3. And then, yeah, so plus 4 is 7. Then you can also subtract by 5. 7 minus 5 is 2. And then reverse here, so 5 plus 5 is 10, or the vortex sum is 1, then plus 5 is vortex sum is 15, or plus 5 is 15, and then we'll have vortex sum is 1 plus 5 is 6, or you could just subtract by 4, so 5 minus 4, and then the next one, or you could add 5, so plus 5, 6, minus 4, just whichever one's easier, because you could wrap around either, or you could just go with the other polar pair of it. And yeah, so adding 4 is the same as subtracting 4, or adding 5 on this other side there. But on this side, adding 4 is the same as minusing 5, it's a polar pair. So writing the polar pairs as differences of 9 show the resulting continuous horizontal and vertical loops. So we have over here 9, 9 minus 8, 9 minus 7, 9 minus 5, and loops around here. This is plus 1. Let's just write this down. This is going to be plus 1. This is plus 1 or minus 8. And this one's going to be plus 2. And notice that, yes, that's going to be plus 3, etc. And it goes dot, dot, dot. So you can just see them all there. So erase this. Here, yeah, just get rid of it just for, just keep it as is. So you can see here, so it's going to go plus 1 down like this. You can go plus 1 this way. Or you could also, this is a continuous loop here. So 9 minus 1. This is 9 minus 8 is plus 1 all the way. Then if you include this 9 inside, 9 minus 1 plus 1 goes to the 9. Then 9, and then plus 1 is going to go to the next one, 9 minus 8. Which is just a 1, and etc. It keeps going all the way across here. Or you could minus 1 going reverse, or you could plus 8 going, plus 8 going backwards, or you can go minus 8. So yes, fascinating stuff. But then for the next one is going to be plus 2 this way, or you can go minus 2 that way, or you can go minus 7 this way, or you can go plus 7 this way, etc. And then the same for the 3 and 4, and 5 and 6, etc. And then again, notice the loops around here, plus 1, then plus 2, and so on. So the same patterns arise in any general number system, which is shown in simplified form below. So you have here, and wrote it like this, 1, 2, 3, so this includes just the single digits here, and then the differences on this side, so p minus 1, p minus 2, p minus 3. So you get, and it goes down like this. So it goes plus 1 down here, plus 2 down over here, 2, 4, 6, and also plus 2 this way, plus 1 this way, or you can go subtract its difference, or minus its mirror pair, 9 minus 1, which same thing as writing negative 1 plus 1. So in other words, yeah, it's the same thing. This 9 just means you're wrapping around, because these are just mirror pairs of themselves, and this way you go negative 1 or 9 minus 1, like that. Yeah, or plus its mirror pair. So yes, fascinating stuff. So yes, fascinating stuff here. And I noticed the loop around here. So this is plus 1 down here. This one's going to be minus 1, or in other words, plus 1. So this wraps around over there. And note that for odd-based number systems, yeah, the number modulus divided by 2 is its own polar pair. And so adding by modulus 2 is the same as subtracting. Yeah, same as subtracting by modulus 2, as shown in the base 5 example below. So if you have base 5, you have an even modulus 4. And then 4 divided by 2 is 2, it goes over there. And when you increment by 2, or 2 plus or minus 2, it goes like this. 2, 4, if you subtract it, gets to the 0, which is equal to 4. Set it to equal to 0. Then, yeah, so plus 2, and then the next one's going to be 2, 4, 2. Again, you're also taking the vortex sum of it. So 2 plus 2 is 4, 4 plus 2 is 6, which is vortex sum of just 2. And it keeps going down here, plus or minus 2, 4, 2, 4, 2, 4. This is its own polar pair, so that means if you're going this loop, this loop right here where 1 and 3 are mirror pairs, then so when you increment on this side, plus 1 or subtracting is mirror pair 3. So you get plus 1, 2, 3, 4, or 4 minus 3 is 1. And yeah, so we get it like this way. This way it's the reverse. We get subtract by 1 or plus 3. So 3 plus 3 is 6, which is vortex sum goes to the 2, or mod 4 is 2. And then 3 minus 1 is 2, minus 1 is 1, and then you could go plus 3 is 4. And then notice the vertical or corresponding vortex circle loops. You get 1 plus 1, 2, 3, 4. This one goes plus or minus 2. Plus or minus 2 goes 2, goes to the 4, goes to the 2, goes to the 4. So I subtract it or plus it. It's the same thing for vortex sum purposes, and that's where that's the only difference. This overlaps the plus and minus. And the next one here, we get a plus. It goes going in reverse, or you get minus. So 3 minus 1 is 2. 2 minus 1 is 1. 1 minus 1 is 0, which equals to 4. Or you can go the reverse. Plus 1, plus 2, plus 1, 2, 3, 4. The next one's going to be 0, and then it goes back to the plus 1, 2, and 3, 4, etc. And addition between two numbers results in the same vortex sum as addition involving their vortex sum. In other words, a equals to factor of 9 plus remainder. And then if you add another integer, yeah, so b plus this a, it's just going to equal to b plus this factor of 9 plus remainder, because you could write any number like that. And then v equals to, well, just b. This factor of 9 is not affected. When you take in vortex sum purposes, that just cancels out, just gets away. So all we're left with is b plus remainder. So in other words, it's the same as just looking at the vortex sum of a. So incrementing by this integer, we could just always cast out the 9, and then we'll have this v equals to b plus this remainder, which is just a vortex sum here. So this one is now over there. This can be written in modulus form and for any general modulus p. So a plus b mod p equals to a mod p plus b mod p, and then all of it mod p. And then you also have a plus b, any general modulus or any number. Yeah, this is just any general number or any general modulus, but then it just wouldn't be for vortex sum. If it's modulus p, then it's a vortex sum. And like always, you could show this a plus b. You could always just do it with this one of them. Yeah, we could just write this as a plus b mod p is just equals to, well, a mod p plus b, and then all mod p. Or you could do it for the b only, so a plus b mod p equals to a plus b mod p, then all of it mod p. And this is simply because if one of them is true, then you can just keep repeating the same thing for any other one. Because a mod p gets an integer, and b plus b mod p also gets an integer. And so if an integer plus an integer mod p, it equals to any one of these. It equals to this one is the same thing as throwing this back into this a plus b and just rearrange it and so on. So this is just modular arithmetic. It's pretty fascinating stuff. So anyways, conclusions. So yeah, finally we've done all the summary and conclusions. Hopefully you follow along. It's pretty epic stuff. And yeah, I just wanted to get a brain workout, just getting all this sorted, because I didn't see this anywhere else. So conclusions, this was the first time I had studied number theory, modular arithmetic, and general based number systems in any kind of detail. So this was a great mental workout, since I had mainly done calculus math videos up until now. Studying Vortex Math helps in obtaining a deeper understanding appreciation of the fundamental mechanisms of the entire concept of numbers. The relation between Vortex Math, modular arithmetic, and general symmetry of base number systems helps to make sense of many of the patterns and calculations that arise. That being said, the many outlandish claims by Vortex Based Mathematics proponents, as well as the dismissive mainstream quote debunkers, only serve to keep people in a state of perplexity, confusion, and separation from true scientific exploration and discovery. So yes, there's literally a divide. There's people that think this Vortex Math somehow does some magical stuff, and then the mainstream ones, they just debunk it without actually describing anything. So you're not getting any value out of these guys. And the other ones makes it look like you're a bit of a madman with the claims. So anyway, so they're both in my view mirror images of each other, but on different spectrums. Because remember, the goal is to get the goal is to help people understand, not tell them this or that with a dogmatic or just fanatical fanatical perception. And yeah, so hopefully I bridge the gap between the mainstream and the Vortex Math people. This is pretty interesting stuff. And yeah, nonetheless, don't make claims that have a counterintuitive effect, that have a counterproductive effect where people just start attacking. So anyways, future parts. In future parts, I will be exploring general torus geometry, constructing the vortex torus, and exploring coil windings, and exploring 3D modeling software. Yeah, exploring 3D modeling software such as Blender. If you have any good Blender tutorials or how to use it properly, or would like help, or would like to help model for me, just let me know. Keep in touch. Just message me. So also, I will explore more vortex or more advanced vortex patterns. So stay tuned for that. Yes, there's also some more quote advanced ones. Anyways, stay tuned for MES Science 3 and/or Vortex Math Part 2, and hopefully enjoy this pretty epic long video. And I think I sorted why it was glitching a lot at OneNote. I think as a recording, it stores a cache, so I gotta close it and open it in the middle of recording just to reset the cache on this OneNote docker. Anyways, that is all for today. Let's scroll back up. It's gonna be a pretty long scroll, and yeah, hopefully follow along. It's pretty epic stuff. So yes, there's the yin yang, and yeah. So Vortex Math aside, Marko Rodin and others have very interesting philosophical descriptions of reality and so on. But again, you have to be very mathematical. If you're dealing with math, you got to be mathematical. Meaning claims need proof. And a divine claim of reification or deification of numbers requires requires exploring beyond just whatever the pattern is and trying to figure out the actual causation, because we're dealing with math. And yeah, this video took a while to make because first I was researching every single thing I could find on Vortex Math, and then there was very little actually concrete, like step-by-step of what is happening, so I had to just do it myself. And also because when dealing with math, that's why I started my channel, is because there are right and wrong answers in math. Everything else is very hard to get a right and wrong answer that is not subjective, whether it's politics or even physics or science. Because those ones depends on depends on how you're observing or what theory that you're applying. But with math, once you define something, then everything can follow cleanly from it. So you can either be right or wrong based on whatever you defined earlier. But again, if the definition's wrong, then by definition everything else will be wrong too. Which is why math, you gotta be very, very concrete, and that's why I started my channel. Anyways, just keep scrolling up. Yes, fascinating stuff, and yes, I'll be looking to get more videos. Just the overall production sped up, or just a more routine. And yeah, so this doing this video helped structure my work research routine much better. Anyways, keep scrolling up. This will be pretty epic. Scrolling. So yeah, it's not even lagging, even though I'm scrolling up now a whole bunch. Because yeah, just closing the OneNote, opening it fixes everything. Anyways, that is all for today. Thanks for watching. Let me scroll up. Keep scrolling. Yeah, there's the torus. Yeah, this torus grids one have some pretty epic patterns and causation effects that I discovered, or just helped illuminate. And I'll do that in another video. Anyways, that is all for today. Also, some very interesting stuff on the Baha'i faith as well. Apparently, that was the first time that was I think 100 years ago, or 100 plus years ago, that was referenced for the phrase New World Order, which is another very interesting thing. Anyways, that is all for today. Thanks for watching, and like always, you can download these exact notes in the link below, as well as viewing it on Hive. And you can see that on peak.com/MES to get my Hive. Yeah, so this is right here, peak.com/MES, and I'll explain why. Yeah, I'm on Hive now. Instead of Steam, I'm more on Hive than on Steam. Still on it a bit, and I'll explain that in another video. I should be doing a video on blockchain, the big picture, in a bit. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.